recording this now because I am not going to export this 9-hour beast of a video twice. This has all of the GE2000 AI slop audios from Notebook LM. So put this on, go to sleep, and dream about GE2000.
Welcome back to the deep dive. There are some numbers that just sort of break your brain a little when you try to actually comprehend them. The distance to a galaxy, maybe. But for me, it's always been the sheer scale of geologic time.
It's almost impossible to get your head around.
It is. I mean, if you were to squeeze the entire 4.5 billion years of Earth's history into one calendar year, all of recorded human history would be, what, the last few seconds of New Year's Eve?
Something like that, yeah. And for most of our history, that immense timeline was just a complete mystery. People knew the Earth was old, you could see it in the rocks, but how old? That was the big question.
Absolutely. And our sources for today really walk through that struggle.
Yeah.
I mean, you look at some of the early attempts to put a number on it, and they were trying their best, but they came up so short.
Wildly short.
There's that 1889 estimate you see a lot, where they try to calculate the Earth's age from how salty the oceans are.
Right, based on the rate of salt accumulation,
Right.
and they got, what, 90 million years or something?
Yeah, around 90 million. And then, even more famously, you have Lord Kelvin in the late 19th century.
Kelvin, the giant of 19th century physics. His calculation was, you have to admit, very elegant.
It was, but it was just based on thermodynamics.
Right.
How long would it take for a molten ball the size of Earth to cool down to its current temperature?
And his answer put geologists and especially biologists in a terrible spot. He was saying the Earth couldn't be older than maybe 20 to 40 million years.
Which just wasn't enough time. Not for geology, and definitely not for Darwin's theory of evolution.
Not even close. So you had this huge conflict between the physicists and the naturalists. Kelvin's math was solid, but his model was fundamentally missing a piece.
A huge piece. A source of heat inside the Earth that he knew nothing about. They were trying to time a marathon with a stopwatch that was, well, just completely broken.
And that's really why we're here today looking at this stack of research, because it all pivots on a single moment in 1896.
The discovery of radioactivity.
Exactly. It just completely rewrote the rules and overnight made those old estimates obsolete.
So that's our mission for this deep dive. We're going to try to give you a shortcut to understanding the core concepts that let scientists finally unlock the planet's real age. We're leaving behind relative dating. This rock layer is older than that one, and getting into the physics of absolute dating. Okay, let's unpack this.
We have to start with this idea of atomic decay, which happens at a fixed, constant rate. This process doesn't care about heat, it doesn't care about pressure. It's just this perfect, unbreakable clock ticking away inside the rock itself.
A clock that runs on atomic failure.
That's the beautiful irony of it. So we're going to break down the fundamentals, isotopes, half-life, the ways atoms decay, because that's what makes these incredibly precise age measurements possible. This is the foundation of the entire geologic timescale.
So to date a mountain range, we have to start with something impossibly small. We have to go inside the atom.
Right down to the nucleus. You've got the electrons orbiting on the outside, but the real action, for our purposes, is in that central hub.
Inside the nucleus, where you have the protons and the neutrons.
Exactly. That's the heart of the matter.
And the protons, they're the positively charged particles. Their number is what defines an element, right? It's like a chemical fingerprint.
It's the atomic number. 6 protons, your carbon, 8 your oxygen, 92 your uranium. That never changes for that element.
Okay. And then you have the neutrons. They're neutral, no charge, but they add mass.
They add mass. And when you add the number of protons and the number of neutrons together, you get what's called the mass number. And this is the part that can change.
And that variability is where we get the concept of isotopes.
Yes. This is the absolute key to the whole system.
So let's use carbon as an example. Carbon always has 6 protons. That's non-negotiable. But it can have different numbers of neutrons.
Right. Most carbon in the world, carbon-12, has 6 protons and 6 neutrons. But a little bit of it, carbon-13, has 6 protons and 7 neutrons.
And then there's the famous one, carbon-14, with 6 protons and 8 neutrons.
Exactly. All 3 are isotopes of carbon. They behave the same way in chemical reactions because the proton number is the same, but they have different masses. They weigh different amounts.
And that difference in the neutron count is what makes some of them unstable.
That's it. You can think of the nucleus as being held together by a delicate balance of forces. If you have too many neutrons, or too few relative to the protons, that balance gets thrown off. The nucleus becomes unstable.
And that instability is what we call Radioactivity.
Radioactivity is just the process of that unstable nucleus spontaneously changing itself to become stable. It rearranges its internal structure,
So the starting isotope, the unstable one, that's the parent.
the parent isotope. And when it decays, it transforms into a new stable isotope, which we call the daughter. And that transformation from parent to daughter happens at that fixed, predictable rate we talked about. That's our clock.
Okay, so this decay, this transformation, it's not just one thing that happens. There are specific ways an atom tries to fix its imbalance, right?
Yes, there are three primary ways, and they each change the nucleus in a very specific way.
Let's start with the most dramatic one, alpha emission. You called it the heavy ejection.
I did. This is what really heavy, unstable atoms like uranium do.
Yeah.
The nucleus is just too big. There's too much repulsion between all those positive protons. So the quickest way to get smaller and more stable is to just throw out a big chunk of itself,
And that chunk is an alpha particle.
which is two protons and two neutrons all stuck together. It's basically a helium nucleus.
So when it ejects that particle, its mass goes down by 4, and its atomic number drops by 2 because it lost 2 protons.
Right. It literally turns into a completely different element. Uranium-238 does this and starts its long decay chain by turning into thorium-234.
Okay. What's next type?
The next one is more subtle. It's beta emission. We called this the neutron flip. This happens when an atom has too many neutrons. It's neutron-rich.
So how does it fix that?
Well, inside the nucleus, one of those extra neutrons spontaneously transforms into a proton.
But wait, that would change the charge, right? You're going from neutral to positive.
It would. So to balance the books electrically, the nucleus has to eject a negative particle at the exact same time. It shoots out a high-energy electron, and that's the beta particle.
So a neutron becomes a proton, and an electron gets ejected. The total mass number stays the same, but the atomic number goes up by 1.
Precisely. The perfect example is carbon-14 decaying to nitrogen-14. They both have a mass of 14, but C14 has 6 protons and 8 neutrons, while N14 has 7 protons and 7 neutrons. It's that one beta decay that makes all of radiocarbon dating possible.
And the third way?
The third is basically the reverse. It's called electron capture. This is for atoms that are proton-rich, too many positive charges.
So instead of throwing something out, it pulls something in.
It does. The nucleus actually captures one of its own inner shell electrons. It pulls it right into the nucleus.
And what happens then?
That captured electron combines with the proton, and together they form a neutron. So again, mass number is unchanged, but this time the atomic number goes down by 1. This is one of the ways potassium-40 decays, which is a hugely important tool for dating very old rocks.
So you have these 3 very precise physical mechanisms. The parent becomes the daughter. And that relationship is, as you said, the engine of the whole thing. Now we have to translate that into an actual number, an age.
Right. And that brings us to the core principle of radiometric dating. What's fascinating here is how simple the idea is at its heart. You just need to measure the ratio of how many parent atoms are left compared to how many daughter atoms have been created.
Assuming you know what the starting ratio was.
And we do. When an igneous rock crystallizes from magma, it's essentially 100% parent, 0% daughter. The clock is set to 0. So if you measure that ratio today and you know the rate of decay, you can calculate exactly how much time has passed.
And that rate, the thing that makes the clock reliable, is the concept of half-life. This is the mathematical key, right?
This is the entire key. The half-life of a radioactive isotope is the amount of time it takes for exactly half of the parent atoms in a sample to decay into daughter atoms.
And the critical thing here is that this rate is exponential, and it's constant. It's not affected by anything happening outside the atom.
You could heat the rock, crush it, dissolve it in acid. The half-life of the isotopes inside does not change. It's an immutable property of that nucleus. It is the perfect clock for geology because it ignores all the geological chaos.
Okay, let's make this concrete. Let's use that potassium-40 example you mentioned. Its half-life is 1.3 billion years.
A nice long time. Perfect for dating the ancient rocks that make up the continents.
So imagine a new rock forms. At time 0, it's 100% parent K40 and 0% daughter products, which are argon-40 and calcium-40.
Okay, clock starts.
We let 1.3 billion years go by. One half-life. What does our sample look like?
It's now a perfect 50-50 split. Half the original K40 is gone, decayed into its daughters. So you have 50% parent, 50% daughter.
Now, here's the exponential part that's so important. We wait another 1.3 billion years. So we're at 2.6 billion years total. 2 half-lives.
What happens is you don't lose another 50% of the original amount. You lose 50% of what was left.
Right. half of the remaining 50%.
Yeah.
So you're left with 25% parent.
And the daughters now make up the other 75%.
And after a third half-life, at 3.9 billion years, you're down to 12.5% parent, and so on.
So on. 6.25%, then 3.125%. You can see how the parent isotope gets harder and harder to measure over time, which is why each dating system has an effective age range. You eventually just run out of parent atoms to count.
It's just amazing that you can take a rock, measure that tiny residual ratio, and confidently say it's, 2.6 billion years old. But this whole thing depends on one huge assumption.
It does. The whole house of cards rests on the sample being a closed system.
What does that mean exactly?
It means that from the moment that rock crystallized, nothing has gotten in or out. No parent atoms have been added or lost, and this is the crucial part. No daughter atoms have been added or lost. The rock has to be like a perfectly sealed time capsule.
But we're talking about billions of years of Earth history.
Yeah.
Rocks get buried, heated, squeezed, weathered. How often is that system really closed?
That's the single biggest challenge in geochronology. It's a constant concern. Let's go back to that potassium-40 system. One of its main daughter products is argon-40.
Which is a gas.
And an inert gas. So imagine that rock gets deeply buried and heated up millions of years after it formed. That heat can allow the argon gas to literally leak out of the crystal structure.
Ah, so your time capsule springs a leak.
Exactly. And if you lose some of the daughter product, when you measure the ratio later, it's going to look like less time has passed than actually has. It will give you an age that's artificially young.
Okay, so given that risk, and given that we're often measuring these tiny, tiny amounts of isotopes, how do they physically do it? What's the technology?
The key piece of equipment is the mass spectrometer. This machine is what turned radiometric dating from a theoretical concept into a practical tool.
How does it work?
Well, in a nutshell, you take a tiny fragment of your mineral, you vaporize it, and you ionize the atoms, which means you give them an electric charge.
Okay.
Then you fire this beam of ions into a vacuum chamber and through a very powerful magnetic field. The magnet bends the path of the ions.
And the amount of bending depends on the mass.
Precisely. Heavier ions, like the parent isotope, have more inertia, so their path doesn't bend as much. Lighter ions, like the daughter isotope, get deflected more sharply.
So the machine physically separates the atoms by weight, and then a detector at the other end can just count them.
It counts them. It gives you an incredibly precise census of the parent versus daughter atoms in your sample. The sensitivity is just staggering.
And to deal with that leaky time capsule problem, I imagine they don't just rely on one measurement from one rock.
Never. The sources all stress that good science requires multiple cross-checks.
What does that look like?
You might date several different minerals from within the same rock. If the biotite, the feldspar, and the zircon all give you the same age, your confidence goes way up.
And you can also use different dating systems, right?
That's the other big one. You might date a rock using the potassium-argon system, and then also date it using the rubidium-strontium system. They have totally different parent isotopes, daughter isotopes, and half-lives. If two completely independent clacks give you the same time, you can be pretty certain that your data is robust.
It's this system of checks and balances that lets them get those incredibly small margins of error, even on rocks that are billions of years old.
It's an entire process designed to catch and account for the geological chaos.
Okay, so we got the theory down. Now let's talk about the specific tools in the toolkit. You need different clocks for different timescales.
You really do. For dating something like the formation of the Earth itself, you need a clock with a half-life that's just as long.
And that means using the really heavy elements.
We're talking about uranium, specifically the isotopes uranium-238, with a half-life of 4.5 billion years, conveniently about the age of the Earth, and uranium-235, with a half-life of about 700 million years.
Here's where it gets really interesting. Because unlike the KR system that produces a gas, the uranium decay systems are much more complex.
Yeah, U-238 doesn't just decay in one step. It goes through a whole chain of 14 different decay steps before it finally becomes a stable isotope of lead.
Specifically, lead-206. And U-235 decays to lead-207.
And this is brilliant for two reasons. First, lead is a heavy metal. It's not a gas, so it's much less likely to leak out of the crystal. The closed system is more secure.
And the second reason?
You have two different independent clocks, the 238 clock and the 235 clock, running in the exact same mineral sample. If you measure the age from both systems and they agree perfectly, that date is considered effectively bulletproof. It's a method called Concordia-Discordia dating.
And for this UPEEP system, there's one mineral that's considered the absolute gold standard for dating.
The tiny but incredibly tough zircon grain.
Why are zircons so special?
It's their chemistry. When a zircon crystal forms in cooling magma, its crystal lattice structure loves to incorporate uranium atoms. They fit nicely, but that same structure actively rejects lead atoms.
Feels like a filter.
A perfect filter. It lets the parent in, but it keeps the daughter out. This means when the zircon is born, it contains uranium, but absolutely zero lead. The clock is perfectly set to zero. Any lead you find in that zircon today must have come from the decay of uranium after it formed.
It's a perfect little time capsule.
It is. These tiny grains are the reason we know the age of the oldest rocks on Earth.
It's incredible to think about the level of precision needed. You mentioned the geochemist Claire Patterson, who first pinned down the age of the Earth with this method.
His story is amazing because it highlights the biggest technical challenge he faced: contamination.
Lead contamination.
From everything. Lead was in gasoline, paint, pipes. It was floating in the air everywhere. Every time he tried to measure the tiny amounts of natural lead in his meteorite samples, he'd get way more lead from the lab environment.
So what did he do?
He had to invent the concept of the ultra-clean lab. He built a laboratory that was completely sealed with filtered air where every surface was acid washed. He essentially had to create a space cleaner than any that had ever existed just to get a reliable measurement.
And that's how he got the first accurate age for the Earth, around 4.55 billion years. An amazing story.
So that's deep time. But if we want to date something much more recent, say within human history, we need a completely different clock.
Right. And that brings us to the one everybody's heard of, carbon-14 dating.
A completely different beast. Its half-life is only 5,730 years.
So it's useless for dating rocks, but perfect for things like archaeology.
Exactly. And the mechanism is different, too. It's all tied to the atmosphere.
Carbon-14 is constantly being created up in the upper atmosphere, right?
Yeah.
Cosmic rays hit nitrogen atoms and turn them into C14.
Correct. And that radioactive C14 then combines with oxygen to make carbon dioxide, which gets mixed throughout the atmosphere.
And plants breathe in that CO2 for photosynthesis, and then animals eat the plants.
So all living things are constantly taking in a tiny amount of carbon-14. As long as an organism is alive, the ratio of radioactive C14 to stable C12 in its tissues is the same as the ratio in the atmosphere. It's an equilibrium.
But then it dies.
The second it dies, it stops taking in new carbon, the intake of C14 stops, and the clock starts ticking.
Because the C14 that's already in its body starts to decay back into nitrogen.
At that fixed half-life of 5,730 years. So by measuring how much C14 is left in a piece of wood or bone or charcoal, you can figure out how long ago that organism died.
But there's a hard limit on this, isn't there?
Oh, absolutely. Because the half-life is so short, after about 70,000 years, that's roughly 12 half-lives, there's just not enough C14 left to measure reliably. The signal fades into the noise.
But it's only for very, very recent geologic history.
And one other thing to mention is that the amount of C14 in the atmosphere hasn't been perfectly constant over time. It wiggles a bit with things like solar activity.
So how do they account for that?
They have to calibrate it. Scientists have built calibration curves using things with known ages, like tree rings that go back thousands of years, to correct the C14 dates and make them more accurate. It's a science that's always refining itself.
Okay, so we've got the tools for deep time and for recent time. But we really need to dig into the limitations. You said not all rocks can be dated.
This is a huge point. Geologists overwhelmingly prefer to date igneous rocks.
Rocks that form from
What?
cooled magma or lava.
Right, because that moment of crystallization is a clear, definitive starting point. The minerals form, the system closes, and the clock starts. It's a clean slate.
But most of the rocks we see at the surface, and almost all the rocks that contain fossils, are sedimentary rocks.
And that's the problem. You generally cannot get a reliable radiometric date from a sedimentary rock.
Why not?
Think about what a sandstone is. It's a bunch of little sand grains cemented together. Those sand grains are bits of eroded rock from some ancient mountain.
So if you date a sand grain, you're not dating when the sandstone layer formed.
You're dating when that grain first crystallized in its original parent rock, which could have been hundreds of millions or even billions of years earlier. It tells you nothing about the age of the sedimentary layer itself.
So, how on earth do they date the fossil record then, if all the fossils are in these undatable rocks?
They have to get clever. They use a technique called bracketing.
Bracketing.
They look for layers of igneous rock above and below the sedimentary layer they're interested in. For example, a volcanic ash bed is perfect. It's an igneous layer that gets laid down very quickly over a wide area.
Okay.
So if you find a sedimentary layer with dinosaur fossils and it's sitting on top of a lava flow you can date to, say, 70 million years ago, and it's covered by a volcanic ash bed you can date to 67 million years ago,
Then you know the fossils have to be between 67 and 70 million years old. You've bracketed them.
that's exactly how it's done. You combine the principles of relative dating like superposition with the absolute dates from the igneous layers to constrain the age of the fossil record. It's a beautiful synthesis of the two methods.
Let's circle back to that closed system problem, the leaky time capsule.
Yeah.
How do geologists know if a date they get is the real formation age, or if it's been messed with by some later heating event?
This is where things get really sophisticated. Sometimes a bad date is actually a source of new information.
How so?
Different minerals in the same rock can lose their daughter products at different temperatures. They have different closure temperatures.
Okay.
Let's say you have a granite that formed 1 billion years ago. It has two minerals in it, biotite and feldspar. Biotite is like a leaky plastic container. It loses its argon at a relatively low temperature, maybe 300 degrees Celsius. Feldspar is like a stronger glass jar. It holds onto its argon until much higher temperatures.
So they have different levels of heat resistance.
Exactly. Now imagine that 1 billion-year-old rock gets buried and reheated to 400 degrees, maybe 500 million years ago. The biotite clock would be a completely reset. It would lose all its old argon and start counting again from zero. If you dated the biotite, you'd get an age of 500 million years. But the feldspar might have held on to all its argon, so it would still give you the original 1 billion year age.
Wow. So if you date both minerals and get two completely different ages.
It doesn't mean the method failed. It tells you the rock has a complex history. It tells you the rock originally formed 1 billion years ago, and then it experienced a major heating event 500 million years ago. The discrepancy is the data.
That's brilliant. You're not just getting a date, you're reconstructing the rock's entire life story.
That's the goal. It's geological detective work.
So we have the clock, we have the tools, we have the quality control. Now let's use all that to build the actual calendar of Earth's history, the geologic timescale.
This is really the crowning achievement of all that work. It's the framework that organizes everything we know about the planet's past.
And it's structured hierarchically, right? Big chunks of time divided to smaller ones.
Exactly. The largest divisions are the eons. Eons are then broken down into eras into periods, and periods into the smaller epochs.
And the lines between them aren't just arbitrary numbers. The boundaries mark major events.
Huge events. Often it's the appearance or disappearance of major groups of organisms in the fossil record. Mass extinctions are very popular boundary markers for obvious reasons.
When you look at the eons, the biggest slices of time, there's a really lopsided story.
Incredibly lopsided. The most recent eon, the one we're in, is called the Phanerozoic. It means visible life.
And it started only about 540 million years ago.
Right, and everything before that, the vast majority of Earth's history is just lumped together into one super eon. It's Precambrian.
And this is the number that just floors me every time I see it. The Precambrian accounts for 88% of Earth's history.
88%. It's staggering. Almost everything that had to happen to make our world possible, the formation of the planet, the origin of life, the creation of an oxygen atmosphere, the assembly of continents, it all happened in this enormous shadowy period we know the least about.
Because the evidence is so sparse and so old.
Exactly.
So within that giant 88%, what are the subdivisions?
The Precambrian is itself divided into 3 eons. Going backward in time, you have the Proterozoic, which means earlier life, the Archean, or ancient life, and the very earliest, the Hadean.
The Hadean, named after Hades.
Oh,
So I'm guessing that was not a pleasant time.
probably not. The Hadean starts with the formation of the Earth 4.5 billion years ago. For much of this time, the planet was a molten magma ocean, constantly being slammed by asteroids and comets left over from the formation of the solar system.
This is when the moon formed, right? From that
Okay.
giant impact.
That's the leading theory. A Mars-sized body smashed into the early Earth. The energy from that alone would have been unimaginable. There was no stable crust, no oceans, and certainly no life. The only physical evidence we have from the Hadean are some of those incredibly durable zircon crystals.
The only thing tough enough to survive. So what happens after the Hadean?
As the bombardment slows and the planet cools, we enter the Archean Eon, around 4 billion years ago. This is when the first stable continental crust starts to form. The planet begins to look a bit more familiar.
But the atmosphere was totally different.
No oxygen to speak of, it was mostly nitrogen, methane, carbon dioxide. But this is the crucial time because this is when life first appears.
Simple, single-celled life.
Prokaryotes, bacteria and archaea. We have fossil evidence from structures called stromatolites, which are layered mounds built by colonies of photosynthesizing cyanobacteria. And this is so important because these tiny organisms began to slowly pump oxygen into the oceans and atmosphere as a waste product.
A waste product that would eventually change the entire planet.
Completely. And that brings us to the next eon, the Proterozoic, starting about 2.5 billion years ago.
This is the longest eon, right? Almost 2 billion years.
It is. This is the boring billion to some, but so much happened. The continents grew larger and started assembling into the first supercontinents. Life became more complex. We see the evolution of eukaryotes, cells with a nucleus.
And the climate went through some pretty extreme phases.
Extremes putting it mildly. The Proterozoic saw multiple intense global ice ages, the snowball Earth events, where the entire planet may have frozen over from poles to equator.
So the Precambrian sets the stage. By the end of it, you have stable continents, an oxygen-rich atmosphere, and complex single-celled life ready to go.
Exactly. And then you cross that boundary 540 million years ago into our eon, the Phanerozoic, with its 3 famous eras: the Cenozoic, or recent life, the Mesozoic, the middle life of the dinosaurs,
And the Paleozoic, the ancient life.
And unlike the Precambrian boundaries, which are mostly marked by geological or chemical events, the boundaries in the Phanerozoic are almost all defined by major changes in the fossil record.
By life itself.
Yes, and the biggest change of all is the one that kicks the whole thing off. The event that marks the beginning of the Paleozoic era.
The Cambrian explosion.
The Cambrian explosion. In a relatively short span of geologic time, we see the sudden appearance of almost every major animal group or phylum that exists today. It's an incredible diversification of complex, multicellular life. It's the moment life goes from being a background player to the main character in Earth's story.
Which really brings this whole thing full circle, doesn't it?
It does.
I mean, we started this deep dive with scientists back in the 1880s, looking at the salt in the ocean and trying to make a guess. They were forced by their limited tools to imagine an Earth that was maybe a few dozen million years old.
And now, by understanding something as fundamental as how an unstable atom decides to rearrange itself, by counting those parent and daughter isotopes with incredible precision, we've arrived at an absolute timeline of 4.5 billion years.
It's the framework that lets us place everything in its proper context. The magma ocean of the Hadean, the first bacteria in the Archean, the snowball Earth of the Proterozoic, and that explosion of life in the Cambrian. It provides the scale for the entire grand narrative.
So what does this all mean? To me, it means we've managed to build the most profound, accurate calendar in existence by measuring failure. It's based entirely on the spontaneous, predictable failure of atomic nuclei. Billions of atoms are falling apart in a rock every second, and because that chaos has a mathematical order, it becomes a perfect clock.
The order within the chaos.
Yeah, and I want you to just think for a second about that zircon grain. A tiny crystal forms in magma 4 billion years ago. At that instant, it grabs the uranium it needs but kicks out all the lead. It seals itself. And then it goes on this incredible journey. It gets cooked, crushed, eroded out of a mountain, tumbled down a river, deposited in a sandstone, buried and metamorphosed. It goes through billions of years of planetary violence. And today, we can pick up that single grain, put it in a mass spectrometer, and it will tell us the precise moment it was born 4 billion years ago to within an incredibly small margin of error. That tiny crystal held its memory, its perfect time capsule through all of that. The fact that a system built on constant spontaneous decay can create the most enduring and accurate calendar we have is just an incredible thought. Okay, let's unpack this. Today, we are taking a deep dive into the absolute foundational reality of the world right beneath our feet. We're sort of moving past the general concept of rock and getting right down to the fundamental building blocks of our entire planet, minerals. We received this really extensive stack of source material dedicated entirely to mineralogy.
That's a lot.
It's a huge amount. And this research It covers the incredibly rigorous, non-negotiable criteria for defining what a mineral even is. It delves into the essential role of crystalline structures, explores the vast system of chemical classifications.
And then ties it all back to the fundamental composition of the Earth's crust itself.
Exactly. It's a massive amount of incredibly specific foundational data. We're stretching from the nanoscale architecture of an atom all the way up to the geology of entire continents. So our mission today is to provide you, the learner, with a clear, structured shortcut to understanding exactly what a mineral is, the official scientific definition, and maybe more importantly, what substances, despite how they look, fail to qualify.
Yeah, that's a key distinction.
We need to categorize these, 4,000 plus known entities and explain why the Earth is built overwhelmingly from one single chemical group. It feels like a huge task. Synthesizing all these specific data points, you've got the complex formulas, the crystallographic systems, the elemental abundances. It requires not just a guide, but an expert to help us connect all those atomic dots to the continental scale.
And that connection is absolutely
Yeah.
crucial because mineralogy is the bedrock, and I'm sorry, but the pun is intended, of all geology.
Bravo.
You simply cannot begin to understand plate tectonics or the formation of igneous and metamorphic rocks or even the mechanics of resource extraction without first mastering that mineral definition and understanding the composition of the crust. What's really fascinating here, and what the sources emphasize over and over, is the demanding level of precision this field requires. In mineralogy, we can't just point to something and say that looks like part of a rock. There is a strict 5-point checklist that must be satisfied. And this rigor is the key. Once you understand the rules that define a mineral, the properties like hardness, color, or cleavage, and the entire classification system, they all just naturally fall into place.
Let's start with that all-important checklist then. This is the non-negotiable standard that geological science has established. If a substance is under consideration, our sources make it perfectly clear. It must meet all 5 points to qualify as a mineral. It's an absolute pass-fail test.
No partial credit.
None. So the first criterion is that the substance must be naturally occurring. This seems, almost self-evident, but the implication is huge. It must have formed through natural geological or cosmic processes without any assistance or intervention from human beings.
And this is the immediate gatekeeper. It instantly filters out everything manufactured, synthesized, or, grown in a lab or a factory, regardless of how chemically identical it is to its natural counterpart.
So even if it's the same stuff, atom for atom.
Doesn't matter. If humans were involved in its formation, it is, by definition, a material, not a mineral.
And the sources provide the perfect, memorable counterexample here. Cubic zirconia. If you hold it up, it's hard, it's sparkly, it's visually indistinguishable from certain minerals, and it certainly has an ordered internal structure.
It sure does.
But because it is a synthetic material, it was grown specifically in a controlled, human-managed environment, it fails the very first test. It never gets to criterion number 2.
Precisely. It's out of the running immediately. So if we move on, criterion 2 states that minerals must be inorganic.
Okay.
Historically, this meant they couldn't be derived from living organisms. It was a way of separating the realm of biology from the earth sciences.
Yeah.
You were looking for things created purely through physical and chemical processes like precipitation or cooling or crystallization processes entirely separate from life.
The sources cite a classic example, common salt or halite, which is sodium chloride, NaCl. It precipitates out of evaporating seawater, a purely physical and chemical process. It meets the criteria. But wait a second, if we're talking about things derived from living organisms, this raises an interesting challenge, doesn't it? What about things like seashells or the calcium phosphate that makes up human teeth and bones?
That is a brilliant challenge, and it taps right into one of the most interesting sort of nuanced debates in mineralogy. The bulk of a seashell is calcium carbonate, which is technically calcite, a defined mineral.
So it should count then.
Well, here's the catch. Because the organism biologically controls the crystallization process, it concentrates the material and deposits it in a specific structure. Most mineralogists classify these biogenic substances as biominerals or materials, not true minerals. They kind of violate the spirit of that inorganic and natural rule.
Because they're organically mediated?
Exactly. The process isn't purely geological.
That makes the line much clearer. It's not just the presence of life, but whether life orchestrates the formation. Okay, moving on. Criterion 3. A mineral must exist in a solid state at the standard measurement of room temperature.
This one's pretty straightforward. It defines the physical phase we are studying. We're specifically looking for crystalline solids that maintain a rigid, stable structure under normal planetary surface conditions. The common mineral copper, for instance, maintains this rigid structural stability. And the non-example used in the sources is crude oil.
Right, it's a liquid.
Oil is a liquid, and it is also often highly organic, so it fails on two counts right there. But even if we considered something like frozen water, ice is a mineral.
Wait, really? Ice?
Absolutely.
Right.
Because it's natural, it's inorganic, it's solid, it has a specific composition, H0, and has a crystalline structure. However, liquid water, or oil, at room temperature, lacks the necessary long-term internal order to qualify as a mineral.
Okay, that makes sense. Now we move on to the chemistry. Criterion 4. A mineral must have a specific chemical composition, which means it is chemically homogeneous. This is the ability to write a precise, consistent chemical formula for that substance that holds true regardless of where on Earth you find it.
That homogeneity is the unique identifier. We're talking about strict, fixed ratios of elements. The source cites pyrite, iron disulfide, FeS. If you analyze a sample of pure pyrite, you will find 1 iron atom for every 2 sulfur atoms. That ratio is fixed.
But I have to challenge the rigor here a little bit.
Right.
If the rule is specific composition, what about those minerals that aren't perfectly pure? What about a sample of pyrite that has, say, a tiny trace of gold or nickel substituting for iron? Does that disqualify it? How much, chemical wiggle room is allowed before it's considered a different mineral entirely?
That is the essential question of mineral chemistry, and the answer lies in a concept called solid solution. Mineralogists allow for what we call minor substitutions, or trace elements, within the lattice structure. Provided the fundamental crystallographic blueprint, the structure remains unchanged.
So the house is the same even if some of the bricks are a slightly different color.
That's a great way to put it. In pyrite, for example, if a tiny amount of nickel substitutes for iron, we still call it pyrite. But if that substitution becomes substantial, or if it requires a change in the overall crystal arrangement, then you have crossed a boundary and you've defined a new mineral species. The overall dominant chemical framework has to stay the same, which is why we write Fe0s for pyrite, defining its core expected composition.
That brings us perfectly to the 5th and I think arguably the most fascinating criterion. Minerals must possess a crystalline structure. This means the atoms must be arranged in an orderly, 3-dimensional, repeating internal structure, a lattice, or a blueprint.
And this is where the synthesis happens. The crucial, high-level takeaway is that a mineral is defined by its chemistry and its crystal structure. You can have the perfect chemistry, but if the internal arrangement is random, you do not have a mineral.
So it's not enough to have the right ingredients.
Not at all. The recipe has to be followed perfectly. And the classic non-example here is obsidian. Obsidian is a natural glass formed when volcanic lava cools so rapidly that the atoms don't have time to organize into a crystal lattice.
It's frozen in chaos.
Perfectly put. It's natural, it's solid, it has a specific chemical makeup, but because its internal structure is amorphous, it lacks that orderly, repeating arrangement, it fails the final test. It is simply a natural glass, not a mineral.
So that crystalline structure, that internal architecture, is the hidden key. It's what dictates everything from how a substance breaks to how hard it is. It differentiates a lump of dirt from a precious gem. Let's transition from the chemistry to the architecture and discuss the visible manifestation of this internal order, crystal habits.
Right. Crystal habits refer to the external shape a mineral crystal takes when it's allowed to grow unimpeded in an ideal environment. It's the macroscopic expression of that invisible atomic blueprint.
The big version of the small version.
Exactly. And these shapes are so distinctive that they are often used as a primary identification method out in the field.
We see these distinct geometrical terms used in the sources to describe these habits. I'm thinking of fluorite, which commonly forms perfect octahedral crystals. That's shaped like 2 pyramids base to base, right?
Correct. Or beryl, which is the family that includes emerald, growing as these striking, long hexagonal prisms, these beautiful 6-sided columns.
And then there's the incredibly recognizable perfect cubic crystals of pyrite fool's gold.
Of course. And those precise 90-degree angles you see defining that cube are direct visual proof of the underlying cubic internal atomic lattice. The crystal is just the atomic blueprint magnified millions and millions of times.
The sources even mention copper, which can form these dramatic dendritic crystals. That term, dendritic, it refers to a branching tree-like pattern, doesn't it?
It does. You often see these striking, intricate chemical lightning bolts spreading across a surface, showing the exact path of crystallization.
It's beautiful.
It is. And these growth patterns are heavily dependent on the environment. The sources mention the world-famous discovery of the giant gypsum crystals in the Cave of the Crystals in Mexico.
Oh yeah, those are unbelievable.
They're mind-boggling. And that cave illustrates the power of environment. You have stable temperature, incredibly rich mineral-saturated water, and millions of years of uninterrupted time. Those conditions allowed the gypsum's internal crystal structure to manifest as columns the size of telephone poles.
Wow.
The environment didn't change the chemical blueprint, but it dictated the spectacular final morphology.
But to truly get our heads around the monumental power of structure, we have to talk about the ultimate comparison, which our sources highlight as the foundational concept for understanding materials science: graphite and diamond.
This comparison is, it's required reading for anyone studying mineralogy. Both substances are composed solely of the element carbon, just C. Their specific chemical composition is identical.
One ingredient.
One ingredient. But their physical properties couldn't be more different. One is soft, dark, opaque, and inexpensive. The other is the hardest natural substance known. It's transparent, and it commands astronomical value.
This is where the complexity of the 5 criteria, and specifically that crystalline structure, proves its worth. We call these substances polymorphs, right? Substances with identical chemistry but radically different crystal structures.
Exactly. Let's break down those structures using an analogy, just to make it accessible for everyone. In graphite, the carbon atoms are arranged in these perfect, flat sheets.
Okay.
Think of it like a massive stack of individual sheets of paper. The bonds within each sheet are very strong, but the bonds between the sheets are incredibly weak.
So you can sled them apart.
You can. If you try to slide the stack sideways, the sheets slip and shear easily. That's why graphite is soft and works as a lubricant or in a pencil lead. You're literally sliding their sheets off onto the paper.
Now contrast that with the diamond structure.
It's a completely different world. In diamond, every single carbon atom is bonded to 4 others in a rigid, repeating 3-dimensional tetrahedral lattice. Think of it not as a stack of paper, but as a giant, unbreakable geodesic dome or a complex jungle gym.
So it's interlocked in every direction.
Every direction. The bonds are maximized in all 3 dimensions, creating this immense, continuous, interwoven framework. To break it, you have to break millions of those primary covalent bonds all at the same time. That structural integrity is why diamond is so hard and transparent and stable under extreme pressure.
This comparison is just perfect proof that structure is equally critical as composition. You were defining 2 entirely different minerals, one used for low-friction applications and the other for cutting steel, based solely on the arrangement of the very same carbon atoms.
That is the genius of mineralogy. The architecture defines the properties.
So we have our rigorous rules for defining a single mineral. The next challenge is just the sheer scale of it all. How do we organize the known population of substances that successfully pass that 5-point test?
Yeah, big job.
We mentioned there are over 4,000 known minerals. That number alone is staggering. And our source materials are quick to highlight the dynamic nature of this field, noting that new, unique combinations of structure and chemistry are still being discovered every single year. It is far from a closed book.
Absolutely not. And to make sense of those 4,000 plus distinct entities, mineralogists rely on a classification system that's based on the substance's dominant chemical signature. Specifically, we organize them based on the major anion, or the negative ion they contain.
Okay, so it's the negatively charged part of the formula.
That's the key. This approach results in the 9 major mineral groups that categorize the entire known mineral kingdom.
All right, let's walk through the chemical signature and examples of these 9 groups, focusing on that defining negative ion. This is where the bulk chemistry of the Earth is really revealed.
We have to start with the most important group, the one that basically defines the entire crust. 1. The silicates. These minerals are defined by a combination of metals plus silicon and oxygen, where the basic building block is the silicon-oxygen tetrahedron, the SiO-Euro.
The source gives the example of talc, which has that very long formula, MgZO-Euro, but I guess we shouldn't let the formula overwhelm us. The key is the Si and the O, the silicon and oxygen. That silicate tetrahedron is the basic chemical engine that drives this colossal category.
It absolutely is. Next up are the 2, oxides. These are simple and direct. It's just metals combined only with oxygen. The classic example is hematite, Fe, which is a critical iron ore. Oxides are generally tough, dense, and vital industrial materials.
The third group is the three sulfides. These combine metals with sulfur. Our friend pyrite, FeS, falls right in here.
Yeah. These minerals often form in environments lacking free oxygen, what we call reducing environments, and they're commonly associated with valuable ore deposits, things like copper, lead, and zinc.
Fourth, we have the four sulfates. And you have to notice the small but functionally crucial chemical shift here. Instead of just sulfur S, we have metals combined with sulfur and oxygen, forming the sulfate radical SOO.
Right, and the example given is gypsum, KCOA2H arrow. Sulfates often form in oxidizing environments, particularly when saline bodies of water evaporate, leaving behind these layers of crystallized sedimentary material.
So very different environments.
Completely different. Sulfates are fundamental in construction, as gypsum is the ingredient in plaster and drywall. So sulfides versus sulfates, it's the difference between metal ores formed deep underground and common sedimentary evaporites formed right at the surface.
Group 5 is conceptually the purest. 5, the native elements.
My favorite group.
These are substances that exist in nature uncombined with other elements. The sources list gold, AA, silver, copper, or even carbon in its diamond or graphite forms. They are minerals composed of a single element, which makes them extremely valuable for their purity.
Moving to number 6, the 6 halides. These minerals involve metals combined with a halogen. So that's elements like chlorine, fluorine, or bromine from the periodic table.
And the prime universal example has to be halorite, common table salt, NaCl, where sodium metal is bonded to the chlorine halogen.
That's the one. They're characterized by low hardness, and they're generally soluble in water.
Seventh is the 7, carbonates, which combine metals with the Co group, the carbonate radical. Calcite, Caco, is the defining mineral here. And calcite is critical because it forms these massive rock bodies like limestone and marble, and it's crucial for the global carbon cycle.
Absolutely. Group 8 is the 8. Hydroxides, which involve metals combined with the OH group. The source site's bauxite. Now, bauxite isn't technically a single mineral, but a rock composed primarily of aluminum hydroxide minerals.
But it's the main source of aluminum.
It is the primary ore from which we extract aluminum metal. Again, a huge industrial relevance tied directly to this specific classification.
And finally, the 9th group, the 9 phosphates. These combine metals with the PO group. The beautiful gemstone turquoise, with its super complex formula, CuLHPOR, is a complex, water-bearing example of a phosphate mineral, often valued for its striking blue color.
When you look at this completed system, you really see the elegance of it. By isolating the chemical building blocks, the silicate, the oxides, sulfide, sulfate, and so on, we can sort the entire 4,000 mineral kingdom based on its chemistry. But as we noted, that first group, the silicates, is so overwhelmingly abundant that it renders all the others geologically secondary in scale.
The significance of that silicate group really defines our deep dive. We'll explain the why of that in a moment, but simply put, silicates are the largest and most abundant group, making up a truly disproportionate amount of the Earth's crust. This isn't just one of 9 groups. It is the dominant chemical signature of our planetary surface.
And while the major groups provide the structure, the fact that the list of known minerals is still growing and new classifications are added annually shows that the Earth still holds secrets. This constant discovery injects a real human element into what can seem like a very abstract science.
We have 2 great recent examples that highlight both the structural complexity and the human rigor involved. First, the discovery of miralanite in Tanzania. What makes this mineral so fascinating is its unique layered crystal structure, which forms into what the researchers described as scroll-like whiskers.
Think about that structural implication for a second. The atoms are organizing themselves not just into flat sheets like mica or perfect cubes like pyrite, but into three-dimensional curves.
Like they're rolling themselves up?
Exactly. That new structure dictates entirely new physical properties.
Right.
And the careful, exacting work of the researchers was required to confirm that this scroll structure was stable, repeating, and chemically unique enough to warrant being defined as a brand new mineral species. It's challenging the known bounds of crystallization.
And then there's the trivia. The sources mention the discovery of a new bismuth and gold sulfide found in Hungary named jazzikite. Crucially, it was named in honor of physicist John Jazik of Michigan Tech.
Naming a mineral after a respected scientist is the highest form of academic tribute in the field, and it reminds us of the dedication required. To confirm a new mineral, a team has to submit exhaustive data to the International Mineralogical Association, the IMA.
What kind of data?
Everything. The composition, the crystallography, the origin, the history. They must prove that this specific, natural, ordered solid has never been cataloged before. The naming process itself is a testament to scientific rigor and peer recognition. It confirms that the detailed process of defining a unique crystal chemical entity is an ongoing, vibrant scientific pursuit.
Okay, so now we connect all these definitions and classifications to the largest scale possible, the formation and composition of the Earth itself. If we've defined 4,000 minerals, we have to accept that, geologically speaking, 92% of the Earth's crust is built from just a handful of those classifications. And the driving factor is simple: raw elemental abundance.
We're focusing here specifically on the Earth's crust, that relatively thin outer layer, which ranges from about 20 to 70 kilometers thick. This is the source of all our rocks, our soils, and our extractable resources. And the sources provide a crucial piece of data. Just 8 elements account for approximately 97% of the entire crust's composition by weight.
This big 8 is the key to all mineral formation on the surface. Let's break down the data, starting with the 2 undisputed giants. The undisputed winner, the most abundant element in the Earth's crust, is oxygen, clocking in at around 46% of the crust by weight.
Wow.
Nearly half the mass of the crust is just oxygen.
That's often a massive surprise to people because we associate oxygen with the atmosphere we breathe. But in the crust, it exists not as a gas, but as a massive, stable negative ion, an anion bonded tightly with silicon and various metals.
So it's the structural backbone.
It is. Because the oxygen ion is physically quite large, it occupies the vast majority of the physical space within the mineral lattices.
Right behind it, the second most abundant element is silicon Si, making up a formidable 27% of the crust.
So there you have it.
If you combine those 2, oxygen and silicon, they account for approximately 73% of the entire mass of the Earth's outer layer.
The remaining elements are abundant, but significantly less so. We have aluminum Al, about 8%, and then iron at 5%. And it's interesting to note that iron, while extremely abundant in the Earth's core, drops dramatically in the crust.
The final 4 components of the Big 8 are metals critical to various mineral groups. Calcium Ca at about 3.5%, sodium Na at 3%, potassium K at 2.5%, and finally magnesium Mg at 2%.
And that's pretty much it.
That's 97%. Every other element on the periodic table, including all the rare earth elements, gold, uranium, all of it, makes up the final 3%.
This elemental composition gives us the definitive answer to the question of why the silicates dominate. Since oxygen and silicon are so incredibly abundant, they naturally combine under the high heat and pressure found during the formation of the crust to form the most chemically stable and common compounds possible.
It's just a numbers game.
It's a numbers game based on chemistry. The strength and stability of the Si-O bond are immense. Under geological conditions, forming silicates is the planetary default. This unavoidable chemical conclusion means that because O and Si are 73% of the available material, the silicates make up an astonishing 92% of the minerals in the Earth's crust.
Wow.
The fundamental geological outcome dictated by mass availability.
So if the planet is structurally committed to silicates, what does this actually look like in terms of architecture? We keep talking about the silicate tetrahedron, the Si-O, but how does that little unit build up 92% of our world?
This is the critical piece of technical insight you really need to grasp. The silicate tetrahedron is one silicon atom bonded to 4 oxygen atoms, forming this tiny, rigid pyramid shape. Because oxygen is large and silicate is small, and because the bonds are very strong, this tetrahedron is incredibly stable. The trick of mineralogy is how these individual tetrahedra link together by sharing their corner oxygen atoms.
Okay, so they hold hands.
They hold hands. And by linking up in different geometric ways, they create the entire diversity of the silicate kingdom. For instance, if the tetrahedra are linked only by metal atoms, like iron or magnesium, they remain isolated. This structure forms minerals like olivine.
Got it.
They can also link corner to corner to form long, robust chains. This forms the basis of the pyroxene group. Or 2 of those single chains can bond together side by side, creating the amphibole group.
It's like Lego.
It's exactly like Lego.
Yeah.
Then they can link up to form vast, continuous sheets, which gives rise to minerals like the micas, which explains their perfect sheet-like cleavage. And finally, they can link up in all 3 directions, sharing all their oxygen atoms to form a complex, 3-dimensional framework. This highly stable structure defines quartz, and most importantly, the feldspar family.
That structural explanation is the why. It shows us that the chemistry, the O and the Si, dictates the building block, and the geometry, how the blocks link up, dictates the resulting mineral family and all its properties. Okay, Now that we know the elemental recipe and the structural blueprint, we can look at how these abundant elements combine to form the specific, common rock-forming minerals that define the look and the structure of our continents. If we are discussing the very structure of the crust, we have to start with the single most important mineral family, the feldspar family. The sources emphasize that feldspar minerals account for an unbelievable 50% of the Earth's crust.
50%, half.
Half of all the mineral mass you are standing on belongs to this one group.
Feldspars are essential. They're framework silicates, meaning they have that rigid, stable, three-dimensional structure we just discussed. They're generally divided into two main categories based on the metal that fills the framework.
Okay.
First, there's orthoclase, or potassium feldspar. It's a potassium aluminum silicate, calcarea. This is often the pink or reddish component you see in rocks like granite.
Right, the pink stuff in countertops.
Exactly. It is structurally monoclinic, which means its angles aren't all 90 degrees, which is a subtle but important crystallographic difference.
And then there is the massive complex group known as the plagioclase feldspar series. Now, this isn't one mineral, but a continuous solid solution series. It features two end members, pure albite, which is sodium-rich, and pure anorthite, which is calcium-rich.
The key here is that concept of solid solution again. Most plagioclase you find in nature is not pure albite or pure anorthite. It's a mixture somewhere in between, where sodium and calcium atoms freely substitute for one another in the crystal lattice.
So it's a spectrum.
It's a perfect spectrum. And this is a perfect illustration of how that specific chemical composition rule allows for slight variability within the defined mineral structure. The different compositions affect the mineral's melting temperature, which is crucial for understanding how magmas crystallize.
Beyond the feldspar family, we move to the other key silicates that fill in the gaps and add color and character to our rocks. The simplest major rock former, which is pure framework silicate, is quartz, essentially pure silica.
Right. It is a primary component of many rocks, including granite, and it's famously resistant to weathering because of its extremely stable framework structure.
Next, we have the sheet silicates, the micas. These are so distinctive because of their perfect cleavage. They split into these extremely thin, flexible sheets. And this property is a direct result of their crystal structure, which consists of strong sheets of tetrahedra that are just weakly bonded together.
We distinguish between two main types. There is muscovite, the light-colored or white mica, with its complex formula.
I'm not going to make you say it.
Thank you.
Yeah.
It's known for its shiny, often transparent appearance. Then there's biotite, the dark mica, which has an even more complex composition, KFA-MgLCOFOH. The inclusion of iron and magnesium, Mg, is the planet's way of incorporating those darker, denser elements into the crust, making biotite common in darker, igneous, and metamorphic rocks.
We also have the minerals that link the crust to the deep interior. Olivine, MAGAS-CIR is a perfect example. We noted earlier that it's an isolated tetrahedral silicate. Because it is rich in magnesium and iron, it's a key, very dense mineral in the Earth's mantle.
Right. And when it erupts quickly, it's found in basaltic rocks on the surface, often recognizable by its distinctive olive green color.
Then you have the chain silicates. The pyroxene group, like augite, is built on single chains of tetrahedra. The amphibole group, exemplified by hornblende, is built on double chains.
And these different chain structures result in slightly different cleavage angles, but both are crucial constituents of many igneous and metamorphic rocks. They provide many of the dark oblong specks you see in common stones.
And just to prove that the crust isn't entirely silicates, we have to include the one major common non-silicate rock former that sneaks into the list, calcite, CaCo.
Can't forget calcite. This carbonate forms massive sedimentary rocks like limestone and marble. Its abundance is second only to the silicates, particularly in sedimentary environments.
So if we tie all these concepts together and use the example of granite composition, it becomes visually real for you. Granite is a geological fingerprint created by the blending of these rock-forming minerals, all adhering to that 5-point criteria. You can identify the constituents visually.
You can. The pink grains are typically the orthoclase feldspar.
The potassium-rich one.
Exactly. The gray, glassy, often irregular bits are the quartz.
The pure silica.
The opaque, white, or creamy grains are the plagioclase feldspar.
The sodium-calcium spectrum.
And finally, the dark black specks are the denser iron and magnesium-rich biotite and hornblende.
That one rock, granite, encapsulates our entire deep dive. It is composed of highly specific, ordered chemical structures, minerals that follow strict geological criteria, and those minerals are overwhelmingly silicates because the Earth is overwhelmingly made of oxygen and silicon. It's a beautifully consistent and elegant system dictated by availability and stability. We started this deep dive with a deceptively simple question. What is a mineral? And we've traveled from the definition checklist to the atomic architecture, and we're concluding with the macro-scale composition of our planet.
It's quite a journey.
It is. We reaffirmed the immense rigor of the five-part mineral definition. A substance must be natural, inorganic, solid, have a specific composition, and possess a crystalline structure. Failure on any single point, whether you are manufactured like cubic zirconia or amorphous like obsidian, means failure to qualify.
We saw the immense power of structure by comparing the polymorphs graphite and diamond, which is the ultimate proof that the arrangement of atoms matters just as much as the chemical recipe. And we quantify the Earth's composition, recognizing that the overwhelming dominance of oxygen and silicon directly explains why silicate minerals, built from that COUO tetrahedron, constitute 92% of the crust, led by the colossal feldspar family.
So we encourage you to look at common objects, whether it's gravel, a countertop, or the salt in your shaker, with a completely new appreciation. That common salt is not just seasoning, it's halite, NaCl, a perfect halide mineral defined by its specific cubic atomic structure. The structure of the Earth isn't random, it is precise, chemically fixed, and geometrically ordered.
And that consistency leads us back to our final provocative thought. We confirm that the list of known minerals is still growing, with new species like marilanite and jazzakite being defined every single year. The Earth is vast, geological processes are constant, and the crust and mantle hold tremendous reserves of material under extreme heat and pressure.
There's still more out there.
So much more. If the list of known minerals is still expanding in the 21st century, this raises an important question for you to mull over. How many structural variations, how many complex combinations of the abundant Big Eight elements we discuss are still hidden in hard-to-reach environments, in deep-sea vents, in the upper mantle, or trapped within massive continental formations waiting to be analyzed and defined?
That's a great question.
What fundamentally new structures or chemical systems are waiting out there to challenge or expand our existing framework of the 9 major mineral groups? The mineral kingdom is far from fully mapped, and every new discovery refines our understanding of what the Earth is truly made of. Okay, let's unpack this. We are tackling the greatest structural mystery right beneath our feet.
A pretty big one.
Yeah, today we are diving deep into the foundational architecture of Earth. We're talking its layers, its composition, and the incredible theory that ties it all together, plate tectonics.
And our mission today is to use the sources you've shared to give you a really comprehensive but fast grasp of what makes our planet tick from the inside out.
Right.
We're going to explore how scientists even figured out the Earth is layered, what it's chemically made of, and, most importantly, why those properties create the movement that sculpts our world.
I think the most mind-blowing fact to start with is just how we figured it out in the first place.
Yeah.
I mean, the deepest hole we've ever drilled barely scratches the surface. How do we know it wasn't just a big uniform ball of rock?
It all comes down to a deceptively simple calculation. It's about density. And that's your first major aha moment right there. If you calculate the average density of the entire planet mass over volume, you get a number. It's about 5.45 grams per cubic centimeter.
Which is heavy. Really heavy.
It's very heavy, but that's the average for the whole planet.
And when we look at the rocks, we can actually hold the stuff on the surface, the crust. What's that?
Well, those rocks average only about 2.7 grams per cubic centimeter.
Whoa, that's about half.
Exactly. Half. That massive discrepancy, just that one piece of math, tells you immediately that the Earth cannot be the same stuff all the way through.
So there has to be something incredibly dense hidden deep inside.
Deep inside, yeah, to balance out the calculation.
Okay, so that density difference is the smoking gun. It proves the layers exist. But how do we know where they are? How do you map the boundary between, say, the mantle and the core?
That's where physics steps in. So while density gave us the proof of layering, the map itself comes from seismology.
Earthquakes.
Earthquakes. Every single time there's an earthquake, we get this massive sonic scan of the planet. We study how those seismic waves refract, how they bend, and reflect off the boundaries between different materials.
Like bouncing off the difference between solid rock and liquid metal.
Precisely. It's an amazing bit of detective work, really, using planetary vibrations to see what we can't see.
It really is.
Yeah.
That sets the stage beautifully. So let's get elemental. Here's where it gets really interesting for me.
Mm-hmm.
What our planet is actually made of. because the recipe for the whole Earth is just radically different from the recipe for the thin crust we're all standing on.
Completely different. If you could somehow take the entire planet and put it in a blender, core and all, what you'd get is a very metallic, very dense world. Iron feet is the absolute dominant element. It makes up a staggering 35% of the planet's total mass.
35%. So a third of the planet is iron.
Yeah.
It's literally the core engine.
It is. After iron, the next biggest is oxygen at around 30%. Then you have silicon at 15% and magnesium at about 10%.
And the sources are clear that most of that iron is concentrated deep down, right?
Oh, yeah. It's not evenly distributed. It's mostly existing as liquid iron and nickel in the outer core and solid iron and nickel in the inner core. Our planet is fundamentally an iron planet that has separated out.
Differentiated. That's the key word. So now let's jump up to the surface and compare that 35% iron figure with what our crust is made of.
It's a different world.
A completely different world. Our sources show that up here on the surface, oxygen just completely dominates. It's clocking in at around 46%.
Almost half of everything you can touch on the surface is in some way oxygen, mostly locked up in silicate minerals.
And silicon comes in second at about 27%, which makes sense. That's why we call it a silicate world. Granite, basalt, all silicate.
Exactly. We live on a thin, oxygenated silicate veneer.
And look how the metals drop off. Aluminum is next at about 8%, and iron, the planet's #1 element, is down to only 5% of the crust's mass.
Just 5%. It's a huge drop.
Then you have calcium, sodium, potassium, magnesium. It's such a stark contrast. The deep planet is heavy metal, and the surface is this light, silicate-rich, like foam that floated to the top.
And that's it. That compositional difference is the crucial first step to understanding plate tectonics. The lighter stuff rose to the top during Earth formation, creating this buoyant skin.
A skin that interacts with the much denser, much more massive mantle right below it.
That's the system.
So let's focus on that system. For plate tectonics, we're really talking about the crust and the upper mantle. That's where all the action is.
That's the whole game. And what's so fascinating is how density and composition dictate everything. You have this huge interior and then these two totally different types of skin floating and moving on top.
Let's break down the three main players then, starting with the biggest one by far, the mantle.
The mantle is just, it's overwhelming. It accounts for about 80% of Earth's total mass and volume.
80%.
Yeah.
That is hard to even imagine. So 4/5 of our planet is the mantle.
Pretty much. It's a vast layer stretching approximately 2,800 kilometers thick.
2,800 kilometers. Compare that to the crust, which is measured in, what, tens of kilometers?
Tens, yeah.
Yeah.
It's an incredible difference in scale, and the mantle's composition is primarily a rock called peridotite. It's dense, dark, and has a lot less silica than the crust, only around 40%.
And its density is in that middle range, between the light crust and the super heavy core.
Right. Between about 3 and 6 grams per cubic centimeter. It's hot, it's solid, but it can deform and flow over geologic time. It's the engine room.
The engine room. I like that. Okay, so now for the two types of crust, the actual plates. Let's start with the one we live on, the continental crust.
The continental crust is the great floater. It's much thicker and, crucially, less dense than the oceanic crust.
How thick are we talking?
It can range from about 20 kilometers in flat areas, but it can get up to 70 kilometers thick under major mountain ranges like the Himalayas.
And its density is that low number we mentioned, about 2.7 grams per cubic centimeter.
That low density is why continents rise so high above sea level. Its composition is granitic. It's very high in silica, between 60 and 70%. Think of it as geological styrofoam. It's light, it's thick, it's buoyant.
Geological styrofoam. Okay, now let's contrast that with the other half of the system, the oceanic crust.
Oceanic crust is the total opposite in almost every way. It's much thinner and it is denser.
And that density part is critical.
It's everything. So its thickness is just a sliver, only 4 to 7 kilometers thick, but its density is higher, around 2.9 grams per cubic centimeter.
Wait, so that's simple 0.2 grams per cubic centimeter difference. That's the entire game, isn't it?
That is the entire game. It determines who wins and who loses when two plates meet.
Wow.
The oceanic crust's composition is basaltic, with less silica, only about 50%. And because it's denser, when that thin, dense oceanic plate collides with a thick, buoyant continental plate,
The oceanic one has to go down.
it always goes down. It sinks back into the mantle. We call that subduction. And that single distinction light continental granite versus dense oceanic basalt is the key to all plate movement.
Which brings us to the unifying theory itself.
Yeah.
Plate tectonics. The sources call it the unifying theory in geology.
It really is. Before the 1960s, scientists knew about continental drift, they knew about earthquakes, they knew about volcanoes, but they were all seen as separate phenomena.
Disconnected dots.
Disconnected dots. Tectonics provides the framework that connects all of them into one coherent global picture.
So what's the mechanism? What's actually happening? Are the plates just sliding around?
Well, we conceptualize it as rigid plates. We call this the lithosphere, which is the crust plus the very rigid top of the mantle, and they slide over a weaker, more plastic layer below.
The asthenosphere.
The asthenosphere.
Yeah.
And that weak layer is still solid rock, right? It's not a liquid ocean down there.
Right, that's a common misconception.
A huge one. It's solid, but it's so hot and under so much pressure that it's close to its melting point. It has a plasticity to it. It can flow very, very slowly.
Which allows the rigid plates on top to just glide over it.
Exactly. The convection happening in the deeper mantle, that massive engine room, drags the plates along from below.
So connecting it all together, the massive slow churning in that 80% volume mantle is the engine. And it's dragging these thin floating plates around like pieces of a giant jigsaw puzzle.
That's a perfect analogy. It's a system of constant mass and heat redistribution.
And the action happens where the puzzle pieces meet at the boundaries.
At the boundaries.
Yeah.
Where plates pull apart what we call divergent boundaries, hot mantle material rises up and creates new oceanic crust. That's what's happening at the mid-ocean ridges.
A constructive process. Building new plate.
Right. And where they grind past each other at transform boundaries.
And that's where you get the big earthquakes, like the San Andreas Fault.
That's where you get intense friction, yeah. Massive shallow earthquakes.
And finally, the most dramatic zones. Convergent boundaries. Where they smash together. This is where that density difference becomes destiny.
It really is destiny. When dense oceanic crust meets buoyant continental crust, the oceanic slab always subducts. It sinks.
And that sinking process, that creates the deepest parts of the ocean, the trenches.
The deep trenches, and it also generates melting in the mantle above the sinking slab. That melted rock then rises to the surface.
And feeds the volcanoes on the continent, the volcanic arcs.
And builds massive mountain ranges like the Andes. So the fact that oceanic crust is just 0.2 grams per cubic centimeter denser is the reason we have volcanoes, trenches, and the Andes all along continental edges.
It connects every single one of those features back to basic chemistry and density.
That's the power of the unifying theory.
So what does this all mean for someone trying to grasp this? Let's recap the core takeaways.
Okay, first thing we remember. We know the planet has layers because of physics, not because we've seen them. It's that huge density difference between the whole Earth and the crust.
5.45 versus 2.7.
Right. And that's confirmed by how seismic waves map out the internal boundaries.
Second, composition is key. The whole Earth is mostly iron, but the crust we live on is mostly oxygen and silicon, a low-density skin that's separated from a heavy core.
And third, and this is the big one for tectonics, the whole engine relies on the difference between the two types of crust.
Continental is less dense and thicker,
2.7 grams per cubic centimeter, 20 to 70 kilometers thick.
while oceanic is more dense and thinner.
2.9 grams per cubic centimeter, only 4 to 7 kilometers thick. And that small difference dictates everything we see on the surface.
It's just incredible how such precise measurements dictate the fate of entire continents.
It is. And based on all this, I want to leave you with a final thought to mull over, one about scale.
Okay.
We said the mantle makes up 80% of Earth's mass and volume. That enormous layer, 2,800 kilometers thick, is the powerhouse. Now think about the crust. That fragile skin, ranging from just 4 kilometers thick under the oceans to maybe 70 under the mountains.
Where all known life exists.
All of it. So the question to think about is, how did the sheer size and the compositional dynamics of that vast hidden mantle actually drive the movement, shape the land, and ultimately control the environment of that incredibly thin, fragile surface we live on? It really makes you appreciate the forces at play.
A perfect and humbling thought to consider. Thank you for joining us for this deep dive into Earth's engine room. We'll catch you next time.
Welcome back, everyone, to The Deep Dive.
It's good to be here.
This is the show where we take a huge stack of research, all the data, all the sources, and we just distill it down to the essentials.
Right. The actionable knowledge you actually need to be, thoroughly informed on a topic. We cut through the noise for you.
And today, we are attempting something pretty ambitious, a true feat of internal exploration.
That's a good way to put it. Forget looking out at the stars with the James Webb or sending rovers to Mars. We are journeying deep inside our own planet.
Exactly. We're going to try and decode the internal structure of the Earth, look at its, frankly, strange composition.
And then unravel the magnificent unifying theory that governs literally everything. Every mountain, every earthquake, every single ocean trench. We're talking about plate tectonics.
Okay, let's unpack this then. The sources you've provided they're foundational. They really force you to reconsider the ground you're standing on, that it isn't as stable as it feels. So our mission today is to analyze the evidence. How do we even know the Earth has layers? What's the bizarre chemical recipe that defines them?
And then how do those internal elements generate all the action we see on the surface every single day? It's a mission to the center of the Earth, but one we're doing entirely through deduction.
Some serious planetary detective work.
Exactly. And the discoveries, I promise you, the composition, the density, the sheer scale of what's down there, it's far more surprising than most people realize.
And we're going to start right at the beginning with the most fundamental evidence, some basic facts about density and seismic waves that just completely shatter the idea that Earth is, one solid, uniform ball of rock.
Let's do it.
So when you just look around, the Earth seems solid, right? Stable. You'd think it's just a massive sphere of the same stuff all the way through.
It's the logical assumption. But the science, as you said, tells a very different story.
A really different story. Our sources make it abundantly clear that the Earth has this complex tiered structure.
With both solid and, crucially, liquid components. It's layered, almost like an incredibly dense, incredibly old onion.
And understanding that layering isn't just some academic exercise, it's fundamental to getting a handle on the energy system that drives the whole planet.
Right. But, like we said, we can't just drill down 6,000 kilometers and take a peek, so we have to rely on this planetary detective work. And that starts with two huge, irrefutable pieces of evidence.
The first one is what scientists call the density paradox. This is where the numbers, they don't add up. Not unless there's something massive and heavy hiding deep inside.
Okay, so let's walk through the numbers because they're so important. The density of the rocks right here on the surface, the stuff we see and walk on.
The typical crustal density.
Exactly. It's only about 2.7 grams per cubic centimeter.
Which is relatively light rock, think granite, things like that.
Yeah, the 2.7 is what we measure where we live and build. It feels solid to us, but on a planetary scale, it's actually kind of airy.
And here's the paradox. When scientists calculate the Earth's total mass and its total volume, they figure out that the average density of the whole planet has to be 5.45 grams per cubic centimeter.
Right. That's not a guess. It's a requirement based on the gravitational pull we observe. The planet has to weigh that much.
Okay, let's just pause on that contrast because it's really the linchpin of the whole argument. The surface rocks are 2.7.
But the planet's average is 5.45.
That is more than double the density?
Precisely. And this disparity is the first huge clue. It tells us the Earth cannot possibly be a uniform ball of surface rock. It's mathematically impossible.
So if the outer shell is comparatively light,
then the interior, the vast bulk that we can't see, must contain significantly denser material to balance that average all the way up to 5.45.
We're talking about materials under incredible pressure that are dramatically heavier than anything we'd find on the surface.
Absolutely. So we're forced to conclude there have to be these massive, super heavy, almost certainly metallic layers deep inside.
Otherwise, the total mass of the Earth would be way less than what physics dictates it has to be.
And that density difference, that's the primary non-negotiable proof of a layered, chemically differentiated Earth. It tells us that the Earth is layered.
Okay, so that's the what.
Okay.
The second piece of evidence tells us the where.
Right. Where those layers are, and this is critical, what state they're in, solid or liquid. And that comes from using seismic waves as diagnostic tools.
This is just ingenious science. We don't need giant drills or probes. We use the natural energy released by earthquake.
Every earthquake is basically an internal echo sounder for the entire planet.
It sends out these waves of energy.
Exactly. Seismic waves. And these waves travel through different materials at different speeds. What's really critical here is that earthquakes generate two main types of body waves,
Right.
P waves and S waves.
Okay, so let's define these, because their behavior is how we know almost everything about the deep interior.
So P waves are primary waves. You can think of them as compressional waves, kind of like sound waves. They push and pull the material they move through.
So they sort of squish and stretch the rock as they go.
A perfect way to put it. And crucially, they can travel through solids, liquids, and gases. They are fast, and they can pass through just about anything.
Okay, so P waves go everywhere. What about S waves?
S waves are secondary, or shear waves. They move material from side to side, perpendicular to the direction of travel.
Oh, so like shaking a rope.
Exactly like that. S waves are a bit slower, but here is their absolute defining characteristic. They cannot travel through liquids
Why not?
because liquids can't sustain a shear stress. You can't shake a liquid from side to side and have that wave propagate. The energy just dissipates.
Ah, so that's the diagnostic key.
That is the key. If an S wave is traveling down through the Earth and it suddenly disappears from our sensors on the other side.
Scientists know with absolute certainty that it must have hit a boundary with a liquid layer.
Precisely. And that is how we discovered and defined the outer core. S waves travel through the solid mantle, they hit that boundary with the outer core, and they just vanish. That confirms the outer core is liquid.
That's incredible. What about the P waves then?
Well, both P waves and S waves do something else. They refract, which means they bend, and they reflect, meaning they bounce off boundaries between layers of different densities.
So if a P wave is going from the less dense mantle to the super dense core, it doesn't just pass through smoothly.
No, it bends sharply. It's exactly like light passing from air into water. The change in density changes its path.
It's just wave physics applied on a planetary scale.
That's all it is. And by tracking the time it takes for these different waves to arrive at seismic stations all around the globe, and noting where certain waves, like the S waves, disappear entirely,
You can create a remarkably detailed map of the internal structure.
you can pinpoint the boundaries
Yeah.
between the crust, the mantle, the liquid outer core, and the solid inner core. This differential behavior is what confirms the distinct internal layers and their physical state.
Okay, so to recap, we know the Earth is layered because of the density paradox.
Right.
And we know where those internal boundaries are and which layers are solid versus liquid because of how seismic waves behave.
That gives us the structure.
The blueprint.
That's the foundation. And here's where it gets really interesting. What are these layers actually made of? We've proven the layering exists. Now we move to the elemental secrets, the planetary recipe.
Right. And when we talk about composition, we have to look at two really distinct things, and the contrast between them is just staggering.
You mean the planet as a whole versus just the crust?
Exactly. We need the composition of the entire planet and then just the composition of this very thin skin we live on. And the difference between those two lists tells us so much about Earth's violent early history.
So let's start big picture. The whole Earth composition, the planetary blueprint. If you could somehow average out every single atom from the core all the way to the atmosphere, one element just absolutely dominates the system.
And that element is iron. Fe.
Yeah. Our sources confirm that iron makes up a colossal 35% of the entire Earth. It is the dominant structural material, not just by volume, but by weight and by influence.
35%? That's a third of the whole planet.
It is. Following iron, you have oxygen at 30%, then silicon at 15%, and magnesium at 10%.
So those four elements alone, that's 90% of the entire Earth.
Pretty much the whole recipe. And the presence and dominance of metallic iron, that 35% figure, that fully explains the density findings we were just talking about.
Huh?
The interior is fundamentally an enormous reservoir of metal.
And we know from the seismic data that this massive iron reservoir is further segregated.
The core material contains both the liquid Fe along with some nickel in the outer core.
Which is what the S waves can't pass through.
Right. And then the solid Fe, again with nickel, in the inner core, which is solid due to the immense pressure.
The sheer dominance of iron and nickel, these really heavy, dense elements, that's so profound. It must point to some kind of process, right? They didn't just end up there by accident.
They did not. It points to a process called planetary differentiation.
Okay, we need to spend a minute here. This feels like a key insight that links everything together. What is differentiation?
Imagine the Earth shortly after it formed, maybe 4.5 billion years ago. It was likely a much hotter, largely molten place, a fiery liquid globe constantly being hammered by leftover debris from the early solar
A
system.
giant ball of lava.
Basically. And in that hot liquid state, gravity takes over. It's like if you shake a jar of oil and water and sand. Over immense timescales, the heaviest elements like iron and nickel gravitationally sank through all that molten material.
It just fell toward the center of the planet.
They sink right to the center. It's like a cosmic blast furnace where the heavy slag sinks to the bottom and the lighter impurities float to the top.
So the heaviest stuff, the metallic iron, sank down and created that super dense core.
Which is exactly what we need to get the planet's average density up to that 5.45 GC figure.
And what happened to the lighter stuff?
The lighter, more reactive elements, things like oxygen and silicon, which bond together really easily, they migrated outward toward the surface. They were just more buoyant compared to the pure metal.
So that early sorting process is what created the compositional layering we see today.
It was incredibly efficient, and it set the stage for everything that followed.
Okay, so that's the whole planet, dominated by sinking heavy metals. Now let's talk about that thin skin we live on, the crust.
When we look at the Earth's crust composition, you see a complete elemental inversion, a truly dramatic shift.
Right. While iron dominated the whole planet at 35%.
The most abundant element by far in the crust is oxygen, O2. It makes up approximately 46% of the crust by weight.
46%. That feels so counterintuitive. We think of the crust as rock. We associate oxygen with the air we breathe.
It's what you call the oxygen anomaly. And it's important to remember this oxygen isn't free gas. It is chemically bound up in vast silicate and oxide compounds. It's what forms the rocks and minerals we know. It's the lightest, most reactive element, and it combined with everything else that floated to the surface.
And after that massive oxygen concentration, what's next?
Silicon, C, at about 27%,
So the crust is essentially dominated by oxygen and silicon.
which combine to form the silicates. These are lightweight compounds compared to the dense metals concentrated in the core.
And after those two?
After that, you find aluminum, Al, at around 8%, and only then does iron Fe show up in any significant way.
And it clocks in at a mere 5% in the crust?
Just 5%. It's a huge drop-off. The remaining bit is made up of other key elements like calcium, sodium, potassium, and magnesium.
Okay, so let's just restate that central insight because it's so powerful. Iron dominates the whole planet.
But oxygen dominates the crust.
Which means this thin outer layer is essentially the oxidized, low-density slag that floated to the top when the Earth was differentiating billions of years ago.
And that thinness is so crucial to understand. You can think of the Earth as a peach. The core is the pit. The mantle is the vast, juicy flesh around it. And the crust is the incredibly thin, fragile skin.
I like that analogy.
And that skin, that oxygen-rich layer, it's not uniform. It's segregated into two completely different types of material. And it's those two materials that make plate tectonics possible.
Okay, so to go from the chemistry, the composition, to the movement, the mechanics of it all, we need to focus on the components that are actually relevant to tectonic movement.
Right. Our source material points out that all the action happens exclusively in the crust and the upper part of the mantle.
And this is where we have to introduce a new distinction, right? A mechanical one, which is different from the chemical one we just discussed.
Yes. Chemically, we have the crust and the mantle. But mechanically, we have the lithosphere and the asthenosphere.
Let's define that boundary very clearly, because this is the core distinction that allows the plates to move in the first place.
Okay, so the lithosphere, which literally means the rock sphere, is the rigid, brittle, outermost shell of the Earth.
And it includes all of the crust?
Yes, all of the crust, plus the uppermost, very rigid part of the mantle. This entire layer acts as one solid, unyielding unit.
So when we say tectonic plates, we're actually talking about pieces of the lithosphere.
That's exactly what they are. These are the plates in plate tectonics.
And what about the asthenosphere? What is that?
The asthenosphere is the layer directly underneath. It resides entirely within the upper mantle. Now, it is solid rock, but crucially, it's extremely hot and under a lot of pressure, which makes it ductile and weak.
What does ductile mean in this context?
It behaves plastically. Think of something like silly putty. If you hit it fast with a hammer, it shatters like a solid. But if you push on it slowly, it flows.
Ah, okay. So it's solid, but it can flow over very long geological timescales.
Exactly. So you have these rigid lithosphere plates literally sliding over this weak, ductile asthenosphere. That mechanical separation is the entire foundation of the theory.
The plates are just floating on top of this weaker, flowing layer.
You got it. And the lithosphere itself, the plates, are split into two main types. And it's how these two types behave that determines everything. We're talking about the continental versus oceanic divide.
Okay, let's start with the stuff we're all standing on. The continental crust, the land masses that are, in some cases, billions of years old.
Continental crust has what we call a granitic composition. Granite is characterized by a very high silica content.
Silica being silicon dioxide, SiO2.
Right. We're talking 60 to 70% SiO2. It's made of light-colored minerals like quartz and feldspar. Because it's so high in silica and aluminum, geologists call it felsic.
And its thickness is just staggering compared to the other type of crust. It can range anywhere from 20 kilometers under stable land.
All the way up to 70 kilometers thick under massive mountain ranges like the Himalayas.
And critically, its density is the lowest of all. It's that 2.7 grams per cubic centimeter figure we started with.
It is essentially the planetary styrofoam. It floats high, it resists sinking, and that's why it's so incredibly old and stable.
Okay. Now let's contrast that with oceanic crust, the material that floors all the world's deep oceans.
A completely different animal. Oceanic crust has a basaltic composition. Basalt is rich in heavier elements like magnesium and iron. We call this mafic.
Okay, so felsic is light, mafic is heavy.
In simple terms, yes. And because it's mafic, it has a lower SiO2 content, sitting around 50%. It's a much darker, denser type of rock.
And because it's denser, it's also dramatically thinner.
Oh, yeah. Oceanic crust only measures about 4 to 7 kilometers thick. We're talking about a scale contrast of maybe 70 kilometers for a continent versus, say, 5 kilometers for an ocean floor.
Let me try to put that in perspective. If the Earth were the size of a basketball, the thick continental crust would be like several thick layers of paint in some spots. But the oceanic crust would be more like a single sheet of paper just glued onto the surface.
That's a great analogy. But here's the twist. The paper is heavier than the paint.
Right. The most important contrast is the density. Oceanic crust clocks in at about 2.9 grams per cubic centimeter.
Which summarizes the key insight perfectly.
Yeah.
Oceanic crust is thinner, but it is more dense than continental crust. And that differential density is absolutely critical for how the plates move and interact.
So that tiny difference, 2.7 versus 2.9, that's the whole ballgame.
That's the mechanical force that dictates the fate of the plates.
So if the oceanic crust is denser, it means when it collides with the lighter, more buoyant continental crust.
The oceanic material is mechanically obligated to sink beneath it.
And that's subduction.
That is the genesis of subduction zones, deep ocean trenches, and the vast majority of the world's most violent earthquakes and volcanoes.
All because of that tiny 0.2 grams per cubic centimeter difference.
That difference controls the entire tectonic conveyor belt. It makes the oceanic crust disposable. It's constantly being created and then recycled back into the mantle.
While the continental crust is almost immortal, it just keeps floating.
Exactly. But the energy for this massive slow-motion movement has to come from somewhere, and that brings us to the mantle, the vast engine room of the planet.
The mantle is the layer we so often overlook because it's just invisible, but its scale is hard to comprehend. Our sources note its thickness is a colossal 2,800 kilometers.
That is nearly half the diameter of the planet. It's huge.
And it accounts for 80% of the Earth's mass and volume.
Let that sink in. When we talk about the Earth, 4/5 of what we're talking about is the mantle.
And what's it made of?
It's composed primarily of rock called peridotite. It's a dense, crystalline rock, very low in silica, around 40% IO2. And its density ranges from about 3 up to 6 grams per cubic centimeter as you go deeper.
So if the core is the super heavy anchor.
The mantle is the vast, hot cushion that fills almost the entire rest of the planet.
And what's so fascinating here, as you said, is its dominance. Its sheer vastness means it's the primary reservoir of all the thermal and mechanical energy that drives those surface plates.
And even though it's solid rock, the immense heat coming off the core and the pressure from above cause it to behave plastically, especially in that asthenosphere layer we just discussed.
So we have this relatively thin, brittle layer, the lithosphere, with its two types of crust.
Floating on top of this enormous, hot, dense, and slowly flowing mass, the mantle.
And that thermal energy from the core heats the bottom of the mantle, which creates these slow-moving convection currents.
It's just like boiling water in a pot, but moving at centimeters per year. Hot material rises, cools, and sinks.
And that incredibly slow-moving convection is the enormous geothermal engine that drives the whole surface conveyor belt.
The sheer scale of it, 80% of the planet, means that even though the movement is glacially slow, the resulting force that gets applied to the bottom of the crustal plates is just unimaginable.
So this dynamic relationship, this interaction between the rigid surface plates and the viscous circulating mantle beneath them.
That is the fundamental mechanical reality that gives rise to the unifying theory of geology.
Okay, we've done all the setup, we've established the structure, a super heavy core, a massive flowing mantle, and this thin, rigid shell called the lithosphere broken into plates.
Now we put it all together.
Right. And the theory of plate tectonics is not just one idea among many. It's the comprehensive framework that ties every major geological process, from earthquakes to mountains to continental drift, into a single, cohesive picture.
The theory is really powerful in its simplicity. It just states that the Earth's surface is broken up into these rigid plates, the lithosphere,
And those plates slide over the weaker, deeper, ductile layer.
the asthenosphere, which remember is part of the mantle,
And the brilliance of this framework is how it instantly converts what was just a pile of isolated, seemingly random geological events.
into a single, interconnected global system. It's why our source material calls plate tectonics the unifying theory in geology.
That's a powerful title.
And it's absolutely deserved. Think about what geology was like before this theory was widely accepted in the 60s and 70s.
You had all these separate ideas.
Totally separate, often conflicting theories. You had one theory for how continents moved, called continental drift, another for how mountains formed, called isostasy, another for why volcanoes existed in certain places. They were all siloed concepts.
So the unifying theory connected all those dots. It showed that continental movement and mountain building and deep ocean trenches, they weren't separate phenomena at all.
They were all different manifestations of the same single underlying engine, the movement of these plates.
The movement of the plates causes the drifting, it causes the mountains, it causes the volcanoes.
Yes, it provides a single mechanical explanation rooted in density and heat for almost every major geological process. It explains and supports them all simultaneously.
And the most dramatic, visible examples of that unifying power have to be earthquakes and volcanism.
Without a doubt, if you look at a world map that plots out every earthquake and every volcano,
Mm.
they are not scattered randomly.
Not at all. The source material emphasizes this over and over, the distinct, predictable global pattern of earthquakes and the global pattern of volcanism.
These patterns don't happen in the middle of continents or randomly out in the deep ocean.
Yeah.
They cluster almost exclusively along the boundaries where these rigid lithospheric plates meet.
Where they interact, where they collide or pull apart or slide past each other.
So if you draw a line around where all the world's major seismic and volcanic activity occurs, you are, in effect, drawing the precise outline of the plates themselves.
The process defines the product.
Exactly, and there are three main ways those plates interact, which determines the kind of activity you see. First, you have divergent boundaries.
Like the mid-ocean ridges.
Right. This is where the mantle convection currents are pulling two plates apart. Magma wells up from the mantle to fill the gap, creating new oceanic crust.
And what kind of activity do you get there?
Relatively gentle earthquakes and very predictable, quiet volcanism. Not explosive.
Okay, then you have transform boundaries.
This is where plates slide past each other horizontally. That sideways motion builds up an immense amount of friction and stress.
And when that friction is suddenly released,
You get massive, shallow, destructive earthquakes. This is what you see along the San Andreas Fault in California. Typically no volcanoes, just a massive release of seismic energy.
and finally the most violent interaction, which brings us all the way back to our density discussion, convergent boundaries.
This is where plates collide.
Huh.
And this is where that tiny density difference between 2.7 and 2.9 becomes catastrophic.
So when the less dense continental crust collides with the denser oceanic crust,
The oceanic slab is forced to subduct. It has to sink back down into the mantle.
and that sinking process, that friction,
It causes the deepest, most powerful earthquakes on the planet. And it melts the sinking slab, which leads to the explosive chains of volcanoes we see all around the Pacific Ring of Fire.
so the lighter continental crust just rides high like a massive stable raft.
While the denser, thinner oceanic crust sinks back into the mantle when it gets pushed, completing the cycle. It is a slow, relentless planetary recycling program.
It's a closed, dynamic system. It's driven by the immense internal heat from the core, and it's governed by these simple rules of density and buoyancy and mechanics.
If we connect it all back to the big picture, the movement of these rigid plates over the weaker, deeper mantle is the fundamental engine that shapes our entire world.
And that energy from that massive 80% volume mantle layer gets channeled into these narrow plate boundaries, manifesting as geological creation and destruction.
And that initial small density difference we talked about,
Yeah.
and it's literally responsible for the existence of the Andes Mountains, the Marianas Trench, and every explosive volcano on Earth.
Wow. Plate tectonics really is the operational guide to understanding why our planet looks the way it does.
It is, okay.
We have covered an incredible amount of ground today. We've gone from gravitational calculations to seismic wave physics, all the way up to the global mechanism of plate motion.
It's been a journey.
It has. So let's try and synthesize the most surprising, most important nuggets of knowledge that we've extracted from all this. The things we really want you, the learner, to carry forward.
For me, the first one has to be the density paradox.
I agree.
That shocking contrast between the light, 2.7 GCC crust, and the required 5.45 GCC average density. That alone proves the existence of a high-density metallic iron-nickel core. It validates the whole concept of differentiation before you even look at anything else.
And the second one for me is the elemental switch. The fact that the planet is engineered in such a way that iron dominates the bulk composition at 35%.
Yet oxygen dominates the surface crust at 46%.
Yeah. That segregation of heavy metals to the core and light silicates to the surface defines planetary differentiation. It explains why the surface is so low density and buoyant in the first place.
And finally, the third big takeaway has to be the mechanical consequence of all that differentiation. The critical difference between oceanic and continental crust.
Right. It's not just that the oceanic crust is thinner, 4 to 7 kilometers versus up to 70.
It's that its slightly higher density 2.9 versus 2.7 seals its fate. It forces subduction and organizes all of the planet's major earthquakes and volcanism into those predictable, narrow, global patterns along the plate boundaries.
So this foundational knowledge, it really provides you with a completely new lens for understanding current events. The next time you hear about a major earthquake, you'll know it's not some random event.
It's the inevitable consequence of a brittle, rigid layer, the lithosphere, moving over that ductile 2,800 kilometer thick engine, the mantle.
Everything is connected to that slow, deep convection that's driving the surface, moving whole continents at about the same speed your fingernails grow.
Which leads perfectly to our final provocative thought for you to consider.
Go for it.
We learned that the mantle is a behemoth. It makes up 80% of the Earth's mass and volume. It operates almost entirely out of sight, driving these surface processes that take millions and millions of years to fully unfold.
We can measure the plates moving now, but we're only seeing an instantaneous snapshot of the surface.
Exactly. So given that immense scale and that deep geological timeline, what unseen compositional changes are happening in that 80% right now? Changes in temperature, or in the rate of convection, or maybe the stability of the asthenosphere itself. Changes that future geologists millions of years from now will look back on and realize defined a major new era of Earth history.
That's a powerful thought.
It's just a reminder that beneath our feet, the geological story is constantly being written, and the most important chapters are happening right now in the darkness.
Keep digging.
Keep learning. We'll see you on the next deep dive.
Okay, let's unpack this. Welcome back to the Deep Dive. Today, we are strapping in for what is perhaps Earth's most dramatic and certainly most terrifying natural phenomenon, the earthquake.
It really is.
And we are taking a full, scientifically rigorous deep dive into the source material a listener shared, completely bypassing the headlines to get to the fundamental physics of seismology.
That's absolutely right. Our mission today is a journey of discovery, relying entirely on Earth science. We're focusing on three interconnected questions. First, what is the precise underlying mechanical engine? How exactly does the Earth store these massive amounts of energy only to release it so violently?
And second, we're going to decode the secret language the Earth speaks when this happens, the seismic waves. We need to know who those messengers are, what they tell us, and critically why they travel at different speeds.
And third, we are going to use those waves as a kind of window, allowing us to peer thousands of kilometers beneath our feet to reveal the mysterious layered structure of the Earth's interior. The parts we can never, ever touch or drill into.
And what makes this deep dive so potent are the specific foundational concepts that define modern seismology. I'm especially looking forward to detailing the sheer elegance of the elastic rebound theory.
It's a game changer.
It is. And the absolute critical difference in speeds between the P&S waves, those 6.1 versus 4.1 kilometers per second markers, and crucially, the shift we've made from the limited Richter scale to the superior geologically informed moment magnitude scale. This is about understanding Earth's power at a scale we can actually grasp.
It is. It's about moving past what happened to the deep mechanics of how and why. So let's start right at the source, examining the engine of catastrophe itself.
So let's begin with the absolute basics. When we feel an earthquake, what we're feeling is the vibration of Earth. It's produced by the rapid release of stored energy.
And it is an event of failure. That release happens when brittle Earth material fails under stress. It either forms a brand new fracture or, much more commonly, it slips along an existing one.
That failure point is precisely where all the action starts.
It is. That sudden, instantaneous slip generates a massive pulse of energy that propagates outward in all directions as elastic waves. And those are the detectable seismic waves we measure.
And this gives us our first crucial set of terms that even professionals sometimes confuse.
They do.
Right, the difference between where it starts and what we see above it. The hypocenter versus the epicenter.
The hypocenter, or the focus, is the specific point within the Earth where the actual energy release occurs, where the rock failed. It is the true source of the earthquake.
Then the epicenter.
The epicenter, on the other hand, is just the spot on the Earth's surface directly above that focus. And while the epicenter is what we map and what you see in news headlines,
Understanding the location and, critically, the depth of the hypocenter is far more valuable for seismologists.
oh, immensely. The depth tells you so much. A shallow earthquake is generally far more destructive than a deep one of the same magnitude.
With all of this failure, this slipping, it happens along faults, which the source material simply defines as fractures in the earth where movement has occurred.
And this movement isn't random. It's governed by a cycle of accumulating stress and then sudden release. Which brings us to, I think, the monumental breakthrough in seismology, the elastic rebound theory.
This theory is truly the aha moment. It wasn't until H.F. Reed meticulously analyzed the data from the great 1906 San Francisco earthquake that we moved past these sort of vague concepts of movement and got a concrete mechanical explanation.
Yes, how energy is stored and then violently released.
Reed's genius was realizing that the energy wasn't just there, it was being stored through deformation, much like winding up a spring or, pulling back a slingshot.
That's a great analogy. Let's walk through the exact steps this model outlines, because it is the fundamental mechanism that generates virtually every major tectonic earthquake.
Okay, start the clock on the stress accumulation.
So, step 1. Tectonic forces, driven by plate movement, are constantly pushing or pulling, slowly but inexorably deforming the rocks on both sides of a fault.
The land on either side is trying to move relative to the other.
It's trying to, but the Earth is incredibly strong, so it resists that movement initially. The rocks bend, and in bending, they are storing vast amounts of potential energy, elastic energy. Think of a giant, thick steel ruler being slowly bowed. It's holding a tremendous amount of tension.
And this phase of stress buildup can last years, decades.
Or even centuries, which is exactly why earthquake prediction is so difficult. The stress is invisible. It's the slow motion deformation.
Wait, if the rocks are bending for decades before the earthquake, why don't instruments on the surface detect that slow deformation before the snap?
That's a fantastic question, and seismologists do detect it now, especially with modern GPS and high-precision strain meters. They measure what is called seismic creep or slow slip events. But historically, and relative to the sudden release, that slow deformation is imperceptible without those modern tools. And this slow movement is also resisted by the third critical step, frictional resistance.
Frictional resistance is the grip, the glue.
Exactly. This enormous frictional force holds the rock faces together, preventing movement even as the elastic stress builds to these monumental levels. The movement wants to happen, but friction is just too strong.
So the stress reaches a critical threshold.
And that's the final release. Step 4. When the accumulated stress finally overcomes the sheer strength of the rock and the frictional resistance holding it, sudden slippage occurs at the weakest point, the hypocenter. This is the earthquake itself. This release is extremely fast.
And then the signature action that gives the theory its name.
The elastic rebound. The vibrations we feel occur as the deformed rock, now released from friction, rapidly springs back or rebounds toward its original undeformed shape.
So it's literally the physical snapping of the bent material that sends those powerful waves radiating outward.
That's it. If you were standing on the surface during the event, you would see the ground on one side of the fault shift relative to the other, but the motion would be fueled by the instantaneous return to that relaxed post-slip state.
That distinction, that the earthquake is caused not just by the slip, but the snapping back of the material, makes the energy source much clearer for me, and I'm sure for you, the listener.
It connects the physics of elasticity directly to the global movement of plates. This accumulation and release defines tectonic activity worldwide.
Speaking of tectonic activity, we know the vast majority of major quakes happen along plate boundaries, where plates collide, diverge, or slide past each other. But the sources surprised me with how many non-tectonic sources can also trigger a measurable seismic event.
This really broadens the scope of seismology significantly. While, maybe 90% of large quakes are tectonic, there are powerful localized stresses that can induce seismicity. We often call these induced earthquakes.
What are some of the most surprising examples?
The human factor is incredibly relevant today. The source mentions hydroelectric projects. The massive weight of water in large reservoirs, like the one behind the Koyna Dam in India, a very well-studied case, can stress the underlying crust sufficiently to trigger movement on pre-existing faults.
So faults that were already near their breaking point.
Exactly. That localized pressure change is just enough to destabilize the crust.
And in modern times, hydraulic fracturing or fracking often comes up in this conversation.
Precisely. The injection of fluids deep underground, particularly wastewater disposal, can increase the pore pressure within rock formations. This acts as a kind of lubricant.
It reduces the friction.
It reduces the effective frictional resistance along existing faults, accelerating the failure process. This has led to measurable, significant increases in seismic activity in regions like Oklahoma, which historically had very few earthquakes.
So we're not necessarily creating new stress, we're just
Yeah.
reducing the friction that's holding the existing stress in check.
That's a perfect summary. We are moving the fault closer to its breaking point by reducing the necessary grip.
And other non-tectonic sources are more explosive, literally.
They are. Volcanic activity, as magma moves beneath the surface, creates measurable tremor. Large landslides hitting valley floors or water bodies can register. And then we have the instant, massive external forces.
Like large meteorite impacts or human activities like controlled mining explosions or even nuclear blasts.
Absolutely. Seismographs around the globe are incredibly sensitive. The USGS constantly monitors for human-caused seismic events, particularly nuclear tests, because they generate these detectable signature P waves that allow analysts to distinguish them from natural tectonic activity.
So whether the event takes a century of elastic stress buildup or a fraction of a second via an explosion, the result is the same.
The generation of those elastic waves.
That's our perfect transition. We've defined the engine. Now we need to define the language it speaks. Let's move into part 2 and understand those messengers traveling through the Earth.
If the earthquake is the voice of the planet, the waves are the words. The entire field of seismology is devoted to studying these waves.
And the tools of the trade are the seismographs. I find the physics behind them beautiful in its simplicity. They are designed to measure the movement of the Earth relative to a stationary mass.
Right. The Earth moves, but the heavy mass, suspended by springs or wires, lags behind due to inertia, and that allows the instrument to record the relative movement.
That relative movement is recorded as the seismogram, that squiggly line we've all seen. This detailed trace is the raw data that allows seismologists to analyze the event.
But the analysis relies entirely on our ability to distinguish between the three major categories of waves: the body waves and the surface waves.
Let's start with the body waves, those that travel through the planet's interior. First up are the P waves, or primary waves,
Named because they are the first to arrive.
the first to the party.
P waves are the uncontested speed champions. They travel at phenomenal speeds, around 6.1 kilometers per second in the upper crust, and they increase dramatically as they go deeper. But their defining characteristic is their motion. They are compressional, or push-pull waves.
What does that mean in practical terms for the rock?
It means the rock material is compressed and stretched, like the coils of a slinky being pushed together and pulled apart in the same direction that the wave is propagating. The energy moves through the material by literally squeezing and expanding it.
And because of that specific, pure compressional motion, P waves are incredibly flexible in terms of the medium they can travel through.
This is an absolutely crucial point for seismology in our understanding of the Earth's interior. P waves can travel through solids, liquids, and gases.
Anything that can be compressed.
If there's material present that can be compressed, the P wave can move through it. They maintain the greatest velocity of all earthquake waves precisely because they are not limited by the state of matter. They are the initial warning sign, arriving first at every single station.
Now let's contrast that with the S waves, or secondary waves. They are the second arrivals, substantially slower.
S waves lag considerably behind P waves, traveling at roughly 4.1 kilometers per second in the upper crust. Their motion is fundamentally different. They are shear waves, characterized by a shake motion.
So the rock deformation is perpendicular at right angles to the direction of wave travel.
Exactly. Imagine holding a rope and quickly snapping your wrist up and down. That's the motion.
And that motion creates a huge physical requirement for the material it's traveling through.
It does. Shear motion requires that the material resist being pulled out of shape. It needs what we call shear strength.
Yeah.
If you push on a liquid or a gas, it simply flows. It doesn't resist that deformation. Therefore, S waves can travel only through solids.
Only through solids.
If an S wave hits a liquid boundary, it is immediately stopped, reflected, or converted into another wave type.
This single physical principle is the most important takeaway for understanding the deep Earth. The limitation of the S wave is what gave us the internal map of our planet.
It is the scientific linchpin. The existence of the liquid outer core, which we'll get to later, is proven entirely by the systematic absence of S waves in certain zones.
So we have P and S body waves traveling through the interior. But when we look at destruction, the surface waves, though they're the slowest, are often the culprits.
The surface waves are truly the destruction agents. They cause the visible collapse and the ground displacement. They are complex manifestations of P and S wave energy. They get trapped and travel only along the outer part of the Earth, not through the interior.
They are the slowest, so why are they the most destructive?
They possess a couple of characteristics that amplify their impact. First, they exhibit the greatest amplitude, meaning the physical size of the wave oscillation is largest at the surface. And second, they have the property of least attenuation.
Least attenuation. Can you unpack that for the listener?
Sure. Attenuation is the loss of energy over distance. Because surface waves travel along the surface boundary, they lose their energy very slowly compared to body waves that dissipate energy throughout the entire volume of the Earth.
So they can travel the furthest distances while still retaining massive destructive power.
Exactly. They are slow, massive, and persistent. They have a complex motion. The sources describe two main types: love waves, which are side-to-side shearing motion, and Rayleigh waves, which are the rolling vertical motion, kind of like ocean waves.
And they also typically have lower frequencies than body waves.
They do, which often synchronizes poorly with the natural resonance frequencies of large human structures, maximizing the damaging oscillation. If you feel a prolonged, rolling, violent shake, that's the surface wave energy.
Okay, we've differentiated the types of waves, but the sources stress that their velocity isn't fixed. It changes based on the material. This is where the waves become a diagnostic tool.
This moves us into understanding Earth heterogeneity. Wave velocity depends entirely on the material's elastic properties, specifically its bulk modulus and its shear modulus.
Okay, these sound like textbook terms. Can we explain them practically?
Certainly. The bulk modulus is simply the material's resistance to compression. A high bulk modulus means the material is rigid and resists being squeezed.
And the shear modulus.
That's the material's resistance to shape change, how much it resists the shearing side-to-side motion of an S wave. The greater these moduli, the faster the wave travels.
And inside the Earth, these properties are constantly changing with pressure and temperature.
Immensely so. As depth increases, two things happen. First, the temperature rises, which tends to soften the rock and would naturally slow the waves down. But far more powerfully, the immense pressure increases, which makes the rocks dramatically more rigid and incompressible.
So pressure is the dominant force in the deep mantle.
It is. The crushing force of gravity compacting the material wins out over the softening effect of heat. This general trend causes seismic wave velocities to increase the deeper they travel through the mantle.
And since the waves are traveling faster in the deeper layers, they don't follow straight lines.
That's the key investigative detail. When seismic waves encounter a geological boundary, a transition between materials with dramatically different elastic properties, say the boundary between the crust and the mantle, two things happen. They reflect, bouncing off the boundary, and they refract.
Refract, meaning they bend.
They bend. This bending causes them to follow curved paths back toward the surface.
It sounds like light bending as it passes from air into water.
It's the same physics. It's really the same principle. Seismologists can measure the angle of those reflections and refractions, and by plotting those paths, we can determine exactly where the boundaries are and what the material properties must be on either side. We are mapping the Earth's interior entirely by measuring these subtle shifts in velocity.
It's incredible how the differences in wave speed, just a few kilometers per second, are enough to generate the data that allows us to map the entire planet. And that difference in arrival time leads us directly into our next section, measuring the location of the event.
Absolutely.
We've established that P waves are faster than S waves. That speed difference is the foundation of locating an earthquake's epicenter through the process we call triangulation.
Triangulation is an elegant mathematical solution to a physical problem. Because the S wave is slower, the further away a seismograph station is from the epicenter, the greater the time gap or lag between the arrival of the first P wave and the first S wave.
This is the crucial data point, the PS lag time. If the lag is 2 seconds, you're close. If it's 2 minutes, you're hundreds of miles away.
That's the entire premise. The task for seismologists is turning that measured time difference into a concrete distance. They do this by using pre-calculated P and S wave travel time curves.
How do those curves work?
Well, these curves are the cumulative result of decades of global seismic data analysis, and they show the precise relationship between distance and arrival time. For any given PS lag time you observe at a station, you can look at the curve and say, for this difference to occur, the waves must have traveled exactly X distance.
So the station calculates its distance, and now the triangulation begins. One station gives us a radius, right? Meaning the epicenter is somewhere on a giant circle centered at that station.
Exactly. That circle is purely a distance measurement. A single measurement gives you infinite possibilities. To pinpoint the location, you have to gather readings from at least 2, but preferably 3, different seismograph stations.
And when you draw the second circle, you narrow the location down to just 2 potential intersection points.
And the third station eliminates the ambiguity. The point where all 3 of those circles intersect is the precisely calculated epicenter of the earthquake. It's a remarkable system that relies on incredibly sensitive timing and the consistent, predictable physics of wave travel through the Earth.
Moving from location to size, we have to clarify the distinction between intensity and magnitude. These are 2 terms the public uses interchangeably, but they mean completely different things to a scientist.
This is a critical distinction. Intensity is a measure of the degree of shaking at a specific location. It's subjective and based entirely on local effects, what happened to structures, people, and the landscape right there.
And the common scale for that is the modified Mercalli intensity scale.
Correct. It runs from Roman numeral I, which is not felt, up to 12, catastrophic destruction. It's invaluable for emergency planners because it tells them what actually happened on the ground, but it doesn't tell us how powerful the event was at its source.
And that's where magnitude comes in.
Exactly. Magnitude is the scientific estimate of the total amount of energy released at the source, the hypocenter. It's an absolute measure of power.
For decades, that absolute measure was the Richter scale. Developed by Charles Richter in the 1930s, it was based on the amplitude, the height, of the largest seismic wave recorded by a standardized seismograph. It revolutionized early seismology.
It really did. But the numerical relationships on that scale are what truly convey the power of these events. The scale is logarithmic, not linear.
This is where we need to spend some time because it's so important.
It is. The Richter scale is deceptively simple. Each unit of increase, say, from a 5.0 to a 6.0, corresponds to a 10-fold increase in the measured wave amplitude. That alone is enormous. But the energy relationship is what matters for destruction.
Unpack that energy nugget for us.
That single unit increase translates to a substantial 32-fold increase in the total amount of energy released by the earthquake. Going from a 6.0 to a 7.0 is 32 times the power.
So think about the difference between a magnitude 6 earthquake, a major event, and a magnitude 8.0. That's 2 units. That's 32 times 32.
Meaning the 8.0 event releases over 1,000 times more energy than the 6.0.
That is an astronomical jump in destructive potential. A magnitude 9 event is almost 1,000,000 times more powerful than a magnitude 5.
It illustrates why preparation for a magnitude 9 event requires planning on a completely different scale than for an 8.0, even though they are numerically close. But despite this impressive logarithmic scale, the source material correctly notes that the Richter scale is no longer preferred for large events.
Why the shift? What were the limitations that made it obsolete for major quakes?
The primary limitation is something called saturation, because Richter relies on the amplitude of a specific short period wave for truly massive earthquakes, those that involve ruptures hundreds of kilometers long. The scale tended to saturate.
What does that mean, saturate?
It means a magnitude 8.5 quake might only register marginally higher than a magnitude 8.0 on the Richter scale, even though the 8.5 event released vastly more energy over a much larger area and duration. It just couldn't capture the full scope of the rupture.
So it was an instrument-specific measurement that didn't fully account for the geological reality of the fault failure itself.
Exactly. This led to the adoption of the modern standard, the moment magnitude scale, which directly measures the total energy released. It's a physical geological measurement.
And the moment magnitude scale overcomes the saturation issue by calculating the seismic moment. It moves beyond just the seismogram amplitude and focuses on the 3 physical factors of the rupture.
That's its genius. Instead of measuring the squiggle, we measure the physical size of the failure. The 3 factors are, first, the average amount of displacement along the fault. How many meters or tens of meters did the ground actually move? Second, the total area of the rupture surface. Was the fault slip 50 kilometers long or 500 kilometers long? And third, the shear strength of the faulted rock. How much resistance did the rock offer before it failed? This relates to the rigidity and pressure at the fault depth.
By incorporating the shear area of the rupture and the movement, It captures the complete picture of energy release, especially for those enormous events.
It provides consistency and accuracy, particularly on the high end of the scale. And to give you, the listener, context on just how powerful the high end is, the sources list the 5 largest recorded earthquakes since we began accurate measurement.
These are planet-shaping numbers. The largest recorded event was in Chile in 1960 at a magnitude 9.5.
An unbelievable amount of energy.
That's followed by the 1964 Alaska event at 9.2 and the devastating 2004 Sumatra Boxing Day event at 9.1. Then we have Japan, 2011, and Russia, 1952, both registering 9.0.
And remember, that 32-fold difference. The 9.5 event in Chile was over 3 times more powerful in energy release than the 9.0 events in Japan and Russia. The scale is just immense, and the moment magnitude scale is necessary to appreciate that difference fully.
The sheer physics of those numbers leads us directly to the physical consequences. Let's move to part 4 and discuss the destruction earthquakes unleash.
When we talk about destruction, it's rarely just the size of the magnitude that matters. Structural damage is a complex interplay of 4 key factors that city planners and engineers must always consider.
The first 2 are related to the seismic source itself, the intensity of the earthquake, and, crucially, the duration of the vibrations.
A short, sharp tremor is manageable, but a prolonged shaking period, sometimes lasting for minutes, especially with surface wave subjects structures to cyclic loading that rapidly accelerates fatigue and failure. Duration is absolutely lethal.
The third factor is all about the foundation, the nature of the material upon which the structure rests.
This is often the hidden killer, particularly in major urban centers built on river deltas or reclaimed land. Poor ground conditions can amplify seismic waves or lead to catastrophic ground failure.
And the final factor, of course, is the human element, the design of the structure itself.
Whether it was built to code, whether it has flexibility, and whether it is aging appropriately. Let's detail the hazards themselves, starting with the immediate primary effect: ground shaking.
This is the direct result of those PS and surface waves interacting with the surface environment.
Yes, and it's important to note that the shaking is not uniform, but the sources point out that within the core rupture zone, it's consistently intense. Regions within 20 to 50 kilometers of the epicenter often experience the same peak intensity of shaking.
So within that core zone, whether you're right on the fault line or 40 kilometers away, the potential for catastrophic ground shaking is nearly equal.
Pretty much, yes. But a more insidious hazard, especially in areas with unstable ground, is ground failure and liquefaction. I want us to spend time on this one because it's responsible for so much widespread, non-structural collapse.
Liquefaction. It sounds terrifying.
It is a terrifying process. It happens when unconsolidated materials like loose sand, silt, or artificially dumped fill that are saturated with water are subjected to strong, cyclic seismic shaking.
Walk us through what happens to the ground.
The vibration temporarily increases the water pressure trapped between the individual grains of soil. This pressure increase forces the grains apart, causing the material to lose its effective strength and rigidity entirely. It temporarily behaves like a mobile fluid.
So the ground is no longer solid. It's acting like quicksand, even if it looks dry on the surface.
Exactly. Imagine trying to stand a massive structure on a bowl of watery oatmeal. It just collapses and sinks. Buildings tilt, foundations fail, underground pipes float up to the surface, and infrastructure systems are completely destroyed.
This hazard is why areas built on historic marshes or coastal fill are exponentially more vulnerable than those built on bedrock.
Absolutely. Next, we have the immense destructive potential of the tsunami, or seismic sea wave, which, as the source materials remind us, is a completely different phenomenon than a tidal wave.
Right, tides are gravitational. This is displacement.
It's pure displacement. Tsunamis are destructive waves generated by the sudden, massive vertical movement of the seafloor, usually a thrust fault during a major subduction zone earthquake. That upward or downward motion displaces the entire water column above it.
And they can travel across entire oceans, almost unnoticed in the deep water, only to surge to enormous heights when they hit shallow coastlines.
The speed is incredible in the open ocean, often comparable to a jet plane, and because the wave is the entire depth of the ocean, the energy is enormous. When they interact with a shallow coastal shelf, the wave height grows dramatically, leading to catastrophic coastal flooding and scouring far inland.
And finally, we have the secondary hazards that often compound the chaos after the primary shaking stops.
These are often the most difficult to manage in the immediate aftermath. We see landslides triggered by instability on steep slopes, ground subsidence where the land level drops permanently, and critically, secondary damage like massive fires.
And the fires are so hard to fight.
Because they're often caused by ruptured gas lines and electrical failures, compounded by the fact that water mains are frequently broken simultaneously by the shaking and liquefaction. It makes firefighting almost impossible.
To make these concepts stick, let's look at 3 specific historical events cited in the sources, starting with the 1989 Loma Prieta earthquake in California, a magnitude 6.9 event.
Loma Prieta is a great case study for infrastructure vulnerability. While it was a moderate to large event, it famously demonstrated the fragility of elevated structures built on soft material. The collapse of a section of the Nimitz Freeway, for example, was a clear consequence of different soil types reacting differently to the seismic energy.
It highlighted the need for stricter engineering standards.
It really did. Then we have the tragic 1985 Mexico City earthquake. The epicenter was far offshore, yet the city suffered catastrophic damage. This speaks directly to that third factor we mentioned, the ground material.
It's the quintessential example of the amplification effect of soft ground, isn't it?
It is. The city sits primarily on the soft, water-saturated clay remnants of an ancient lake bed. The seismic waves, as they transition from the hard bedrock surrounding the basin into that soft, sort of gelatinous clay, were amplified in both amplitude and duration.
Like a bell being rung.
That's a great way to think of it. The city's foundations literally shook longer and harder than they should have, leading to the disproportionate collapse of mid-rise structures. It turned a distant tremor into a localized catastrophe because of the underlying geology.
And finally, the ultimate demonstration of the tsunami hazard. The 2004 Boxing Day earthquake off Sumatra, a magnitude 9.1.
The 2004 event was a generational defining disaster. The rupture surface was estimated to be over 1,500 kilometers long, a massive scale that the moment magnitude scale finally allowed us to appreciate.
And the subsequent displacement of the seafloor was so vast.
It generated a series of colossal tsunamis that crossed the entire Indian Ocean, impacting coastal communities in over a dozen countries, stretching from Indonesia all the way to East Africa.
It drives home that seismic hazards are not contained. A 9.0 event in the Pacific can affect the entire Pacific Rim.
It connects global seismology to coastal geography and demonstrates the need for global warning systems, a direct application of the science we're discussing. The historical context shows us that ground motion and wave behavior are the primary architects of destruction.
And the knowledge of those wave behaviors is now going to serve a completely different purpose. We're going to use them to solve the Earth's greatest mystery. What's inside?
This is the most profound application of seismology. We cannot drill more than a few kilometers into the crust. Therefore, earthquakes provide the only practical and comprehensive window we have into Earth's deep interior.
It's the ultimate investigative tool, reading the planet's internal structure entirely through wave paths. We can start with the basic layers defined by their composition.
Compositionally, the layers are straightforward. The relatively thin, rocky outer skin we live on, the crust, the massive rocky shell underneath, the mantle, which accounts for, I think, about 84% of Earth's volume, and finally, the extremely deep, dense, iron-rich core.
But seismology allows us to move past composition and define the Earth based on its physical properties, how rigid, weak, or liquid the material is. This is the definition set that is most critical for plate tectonics.
Absolutely. We start with the lithosphere. This is the rigid outer layer, comprised of the entire crust and the uppermost mantle. This is the cold, strong, brittle plate itself, the part that moves and breaks, causing the earthquakes we study.
And beneath that rigid shell, we find the critical layer that enables plate movement.
That is the asthenosphere. It's located beneath the lithosphere,
Right.
and though it's still chemically part of the mantle, its physical properties are dramatically different. It is soft and weak, almost plastic, allowing it to flow very slowly.
And this difference in strength is what permits the rigid lithospheric plates to glide, float, or slide across the top, driving plate tectonics.
That's the mechanism. Below that weak layer, rigidity returns. The mesosphere, or lower mantle, is below the asthenosphere. Despite the intense heat, the pressure is so immense that the rock becomes much more rigid again. This pressure ensures that seismic wave velocities increase rapidly through this lower region.
And finally, the core, which is defined by 2 different physical states.
The outer core is the layer that is definitively liquid. It's a vast ocean of molten iron and nickel. Its convection and movement are responsible for generating Earth's magnetic field.
And deep inside that,
Deep inside, extreme pressure overwhelms the temperature, forcing the iron atoms into a crystalline structure to form the dense, solid inner core.
Okay, we have this model, but how do we know, for example, that the outer core is liquid? We can't get there. That certainty comes back to our messengers, the P&S waves and the concept of shadow zones.
This is the moment when the physics of wave travel confirmed the internal map of our planet. The behavior of seismic waves provided the direct, irrefutable proof of the state of these deep layers.
Let's focus on the definitive proof for the liquid state, the S-wave shadow zone.
So, recall the critical limitation of the S-wave. It requires sheer strength. It cannot travel through liquid. The S-wave shadow zone is a huge belt spanning roughly 103 degrees to 180 degrees angular distance from the epicenter on the side of the Earth opposite the earthquake, where S-waves are simply not detected. They are stopped completely. They vanish.
If S-waves were traveling all the way through, we would detect them globally. The fact that they vanish in this enormous zone proves something massive and liquid is in the way.
It is the single direct piece of evidence proving the outer core is liquid. The S-waves hit the solid mantle liquid core boundary and are absorbed or blocked because the liquid iron lacks the necessary shear strength to transmit the wave. No other scientific observation is required for this conclusion.
So the lack of a wave tells us more than its presence.
In this case, yes.
Meanwhile, P waves, which can travel through liquid, still produce their own unique pattern of absence, the P wave shadow zone.
The P-wave shadow zone exists, but for a different reason. As the P-waves hit the core mantle boundary, they encounter a massive change in density and elastic properties. This causes them to be dramatically refracted or severely bent.
They bend so much that they skip a certain area on the far side of the planet.
Exactly. The extreme refraction creates a P-wave shadow zone between about 103 degrees and 142 degrees from the epicenter. The P-waves that pass through the core are bent inward, causing them to reappear outside that 142-degree mark, having traversed the liquid outer core.
So the P wave data confirms the size and location of the boundary.
While the S-wave data confirms the state of the material inside it, it is a complete internal picture created purely from analyzing the travel times and the physical properties of seismic waves. It's seismology giving us X-ray vision of our own planet.
It is the triumph of theoretical physics applied to observational geology.
It really is.
That was an immensely detailed deep dive into the language and engine of earthquakes. To quickly synthesize the most valuable takeaways for you, our listener, remember the clear distinction between the three wave types. P waves are fast and compressional.
S-waves are slower and sheer motion, and crucially, S-waves cannot travel through liquid.
Right. And when measuring an event, locating the epicenter is a function of the PS lag time, while measuring the total energy released is now achieved using the moment magnitude scale.
And that scale uses the physical parameters of the rupture displacement, area, and shear strength to give an accurate picture of total power, making it vastly superior to the amplitude-based Richter scale for large events.
But as we close, let's return to the interior. The S-wave shadow zone proves the existence of that liquid outer core. What does the existence of that vast, deep, churning sea of liquid iron imply for the processes happening on Earth, far beyond just seismology and geology?
It implies everything about habitability. The liquid outer core is not just a geographical layer, it is the engine room of the geodynamo. The convection currents within that liquid metal generate the immense electric currents that create Earth's magnetic field. This field is our planetary shield. Without the magnetic field, the solar wind would gradually strip away our atmosphere, and life as we know it would become unsustainable. The existence of the S-wave shadow zone and the discovery of the liquid outer core that it verified is fundamentally essential, not just for seismology, but for understanding why our planet is the way it is, a dynamic, living world with sustained plate tectonics and a protected atmosphere. It reminds us that the processes discovered deep beneath our feet are still violently active and incredibly important right now for every breath we take.
A profound thought to end on. Thank you for joining us for this deep dive.
Welcome back to the Deep Dive. Today, we are kicking off a really fundamental geological journey.
We really are.
You know, all those things we rely on every single day. The copper in the wiring in your home, the platinum in your car's catalytic converter, the aluminum in an airplane.
Or even just the gravel under the highway you drove on this morning.
Exactly.
Yeah.
We almost never stop and think, where did all this raw material actually come from?
And that's the thing, it's not random. We live in a world that is I mean, it's literally built on concentrated mineral wealth. But that wealth isn't just scattered around.
No.
It's the result of these incredibly complex, sometimes deep-seated, and often, just spectacular geological sorting mechanisms that have been working for billions of years.
So our mission today is to synthesize these surprisingly diverse geological factories that create these resources for us. We're going to dive deep into the 5 main processes, right? From the intense heat of the Earth's core all the way up to surface weathering to see how elements get concentrated into forms we can actually use.
And this deep dive, it's really tailored for you, the listener, who wants to get a quick but thorough handle on the mechanics behind all this. We're going to zero in on the key examples and the science underneath.
So you can walk away not just knowing what we think, but why a certain metal is only found in, say, 1 or 2 very specific places on the entire planet.
That's the goal.
Okay, so before we dive in, let's establish a bit of a common language. I think we need to be really specific about some terms, because in geology and, economics, the difference between a resource, an ore, and a reserve is, well, it's everything.
It's absolutely crucial. Let's start with the biggest, broadest concept: mineral resources.
Okay.
Simply put, this is just the entire inventory. It's any element, any compound, mineral, rock, anything that's been concentrated in a form that could, potentially be extracted and turned into something useful.
Potentially. That's the key word there.
It is. It's the geological possibility.
But just because it exists doesn't mean we can get to it or that it's worth getting to. And that, I think, brings us to the next step down. Or.
Yes. Or is where geology smacks right into economics. Into the spreadsheet, as you said. Or refers specifically to useful minerals, metallic or not, that can be mined. And this is the critical part. At a profit.
So profitability is the only real distinction.
It's the great filter. You could have an entire mountain that's, peppered with copper, but if that concentration is too low, or if the mountain is, say, in the middle of Antarctica, where extraction and transport costs are astronomical.
It's still a resource, but it's not an ore.
Precisely. It stays on the potential list.
So that means the definition of what constitutes an ore can actually change, like overnight.
It's completely dynamic. A swing in the commodity price for copper could suddenly make a low-grade deposit profitable. Or, and this is a huge one, a technological breakthrough can do the same.
Can you give an example of that?
Absolutely. Think about copper again. There were massive deposits with very low concentrations that nobody considered ore 50, 60 years ago. They were just, worthless rock. Then, large-scale crushing techniques and, critically, flotation technology became widespread, and suddenly technology turned this enormous low-grade resource into a massive, highly profitable reserve, almost in the blink of an eye, geologically speaking.
Which brings us to that final, most profitable category, the absolute cream of the crop, the reserves.
Yeah, this is the top tier. Reserves are the most highly defined, confident subset of ore. These are deposits that have already been identified, mapped out.
We know they're there.
We know they're there, and we know we can extract the minerals from them profitably using current technology, under current laws, and at current market prices.
So these are the resources we're actually banking on right now.
They're the engine. They're driving the entire global resource supply as we speak.
Excellent. Okay, now that we have the vocabulary down, let's fire up the engines. Our roadmap, as we said, starts deep underground with magmatic processes. Then we'll look at what hot fluids do in hydrothermal and metamorphic settings. And then we finished right up here on the surface looking at weathering and mechanical sorting, what we call placer deposits.
All right, so our journey begins deep in the earth, in the subterranean heat. We're starting with the most, dramatic and deep-seated processes.
The ones driven by molten rock, yeah.
Where the magma itself is acting like this gargantuan separation vessel.
This is the realm of igneous processes. It's where material from the Earth's mantle or deep crust gets mobilized. And the foundational concept here is something called magmatic segregation.
Okay.
Which is, at its heart, the natural separation and concentration of specific minerals inside a massive, slow-cooling body of magma.
I think we need to break that down a bit. Beyond just saying things separate, what's actually driving this incredible sorting process on such a huge scale?
Well, the mechanism is really governed by 2 pretty straightforward principles: fractional crystallization and density.
Right.
So imagine you have this huge blob of magma, a magma chamber, cooling deep within the crust. This isn't a fast process. It can take millions of years. And not everything solidifies at once.
Not at all. Minerals crystallize sequentially, one after another based on their melting points. And this sequence is famously described by something called Bowen's reaction series.
That series it's like the rule book for this whole process, isn't it?
Yeah.
It dictates the exact order of crystallization.
It really is the foundational rule book. At the really high temperature end of the scale, minerals that are rich in iron and magnesium, things like olivine and pyroxene, they crystallize out of the melt first.
And these early forming minerals have a key property.
They're heavy. They are typically much, much denser than the liquid magma that's still surrounding them. And because they're denser and they're forming continuously, gravity takes over. They simply sink.
They settle out.
They settle out. They sink to the bottom of the magma chamber. We call it gravitational settling.
So that's one half of magmatic segregation. You get these heavy early minerals sinking to the bottom. What's the other half of the process? What's happening to the liquid that's left over?
Well, the second half involves all the elements that don't fit neatly into the crystal structures of those common early forming minerals.
The incompatible elements.
Exactly, the incompatible elements, things like lithium or rare earth elements. They get left behind, dissolved in the residual melt. That's the liquid portion that's going to crystallize last.
Okay.
So as the magma keeps cooling and the total volume of liquid shrinks and shrinks, these leftover elements become more and more concentrated in that last little bit of melt.
So when that last bit finally solidifies,
You get these incredibly rich pockets of rare elements. It's the complete opposite of the settling process, but it's part of the same system.
and that settling process, the sinking of the heavy minerals, leads directly to these incredible geological formations that geologists call layered igneous intrusions.
Oh, they are spectacular, truly. Because the cooling is so slow and so undisturbed, this gravitational settling creates these distinct, almost perfectly flat layers of different minerals.
You can actually see the layers in the rock.
You can literally walk up to a cliff face and see a layer of rock that's, hundreds of meters thick, and it's almost pure chromite. And then the layer above it is something else, and then maybe another layer above that is enriched in platinum.
Oh.
It's chemical stratification on a continental scale. It's beautiful.
And what are the key products? What are we mining from these immense, slow-motion geological centrifuges?
Well, the primary products from that early gravitational settling are things like chromite, which is the main ore of chromium.
Used in stainless steel.
Right. Then there's magnetite. The Bushveld complex is the textbook example. It is the epitome of a layered intrusion. Geologists think it's this massive kind of bowl-shaped structure that covers an area bigger than Ireland.
Wow.
And it solidified over 2 billion years ago. It's just a stunning testament to the sheer scale and the efficiency of these magmatic processes. When you talk about PGMs, you have to talk about Bushveld.
So what is it that makes it so disproportionately important to the global supply chain?
It really just comes down to concentration, the sheer concentration.
So how much are we talking about here?
Well, estimates are that it contains over 70%, 70,
70% of the world's total platinum reserves in one spot.
in one geological complex, yes. And within that massive complex, there are these very specific, sometimes thin layers, like the Merensky Reef, where the concentration is high enough to be economic.
So one ancient cooling event, 2 billion years ago, basically dictates the entire global availability of metals that are essential for our modern technology.
That's it. Catalytic converters, hydrogen fuel cells, high-tech electronics. Their supply chain starts in that single intrusion.
So what are the economic implications, the geopolitical implications of having 70% of a strategic resource concentrated in one geological location?
It creates a massive vulnerability, both geopolitically and for the market. If there are any extraction issues, any political instability in that one region, the global supply of these critical materials is immediately threatened.
It's a huge risk.
It's a huge risk. It elevates geology from just a scientific curiosity into a primary factor in international strategy. The geological efficiency of the process actually created a modern-day risk.
Okay, so now let's take that same idea of magmatic origins, but push it way, way deeper
Yeah.
into the realm of truly extreme pressure.
Right.
We're moving to kimberlites. Now, these are often talked about as being fundamentally different, mainly because of where they come from.
They are fundamentally different, both in what they're made of and, how they behave. Kimberlites are what we call ultramafic rocks.
Let's define that term, ultramafic.
Ultramafic just means they're extremely rich in magnesium and iron oxides, and at the same time, very, very poor in silica. This composition is typical of the deep earth. It's the raw material of the mantle.
And just how deep are we talking here? When you say deep, what does that mean?
We are talking about a region called the subcontinental lithospheric mantle. It's between 150 and 450 kilometers below the surface.
450 kilometers.
Yeah.
That's hard to even imagine.
It is. And that immense depth is the whole key. It's the factory floor. It is the only place in the Earth where the pressure and temperature conditions are just right to form the mineral they're famous for carrying.
And that is.
This is the diamond stability field.
So the treasure, the diamonds, they form way down there. But how on earth did they get all the way up to the surface without being destroyed? Or just turning back into boring old graphite once the pressure is gone?
And that is the most incredible part of the story. It's all about the ascent. If this chunk of rock rose slowly, the diamonds would simply, melt, or they'd re-equilibrate and transform back into graphite, their low-pressure form. That doesn't happen.
Why not?
Because kimberlite magma is thought to be highly volatile. It's super rich in gases like CO2 and water, and that results in an extremely rapid, almost explosive ascent.
So it's not a slow ooze.
No. Think of it like uncorking a giant, highly pressurized champagne bottle, but the bottle is 400 kilometers long.
And that rapid release of pressure just forces the material straight up.
Incredibly quickly, through these carrot-shaped or pipe-shaped conduits.
And what does that speed do, geologically speaking?
It achieves what you could call a geological quench. It freezes everything in place. The rapid rise brings the diamonds and other deep mantle fragments we call xenoliths up to the surface so fast that they just don't have time to chemically change.
So the kimberlite pipes we find are like frozen snapshots of this incredibly violent deep earth delivery system.
That's a perfect way to describe it.
And the treasure that's delivered from 450 kilometers down.
It is, of course, the primary commercial source of diamonds. Chemically, a diamond is incredibly simple, right? It's just pure carbon.
Right.
But its entire value comes from the extreme pressure needed to form it, and then this violent, incredibly rare geological process, the kimberlite pipe eruption, that's required to bring it to the surface intact.
It's a perfect example of how a unique geological event creates rarity and therefore value.
It really is.
What I find so fascinating here is the contrast between these two igneous processes. You have magmatic segregation, which is like the slow, patient hand of gravity working over millions of years to layer heavy metals. And then you have kimberlites, which are this high-speed, volatile, violent eruption, bringing treasure up from an impossible depth.
It just shows you the diversity within the same broad geological category. Both processes use magma as the medium, but one relies on time and density, and the other relies entirely on pressure and speed.
Okay, so moving away from just pure molten rock, we're now transitioning to the role of fluids and, regional heat and pressure.
Yeah, this is where water gets involved in a big way.
We often think of water as something that, erodes things. It's corrosive. But when it's superheated and under immense pressure deep in the crust, it becomes one of the Earth's most efficient metal scavengers.
And that brings us to the incredibly widespread world of hydrothermal solutions. The name really tells you the whole process. Hydro for water and thermal for heat.
So we're just talking about hot, metal-rich fluids moving through the crust.
That's all it is.
But where does this powerful fluid actually come from? And why is it so good at dissolving metals that, regular water on the surface can't touch?
The fluid can actually come from a few places. It can be magmatic water that's literally released by a cooling body of magma. It can be groundwater, rainwater that has circulated incredibly deep into the crust.
Okay.
Or it can even be water that's squeezed out of rocks during metamorphic reactions. But no matter where it comes from, when it gets down deep at high temperatures and pressures, water enters a supercritical state.
And what does that mean, supercritical?
It's kind of a fourth state of matter, neither liquid nor gas. And in that state, it acts as this extremely powerful, almost non-selective solvent. It's capable of dissolving trace amounts of metals, copper, gold, silver from huge volumes of rock that it passes through.
So the fluid is like a sponge, just soaking up metals as it moves. But how does it then concentrate that metallic load into a deposit that we can actually mine?
The key is precipitation. It's all about forcing the metals to drop out of the water.
Okay, and how does that happen?
It happens when the fluid's ability to hold those metals in solution is suddenly compromised. So as the fluid moves upwards, it might cool down significantly. or it might experience a sudden drastic pressure drop as it enters a big open fracture.
So physical change.
A physical change, or critically, a chemical change. It might run into a different type of host rock, like limestone, which completely changes the pH or the oxygen balance of the fluid.
Yeah, any of those triggers.
Any of those triggers will cause the dissolved metals to suddenly become insoluble, and they just bam, they precipitate out of the fluid, forming a solid mineral deposit.
And this precipitation process leads to the two main types of hydrothermal deposits we mine. Let's start with the classic image of mining. Vein deposits.
Right. Vein deposits are what you picture from the old gold rush movies. These are the high-grade legacy deposits.
So what's happening there?
The metal-rich fluids are finding and filling pre-existing fractures, faults, and cracks in the host rock. Because that space is so confined, the precipitation is highly concentrated.
So you get these thin but incredibly rich linear deposits.
Exactly. You'll often find these beautiful quartz veins that are just packed with flecks of pure gold or seams of silver.
And the key products found in these, high-grade but low-volume veins are what?
It's primarily those high-value precious metals, gold, silver, mercury. These deposits were so sought after because their grade, the concentration of metal, is extremely high. That high value offsets the cost of trying to find and follow a relatively small, narrow target.
They were the first to be exploited because they were so obvious and so rich.
They were the low-hanging fruit of the mining world.
But the scale of modern industrial mining, it relies much more heavily on the second type, doesn't it? The much lower grade deposits.
Oh, absolutely. The modern world runs on disseminated deposits.
And these are basically the opposite of veins.
The complete opposite. Instead of a narrow fracture, here, the hydrothermal system permeates an enormous volume of rock. A whole mountain sometimes.
So it's not filling big cracks.
No, the fluids are depositing minute masses of or tiny little grains or coatings throughout the entire rock mass. They're filling microscopic pores and microfractures. The overall concentration is much lower, often less than 1% metal.
But it's spread over a deposit that can cover several cubic kilometers.
Exactly. Low grade, but massive, massive tonnage.
And the key product here, the one we always associate with this style, is copper. Specifically in what are called porphyry copper deposits. Why is copper so often found this way?
Well, these porphyry copper deposits are almost always linked to huge, relatively shallow igneous intrusions. The magma body itself and all the surrounding rock become the engine for this massive hydrothermal system.
It's a much bigger system.
A much bigger, longer-lasting system. And copper is pretty abundant in the crust, so these systems can scavenge a lot of it. The low-grade nature means you need a truly gigantic volume of rock to make a profit, and that's exactly what these porphyry systems provide.
And this brings us back to scale and profitability. I mean, the real-world benchmark for this has to be the Bingham Canyon copper mine in Utah.
Bingham Canyon, or Kennecott's Utah copper mine is. It's just hard to describe the scale. It's one of the largest man-made excavations on Earth. It is a living, breathing textbook on how technology makes disseminated deposits possible.
They're literally moving a mountain.
They are moving millions of tons of rock every single day, where the copper concentration might be well under 1%.
But the key insight here for the listener is, how did mining make that switch? How did we go from chasing narrow, high-grade gold veins to being willing to process these huge, low-grade copper mountains?
The pivot was one specific technological innovation, the flotation process.
Okay.
Before the early 20th century, mining this kind of low-grade ore just wasn't economic. Flotation technology allowed miners to crush the rock into a fine powder, mix it with water and chemicals, and then literally float the tiny copper mineral grains to the surface on bubbles, separating them from the waste rock.
And that single invention.
That single technological innovation unlocked the value in these massive porphyry copper deposits and made them the world's most important source of copper. It changed everything.
Okay, so we've seen magma at work, we've seen hot water at work. Now let's talk about the silent, powerful transformation that's driven by pure pressure and heat reworking existing rock.
Right, now we're into the world of metamorphic processes.
Metamorphism.
And metamorphism is all about change. It's mineralogical and textural change in a rock, but crucially, without it completely melting.
So it's the Earth basically recycling and reforming its own crust.
That's a great way to put it. And when we talk about resource concentration here, we're looking at how that heat and pressure cause elements to migrate and reform into more concentrated, more valuable mineral structures.
So let's distinguish between the two main types, starting with the more localized change, contact metamorphism.
This creates a zone of really intense local alteration. It happens when a very hot igneous intrusion, a body of magma, pushes its way up into cooler surrounding rock.
Okay.
The heat from that magma and the hot fluids streaming away from it basically cook the surrounding rock, the host rock, right at the point of contact.
Yes.
This creates what geologists call a metamorphic halo or an aureole.
And what key minerals get concentrated in this cooked zone?
We often find really rich deposits of sulfide minerals in these zones, which are technically known as skarn. And these include things like sphalerite, which is zinc ore, galena, which is lead ore, and chalcopyrite, which is a copper ore.
So these elements might have been there in the host rock already, but in tiny amounts.
Exactly. They were subtly present, disseminated. But the intense heat and the chemical flux from the intrusion mobilizes them, causing them to concentrate rapidly and precipitate right at that thermal and chemical boundary.
Okay, so now let's contrast that very local process with a much larger, slower moving one. Regional metamorphism.
Regional metamorphism operates on a completely different scale, a massive scale. This alteration is driven by immense pressure and high temperatures affecting rocks over, entire swaths of continents, kilometers and kilometers deep.
And what causes that kind of widespread pressure?
It's primarily associated with major tectonic collisions, when two continental plates smash into each other, burying and heating huge volumes of rock, and typically forming massive mountain ranges like the Himalayas.
So if the force is applied over such a huge area, and the temperatures are sort of moderate but sustained for millions of years, how does that lead to an economic concentration of minerals?
The mechanism here is often less about adding new elements from a magma and more about recrystallization and structural alignment of what's already there.
Okay.
The massive directed stress forces minerals to realign themselves. It can physically squeeze out fluids that contain impurities, and that process purifies and concentrates the remaining desired material. The minerals that form are often quite different from the metallic sulfides you see in contact zones.
So what are the key industrial minerals that form under these vast regional mountain building conditions?
The output here tends to be heavily skewed toward industrial non-metallics. Prime examples would be talc, which forms under that directed pressure in magnesium-rich environments.
And graphite.
And graphite, absolutely. Graphite forms from the high-temperature, high-pressure metamorphism of carbon-rich sedimentary rocks like coal or shale. They need that widespread, sustained pressure of a mountain building event to get the necessary purity and the crystalline structure that makes them useful for industry.
So it's a really crucial takeaway here. The nature of the geological process itself really determines the type of resource we get.
Completely.
We've gone from deep, massive sorting of heavy metals in magma to hydrothermal systems chasing fractures with hot water, and now to continental-scale crushing that gives us these vital industrial minerals. We've made it up from the mantle, through the crust, and now we're looking at the slow, pervasive factory that operates right here on the surface,
Right where we live.
where elements are interacting with the atmosphere, with water, with life itself. And these processes might seem subtle, but they are incredibly patient and incredibly effective sorters.
We're going to focus on two key mechanisms here that rely entirely on surface conditions. We'll start with weathering, or what geologists often call secondary enrichment.
Which is really just intense chemical attack over a long time.
That's all it is.
And the poster child for this mechanism has to be bauxite formation, which gives us the raw material for all the world's aluminum.
Bauxite is a fantastic example because its formation is fundamentally tied to a specific environment. It forms almost exclusively in humid, rainy, tropical climates near the equator.
And why there? What's so special about the tropics?
Because chemical weathering, the dissolution of rock by water and natural acids, operates at its absolute maximum intensity in these hot, wet regions. The heat and the water act as a powerful chemical engine.
So can you detail that mechanism for us? It almost sounds like nature's own extreme purification process.
It is. It's the power of intense leaching. You start with a parent rock that's rich in aluminum silicates, something like a feldspar in granite. And that rock is exposed to just relentless heavy rainfall and high temperatures for millions of years. This environment aggressively promotes the chemical dissolution of the most soluble materials in that rock, especially silica, but also iron and magnesium. The water acts as this incredibly powerful stripping agent.
So the concentration of aluminum happens not because you're adding aluminum, but because you are systematically washing everything else away.
That is precisely it. The aluminum oxide and hydroxide minerals, which make up bauxite, are highly resistant to being dissolved in those particular conditions. They're insoluble.
They get left behind.
They get left behind. As all the soluble elements, all the impurities are carried away by groundwater, the residual soil becomes more and more enriched in that less soluble aluminum. The concentration only rises to economic levels after millions of years of this persistent tropical rain has removed all the competing elements.
So it's an additive process of subtraction.
Perfect. That's a great way to think about it. And what's left is this reddish clay-like rock we call bauxite.
What does that strict requirement for a tropical climate tell us about the global distribution of aluminum resources?
Well, it severely limits where we can find high-grade aluminum ore. It makes it geographically restricted to these stable, ancient, tropical land masses that haven't been scraped clean by glaciers recently or, buried by volcanoes.
So unlike hydrothermal gold, which can form anywhere you have heat and water, bauxite requires deep time and stability in a very specific aggressive climate.
Correct.
All right, our final mechanism is maybe the simplest of all. It relies on pure, straightforward physics. We're talking about placer deposits.
This is where moving water does all the work, mechanically sorting materials based on nothing more than their density.
And these deposits form when heavy resistant minerals get concentrated by currents, usually in high-energy places like streams and rivers, or even along coastlines.
Exactly.
So let's go a little deeper into the physics of why this is so effective. Why does the water drop the valuable, heavy stuff but just keep carrying away all the junk?
It all comes down to a massive difference in specific gravity, which is just another word for density. So quartz, which is the main component of sand and the most common mineral on the surface, has a specific gravity of about 2.6.
Right.
Gold, on the other hand, has a specific gravity of around 19.
19. That is a staggering difference.
It's almost 8 times heavier for the same volume. So when water is flowing in a river, it's exerting a drag force on all the particles. The lighter, less dense minerals like quartz get easily swept along or held in suspension.
But the gold doesn't.
The gold is just too heavy. Whenever the water velocity drops, say where a river widens out or on the inside bend of a meander, or when it gets trapped behind a big rock, the high-density minerals settle out almost immediately. They're simply too heavy for the slower current to keep them moving.
So these deposits start to accumulate in very predictable spots, anywhere the hydraulic energy of the river dissipates.
Yes. They concentrate in places like cracks in the bedrock, on the upstream side of boulders, or in the deepest part of a river channel. These natural accumulations are the placers. The ancient gold rushes were built entirely on prospectors learning how to read a river and find these spots.
And what are the common minerals that are tough enough to survive the weathering and dense enough to be concentrated this way?
It's a pretty short but very valuable list. It includes the native metals like gold and platinum, and then some chemically and physically resistant minerals like cassiterite, which is tin ore, rutile for titanium, and interestingly, diamonds.
So diamonds are back again. It's interesting. We talked about their violent birth in kimberlites 450 kilometers down, and now here they are, being passively concentrated by a gentle stream.
It's a great illustration of the entire resource life cycle. Diamonds are so chemically inert and so physically hard, they are the hardest natural substance after all,
Right.
that they survive weathering and erosion perfectly intact after the kimberlite pipe they came from has been exposed at the surface and worn down. Then the river takes over, breaks the diamonds free from the softer host rock, and concentrates them in river gravel, sometimes hundreds or thousands of miles from their original volcanic source.
We've really traveled the full spectrum now, from deep magma settling to hot fluid migration to chemical dissolution, and now, finally, to just simple gravity and physics doing the sorting for us. Now, while the stories of platinum, gold, and diamonds are, they're the dramatic ones, the unsung heroes of geology, in terms of sheer volume, are the non-metallic resources.
Oh, absolutely. These are the materials that make our modern infrastructure physically possible. We often take them completely for granted.
And this section is really shifting our focus to materials that are often low value per ton, but are used in such high volumes that their availability and, crucially, their proximity to market are far more important than their actual grade.
Exactly.
So let's start with the basics. Building materials. We have to acknowledge the sheer necessity of these common rocks, starting with limestone. It is everywhere, but its applications are incredibly diverse.
Limestone is primarily calcium carbonate. It's a sedimentary rock, often formed from the shells and skeletons of ancient marine organisms. And its importance is just. It's hard to overstate.
So what's application number 1?
Number 1, it is the core ingredient for Portland cement, which is the binder that holds all concrete together. No limestone, no concrete.
Okay, what else?
Secondly, it is used as a fluxing agent in steel manufacturing. It reacts with impurities in the iron ore, like silica, and helps carry them away in the slag layer.
Okay, let's pause on that term fluxing agent. That's a great example of a technical term we should unpack for the listener.
Right, so a flux is simply a substance you add to a molten material to help clean it or to lower its melting point. In steelmaking, you add limestone to the furnace. It reacts with all the unwanted stuff at high temperatures and forms a liquid slag that conveniently floats on top of the molten steel.
So you can just scrape it off.
You just scrape it off.
Yeah.
It effectively cleans the metal. Without limestone, modern steel refining would be far less efficient and much more expensive. And thirdly, of course, ground-up limestone is essential in agriculture to correct soil acidity.
Okay, next up we have gypsum. This is the backbone of all our interior walls.
Gypsum is calcium sulfate dihydrate, and it's a classic evaporate mineral.
What does that mean, evaporate?
It means it forms when large bodies of shallow seawater or saltwater lakes evaporate in hot, dry climates, leaving behind thick layers of these mineral salts.
Okay.
Its crucial application is as the essential ingredient for plaster and wallboard. It's soft, it's easy to process, and it has these amazing fire-resistant properties because of the water that's chemically bound in its crystal structure. When it gets hot, it releases that water as steam, which helps cool the wall. It's indispensable.
And finally, the undisputed volume champion, the material that literally defines our entire built environment. Aggregate.
Aggregate, the generic term that covers crushed stone, sand, and gravel. And these are fundamentally necessary for building roads and making concrete. We use more aggregate by weight and volume globally than all other mined commodities combined.
It's an incredible amount.
We're talking billions and billions of tons every single year.
So what's the geological formation story for something like aggregate, since it seems to be everywhere?
Well, it really comes from two main sources. You have crushed stone, which is often mined from huge, durable quarries of igneous or metamorphic rock like granite or basalt.
Okay.
And then you have natural sand and gravel, which are what we call clastic sediments. They're formed by the erosion, transport, and deposition of fragments of other rocks, often found in river valleys or in massive glacial deposits left over from the ice ages.
So why do transportation costs completely dominate the economics of aggregate?
It's because the price per ton is so incredibly low. Moving it even a short distance, say 50 miles, can double the final cost to the customer.
Wow.
Therefore, the most valuable aggregate reserves are not necessarily the highest quality ones. They're the ones located closest to high-density urban areas where the construction is happening. A massive, high-quality granite quarry 500 miles from a city is often less valuable than a smaller, lower-quality gravel pit right outside the city limits.
So in this case, geology is completely secondary to logistics.
Completely. Location is everything.
All right, moving past the structural materials, we have this other category of minerals that are essential not for what they build, but for the industrial processes they enable.
Yes, the industrial minerals. These are the unsung workhorses. They are critical chemical components that facilitate high-tech or large-scale manufacturing.
Let's look at fluorite. We mentioned it in passing earlier, but let's be really specific about its application.
Fluorite, which miners call fluorspar, is calcium fluoride. And its crucial applications are, yes, in steelmaking as a flux, but even more importantly, in aluminum refining.
How so?
Well, aluminum is refined from bauxite using something called the Hall-Héroult process. And a synthetic form of fluorite is used as the solvent in that process because it dramatically lowers the melting point of the alumina.
And that saves energy.
It saves a massive amount of energy, which makes the whole process economically viable. Without fluorite, aluminum would be prohibitively expensive.
Then we have minerals that are valued purely for their incredible physical toughness, specifically their hardness.
The abrasives.
Right, corundum and garnet.
Yes. So corundum is just crystalline aluminum oxide, and on the Mohs scale of hardness, it ranks a 9, which is second only to diamond at 10.
And how does it form?
It forms under high-grade metamorphic conditions, and because of that incredible hardness, it's used in things like grinding wheels and high-performance sandpaper. Garnet is another group of very hard silicate minerals, and it's widely used in sandblasting and in water jet cutting because it has this tough, sharp fracture pattern.
So their industrial value is a direct result of the geological geological stresses that created their incredibly strong crystal structures.
Absolutely. The geology is the property that we value.
And to wrap up these industrial workhorses, we have to talk about a mineral that is vital to global food security: sylvite.
Sylvite, or potassium chloride, is the primary commercial source of potassium, which is often just referred to as potash.
And its crucial application.
Is for fertilizers, period. And just like gypsum, sylvite forms as an evaporate deposit. Potassium is highly soluble in water, which means it concentrates very rapidly when ancient saline seas or lakes dry up.
So we find these massive buried layers of it.
Massive layers left over from geological periods when the climate was much more arid than it is today.
So if you really think about it, the existence of large-scale modern agriculture, feeding billions of people, rests entirely on the chance geological occurrence of ancient seas drying up and leaving behind these massive evaporate basins full of sylvite.
That's exactly right. It directly connects plate tectonics, ancient climate change, and basic chemistry to what's on your dinner table tonight. If these evaporate basins didn't exist in economically mineable concentrations, the yields from current farming practices would plummet on a global scale.
It's just a remarkable connection, showing how necessary that specific geological concentration is for the sustainability of our species.
It really is.
We have completed an incredible journey. We've traced the origins of our civilization's raw materials from the mantle to the farm.
And we've seen that the Earth really operates as this highly specialized factory, taking common elements and concentrating them through very specific means.
We cover the full spectrum of conditions needed, right? From the slow, gravity-driven separation of platinum deep in a magma chamber,
to the rapid, pressurized descent of diamonds in a kimberlite pipe. We looked at how supercritical water scavenges and then deposits gold and copper in fractures.
and how massive tectonic collisions can yield vital industrial materials like graphite.
And then right at the surface, we saw the incredible patience of it all. The millions of years of chemical weathering needed to leach away everything but the bauxite.
And the simple physics of density sorting in a riverbed, creating placer deposits of gold.
So what does this all mean for you, the listener? What's the big takeaway?
Yeah.
It means that understanding mineral resources is fundamentally about understanding the geologic history that created the concentration in the first place. You can't go looking for a massive porphyry copper deposit in a geologically quiet sedimentary basin.
This is the wrong address.
It's the wrong geological address. You have to look in zones of tectonic activity where huge hydrothermal systems were driven by shallow magmas. This knowledge of the mechanism is the most efficient shortcut to being truly well-informed in resource economics and exploration.
It provides the context for the entire global resource map. You stop asking, why do we find gold here? And you start asking, what unique pressure, temperature, and fluid history happened right here that concentrated the gold?
Exactly. And that leads us to a final, maybe provocative thought for you to carry forward. One that ties together deep time and economic viability.
Okay.
We talked about how bauxite forms because intense weathering leaches away the soluble elements, concentrating the aluminum.
Right, the process of removal.
And we talked about how placer deposits use simple density to sort heavy, valuable minerals from light waste rock.
So think about that principle. Geological concentration through subtraction or through mechanical sorting.
Now consider the vast quantities of other essential materials, like magnesium or various rare earth elements that are currently distributed throughout rocks at concentrations that are far, far too low to mine profitably today.
They're resources, but they're not ore.
Exactly. So if current processes like weathering and mechanical sorting are so good at concentrating materials over deep time, what vital, currently low-grade resource, maybe one that's critical for fusion power or for quantum computing, might future long-term geological processes concentrate for us thousands or millions of years from now?
So we're basically harvesting the wealth created by ancient geological events today.
We are. So is it possible that we're also walking on the low-grade factory floor for the civilizations of the future?
A fascinating concept. It forces you to think on a completely different timescale, geological versus human economics. Thank you for joining us on this deep dive into the Earth's most powerful and patient factories. Welcome back to the Deep Dive, where we take the vast, overwhelming ocean of information and distill it down to the essential, fascinating truths you need to know.
And today, we are literally going underground.
We really are. We're doing a deep dive into the very foundation of, well, global energy, industrial society, modern geopolitics,
All of it.
the secret geology of fossil fuels.
Yeah, and this is such a crucial topic because Whether you're prepping for a high-stakes discussion about renewable energy or you're just someone who's really curious about the physical limits of our energy systems,
Right.
understanding the, let's call it the geological recipe for these fuels is it's absolutely necessary.
And our sources for this deep dive give us that foundation. We've pulled together excerpts on the geology of fossil fuels, origin and extraction, and it really covers the hard science.
It does, from
Yeah.
ancient formation, I mean, hundreds of millions of years ago, all the way up to the really complex refinement processes we use today.
Exactly. So we're not just discussing what oil, coal, and gas are. We're analyzing the science of how they're made, why they're found where they are, and the hyper-modern engineering it takes to get them out of the ground.
It's an incredible story. It really is. It's a story of time, pressure, and biology, really.
So what's our mission for you today?
I think our mission is to give you a true crash course in geological literacy. We're going to unpack the huge differences between these fuels. We'll get into the specific, the non-negotiable conditions needed for them to form in the first place. Conditions that took, well, ages to achieve.
So you'll walk away knowing that the location of this energy isn't just a political accident.
Not at all. It's a geological fact. And those facts dictate global power structures. It's that simple.
Okay, before we jump into the ooze and the ancient swamps, we have to start with two quick, crucial definitions.
Yes.
And these get mixed up all the time when people talk about energy security. And this is where geology meets economics.
Yeah.
We need to differentiate between reserves and resources.
And this is more than just, academic jargon. This distinction is the difference between immediate market power and long-term theoretical potential.
Okay, so let's start with reserves.
Reserves are the deposits we've already found. They're identified, and crucially, they can be extracted profitably right now.
Right now, that's the key.
That's the key. The technology has to exist, the market price has to be high enough, and you need the infrastructure to actually move it.
So if any one of those things changes.
Exactly. Let's say the price of oil drops by half tomorrow. Some of those deposits that were called reserves yesterday, they instantly become just resources today. They're no longer profitable to extract.
So reserves are basically money in the bank. It's the known, proven, economically feasible stuff that shapes today's world.
Precisely. But the world's actual physical stock of this stuff is, it's far, far larger.
And that larger pool is what we call resources.
Right. Resources are the reserves plus everything else. Every other known deposit or even undiscovered ones we think are out there, but that are not yet economically extractable.
So maybe it's too deep. Or the fuel is too thick.
Or the technology just isn't there yet, or it's too expensive. A perfect example is all the oil that was trapped in shale rock. For decades, that was just a known resource.
We knew it was there, but couldn't get it out.
We couldn't get it out profitably. Then the technology of hydraulic fracturing came along and unlocked it. And almost overnight, those resources were converted into reserves.
That's a perfect illustration. That distinction, profitability, driven by tech, price, and access. That's the key.
Yeah.
It moves us from geology to, well, Wall Street.
Absolutely.
Okay, let's get into it. Fossil fuels, oil, coal, natural gas, they're all formed from the altered remains of ancient life.
Right, all carbon-based.
They all involve millions of years, immense pressure, but as our sources make clear, their birthplaces could not be more different.
That is the first fundamental concept we need to lock down. We're really talking about two totally separate, distinct creation paths.
Yeah.
Each one needs a radically different environment, different raw materials. You've got the land path, which gives us coal, and then you have the marine path, which gives us petroleum and gas.
Two paths. Let's start on land. Let's talk about coal. Our sources define it as a sedimentary rock formed from just massive amounts of land plants.
Yeah, ancient forests, roots, leaves, wood, all of it piling up. But, and this is the important part, it can't just be any old pile of vegetation.
Right, because if a tree falls in the forest today, it just rots.
Exactly. It decomposes. Bacteria, fungi, they consume it, and the carbon combines with oxygen and goes right back into the atmosphere as CO2. That process is called oxidation.
And oxidation destroys the energy potential.
It erases it. So the absolute non-negotiable requirement for coal to form is the swamp environment.
Okay, why stagnant swamps or marshes specifically? What's the magic there?
The stagnant water is the magic because it's essential for preventing that oxidation. When all that plant material dies and collapses into the water quickly becomes anaerobic.
Meaning oxygen poor.
Very oxygen poor. And without enough oxygen, the bacteria that cause rapid decay just can't thrive. So the plant matter gets submerged and preserved, locking that carbon in.
And that creates the precursor material.
It creates peat. And you have to imagine periods in Earth's history, like the Carboniferous period, where vast, low-lying coastal areas were just covered in these swamps for millions and millions of years.
So the land path is about a perfect failure of decomposition.
Yeah.
You need tons of plants, stagnant water, and that gets us to coal.
That's the path. Now, if the land path gives us the solid fossil fuel, the marine path gives us the liquids and gases that power, well, most of the modern world.
Petroleum and natural gas.
Right. And these aren't derived from trees. They come from the remains of marine plants and animals, specifically tiny single-celled organisms.
Plankton and algae.
Plankton and algae thriving in these vast ocean ecosystems. They are the base of the entire marine food chain.
And just like the swamp plants, they have to die and accumulate in just mind-boggling quantities.
And they have to be buried quickly. Same principle, different environment. You need rapid burial in highly oxygen-poor settings.
So the bottom of the ocean, or maybe deep lakes.
The bottom of oceans, large lakes, deltas, deep lagoons, places where fine sediments like mud and clay are constantly piling up and burying the organic matter before it can rot or get eaten.
And that organic-rich mud becomes the source?
That mud is what will eventually become the source rock for oil and gas.
Okay, that clarifies so much right away. It's why you don't find a huge coal deposit in the middle of the deep ocean.
No land plants there.
And you won't find high-quality crude oil in a mountain range, unless that mountain range used to be a prehistoric seabed that got pushed up.
It all goes back to those two fundamentally different burial mechanisms. The initial geography and the chemistry dictate the final product, every time.
So let's go back to the coal side of things for a minute. Let's track that evolution. Once you have that initial layer of peat in the swamp, it starts a journey.
It starts its journey up what geologists call the coal ladder, or the rank system.
The rank system. This is a progression of more heat, more pressure from being buried deeper and deeper.
And, most importantly, increasing carbon purity.
So the quality of the coal is basically a direct measure of how much geological stress it has survived.
That's a great way to put it. It's essentially a four-stage transformation. And the main process is just squeezing out everything that isn't carbon.
Water,
Oxygen, other volatile compounds. You're left with a pure carbon residue, and that results in really different energy levels and burning characteristics for each rank.
Okay, so what's stage one?
Stage one is peat. This is where we start. It's just partially altered plant material. You can find it in bogs today. It's light. It holds a ton of water.
And it's really smoky if you try to burn it.
Very smoky. And very low energy content, maybe 50 to 60% carbon. It's essentially just compressed, half-rotted moss and vegetation.
So that peat then has to get buried. It needs more heat, more pressure
Sure.
over, what, millions of years?
Tens of millions of years, yeah. The weight of all the sediment that piles on top of it, sandstones, shales, limestones, that's what does the work.
The overburden.
The overburden. It applies pressure and moderate heat, and that leads us to stage two, lignite.
Lignite.
This is a soft brown coal. It's got moderate energy, maybe 60 to 75% carbon. It still has a lot of moisture in it, so it's not super efficient to transport or burn.
But it's useful.
Oh, yeah. Many large surface mining operations around the world pull up lignite for power generation. It's abundant.
And then the next step up is the big one, right? The major leap in energy density.
Now we get to stage three, bituminous coal. This is the soft, black coal. And historically, this has been the major industrial workhorse.
The stuff that powered the Industrial Revolution.
Absolutely. By this point, it's been buried deep enough to drive out most of the moisture and volatiles. You're getting high energy content, maybe 75 to 88% carbon.
It burns hot.
It burns intensely, and it's widely available. Our sources confirm that most of the coal mined in the U.S., especially for electricity, is this mid to low-grade bituminous coal.
Okay, so how much deeper or hotter does it have to get to create that final, purest form?
The jump from bituminous to stage 4, anthracite, is enormous. It's a huge leap. This hard, black coal is geologically defined as a metamorphic rock.
A metamorphic rock, so it's fundamentally changed its structure.
Its crystalline structure has been ulcered. It's been subjected to such intense heat and pressure, often you find it near tectonic plate boundaries or in really deep burial events, that it's just been cooked.
And the carbon content?
It can reach over 90, even 95% carbon. Because there's almost no volatile matter left, it ignites slowly, but it burns consistently. It's the hottest and the cleanest of all the coals.
It's the most geologically mature version of that ancient plant carbon.
That's a perfect description.
And, when you look at the sheer scale of this resource globally, it's really humbling. Our sources point out that coal is by far the most abundant fossil fuel we have.
In terms of both distribution and just raw quantity, yes, it's the heavy, abundant cousin. The estimate that it could last for at least 200 years at current consumption rates, that gives you an idea of the sheer volume that was created.
Especially during periods like the Carboniferous.
Exactly. And, for these thick, mineable seams to form, it requires these large-scale, slow, cyclical changes in sea level.
We're talking about transgressions and regressions.
Yes.
Okay, let's elaborate on those terms because it sounds a little counterintuitive. What does a marine transgression, the sea rising, have to do with land-based coal?
A transgression is when global sea levels rise, or the land itself subsides, and the ocean moves in to cover the land.
Okay.
So when the sea encroaches on those massive coastal swamps we talked about, it buries the peat layer under thick layers of protective sediment. Sandstone, shale, limestone.
And that burial provides the pressure and heat.
That's what kicks off the coalification process. It's the burial that turns peat into lignite and eventually lignite into bituminous.
And so regression must be the opposite.
The exact opposite. The sea level falls or the land rises. The regression exposes new land, which allows the next generation of swamps to grow, and the whole cycle starts over again.
And eventually it brings those now buried coal seams closer to the surface.
It makes them accessible for us to mine. It takes that perfect, repeating dance of geology and climate over tens of millions of years to create these thick, high-quality coal seams.
It's just incredible that a drop in sea level 300 million years ago determines where we build a power plant today.
The past is never dead. It's not even past.
Okay, let's switch gears completely. Let's dive into the geological recipe for oil and gas, liquid gold. This process is about heat, pressure, and, as you said, movement.
Yes, lateral movement is key here. But we start, as we mentioned before, with the source rock.
The organic-rich mud.
Typically a marine shale or limestone where all that dead plankton and algae piled up in that deep oxygen-poor water, and that initial preserved organic gunk is called kerogen.
So kerogen is the raw material. It's like a waxy precursor.
Precisely. It's a solid, it's insoluble, and it's basically useless as a fuel until it gets transformed.
And the transformation happens when that source rock gets buried deep enough for the temperature to really start climbing.
And that brings us to the crucial sweet spot. This is the concept that truly defines hydrocarbon reserves, the oil window.
The oil window.
This is the non-negotiable threshold. As the source rock gets buried deeper, it descends into this optimal range of heat and pressure. And that thermal energy, it acts like a slow cooker over geologic time. It transforms that solid kerogen into liquid hydrocarbons.
Crude oil.
Crude oil. And this window typically happens between, say, 7,000 and 515,000 feet deep.
And what about temperatures?
Temperatures between about 150 and 300 degrees Fahrenheit. If it's too shallow and cool, the kerogen never matures. It just stays kerogen. If it's too deep and hot,
It overcooks.
it cooks right past the liquid phase. It's a very sensitive, very narrow band.
So let's explore that. What happens if it gets too hot, if it's buried for too long or too deep?
This is the critical nuance that determines whether a basin will produce oil or natural gas. If the temperatures get too high, let's say over 300, 350 degrees Fahrenheit, the big, complex oil molecules themselves start to break down.
They crack.
They thermally crack into smaller, lighter, simpler molecules. And the smallest, lightest hydrocarbon is methane.
Natural gas.
Natural gas.
Yeah.
This means the hottest, deepest parts of a geological basin tend to produce pure gas fields, while the moderate depths give us liquid petroleum.
Which explains why you often find gas reserves right underneath oil reserves in the same field. The deeper stuff is just more cooked.
Exactly right. That's a key piece of geological literacy right there.
So once the oil and gas are formed in that source rock, they can't just stay there, at least not traditionally.
No, they have to move. They must migrate. Oil and gas are way less dense than the salty water that fills all the microscopic pores in the surrounding rock.
So they're buoyant. They want to float up.
They want to float up, so they'll naturally move upward and sideways through the rock layers, seeking a path of least resistance. And this upward migration continues until they hit a wall.
They need a place to collect, and critically, they need a lid to stop them from just seeping out onto the surface.
Yes. That requires two more essential components for any economically viable field. First, you need a reservoir rock.
The underground
A
sponge.
sponge. It has to be a highly permeable and porous rock. A well-sorted sandstone is classic, or certain types of fractured limestone can work too.
And permeability is the key word there, right? Because that allows the fluid to actually flow through the rock and into a well once we drill it.
Absolutely. Porosity is how much space there is. Permeability is how connected those spaces are. You can have porous rock that isn't permeable, like some shales. It holds oil, but you can't get it out easily.
So you have the reservoir, the sponge, but if the oil keeps flowing up, it'll just escape.
It will. It'll reach the surface, it'll react with oxygen, and it will just turn into a useless tar seep. So you need the second, absolutely essential component, the cap rock, or the seal.
The lid.
The lid. This has to be a vast, continuous, and impermeable layer. A dense shale is a great cap rock, or sometimes a thick layer of salt. It has to completely stop the oil from rising further, effectively trapping it.
And this is where it gets really interesting because the specific geological structures that concentrate this accumulation, the traps, are these spectacular feats of natural engineering.
And they are what geophysicists spend their entire careers looking for. Our sources detail 4 major types.
Let's start with the most obvious one, the one you can sometimes even see on the surface, the anticline trap.
An anticline visually is just an arch. It's an upward fold in the rock layers. Imagine you lay a bunch of blankets down flat, and then you push them from the ends so they crumple up in the middle. That arch is an anticline. The oil and gas migrating up through that permeable reservoir rock, they hit the underside of the impermeable cap rock, and they just pool at the very top of that arch.
And because anticlines can be huge.
They can be enormous. They are responsible for some of the largest, most famous oil and gas fields in the world. The massive reservoirs across the Middle East are often in these giant anticline traps. They're just the biggest containers nature makes.
Okay, next up we have the fault trap. A fault is a fracture in the crust where the rock on one side moves.
Right. And in this case, that tectonic movement causes a displacement. It moves a permeable reservoir bed directly up against a completely impermeable layer, like a thick shale.
So the fault itself becomes the barrier.
The impermeable rock on the other side of the fault acts as a seal. It blocks migration path and traps the oil in the up-dip section of that reservoir layer. It's a completely accidental but very effective geological wall.
Now, the one that always seemed like science fiction to me is the salt dome trap. This is huge around the Gulf of Mexico.
They're magnificent structures, and they rely on the really unique behavior of rock salt.
What do you mean?
So millions of years ago, massive layers of salt were deposited from evaporating seas. Salt is actually less dense than the sediment layers that pile up on top of it.
So it wants to float up too.
It wants to float up. And under intense pressure, salt behaves almost like a very, very thick fluid. It will slowly, relentlessly rise up over geological time. These rising bodies of salt are called diapirs.
A diapir is like a giant, slow-motion underground bubble of salt punching its way to the surface.
That is the perfect analogy. And as that salt diapir rises, it literally punches through and upturns all the surrounding sedimentary layers.
And that creates the traps.
It creates all these complex pockets, folds, and fractures where oil and gas get trapped against the impermeable face of the salt body itself. The salt is the perfect seal.
Incredible. And finally, the one that's hardest to spot, because it doesn't rely on these big, obvious folds or fractures, the stratigraphic trap.
Right. A stratigraphic trap is created by changes in how the sediments were originally deposited, not by later structural deformation. For a long time, these were, the holy grail for exploration because they are so subtle.
What's a classic example?
The classic example is a pinch-out. Imagine an ancient riverbed, which is full of permeable sand, running across a muddy, impermeable plain. Over time, that whole system gets buried. The oil migrates up into that sandy riverbed.
And it just keeps going until the riverbed ends.
Until it pinches out between 2 impermeable layers of rock. The oil hits the end of the permeable bed, and it's trapped. There's nowhere else for it to go.
And finding these subtle traps, like the ones in the Permian Basin, that really changed the game for domestic energy here in the U.S., didn't it?
Oh, absolutely. Geologists had to stop looking just for these mountain-sized arches and start analyzing the minute depositional history of the seabed. It required a massive leap in seismic imaging and geological modeling to see these things.
So that whole sequence, source rock, oil window, migration, reservoir, cap rock, and then finally the trap bit, It really shows that a major oil field is a rare gift of geology.
It's not just about having dead plankton. It's about a sequence of 6 perfect simultaneous conditions happening over hundreds of millions of years. Any one failure, and you get nothing.
All right, let's shift from the geology to the raw material itself. What exactly is crude oil?
Crude oil, or petroleum, is this incredibly complex, naturally occurring cocktail. It's primarily made up of hydrocarbon chains molecules built almost entirely of hydrogen and carbon.
Now, there are different types.
Oh, yeah. You have simple straight chain molecules called alkanes. You have ring-structured ones called cycloalkanes, and then these complex double-ringed ones called aromatics. It's a hugely diverse mix, which is why it needs such sophisticated refining.
And it's the energy density locked inside those hydrocarbon bonds that makes it so valuable.
That's the whole game. Our sources quantify this really well. A single 42-gallon barrel of crude oil contains approximately 5,781,990 BTUs of energy.
Okay, we need to put that number in context.
Mhm.
What is a BTU, a British thermal unit?
A BTU is just a standard measure of heat energy. It's the amount of energy needed to raise the temperature of 1 pound of water by 1 degree Fahrenheit.
So what does nearly 6 million of them in one barrel actually mean?
Well, to put that in perspective, that's enough contained energy to heat a small home in a cold climate for nearly half a year. That tremendous concentrated power is why oil is the basis for almost all modern transportation.
Gasoline, diesel, jet fuel.
And it's also the raw material, the feedstock for petrochemicals. That's the building blocks for everything from plastics and synthetic rubber to fertilizers and pharmaceuticals.
And the quality of that raw crude oil matters immensely. It affects everything from price to the cost of gasoline. So how do we classify it?
We use 2 main characteristics, its density and its sulfur content. For density, we usually just simplify it into light crude or heavy crude.
Light is better?
Light crude is more desirable. It has a low density, it's thinner, it's easier to pump, and it more easily produces high-value products like gasoline. Heavy crude is thick, high density, and often needs to be heated or diluted just to get it out of the ground.
And then there's the sulfur content. That's where we get the famous sweet and sour terms.
Right. Sweet crude has low sulfur content. This is the most desirable because sulfur is highly corrosive to refinery equipment and it has to be removed, which costs a lot of money.
So sour crude has high sulfur.
High sulfur. And refiners have to spend a lot more money and energy to strip that sulfur out, a process called hydrotreating, to meet environmental standards.
Which is why light sweet crude, like the benchmark West Texas Intermediate, always commands the highest price.
Because it's the easiest, most efficient, and cheapest feedstock to turn into the products everyone wants.
It makes sense that the global oil market is really defined by where these different qualities are found. You've got places like Saudi Arabia, Venezuela, Canada.
And they are a perfect example of that quality spectrum. Saudi Arabian oil is often the gold standard, light and sweet.
Right.
Venezuelan oil is typically very heavy and very sour. It requires intensive upgrading before it can be used widely. And then Canada has its unconventional heavy oil and bitumen from the tar sands, which is the most difficult and energy-intensive of all to refine.
And that brings us to the refining process itself. It's a common misconception that we just pump oil out of the ground and put it in our cars.
Not even close.
Yeah.
The refining step is arguably the most crucial part of the value chain. It's essentially a massive chemical factory that's dedicated to separation and conversion.
And it starts with a process called fractional distillation.
Yes. It's a process that separates the crude oil into its different component parts, or fractions, based on their boiling points.
So walk us through that. What happens inside one of those giant distillation towers you see at a refinery?
The crude oil is heated up to several hundred degrees, and it's fed into the bottom of a very tall distillation column. The lighter hydrocarbons, the ones with the lowest boiling points, like gases and naphtha, they immediately vaporize and start to rise up the tower.
And the heavy stuff stays at the bottom.
The really heavy, high boiling point fractions, like lubricating oils and the gunk that becomes asphalt, they stay liquid near the bottom. And as that hot vapor rises up the column, it cools.
And different things condense at different levels.
Exactly. Different fractions condense back into liquid on trays that are set at different temperature levels all the way up the column.
So high up in the tower, you get the valuable light stuff.
High up, you get the components for gasoline and jet fuel. In the middle, you get diesel and heating oil. And way down at the bottom, you get the heavy fuel oils and the residue for asphalt.
But it doesn't even stop there, does it?
No. Refiners often use other techniques, like cracking, where they use heat and catalysts to break down those less valuable heavy fractions into more of the lighter, more valuable fractions. They're trying to maximize the output of gasoline and diesel, which are always in the highest demand.
Without that complex, multi-stage
Mhm.
process, crude oil is just a useless black sludge.
Largely, yes.
That complexity is so important to understand. Okay, let's move on to natural gas. It's often overshadowed by oil, but its role is becoming more and more pivotal.
Especially as a bridging fuel, yeah.
And natural gas is overwhelmingly just methane, CH4. Where does it traditionally come from?
Traditionally, you find natural gas in one of two settings. Either it's dissolved in crude oil or it's sitting as a free gas cap above an oil reservoir. We call that associated gas.
Okay.
Or you find it in isolated gas fields. And these are places where the original source rock was buried too deep or got too hot, pushing the hydrocarbons right past that oil window and firmly into the gas phase.
But the real energy story of the last couple of decades has been the explosion of what we call unconventional gas sources.
Yes, these are the frontier reserves. The stuff that was considered too difficult or too expensive to get for generations, they represent a major shift in how we calculate energy security globally.
Because the easy stuff is getting harder to find.
The conventional reservoirs, those easy-to-flow, porous sandstone sponges, have been significantly depleted. So we've been forced to go after sources that are trapped in rock that just doesn't have that easy permeability.
So let's look at the three key unconventional sources, starting with the one that really kicked off the North American energy boom, shale gas.
Shale gas is simply natural gas that is still trapped inside its low permeability source rock.
So we're going right back to the kitchen where it was cooked.
Exactly. In conventional geology, the gas migrates out of the shale source rock and into a porous reservoir. But in huge areas, the gas never left. It stayed locked inside the shale itself because there was no easy pathway out. It's just diffused throughout the shale's tiny, disconnected pores.
So we're tapping the origin point directly instead of waiting for nature to concentrate it for us.
That's the perfect way to put it. Then next, we have coal bed methane. This is another form of gas we find in a really unexpected place, tying back to our coal discussion.
This sounds inherently dangerous given the history of coal mining explosions.
It is the exact same methane gas that coal miners used to call fire damp because of that explosive danger. Coal is a very porous rock, and it can hold huge amounts of methane locked within its structure.
So how do you get it out?
You drill directly into the coal seams, and you start pumping out the water that's naturally in there. It's the water pressure that holds the methane in place. By pumping out the water, you drop the pressure, and the methane desorbs from the coal surface and flows out.
And finally, the really massive, but for now untouchable source, methane hydrates.
Methane hydrates are just, they're bizarre. They're these ice-like crystalline solids.
Ice that burns.
Literally. Molecules of methane are trapped inside a frozen cage of water molecules. It's a structure called a clathrate.
And where do you find them?
In vast quantities in deep-sea sediments and under Arctic permafrost, places where the pressure is incredibly high and the temperature is very low. And our sources highlight their significance because the amount of carbon stored in these hydrates, it potentially far exceeds all other known fossil fuel reserves combined.
But the key phrase here, and it connects right back to our first definitions, is not yet economically viable.
Not even close.
What are the engineering roadblocks? Why can't we just go get it?
Because they are inherently unstable. They only exist in a very narrow pressure and temperature zone. If you disrupt that, if you raise the temperature a little or drop the pressure too fast, the methane hydrate rapidly decomposes, releasing huge volumes of pressurized methane gas.
So it's a safety nightmare.
An astronomical engineering and safety challenge. And on top of that, methane is a way more potent greenhouse gas than CO2, so any accidental release carries this massive environmental risk. For now, they remain theoretical resources, not practical reserves.
Which raises an important question.
Yeah.
We've established that the easy oil and gas is in these conventional permeable reservoirs. But the new stuff, shale gas, shale oil, tar sands, is locked in rock that barely lets anything move. The problem is a lack of permeability. So how do we get it out?
We have to look at the advanced extraction techniques. But before you can drill, you have to find it. And that initial step is always exploration geophysics, especially the seismic reflection method.
Which you described before as giving the Earth an ultrasound. How did that actually work to find, say, an anticline 10,000 feet down?
It's a massive technological effort. On land, you have these specialized vibrator trucks, or at sea, you use air guns, and they generate powerful sound waves.
Okay.
These waves travel down into the subsurface layers. When they hit a boundary between two different types of rock, say a dense cap rock on top of a porous reservoir, a portion of that sound wave is reflected back to the
And we
surface.
have sensors to pick that up.
Highly sensitive sensors called geophones record the precise time it takes for those reflections to come back. And since we know the speed of sound through different rocks, geologists use incredibly powerful computers to build a 3D map of the subsurface.
So they can literally see the folds and faults.
They can see the ancient stratigraphy in sedimentary basins, like the huge Permian Basin in West Texas. And that map guides where they sink the very expensive well.
So once a structure is found, conventional extraction is pretty straightforward, right? You drill a vertical well straight down into that porous reservoir.
And the oil just flows up, often driven by natural pressure at first. But when we get to these unconventional resources, the technology has to get much more aggressive to overcome nature's limitations.
Let's start with the heavy, thick stuff. Heavy oil and tar sands.
These deposits contain bitumen, which is basically thick, asphalt-like crude oil. It's so viscous it won't flow at reservoir temperatures. The Athabasca tar sands in Canada are the most famous example.
And a lot of that is so shallow you don't even drill for it.
It's literal open-pit mining. They dig up the sand and clay that's saturated with the bitumen. It's much closer to coal mining than oil drilling.
And what?
After they mine it, the material goes through this intensive processing. They mix it with hot water and solvents to separate the bitumen from the sand. It's complex, it uses a ton of energy, and it generates these massive wastewater ponds.
And what if it's too deep to mine?
Then they use techniques like steam-assisted gravity drainage or SEGD. They inject high-pressure steam down one well to heat the bitumen, make it fluid, and then it drains down and gets pumped out another well. It's
Yeah.
manufacturing, not just drilling.
And the other major unconventional source, which uses a totally different kind of force, is shale oil and gas. And that relies on hydraulic fracturing or fracking.
Fracking is the key that unlocked the entire global shale revolution. It's how you extract hydrocarbons directly from that low permeability source rock by basically creating the permeability that geology didn't provide.
Okay, so detail the process for us step by step. It's so critical to modern energy.
It was the combination of two technologies that made it work. First, instead of just drilling straight down, the operator uses these sophisticated guidance systems to turn the drill bit and drill horizontally right into the target shale layer.
And that horizontal section can go on for miles.
It can go for a mile, 2 miles, right through the rock bed, maximizing the contact area with the source rock. It creates a well path shaped like a giant L underground.
And then comes the fracturing.
Once the horizontal well is in place, stage 2 begins. They pump what they call fracking fluid, which is about 90% water, 9.5% sand, and a tiny bit of chemical additives down the well bore at incredible pressures,
High enough to break the rock.
high enough to exceed the physical strength of the shale. And that pressure creates a huge network of tiny fractures or cracks that extend hundreds of feet out from the well bore into the rock.
And the sand is the unsung hero of this whole thing, right?
The sand is the absolute key. The sand in the fluid is called a proppant. It gets forced into all those tiny new fissures. And when they stop pumping and the pressure relaxes, the rock wants to close back up.
But the sand keeps it open.
The sand props the fractures open. And that creates the permanent highway for the trapped gas and oil to flow out of the shale through the fracture network and back up the well. It's a brilliant, high-intensity method that has turned vast, useless resources into accessible reserves.
It's an astonishing piece of engineering.
Yeah.
You're essentially forcing nature to give up what it refused to yield. But of course, the environmental balance sheet has to be analyzed.
Absolutely. The extraction and the combustion of these fuels come with known significant environmental issues which our sources address head-on.
And we can really categorize these impacts into two groups.
Yes. The impacts related to combusting the carbon and then the impacts related to the extraction process itself.
Okay, starting with combustion, the primary global scale issue is greenhouse gas emissions.
Right. When you burn any fossil fuel, I don't care if it's the cleanest anthracite or light sweet crude, the carbon that was locked away for millions of years combines with oxygen and is released as carbon dioxide, CO2.
The primary greenhouse gas.
The primary long-lived greenhouse gas. And its accumulation in the atmosphere is a direct contributor to global warming. That's a first-order, unavoidable consequence of using these fuels for energy.
And the second major combustion impact, historically associated with coal, is acid rain.
This comes from the fact that coal naturally contains sulfur. When you burn the coal, that sulfur gets oxidized and goes up the smokestack as sulfur oxides.
In the atmosphere.
In the atmosphere, those compounds react with water vapor to form sulfuric and nitric acids, which then fall back down to Earth as acid rain, which can devastate ecosystems.
Okay, then we have the more localized issues from the extraction process itself, especially with fracking. The first major concern is the potential for groundwater contamination.
This is a complex risk. It can come from a couple of different pathways. One is a structural failure. A faulty well casing or bad cement job could allow methane or the fracking fluids to leak up into shallow drinking water aquifers.
But the bigger risk is from the wastewater.
Often, yes. The handling and disposal of the huge amounts of flowback water. This is the salty, chemically laden fluid that comes back up the well from the deep formation. If that wastewater is spilled or improperly stored at the surface, it can contaminate shallow groundwater.
Which leads directly to the second highly publicized concern: induced seismicity or earthquakes.
And it's really crucial to be precise here. The actual act of fracking the rock deep underground is very rarely the direct cause of a large earthquake that you can feel.
So what is the cause?
The key issue is the management of all that wastewater we just talked about. The process of injecting massive volumes of this recovered wastewater deep underground into disposal wells, that is what's strongly linked to induced seismicity.
How does injecting water cause an earthquake?
It's essentially lubrication effect. The Earth's crust is full of pre-existing faults that are under stress. When you inject high-pressure water deep underground, it increases the fluid pressure inside the rock, pours along that fault.
And that makes it easier for the fault to slip.
It reduces the friction holding the fault faces together. It lubricates it. And that can allow the stored tectonic stress to be released suddenly, causing an earthquake.
So it's the sheer volume and pressure of the wastewater disposal that's the trigger.
Far more than the initial fracking event itself, yes.
It just synthesizes the complexity perfectly. We rely on these incredibly specific geological formations for our energy. The engineering to get it is breathtaking, but the consequences force this critical look at the full life cycle.
Right, from the ancient swamp all the way to the modern deep disposal well.
So what are the core takeaways for you, the listener?
I think it's this. Understanding the energy market means understanding the geology. Oil needs that specific narrow oil window of heat and pressure, and it has to be concentrated by a geological trap.
Coal needs stagnant swamps, and it's ranked by how much it's been cooked.
And finally, a lot of modern energy independence relies on this incredibly advanced, high-intensity technology horizontal drilling and fracking to get at the resources that are locked away in the source rock itself.
So what does this all mean for us? The knowledge we gain today is really a shortcut to understanding the physical limits and the geological opportunities that dictate global energy policy, economics, and all the environmental trade-offs that come with it.
The location of energy is not random. It's a map of ancient geography, climate, and tectonic history.
And as we look forward, the geological limits we face today are just going to be magnified.
Absolutely.
Which brings us back to that most provocative of the unconventional sources, the one that is still firmly in the resource category: methane hydrates.
The burning ice.
We discussed how they potentially contain more carbon than all other fossil fuels combined. But they're not economically viable because of the volatility and the engineering challenges. For now. But consider the ultimate engineering and environmental trade-off. If global energy demand keeps rising and the conventional, easy-to-get reserves begin to dwindle, when does the need for energy outweigh the massive risk of unlocking that enormous volatile resource?
When does technology advance enough to make the impossible profitable?
And what will the environmental cost of that new geology be? That is a question for you to mull over as you continue your own deep dive.
The geology always defines the challenge and eventually the solution.
Thank you for joining us for this deep dive. We'll see you next time. Welcome back to the deep dive. Today, we are undertaking a truly colossal mission.
I think colossal is the right word.
We are diving into the world of glaciers. And we're not just talking about mountains of static ice, but these dynamic, moving masses that have literally sculpted continents and hold the key to our planet's climate history.
They absolutely do.
We have a pretty robust stack of sources here, everything from deep geological texts to, modern glaciology reports.
It's a journey that really connects high-level physics to deep time history. Glaciers are, I would argue, the most powerful yet delicate geological agents on Earth.
Delicate, that's an interesting word for them.
Well, they operate as these immense natural archives on one hand, and on the other, they're critical infrastructure for the global water supply. That balance is surprisingly fragile.
Okay, so our mission here is, well, it's straightforward, but the subject is anything but simple. We're aiming to synthesize all this information so you, the listener, can get a thorough but not overwhelming understanding. We want to know exactly how these frozen behemoths are formed,
Yeah.
the surprising physics behind how they move, and the spectacular, long-lasting legacy they leave etched across the face of the Earth. We're moving well beyond just big, cold ice.
We're going to pull the thread from, the crystalline structure of a single snowflake all the way up to the astronomical forces that dictate the flow of ice across vast continents. It's a truly systemic look.
Okay, let's unpack this then. Let's start with the sheer scale of it all and the fundamental definition. Because when we talk about a glacier, we're talking about something very specific in geological terms, right? It's not just permanent snow that doesn't melt in the summer.
Not at all. That's a crucial distinction. Our sources define it very precisely. A glacier is a large, long-lasting mass of ice formed on land that moves downhill under its own weight.
And that movement component, that's the key.
That is the absolute non-negotiable definition. That flow component is everything. If it's not moving, it's just a snowfield or a static ice patch.
Just a pile of ice.
Exactly. A glacier is, by definition, kinetic. It is an active participant in reshaping the landscape. And the scope of this active material is just staggering.
So how staggering are we talking? Give us the numbers that should really hit home.
Okay, so right now, glaciers cover about 10% of the Earth's land surface.
10%.
Which is roughly 15 million square kilometers. That is a substantial piece of real estate dedicated to flowing ice. But while that land mass is impressive, the truly critical statistic, the one you always have to come back to, relates to fresh water.
Right.
Approximately 75% of the entire world's fresh water is stored in glacial ice.
75%. That statistic is a fundamental game changer, isn't it? It just instantly elevates glaciers from some remote geographical feature to a critical global resource.
A resource whose stability affects every aspect of human and ecological life on this planet. Precisely. And by acting as these colossal high-altitude reservoirs, they are deeply integrated into Earth's major cycles.
Okay, like what?
Well, they're obviously central to the hydrologic cycle, regulating water release over centuries, often sustaining massive river systems far, far downstream. But we also have to remember their powerful role in the rock cycle.
How so?
They are agents of erosion and deposition on a scale that's hard to comprehend. They carve out mountains and transport sediment across entire continents. Their influence is systemic. It spans water, rock, and climate.
That sits the global context perfectly.
Yeah.
Now let's get into the anatomy of ice, because I think people have different pictures in their heads. An ice stream flowing down a mountain is structurally and dynamically very different from a mass that covers a land mass the size of Australia.
Absolutely. We categorize them largely by their size and the geography that constrains them. So on the mountain scale, we have what are called valley glaciers or alpine glaciers.
So ones you see in pictures of the Alps or the Rockies.
Exactly. They are the most familiar type. They're confined entirely by the walls of existing mountain valleys, flowing from a high elevation accumulation center at the head down to lower elevations. They follow the path of least resistance, much like a river, just much, much slower.
Okay, but then when we talk about glacial scale, on a truly planetary level, we jump up to the ice sheets.
Also known as continental glaciers. And they're monumental formations. They are not restricted by any valleys. In fact, they're so thick and expansive that they completely bury the underlying topography. The mountains, the valleys, it's all underneath the ice.
So they create their own topography in a way.
They do, and they flow outward in all directions from one or more accumulation centers, just under their own immense self-generated pressure.
And it's vital to remember the size of these things. We only have two major ice sheets on Earth today, right?
That's right, the Greenland ice sheet and the Antarctic ice sheet. And to give you a sense of scale, Antarctica alone covers nearly 14 million square kilometers. Its average depth is over a mile, over 1.6 kilometers.
A mile of ice.
A mile of ice. They house the vast majority of that 75% freshwater reserve. These are quite literally the world's largest objects made of ice.
And besides those giants, the sources describe a few other key classifications. These are sort of intermediate scales.
Right, you have ice caps, which are basically smaller versions of ice sheets. They still cover uplands and plateaus, they often bury the peaks, but they're generally less than 50,000 square kilometers in area. They flow outward from a central dome, but they just don't reach that immense continental scale.
And then there are the ones that I find really visually interesting, the Piedmont glaciers. I always picture these as the moment the ice finally breaks free from its mountain prison.
That's a perfect visual. That's exactly what they are. Piedmont glaciers are transitional. They form when one or more valley glaciers exit the steep, confining walls of their mountain valleys and just spill out onto a broad, relatively flat lowland at the base.
So they spread out.
The ice loses its lateral restriction, and, relieved of that pressure from the valley walls, it spreads out like a massive frozen fan or a bulb. They look like giant, slowly melting pancakes of ice at the foot of a mountain range.
That covers the different types. But how? How do we get from a fluffy, weightless snowflake to a block of ice that's dense enough to flow and carve granite? What's that transformation sequence?
It requires a very specific set of environmental conditions. The essential prerequisite is that a glacier can only form in a region where snow accumulation consistently exceeds melting or wastage.
Wastage. That's what glaciologists call ablation, right?
Correct, ablation. You need a positive net balance of snow year after year after year. That guarantees you have perennial snow cover.
So once that accumulation starts happening, the snow begins this remarkable journey.
It's a process defined by compression and recrystallization. It's really fascinating. The transformation begins when the initial hexagonal snow crystals are compacted by repeated freezing and thawing, but also just the sheer weight of subsequent snowfall.
Squeezing all the air out.
Exactly. That pressure begins to squeeze the air out. So the fluffy snow first transforms into a granular, denser material we call firn. F-I-R-N. Think of firn as about halfway between snow and true ice. It's still got a significant amount of interconnected airspace, but it's much denser than snow.
And then that process just continues, deepening the compaction.
Exactly. The firn then undergoes further and much more intense compaction over decades, sometimes centuries, depending on the accumulation rate. The pressure squeezes virtually all the remaining air out of the matrix. This forces the individual crystals to interlock into a dense, non-porous structure.
And that's glacial ice.
That dense interlocking mass is the true glacial ice. The lack of airspace is actually why deep glacial ice often appears that striking blue color.
Oh, right, because it absorbs all the other wavelengths of light.
Precisely. And this transformation is what gives the ice the required internal structure to behave dynamically and, begin flowing.
We've established the flow, which leads us directly to what you could call the operational health report of the glacier, the glacial budget. This concept seems to dictate everything about a glacier's future.
It really does. The glacial budget is simply the balance, or more often the imbalance, between the gain, which is the accumulation of ice, and the loss, which is that ablation or wastage.
Okay, and to measure this budget, you divide the glacier into two main zones.
Right. Two zones defined by their annual performance. The first, operating in the high, cold upper reaches of the glacier, is the zone of accumulation.
So that's the positive side of the ledger.
That's the source region. It's where snow input consistently exceeds loss, even in the warmest months. This is where the glacier forms, grows, and adds mass to its budget. New ice is constantly being created and pushed downhill from here.
And then further down the mountain, the balance shifts. You get into the zone of ablation or wastage.
This is the area where there is a net loss of ice. This loss happens primarily through simple melting, which often results in these significant streams flowing from the terminus, the front of the glacier.
But there are other ways it loses mass too, right?
Yes, two other powerful forms of loss we have to account for. One is sublimation, where the ice turns directly to water vapor.
Not a huge factor, I imagine.
Less so than the second, and arguably more dramatic form. Calving.
Where the big chunks fall into the ocean.
Exactly. This is a major subtractive process, especially for glaciers that terminate in the ocean or a large lake. Calving is the sudden, sometimes violent, breaking off of large, massive chunks of icebergs when the glacier reaches deep water. It's an immediate and spectacular way to lose mass from the glacial budget.
So you've got the gain zone and the loss zone. There must be a boundary line between them.
There is. That boundary is the equilibrium line. Sometimes it's called the firn line. If you were to walk along the surface of a glacier at the very end of the summer season, this line represents the elevation where the snow accumulation from the previous winter exactly balanced the amount of ice lost through ablation during the summer.
And crucially, this line isn't geographically fixed. It's like a climate barometer.
It is an extraordinarily sensitive climate barometer, absolutely. If you have a series of cold, snowy winters and cool summers, that equilibrium line will migrate to a lower elevation. That means the zone of accumulation has expanded.
And the reverse is true for warm years.
Conversely, yeah. If you have a series of warm, dry summers, the equilibrium line will move higher up the mountain, shrinking the accumulation zone and increasing the ablation zone. Its position is the visual indicator of the glacier's annual health.
Okay, here is where the concept gets really interesting, and I think it often trips people up. We constantly hear reports that a glacier is retreating, and the intuitive leap for most people is that the ice has stopped flowing or is somehow moving backward up the mountain.
Okay.
But our sources make it crystal clear that is fundamentally wrong.
It is a critical misconception we have to clarify. The ice mass itself is always flowing downhill due to gravity. That movement is relentless. It's like a slow-motion river. The movement of the front of the glacier, the terminus, is simply the net result of that glacial budget.
It's the visible manifestation of how the flow rate compares to the melt rate.
Perfectly put.
So let's run the three scenarios. Let's use the conveyor belt analogy. If the rate of ice flow delivering material to the terminus is exactly equal to the rate of melting and calving at the terminus, what happens?
The glacier front remains stable. It holds its position. Even though tons and tons of ice are flowing through it every single day, the front doesn't move. The conveyor belt is delivering ice at the same rate that it's being removed at the end. The budget is balanced.
Okay, scenario 2. The glacier is healthy and thriving. Accumulation is greater than ablation.
Then the flow rate delivers more ice than is being lost. The glacial front advances. It pushes further down the valley or across the landscape, forcing the terminus position forward into a new area.
And now the paradox.
Yeah.
The retreat scenario. When we hear a glacier is retreating, it means ablation is exceeding accumulation.
Correct. When the glacier is retreating, it simply means the ice is melting faster at the terminus than the ice flow is capable of delivering new mass to the front. The flow never stops. The ice mass is still moving due to gravity.
It's just losing the race against melting.
It's losing the race. The flow is just insufficient to compensate for the rapid rate of loss. So the terminus position is pulled back uphill, but the ice mass itself continues its slow gravitational journey.
That distinction, the difference between the movement of the ice mass and the position of the ice front, that's essential. It's a flow dynamic, not a reversal. So this brings us naturally to the physics of that flow. How does a solid material like ice actually move?
The primary driver, as we've said, is gravity. But the flow is achieved through two distinct mechanisms that operate at the same time. The first one, and maybe the most interesting, is plastic flow. This describes the movement and deformation within the ice mass itself.
Plastic flow. That sounds strange. We think of ice as brittle, right? Something that shatters when you hit it.
And it is brittle at the surface.
Mm-hmm.
But that's the critical insight from decades of research. Below a certain depth, usually about 50 meters, the ice stops behaving purely as a brittle solid. The immense weight of the overlying ice creates pressure that is high enough to induce what's called shearing stress.
And how does that shearing stress affect the ice's crystalline structure?
Well, ice crystals are hexagonal, and under that intense, constant pressure, the internal structure of those crystals actually allows them to glide and realign themselves along preferred structural planes. This movement is called crystal creep.
So the crystals themselves are sliding past each other.
They are. It means the ice mass can internally deform. It stretches and warps without fracturing. It flows like a thick, cold, highly viscous syrup. This internal deformation allows the deeper layers of the glacier to move faster relative to the layers above them.
So below 50 meters, the ice is pliable and it flows. But there's a second major mechanism, one that affects the entire mass at the interface with the ground.
Yes, and that is basal slip. This is where the entire ice mass literally slips and slides along the ground, the bedrock beneath it. This mechanism is hugely important for fast-moving glaciers, and it's facilitated by a crucial ingredient, meltwater.
But why does meltwater form at the base? I mean, especially when the air temperature is way below freezing.
There are a couple of reasons. The first is just geothermal heat, the residual heat coming up from the Earth. But the second and more potent reason is pressure melting.
Ah,
The immense weight of hundreds or thousands of meters of ice puts enormous pressure on the ice at the very bottom, and that pressure actually lowers the melting point of the ice. So even slight friction generated by the movement can melt it, creating this thin, high-pressure film of water.
And that water acts as a perfect lubricant for the entire mass.
A highly effective, high-pressure lubricant. It allows the glacier to slide much more efficiently over the bedrock. Without basal slip, many glaciers would move significantly slower, relying only on that internal plastic deformation. The interplay between plastic flow and basal slip really defines the overall velocity.
So you have this differential movement. You have plastic flow below, basal slip at the ground, but the top layer isn't deforming. It's just being carried along.
Exactly, and that creates stress. And that stress results in the most recognized feature of a traveling glacier, the crevasse.
Right.
The uppermost 50 meters of the glacier remains the zone of fracture. Because the ice here is under less pressure, it retains its brittle, crystalline nature. As the lower ice stretches, deforms, and slides along the base, that rigid top layer is unable to deform plastically. It's subjected to intense tension instead.
It's like a brittle shell being dragged along a flowing river of syrup beneath it.
That's a perfect way to put it. And that tension causes the ice to fail, creating these large, deep cracks called crevasses. They are a visual signal of active movement, of differential stress, of dynamic change.
And they can tell you what the ice is doing, can't they?
Oh, absolutely. They form perpendicular to the direction of stress. They are crucial indicators of areas where the glacier is accelerating or decelerating or flowing over steep inclines.
Okay, so moving from the internal dynamics to the external consequences, we get to the spectacular legacy of ice. Glaciers are known as monumental sculptors. They fundamentally reshape geography. How do they do it? What gives them this incredible erosive power?
They employ two primary methods that rely on just immense force and constant duration. The first is a process called plucking.
Plucking.
Yeah. Imagine the glacier freezing directly onto blocks of rock along its bed and its sides. This is often aided by water seeping into cracks and freezing, leveraging the sheer force of crystallization.
So the ice is basically bonding itself to the bedrock.
Exactly. And as the ice flows forward, it literally lifts and pries these blocks of rock, and I mean some the size of small houses, right out of the underlying bedrock. It's a geotechnical extraction process on a colossal scale, constantly pulling pieces out.
And the second process is more like a grinding action.
That is abrasion. The ice mass is now heavily armed with all those angular rock fragments it has just plucked. These fragments, embedded in the base of the glacier, act like giant pieces of sandpaper being dragged across the bedrock.
And this happens for thousands of years.
For thousands of years. This constant, relentless grinding produces two distinct, memorable results. The first is rock flour. Rock flour is pulverized rock. It's the finest powder created by this endless grinding action. It's often so fine that it stays suspended in the meltwater, and it's responsible for that characteristic milky, opaque, sometimes turquoise appearance of glacial-fed lakes and rivers.
I've seen that color. It's incredible.
And that fine silt is a critical part of the depositional story later on.
And the second result of abrasion, which must be a treasure for geologists studying ancient ice flows, is striations.
Oh, absolutely. Striations are grooves and deep scratches etched directly into the underlying bedrock. Because the embedded rocks were dragged along the glacier's path, these markings provide definitive directional evidence. When a geologist finds striations, they know 100% that a glacier passed over that spot, and they know the precise path it took.
So now we can look at the stunning landforms carved by this erosive power. These are the mountain features that define the spectacular scenery of places like the Rockies, the Alps, Scandinavia.
They really are. And the most dramatic visual transformation is the creation of the glacial trough, or what's commonly called a U-shaped valley.
Right, because a normal river valley is V-shaped.
It is. A standard stream valley is V-shaped because the stream cuts down vertically. A glacier, however, fills the entire valley. It erodes the sides and the floor equally, transforming that sharp V into a massive, deep, steep-sided U-shape. It often straightens the valley significantly in the process, too.
And if we look up toward the origins of the glacier, we find the birthplace of the ice, the cirque.
Yes, the cirque. It's a distinctive, bowl-shaped depression, like a natural amphitheater, found right at the head of a glacial valley. It's the collection basin where the snow accumulated, compacted into ice, and began its flow. The specific rotational movement of the ice here, sometimes called scour, scoops out the rock, often leaving behind a steep, sheer headwall.
And when you have smaller tributary valleys that used to feed into that main valley, they often get left stranded high up on the walls of the newly deepened trough.
Those are the hanging valleys, and they are a direct result of differential erosion depth. The massive main glacier, which has far greater erosive power, carves its trough hundreds of meters deeper than the smaller tributary glaciers can cut theirs.
So when the ice melts, the little valleys are just left hanging there.
They look like shelves or high-level steps on the side of the main U-shaped valley, and they're often marked by these picturesque waterfalls that plunge into the trough below.
We mentioned that cirques are the scoopers. So what happens when multiple cirques start eroding the same mountain from different sides? They must sharpen the surrounding landscape into these dramatic knife-edge features.
That process creates two spectacular landforms. An arête is a thin, sharp-edged ridge, often resembling a knife blade, that separates two adjacent glacial valleys or sulks. It's the thin partition that's left behind.
And if those cirques manage to erode a mountain on pretty much all sides,
The ultimate result is a striking, sharp, pyramid-like peak known as a horn.
like the Matterhorn.
The Matterhorn in Switzerland is the classic, textbook, breathtaking example of a horn. It was formed by the erosion of three or more cirques eating away at the same mountain mass, leaving only that central, steep spire standing.
Finally, we have to mention a spectacular erosional landform that defines so many high-latitude coastlines, the fjord, or fjord.
A fjord is powerful evidence of glacial erosion extending far below current sea level. It is, simply put, a U-shaped glacial trough that has been drowned by the sea after the ice retreated and global sea levels rose.
So the glacier carved the valley out when sea level was lower.
It carved the valley floor far below the level of the sea, even while it was happening. This is possible because the glacier, having been buoyed and contained by the weight of its own ice, could keep eroding downwards. When the ice melted, the ocean just flooded in. That's why they're characterized by such deep water and dramatically steep, high cliff sides.
So we've covered the sculpting, the subtraction side of the ledger. But glaciers are also immense carriers. They transport vast amounts of debris. When the ice retreats, it drops off everything it has collected, creating an entirely different set of landforms. We call the overall sediment glacial drift.
Glacial drift is the comprehensive, all-embracing term. It's for any and all sediments, regardless of their size, their composition, or how they were transported, that were deposited by or with the aid of a glacier. However, within drift, the mode of deposition is crucial, and it divides it into two very distinct categories.
First, there's the material deposited directly by the ice itself, the stuff it just drops.
That is till. Till is the sediment that was physically dumped or abandoned when the ice melted right where it was standing. And our sources highlight two critical characteristics of till. First, it is wildly unsorted. It's a chaotic mixture containing everything from massive boulders the size of cars down to the finest rock flour, all jumbled together. And second, it is unstratified. It's not laid down in distinct layers. It's just a mess. A pile of material drops straight out of the ice.
And contrasting that chaotic deposit, we have the material that was carried and organized by water.
That is stratified drift. This is sediment deposited not by the ice, but by the rushing meltwater streams, the braided rivers flowing from the glacier. And these streams behave just like any other stream. They organize material based on size and weight.
Why is water so good at sorting things?
It's purely a matter of physics and velocity. As the meltwater stream slows down, it loses its capacity to carry heavy particles. So the largest, heaviest gravel drops out first, then the sand, and finally the fine silt. Therefore, stratified drift is characteristically layered or stratified and sorted by size. It's the organized deposit versus the chaotic dump of till.
Okay, so now let's focus on the distinct features built from these different types of drift, starting with the most common, which are the ridges of material left at the sides and the front of the glacier. Moraines.
Moraines are simply layers or ridges composed entirely of till. They come in several distinct forms, all tied to their relationship with the flowing ice. In a valley glacier, for instance, we find lateral moraines. These are ridges of till built up along the sides of the valley glacier, often plastered right against the valley walls.
And what happens when two of those valley glaciers merge?
Their adjoining lateral moraines join forces to create a striking feature called a medial moraine. This appears as a dark stripe of debris running straight down the center of the now larger composite glacier. It's formed when the debris that was previously pushed against the outer walls is now trapped internally as the two streams of ice fuse together.
And the third crucial type marks the glacier's boundaries.
That's the end moraine. This is the ridge of till that forms right at the terminus or front of the glacier. It acts like a giant debris pile being shoved forward by the advancing ice. A particularly important type of end moraine is the terminal moraine, which marks the farthest extent the ice ever reached. It's a crucial marker for geologists.
Now, shifting to slightly more complex features, especially those left behind by the vast continental ice sheets, we have drumlins. These are visually distinct, and they tell a powerful story.
Drumlins are striking. They are streamlined, asymmetrical hills composed of till. They look like elongated, inverted spoon bowls or basket halves. Their long axis is the crucial part because it provides definitive evidence of the precise direction of the past ice flow.
So they're like geological weather vanes.
Exactly. They were sculpted by the flowing ice, often indicating that the ice mass flowed up and over them, streamlining their shape in the process. They are the geological equivalent of an arrow pointing where the ice went.
Next, we move into the features composed primarily of stratified drift, the material organized by meltwater. Let's start with the most winding and surprising features, the eskers.
Eskers are fascinating. Their formation process is completely counterintuitive. They are these sinuous, winding ridges composed entirely of sorted sand and gravel. They literally look like a fossilized riverbed snaking across the landscape.
But their ridges are raised up.
Right, and that's because they were deposited as sediment settled out from streams that flowed within or, critically, beneath the glacial ice.
So a river was literally tunneling inside the ice mass.
Yes. Under the immense pressure of the ice, meltwater streams carved out tunnels for themselves. When the climate warmed and the massive glacier melted away, the sediment-filled channel was just left standing high above the surrounding landscape as a long, winding ridge. It's a complete inversion of topography.
That's amazing. We also have other forms of stratified deposits that look less like ridges and more like chaotic hills.
Those are kames. Kames are steep-sided hills and mounds, also composed of stratified sand and gravel. They form when meltwater streams deposit sediment into localized holes or crevasses or depressions on the surface of stagnant or melting ice. When the ice finally melts, the sediment pile just collapses into a cone-shaped hill.
And finally, a feature that dots the landscape of formerly glaciated regions all across North America and Europe, the Kettle Lake.
Kettle lakes, or kettles, they're formed by a very specific sequence of events. As the glacier terminus retreats, large, isolated blocks of ice can sometimes become detached and then buried beneath outwashed sediment, that sorted, stratified drift that's flowing away from the margin.
So it's a buried iceberg, basically.
A buried block of ice, yeah, and it can persist there for centuries. When that isolated block of ice eventually melts, it leaves a circular or oval depression in the sediment, which then often fills with groundwater or rainwater to become a kettle lake. They are the footprint of a forgotten block of ice.
That covers the physics of flow and the resulting landscape. But to fully appreciate glaciers, we have to talk about deep time, the millions of years when ice advanced and retreated across the planet. We are, of course, talking about the Pleistocene epoch.
The Pleistocene. It spans over 2 million years, and it fundamentally defined the modern geography of the Northern Hemisphere. Its defining characteristic was the cyclical nature of its climate. There were numerous glacial cold, ice advancing, and interglacial warm ice retreating periods that dictated the rise and fall of global sea levels and the extent of those massive continental ice sheets.
And our sources indicate this cyclical pattern had a very distinct long-term rhythm to it.
Yes, the data is very clear on this. These major cycles of advance and retreat occurred approximately every 100,000 years. This long-term clock dictated the movement of the massive ice sheets across North America and Eurasia, which extended far south into what is now the Midwestern United States and Central Europe.
And to put this into a more modern human timescale, when did the last major pulse of this happen?
Well, the most recent glacial maximum, the furthest extent of the ice baked relatively recently, geologically speaking, around 18,000 years ago.
18,000.
That massive glacial period, the one responsible for carving out the Great Lakes, depositing those vast moraines, and creating the eskers and drumlins we just discussed, officially ended approximately 10,000 years before present. We are currently living deep within an interglacial period known as the Holocene.
It's incredible to think we can map the extent and timing of events that happened tens of thousands of years ago with such precision.
How do scientists get that level of historical detail about climate? It comes down to these incredible natural archives, specifically the information locked inside ice cores.
Ice cores are truly the planet's history books. They preserve layers of accumulation year after year after year. These cores, which are drilled primarily from the thickest parts of the Greenland and Antarctic ice sheets, provide continuous, high-resolution climate records stretching back hundreds of thousands of years, in some cases, nearly a million years.
Yeah.
What specific information is trapped inside those compacted layers of glacial ice? What are they looking for?
As the snow falls and compacts, it traps several things. Tiny bubbles of ancient atmosphere, which is incredible in itself, layers of volcanic ash, dust, and critically chemical signatures within the water molecules themselves. The most important data comes from analyzing the isotopic compositions of oxygen within those water molecules.
Okay, tell us more about the oxygen isotopes. How does a chemical ratio tell us the temperature of the past?
So we look at the stable isotopes of oxygen, primarily oxygen-16 and oxygen-18. O16 is the lighter isotope and O18 is the heavier one. The ratio between these two is sensitive to temperature through a process called isotopic fractionation.
How does that fractionation work?
Well, in cold periods, it is harder for the heavier O18 molecules to evaporate from the ocean surface because they require slightly more energy. Conversely, the lighter O16 molecules evaporate more easily. This lighter water vapor then travels and falls as snow, accumulating in the polar ice sheets. Therefore, during colder glacial periods, the ice cores show a relative enrichment in the lighter O16 isotope.
So a lower O18 to O16 ratio in the ice core means a colder global climate.
Exactly. And conversely, during warmer interglacial periods, the ocean water is more easily evaporated, increasing the O18 content in the snowfall, which leads to a higher O18 ratio in the ice cores. By analyzing this layer by layer, scientists can reconstruct a continuous and highly accurate temperature record, and it aligns perfectly with that 100,000-year cyclical rhythm of the ice ages.
And that rhythm, that 100,000-year clock, is not random chance. It is attributed to predictable external astronomical events named after the Serbian scientist who calculated their influence, the Milankovitch cycles.
Milankovitch cycles are the long-term external drivers for the planet's glacial cycles. They describe the predictable long-term changes in three aspects of the Earth's orbit and its orientation relative to the Sun.
And they don't change the total amount of solar energy Earth receives, right?
Yeah. No, that's a key point. They don't affect the total amount over a year, but rather where and when that energy is distributed across the planet, especially at high latitudes where ice inception begins.
So what are the three components of these cycles?
Okay, they are. Eccentricity, which is the change in the shape of Earth's orbit from nearly circular to more elliptical, that operates on about a 100,000-year cycle.
The dominant cycle?
The dominant one. Then there's obliquity, which is the change in the tilt of Earth's axis that affects the severity of the seasons, and it's on a 41,000-year cycle. And finally, precession, which is the wobble of Earth's axis, kind of like a spinning top, that determines when the seasons occur along the orbital path, on about a 23,000-year cycle.
And it's the combination of these three that dictates the long-term rhythm of the ice.
It's the subtle, synchronized variation of all three cycles that is believed to initiate or end major glacial periods. The critical factor is their cumulative effect on summer insolation at high northern latitudes.
So summer sunlight in the north.
Right. For a glacier to form, you don't necessarily need incredibly cold winters. What you really need is cool summers that fail to melt the previous winter's snow accumulation.
So when the Milankovitch cycles conspire to reduce the amount of summer solar radiation hitting places like northern Canada and Scandinavia, that's the trigger.
That's when accumulation begins to exceed ablation on a planetary scale, tipping the glacial budget into the positive for thousands of years.
It connects the macrocosmic mechanics of the solar system, how Earth tilts and wobbles, to the microdynamics of how a pile of snow transforms into a powerful continent-carving mass of flowing ice.
Exactly. The astronomical configuration provides the trigger, and the movement mechanisms we discussed, the plastic flow and basal slip, are the engine that allows the ice sheet to build and spread.
Okay, let's bring this entire deep dive together.
Yeah.
We have truly spanned the spectrum today, from the basic definition of a glacier as a massive, moving mass of ice, all the way to the astronomical forces that dictate its very existence.
We dissected the anatomy of ice, distinguishing the valley glaciers from the enormous continental ice sheets, and we detailed that essential journey from fluffy snow through fern to dense blue glacial ice.
Crucially, we clarified the glacial budget, that fragile balance between gain in the accumulation zone and loss through melting and calving in the ablation zone, all separated by that sensitive equilibrium line. And we emphasize the paradox that a retreating glacier is always, always still flowing.
We went deep into the physics of movement, contrasting the internal plastic flow, that deep-seated deformation of ice crystals under pressure, with the surface movement facilitated by basal slip, which is lubricated by meltwater, leaving the top 50 meters brittle and prone to those deep crevasses.
And we explored the spectacular permanent legacy these dynamics leave behind. Glaciers are planetary forces that simultaneously carve mountains into sharp horns and arêtes, scoop out massive cirques, and flood coastlines to form dramatic fjords.
On the depositional side, they leave behind two very different signatures. That unsorted, chaotic dump of till in moraines and streamlined drumlins, which contrasts sharply with the layered, water-sorted deposits of stratified drift that we find in snaking eskers and conical cames.
And the ultimate context for all of this is deep time, particularly the Pleistocene, where we saw that 100,000-year rhythm of ice ages confirmed by the chemical signatures found within the ice cores. Those cores use isotopic compositions to tell the precise temperature history of our planet.
The critical concept is that the flow, the retreat, and the advance of the ice is ultimately governed by the Milankovitch cycles, that long, slow, orbital dance of Earth that periodically reduces summer solar energy, tipping the global glacial budget toward accumulation.
And this brings us back to the immediate and global relevance of these systems. We understand now that Milankovitch cycles define the natural, vast timeline of advance and retreat, operating over hundreds of thousands of years.
So if we connect this to the bigger picture, consider that natural, slow, 100,000-year orbital clock. It dictates the long-term rhythm. This raises an important question for you, the listener, to continue exploring. Knowing that the equilibrium line naturally shifts based on these vast, slow orbital changes, how do the dynamics of today, specifically the observed rapid year-to-year changes in the balance of accumulation versus ablation, compare to that slow, gentle pace that historically drove the glacial cycles of the Pleistocene?
A profound thought.
When the natural clock is measured in millennia, what does it mean for the future of Earth's crucial freshwater supply when the rate of ice loss is measurable in mere decades?
That connects the deepest history of our planet with the urgent present. That was our deep dive into the dynamics and monumental legacy of glaciers. Thank you for diving deep with us. Okay, let's unpack this. You're here because you want to get a handle on the real architecture of our planet. We're talking about the stuff that makes up everything from continents to the ocean floor. We're talking about rocks.
Right.
But not just, heavy, static blocks. We are diving deep into the fiery, really dynamic processes that are constantly building and rebuilding the Earth.
Exactly. And we're trying to move beyond just the surface level definitions you get in a textbook. Our sources today are all about the immense dynamism of it all.
The planet's engine room?
The engine, yeah. The rock cycle, the driving force behind that, which is plate tectonics, and then a really forensic look at one of the fundamental building blocks, igneous rocks.
So our mission today is pretty clear. We want to deliver a comprehensive, but also, technically nuanced deep dive into how the Earth's internal heat and pressure work together to create these fire rocks. We want you to walk away not just knowing the names granite and basalt, but really understanding their origin story, their cooling history, and, why one ends up as a high mountain while the other sinks deep under the ocean.
And the material is just fascinating because it proves that rocks are, well, that anything but constant. They're products of this continuous transformation.
Driven by weathering, erosion.
And critically, the energy from deep inside the planet, tectonic activity is like this global conveyor belt of creation and destruction.
The ultimate flowchart for all of this, like you said, is the rock cycle. And plate tectonics drives the whole thing, the movement of the Earth's lithosphere, and that movement dictates where, how, and why all these different rock types form and then eventually get recycled.
And just to set the stage for our main focus, let's quickly frame the three main rock types, but really think about their relationship within that cycle. So first, you have sedimentary rocks. They're crucial because they form from all the broken down bits on the surface. But, and this is really important for our deep dive, they often trap huge amounts of water and organic material.
Ah, so they become carriers.
Exactly. They carry these volatile materials with them when they get pulled back down into the mantle.
Then you've got metamorphic rocks. These are existing rocks that get transformed by intense heat and pressure, usually near active plate boundaries, but without completely melting.
They're the morphs, yeah. They've changed, but they haven't been totally rebuilt from scratch. They tell a story of just immense stress.
And that brings us to our focus today, igneous rocks. The name comes from the Latin ignis, for fire.
Which is perfect, right? They are the direct result of molten material solidifying. Now, whether that material is magma, cooling slowly below the surface to form what we call intrusive or plutonic rocks.
Like granite?
Like granite, exactly.
Yeah.
Or whether it's lava, which is what we call it when it reaches the surface and cools rapidly, forming extrusive or volcanic rocks.
Like basalt.
It's like basalt. And that single distinction, slow cooling below versus rapid cooling above, that is the defining feature of all igneous petrology.
So let's start right there at the very beginning, the engine room. To melt rock, you need a tremendous amount of energy. Where does all that heat come from, and why is it so hard to actually melt rock with it?
Well, the Earth's interior is this really complex thermal system. It's kept hot by two enormous continuous sources. First, there's the residual heat.
Leftover energy.
Yeah, leftover energy from the violent collisions and gravitational compression that formed the planet 4.5 billion years ago. It's like the planet's initial energy budget.
And that's still a huge amount of heat, even today.
Oh, absolutely. But the second source, and this is the one that really keeps the engine running long term, is continuous radioactive decay. You've got isotopes of elements like potassium, uranium, and thorium, and they're just scattered throughout the mantle and crust. And as these elements decay, they release a massive amount of thermal energy. That process is what maintains the incredibly high temperatures deep inside the Earth.
Okay, so here's the puzzle that our sources really highlight, and it's something that often trips people up. Rock melts somewhere between 650 and 1100 degrees Celsius.
Right.
The mantle is definitely hotter than that in most places.
Yeah.
So why isn't the entire mantle just a liquid ocean of magma?
That is the key question. And the answer is the confining pressure. You have kilometers and kilometers of rock pressing down from above. The melting point of any rock is directly tied to the pressure it's under.
The more pressure, the harder it is to melt.
Precisely. Under that immense high pressure, the mineral structure is packed so tightly that even at, say, 1,000 degrees Celsius, the material stays solid. This pressure barrier is why we see these super high temperatures, but a mostly solid, even if it is a bit plastic, mantle.
In fact, the source material notes that new magma is mostly generated from the asthenosphere, the layer just below the lithosphere, and even there, it's often only, 1 to 2% molten?
That's right.
So if just cranking up the heat doesn't work, how do we get around that pressure barrier and actually turn solid rock into liquid magma?
This brings us to the three crucial mechanisms of melting. And what's so fascinating here is that to generate magma, we often don't increase the temperature. Instead, we manipulate the conditions around the rock to either lower its melting point or just reduce the pressure.
Okay, let's start with the most common one, the one that creates new ocean crust. That's decompression melting. How does relieving pressure cause rock to just liquefy?
So think about a rock's geothermal gradient. That's the rate that temperature increases as you go deeper. When a chunk of hot rock from the mantle rises quickly, it cools down a little, but not very fast.
Okay.
Now, if that hot, solid rock body rises fast enough, the pressure confining it drops dramatically, while its temperature stays almost constant.
So you're basically lifting it up to a shallower depth, where the temperature it needs to melt is now lower than its actual temperature. It crosses a threshold.
You've got it. It crosses the solidus curve, which is the line between solid and liquid. That's why decompression melting is the dominant mechanism at divergent plate boundaries like mid-ocean ridges.
Where the plates are pulling apart.
Exactly. As the plates pull apart, the underlying mantle rock rises up super fast to fill that void. The pressure release is enough to trigger widespread melting, and you get these massive amounts of low-viscosity massic magma, basaltic magma, that forms the new ocean floor.
That model makes perfect sense for spreading centers. But the sources also mention that some of those oceanic hotspot volcanoes, like the Hawaiian chain, they show evidence of deeper volatiles and more chemically complex rocks than you'd expect from pure mantle material. How does the pure decompression model explain that little chemical anomaly?
That's a great point, a point of real nuance. While the magma in Hawaii is predominantly basaltic classic decompression melt, The sources do suggest that even mantle plumes rising from deep within the Earth can carry minor amounts of trapped volatiles.
Like water or CO2.
Right, or they can be chemically a bit heterogeneous from some prior process. So while decompression is the dominant mechanism, adding even tiny amounts of water can, enhance the melting process. It lowers the solidus temperature just that little bit more and increases the melt fraction. It just makes the whole process more efficient.
So decompression is the rule for plates pulling apart, but then we shift to a chemical process when plates collide. The addition of water, or volatiles, this is key for building continents.
Oh, absolutely vital. When an oceanic crustal plate subducts, when it sinks beneath a continental plate or another oceanic plate, it takes all these hydrated minerals down into the mantle with it.
So it's dragging water down deep into the Earth.
It is. And as that plate descends into higher temperature and higher pressure zones, the water molecules are literally squeezed out of the crystal structure. It's a process called dehydration.
And this squeezed out water then percolates up into the mantle wedge above it. So what does that water do to the hot, solid rock that's already there?
It acts as a powerful flux. The water chemically interacts with the silicate minerals in that overlying rock, and it effectively breaks some of the strong silicon-oxygen bonds. This just dramatically reduces the melting temperature of the rock.
So you're basically poisoning the structure just enough to let it melt.
That's a great way to put it. You're allowing melting to happen at a temperature that was previously too low to overcome the pressure. So if a rock needed, say, 900 degrees Celsius to melt when it was dry, adding water might drop that threshold to 750.
And this is the fundamental way we generate the more silica-rich magmas, the intermediate and felsic ones, that eventually rise, cool, and build up the continental landmasses.
And if you connect that to the bigger picture, it's perfect. Decompression melting makes the heavy, dense basalt of the ocean floors. But this water flux melting, it generates the buoyant, lighter magmas that become granite, the very backbone of the continents. These two mechanisms drive the fundamental differences on our planet's surface.
That's a powerful distinction. Okay, finally, we have the most straightforward mechanism, but it kind of relies on the first two to even get started. That's heat transfer.
Yeah. This is just simple transmission of thermal energy. Once you have a hot, low-density body of magma that's been generated, say, some basaltic magma from decompression, it starts to rise toward the surface.
Because it's buoyant.
Because it's buoyant. And as it moves up, it naturally transfers heat to the surrounding country rock that it's pushing through. If the magma is hot enough and the country rock has a low enough melting point, the country rock will start to melt too.
And when that country rock melts, that material gets mixed into the magma.
Correct. We call that process assimilation, and it changes the overall chemical composition of the melt. So, for example, if you have a hot mafic magma, which is low in silica, rising up through felsic continental crust, which is high in silica,
it's going to melt and incorporate some of that high silica rock.
And the resulting magma mixture becomes less mafic, it becomes more intermediate or even felsic. This interaction explains a huge variety of igneous rock chemistries that you just can't get from a single source alone.
So we have three paths to magma. You lift the pressure, you add water, or you just heat up the surroundings. And the scale of this, starting with just a 1 or 2% melt deep down, is really impressive. You have to imagine, a 500-mile stretch of the lithosphere as this massive, slow-moving chemical factory.
It really is.
So now that we have this molten material, let's define it. Magma is the parent material. If it solidifies underground, it's intrusive plutonic. If it hits the surface, it's lava, volcanic. But magma isn't just molten rock, right? It's more of a dynamic, multi-phase chemical stew.
That's it, exactly. To understand a rock's behavior, why one flows gently like in Hawaii and another explodes violently like Mount St. Helens, we have to break down its three components. First, there's the liquid portion, the melt itself.
Okay.
This is primarily mobile ions, mostly silicon and oxygen, forming these complex silicate chains and networks.
Then you have the solids.
Right. If the magma has spent any time cooling slowly down at depth, even if it's still mostly liquid, it may have already started to crystallize. So these solids are silicate minerals that are already forming orderly structures, and just having them there influences the viscosity and flow of the whole melt.
And third, the component that you said dictates explosive power, the volatiles, the dissolved gases.
This is the most important one for eruptions. The main gases our sources point to are water vapor, carbon dioxide, and sulfur dioxide. These gases are dissolved under high pressure deep down. They're basically held captive in the liquid.
Like a shaken soda bottle.
Exactly like a shaken soda bottle. When the magma rises, the confining pressure drops, and those volatiles expand dramatically. I mean, hundreds of times their original volume.
And if a magma is sticky?
If the magma is sticky or high viscosity, those gases can't escape easily. The pressure builds and builds until you get a massive explosion that releases them. And that is the difference between a nice, effusive, flowing eruption and a catastrophic eruption of ash and pyroclastics.
So the volatile content is absolutely crucial. But once that magma actually starts to cool, it solidifies. And doesn't do it randomly. It follows this highly predictable step-by-step process called Bowen's reaction series.
Right.
This sounds like the framework for everything in igneous petrology.
It really is. Norman Bowen conducted these groundbreaking lab experiments that showed that as magma cools, ions don't just freeze all at once. They arrange themselves into specific, orderly mineral patterns, and the composition of the liquid that's left over is constantly evolving.
And this series is split into two different but simultaneous branches. Tell us about the discontinuous series.
Okay, so the discontinuous branch involves specific sequential mineral changes. As the temperature drops, a mineral forms. And if that mineral stays in contact with the melt, it will chemically react with the liquid to form the next mineral in the series.
Which has a completely different structure.
A completely different crystal structure. It's like a stair-step process. You start with high-temperature olivine, which has a simple isolated structure, that reacts to form pyroxene, which has a single-chain structure. Then that becomes amphibole, a double chain, and finally biotite mica, which is a sheet structure.
So the actual crystal structure is literally becoming more complex as the temperature drops, and it's getting progressively more silica-rich.
Precisely. And at the same time, running parallel to this is the continuous series. This involves the plagioclase feldspar group of minerals. Here, the mineral structure stays the same, but the internal chemistry shifts gradually. At super high temperatures, the plagioclase is rich in calcium. Then, as it cools, the mineral continuously substitutes more and more sodium into its crystal lattice. It's a smooth, gradual transition within the same mineral family.
The genius of Bowen's work is that it explains why certain minerals are almost always found together, like quartz and muscovite mica, and why others are basically never found together, like quartz and olivine.
Exactly, because they form at completely different temperatures. If you let the whole process run to completion, you eventually end up with the low-temperature minerals: potassium feldspar, muscovite mica, and finally, quartz. And those are the key minerals of felsic or granitic rock.
Okay, here's where it gets really interesting, and this gets into the technical balance. Our sources demand. Magma doesn't just sit still, it evolves. And if Bowen's series is the ideal theory, then magmatic differentiation is what happens in the real world.
Differentiation is critical. It explains how a single, simple starting magma, usually a mafic or basaltic one, can evolve into a whole variety of different rock types, including intermediate and felsic ones. And the key mechanism driving this is called fractional crystallization.
What is that, mechanically speaking? What's happening?
It's the physical removal of the crystals that form early on from the rest of the liquid melt. Because those early formed crystals, like olivine and the calcium-rich plagioclase, are denser than the melt, they tend to sink.
So gravity settling.
Gravity settling right to the bottom of the magma chamber. And once they're physically separated, they can no longer react with the liquid melt to form the next minerals in Bowen's series.
So you're taking the heavy, dark, low silica components out of the equation early on.
Yes, and the remaining liquid is left proportionally richer in silica and all the lighter elements. The melt becomes progressively enriched in silicon dioxide and volatiles, and its temperature drops. This process can literally transform an initial basaltic melt into an intermediate melt, and eventually, if it's really efficient, into a felsic granitic melt. You're evolving the chemistry through physical separation.
That's a huge contrast with the second process, assimilation, which we touched on earlier.
Assimilation is all about external contamination. It's what happens when a rising magma body melts and incorporates the rock around it, the country rock. This isn't about internal evolution, it's about mixing in foreign material.
Right.
So if a mafic magma melts some felsic sandstone, the magma's composition shifts because of that external addition. And the key indicator you look for is often the presence of these partially melted or undigested fragments of country rock, which are called xenoliths, suspended inside the igneous rock.
And then third, the simplest but maybe the most dramatic mechanism, magma mixing.
Magma mixing is basically a sudden external collision. You have two chemically distinct bodies of magma, maybe a deep, hot mafic melt rising up really fast, and it slams into an older, cooler, more felsic melt near the surface.
And they combine.
They combine in a single chamber. And when they blend, they produce this unique single magma body with a composition that's often just an average or intermediate between the two originals.
So differentiation is this slow internal chemical evolution driven by density, while mixing is a sudden external blending of two different magmas. That distinction really helps simplify the huge variety we see in igneous rocks.
It proves that their chemistry is basically a record of their complex geological travel path.
And those processes, fractionation, assimilation, mixing, they ultimately determine the rock's bulk composition, which is how we classify them.
Exactly. We categorize igneous rocks based on their primary mineral content, which is overwhelmingly silicate minerals.
And we split these silicates into two key groups that determine the color and the density of the rock. First, you have the dark or ferromagnesian silicates.
Right. They are high in magnesium, magnesia, and iron ferro. This includes olivine, pyroxene, amphibole, and biotite mica.
And because of the iron and magnesium, these minerals are darker, black or dark green, and crucially, they make for higher density rocks. They crystallize early and form the backbone of the oceanic crust.
The second group is the light or non-ferromagnesian silicates. These are rich in silica, but also potassium and sodium. This group includes quartz, muscovite mica, and all the feldspars. These minerals are typically white, pink, or clear, and their low-density structure leads to buoyant rocks.
And when we combine these minerals based on their silica percentage, we get the four major compositional categories. It's a spectrum, right? From high silica and buoyant to low silica and dense.
And that density difference is literally the reason continents float.
Okay, let's start at the high silica, low density end. Felsic or granitic composition.
These rocks are the definition of continental crust. Felsic stands for feldspar and silica. They're composed almost entirely of those light-colored silicates, quartz, K-feldspar, and sodium-rich plagioclase. They have the highest silica content, generally over, say, 68 to 70%.
And that high silica content makes the magma really viscous like peanut butter, not water. And that contributes to its low density. And this buoyancy is fundamental. It lets the continents ride high on the denser mantle below.
A concept called isostasy, and the primary intrusive example is granite. Because it cooled slowly deep underground, it has a phaneritic or coarse-grained texture. Granite is incredibly durable, it's abundant, and it forms the core of many ancient mountain ranges.
And its extrusive twin
Is rhyolite. Chemically identical, but it cooled rapidly, giving it an aphanitic or fine-grained texture. You find it in continental volcanic fields.
Okay, so moving a little down the silica spectrum, we get to intermediate or andesitic composition. This is a classic signature of destructive plate boundaries.
Intermediate rocks contain roughly 55 to 65% silica. They have a mix of light and dark silicates, so you might find some quartz and amphibole together. Geologically, they are born from that water flux melting process in subduction zones.
Which means the magma is thick and explosive.
Very explosive. This composition is synonymous with the great stratovolcanoes of the Pacific Ring of Fire. The intrusive member is diorite, which is phaneritic. Its extrusive sibling is andesite, aphanitic, named for the Andes Mountains, where this process is still happening today.
And then we get to the low silica, high density, and mafic or basaltic composition.
MEMAF stands for magnesium and ferrum for iron. These rocks are dark in color, dominated by ferromagnesian minerals like pyroxene and calcium-rich plagioclase. Their silica content is lower, around 45 to 50%.
And that low silica means the magma is very low viscosity runny like motor oil, and the resulting rock is dense.
And this composition is so important because mafic rocks make up nearly all of the ocean floor and all the big volcanic shield islands like Hawaii. The most common extrusive igneous rock on Earth is basalt. It's aphanitic, and it forms when that runny lava cools quickly.
And its intrusive equivalent
Is gabbro,
Okay.
phaneritic. It cools slowly deep below the ocean crust. The difference between the continents and the ocean floor is literally just a few percentage points of silica and the density change that comes with it.
And that density difference is what dictates which plate sinks during subduction.
Yep.
It all comes back to felsic floating and mafic sinking.
Absolutely. And then finally, we have the rock type that really defines the deeper Earth, ultramafic composition.
Ultramafic rocks are extremely low in silica and just packed with magnesium and iron. They're composed almost entirely of ferromagnesian silicates, often 90% or more, dominated by that high-temperature mineral, olivine. And they are by far the densest rock type we've discussed.
The main example is peridotite. And while you rarely see it at the surface, peridotite is what we believe based on seismic evidence and mantle xenoliths, makes up most of the Earth's upper mantle.
Which reinforces the whole model. The mantle is hot, dense, and chemically different from the crust, which forces the low-density felsic crust to stay buoyant on top.
Exactly.
Okay, so composition is all about chemistry and density. Now let's turn to the aesthetic and historical side of igneous rocks. Texture. Texture, the size and arrangement of mineral grains, is like the rock's biography. It tells us instantly where and how fast it cooled.
It's a direct historical record. The crystal size is controlled first and foremost by the rate of cooling. That is the dominant factor.
Not the only one.
Not the only one. The percentage of silica, which controls viscosity, and the amount of dissolved gases also play a role. But the simple rule is slow cooling means large crystals because the ions have time to migrate and bond. Fast cooling means small crystals, or even glass, because the ions get locked into place before they can organize.
It's interesting how silica content and cooling are linked. Felsic magma is so viscous, it probably holds onto its heat and cools more slowly than runny mafic magma, even in the same environment.
That's right. High silica means high viscosity, which slows down the movement of ions, making it harder for crystals to grow. But still, the most profound difference in texture comes down to that one question. Did it cool deep below the surface or quickly on top of it?
Let's dive into the 6 key textures, starting with the 2 that separate intrusive from extrusive.
First up is phaneritic texture. That means coarse-grained. This always indicates slow cooling deep beneath the surface, so it's characteristic of intrusive or plutonic rocks.
We're talking cooling rates of thousands to millions of years.
Exactly. This gives ions time to arrange themselves into large, distinct, interlocking crystals that you can easily see with the naked eye. Granite, diorite, and gabbro are all phaneritic.
And the opposite of that is aphanitic texture, which means fine-grained.
Aphanitic texture indicates rapid cooling at or near the Earth's surface, so it's the signature of extrusive or volcanic rocks. The lava solidifies quickly, maybe in days or hours, leaving crystals that are microscopic.
Like rhyolite, basalt, and andesite.
Right, and a key sign of aphanitic texture is often the presence of vesicles, those little holes or voids left when gas bubbles expand and get frozen into the rock as the lava solidifies.
Now, what if we find a rock that has big crystals surrounded by a sea of microscopic crystals? That sounds like a puzzle.
That's solved by porphyritic texture. A porphyritic texture indicates a complex two-stage cooling history. It tells the story of travel.
How so?
The large visible crystals, which we call phenocrysts, they formed first during a period of slow cooling at great depth. Then, the magma was suddenly mobilized, maybe it erupted or was injected into a shallow chamber, and the remaining liquid cooled very quickly.
Forming the fine-grained matrix around the big crystals, the ground mass.
Exactly. It tells a clear story of disruption and rapid ascent.
Okay, the next texture is the extreme end of rapid cooling, glassy texture.
This forms from the very, very rapid cooling of lava. We call it quenching. It's so fast that there is zero time for ions to arrange into an orderly crystal structure. The material freezes into an amorphous solid.
Like obsidian.
Obsidian is the classic example. It's often black and shiny, and it fractures with that distinct conchoidal pattern, just like man-made glass. It tells you that extremely hot lava was exposed to air or water almost instantaneously.
Then we have the violent one, pyroclastic texture.
Pyroclastic means fire fragments. This is a fragmental texture that's produced by explosive eruptions, think Mount St. Helens. The resulting rock is made of cemented fragments of ash, lapilli, and bombs, which we collectively call tephra.
So they almost look like sedimentary rocks.
They often do. Visually, they look like conglomerates, but their origin is entirely igneous. Examples would be tuff, which is cemented ash, and volcanic breccia. This texture tells a story of violence, not slow, quiet flow.
And finally, a texture that's a sign of a really specific chemical environment, pegmatic texture.
Pegmatic describes rocks that are exceptionally coarse-grained. I mean, we're talking about crystals that can be measured in meters. They form in the very late stages of crystallization of granitic magmas, usually in these small, localized pockets within or near a larger batholith.
And what's special about that environment?
Those residual melts become super enriched in volatiles, especially water.
Ah, so the water acts as a hyper-efficient flux again.
Exactly. The high water concentration just dramatically reduces the viscosity of the melt. It becomes incredibly easy for ions to move large distances and arrange themselves into massive crystals very, very quickly. And the resulting rock, a pegmatite, is a geologic curiosity. It's often where you find rare elements and unusually large gemstones.
So we've covered the complexity of melting, the systematic order of crystallization, the chemical categories, and the historical record written in texture. Now we have to connect all this to the massive landscapes we can actually see. What does this all mean for reading the topography of our planet?
It means the fundamental structure of the lithosphere is dictated by these processes. Where you see mountains, you are often looking at felsic, buoyant, slow-cooled magma. Where you see flat ocean floors, you are looking at mafic, dense, rapidly cooled lava. The density, the structure, the resistance to weathering, it's all predetermined by that rock-specific cooling history.
Let's start with a huge example of slow-scale intrusion. Yosemite Valley in California.
Yosemite is just a perfect showcase of an exposed granodiorite batholith. A batholith is the largest type of intrusive igneous body, covering hundreds or even thousands of square kilometers.
And granodiorite is that intermediate to felsic composition.
Right, placing it perfectly on the continental side of the spectrum. The entire body cooled exceptionally slowly over millions of years deep beneath the surface, which is why the massive cliffs and domes like El Capitan and Half Dome are made of this durable, phaneritic rock.
The scale is just staggering. And these bodies are often the product of repeated magma intrusions over tens of millions of years, right? Assimilating tons of country rock as they solidify.
And the resistance of that granite to weathering is why we still have those sheer cliff faces after millions of years of exposure. The forces that exposed it, uplift, and glaciation were powerful, but the granite itself, because of its intrusive origin and felsic strength, it resisted the complete breakdown that a softer sedimentary rock would have suffered.
For something much more dramatic and vertical, let's look at the geological debate around Devil's Tower in Wyoming. This really illustrates the interpretive side of geology.
Devil's Tower is a colossal, isolated intrusion. It's hard to imagine, but the softer sedimentary rock that once surrounded it has completely eroded away over time, leaving this exceptionally resistant igneous core standing all alone.
And it has that columnar jointing.
Yes, which suggests rapid contraction as it cooled, which is typical of certain igneous formations. But the debate, as the sources note, is what type of intrusion is it?
Is it a volcanic neck or something else?
Geologists argue over whether it's the solidified conduit or neck of a long-vanished volcano, or if it's the eroded core of a laccolith. A laccolith is a lens-shaped intrusion that forces the overlying rock layers upward into a dome. But either way, it just illustrates that these massive intrusions are often far more resistant than the rock around them.
That brings up a good distinction. We've talked about vertical intrusions like necks, but they can also be horizontal.
Oh, absolutely. Intrusive bodies come in two main forms relative to the country rock: concordant and discordant. A sill is concordant. It's a sheet-like body that injects itself parallel to the existing rock layers.
In a dike.
A dike is discordant. It's a sheet-like body that cuts across the existing rock layers.
And Shiprock in New Mexico is a really clean illustration of dikes in action.
Shiprock is a classic example. The central spire is generally thought to be the volcanic neck, the main conduit. But radiating outwards from it are those massive jagged walls of rock. Those are the dikes.
So magma filled in these radiating fractures.
It's solidified within fractures that cut right through the surrounding sedimentary strata. And because that igneous dike material is so hard and resistant, it resisted erosion, while the softer sedimentary rock around it washed away completely. And that's why you have these vertical walls standing so dramatically on the plains.
This synthesis is really what this deep dive is all about. By understanding how the cooling rate writes the texture and how silica content dictates the composition, you really gain the ability to read the entire tectonic history of a landscape just by looking at a piece of rock.
You're reading billions of years of transformation, and that transformation relies on one rock type being fundamentally buoyant felsic and the other being fundamentally dense malathic. That difference, established through magma generation and crystallization, is really the definitive code of our planet's geology.
This has been a tremendously comprehensive dive into the Earth's fiery foundations. We've detailed not just the what, but the how and the why of igneous rock formation. Let's quickly summarize the core knowledge we've pulled from the source material.
I think the biggest takeaway is that magma generation isn't just about heat. It's driven by mechanisms that overcome immense pressure. Primarily, you have decompression melting driving mafic generation at mid-ocean ridges.
And the addition of water, the volatiles, driving that intermediate and felsic generation at subduction zones.
Right.
We also established that composition is destiny. The low-density, high-silica felsic rock like granite forms the buoyant continents, while the high-density, low-silica mafic rock like basalt forms the deep ocean floors.
And finally, that texture is history. Phaneritic, coarse-grained, is the result of slow, intrusive cooling, which allows for things like fractional crystallization.
While aphanitic, fine-grained, is the result of rapid, extrusive cooling, often resulting in much more simple, homogeneous rock bodies.
And this entire system relies on the continuous recycling of materials, driven by plate tectonics, and specifically that role of water being injected back into the mantle through subduction.
Indeed, we know that adding water is crucial for generating those silica-rich, lower-density magmas that build and sustain the continents.
It's the continental factory.
It is, and this raises an important question for you to mull over. What if that process, the process of adding water to magma via subduction, what if it suddenly stops globally? Let's say all the subducting plates just seized up. What would be the long-term tectonic consequences? What would happen to the composition of the continents?
That's a great thought experiment. If subduction halts, the continents would still face the relentless forces of erosion, which is always trying to reduce their volume and smooth them out. But without that water flux melting, the primary factory for generating new intermediate and felsic crustal material, the continents would essentially stop growing chemically.
They'd become net losers of material.
Over immense geological timescales, yes. They'd become net losers and potentially less compositionally diverse. It would fundamentally break the cycle responsible for creating buoyant, silica-rich land, leaving only decompression melting of dense mafic material at mid-ocean ridges to drive all global igneous activity. It's a hypothetical that forces you to appreciate just how much of our stable world really depends on the dynamic process of water sinking back into the earth.
A truly provocative thought to end on. Thank you for guiding us through the fiery depths of igneous petrology and giving us the tools to read the cooling history of our world.
It was my pleasure.
We'll catch you next time for The Deep Dive. Welcome back to The Deep Dive. You gave us a formidable stack of reading material geological surveys, mineral dossiers, modern mining reports, all focused on the really unique geology of Michigan's Keweenaw Peninsula.
It's an incredible place, geologically speaking.
Right. So our mission here is to take all that complex information and just give you the ultimate shortcut to being well-informed. We're going to decode the deep time, the immense heat, and, the incredible mineral wealth locked inside that upper thumb of Michigan, jutting out into Lake Superior.
And this is a deep dive that's really defined by extremes. I mean, we are looking at one of the greatest natural geological anomalies on Earth.
It's not just famous for having rocks, then.
No, not at all. The Keweenaw is famous because the forces that shaped it, we're talking millions and millions of years ago, they created conditions that allowed pure metals to precipitate in quantities you find almost nowhere else. The geology here is a story of global significance.
So we're going to cover three massive interconnected themes. First, the incredible volcanic foundations, just tracing the land back to its birth by fire.
Then the treasures themselves.
Exactly. The unique treasures, the native metals, the fluorescent oddities that resulted from that deep past. And finally, the modern economics of it all, the extraction, including the strategic importance of the region today, before we give you like a practical field guide on how to actually identify these things.
And what's fascinating here is precisely how those forces from, a billion years ago directly influence current commodity markets and mining economics.
It's a straight line from the ancient past to today's economy.
It is. To understand why the United States relies on a specific county in Michigan for a critical element like nickel, you have to appreciate the scale, the physics of ancient basaltic lava flows. The geology isn't just history for a lecture, it is the fundamental structure defining modern resource wealth.
Let's jump straight into that deep past then. Lay the groundwork.
Let's do it.
Our journey starts in the Precambrian era, about, 1.1 billion years ago, a time of continental upheaval that birthed the Mid-Continent Rift System, the MCR.
Yeah, and this was not the gentle landscape we see today. This was a landscape defined by massive, slow, continuous eruptions on an almost oceanic scale.
So to visualize this, you need to think of a monumental geological event.
A huge event. The Mid-Continent Rift was this 2,000-mile-long crack in the Earth's crust. It was essentially a failed continental breakup, stretching all the way from Kansas up through the Great Lakes.
A failed breakup.
Right. For millions of years, the crust stretched, it weakened, and it just poured out these immense volumes of molten rock.
Okay, so let's unpack this. When you look at a simplified geologic map of the Keweenaw Peninsula today, The main feature, the thing that defines its shape and structure, is this vast series of bands. They're usually colored green or blue on the maps.
And those bands are the ancient lava flows?
Exactly. They're tilted, folded, incredibly deep. We are literally looking at solidified history, the cooled and weathered remnants of volcanic activity that happened over just immense spans of time.
The scale is almost impossible to grasp. I mean, we aren't talking about a single volcano.
Yeah.
You have to imagine hundreds, maybe thousands of eruptions along these long cracks, these fissures, just building up successive layers that are thousands of feet thick in total.
And those flows define the whole peninsula.
They define the entire structure. And critically, this ancient volcanic structure, this colossal pile of basalt, is the foundational ingredient. It is the porous matrix, the sponge, where all the unique mineralization, especially that native copper, later happened.
So if the MCR hadn't failed to rip the continent apart, if it had actually created an ocean basin,
We wouldn't have the copper.
wow. The fact that the magma stopped flowing and the rocks cooled and settled in this specific way is the entire reason we're having this conversation.
And the specific type of lava is crucial too. It's basalt.
Right. Basaltic lava flows are known for their extreme fluidity. That ties directly to their low silica content, right?
It does. We need a solid analogy here to make that fluidity stick.
Okay, so if you compare, say, a thick, chunky rhyolitic lava to something like toothpaste being squeezed from a tube.
Then basaltic lava is much closer to maple syrup. Or even hot water flowing across a pan. It's incredibly runny.
And that low viscosity, that's what allows it to travel for incredible distances. We're talking dozens of miles maybe before it cools and solidifies.
Precisely. And that fluidity is why the layers are so, geologically speaking, thin and spread out so broadly across the whole region. It creates that layered kind of pancake stack appearance in the deep structure of the Kuina.
And when geologists look at a cross-section of this rock, they see the result of successive pulses. It's not just one uniform mass.
No, you see hundreds of distinct flows stacked one on top of the other. The top of an earlier flow might be highly weathered or porous, and then the next flow comes in and lays this dense, impermeable capstone right on top of it.
And that layering, that's what matters to the treasure hunters.
That's everything. Each layer is a distinct pulse of volcanic activity,
Okay.
and the spaces and the cooling interfaces, the gaps between the flows, they are absolutely crucial. As one flow cools, it provides an insulating layer for the next one, which affects crystallization rates. But more importantly, it creates these permeable zones, and these zones act like conduits, like sponges.
So they let things flow through them.
They let hydrothermal fluids, hot mineral-rich waters, circulate through the porous rock and eventually deposit the valuable metals and gems we prize today.
So the scale of the eruption is important, but the cooling physics between the flows is arguably what made the copper mines even possible.
It's the whole ballgame.
Okay, now we get down to the micro level, the textures. These are essentially fossilized evidence of that cooling process. And we have two key terms here that are vital to understanding how the treasures were made: vesicular and amygdaloidal.
Vesicular lava is the starting point. Think of a freshly poured beer or a soda,
The bubbles.
the bubbles. When lava erupts, it holds a massive amount of dissolved volcanic gases, water vapor, carbon dioxide, sulfur compounds, all dissolved under immense pressure deep within the earth. As the lava rises and that pressure drops, these gases escape and form bubbles. When the lava solidifies, those preserved gas bubbles are called vesicles. If you find vesicular basalt, you are holding a diagnostic indicator of that gas-rich eruption phase.
So those vesicles, those gas pockets, they're the empty spaces that allow the mineralization to begin. But they're just holes until something fills them.
Right.
And that's where the term amygdaloidal comes in, and that's the real gold standard for mineral collectors.
Precisely. Amygdaloidal lava features those vesicles that have been filled or partially filled with secondary minerals. And this process gives us crucial insight into the post-eruption mineralization processes that took, millions and millions of years.
So let's just dwell on the mechanism of filling for a moment, because it's not like paint filling a crack. We're talking about chemistry and deep time.
We absolutely are. So after the massive heat of the lava flow subsides, these hydrothermal fluids begin to circulate through the fractured, permeable rock structure.
The hot water we mentioned.
Exactly. These fluids are hot, often over 300 degrees Celsius, and they are laden with dissolved metals and silica. Now, where does the water come from? Some of it is magmatic, from the cooling magma itself. Some is meteoric, ancient rainwater, and some is connate water that was just trapped in sedimentary layers below.
So a mix of sources.
A mix. And these superheated fluids, they pick up trace amounts of copper and other elements from the surrounding basalt rock and just carry them along.
Like a solvent.
Like a solvent. And when these fluids encounter the empty vesicles, these little low-pressure cavities, and they experience a change in temperature or the chemical environment, the dissolved minerals are forced out of solution. They precipitate layer by layer, crystallizing inside the bubble.
And that's how you get the good stuff.
That is the process that creates agates, copper, dactylite, and the state gemstone, greenstone. The amygdaloidal texture isn't just a physical feature, it's a tiny chemical laboratory that operated for millions of years.
It's still a huge mental leap, though, to visualize a landscape-shaping event that happened a billion years ago. But geologists have an incredibly powerful tool for this.
They do, an active, real-time laboratory.
Modern basaltic volcanism, specifically in Iceland.
Yes, if we connect this to the bigger picture, the study of active lava flows and fissure eruptions in Iceland serves as the perfect, most direct modern comparison to the ancient geology we see in the Kuna.
So Iceland is kind of replaying the events of the Mid-Continent Rift.
It's replicating the process right now, yeah. Albeit on a smaller scale and in a different tectonic setting, but the physics are the same.
So why is that comparison so useful for understanding Michigan?
Because it allows us to reverse engineer the timeline, the events that form the Kuina. Iceland is the closest active analog for basaltic shield volcanism and fissure eruptions, where lava flows out of long cracks rather than a single cone.
Just like the MCR.
Just like the MCR. By studying the flows in Iceland, we can observe key characteristics in real time. We can measure the extremely low viscosity and the high flow rates of the salt. We can watch how the surface crust forms. We can see how the gases escape to form those vesicles in the cooling top layer.
And you can see how they stack up.
And crucially, we can watch how subsequent flows stack up and interact with the previously cooled rock underneath. It helps geologists confirm their models of those ancient processes.
So we can infer things like the original temperature, the volume of the ancient flows, just by looking at what's happening in Iceland today.
Exactly. It brings a billion years of history into a clear scientific focus just by looking at a modern eruption site that is accessible today.
It gives us tremendous confidence that the interpretation of the Keweenaw as a failed rift full of layered, porous basalt is accurate, which is the necessary precursor for the next great section, the treasures themselves.
Yes, the good stuff.
Okay, so we've established the matrix. Immense, porous, layered basalt flows permeated by super hot, mineral-rich hydrothermal fluids. This sets the stage for the Keweenaw's greatest claim to fame, its mineral exclusivity.
And we have to start with the big one. The Keweenaw Peninsula is globally renowned for its native copper deposits. This fact just cannot be overstated. It is unique in its sheer abundance compared to almost every other location worldwide.
And the key word there is native. What makes it native is the critical point. The copper, the Q, is found in its elemental metallic form. It's pure and uncombined.
Right. Most of the world's copper is found locked up in chemical compounds, usually with sulfur and sulfide ores, or sometimes with oxygen as an oxide. It requires tremendous industrial energy smelting, refining to chemically strip the pure metal out of the rock.
But here, the copper it's already metal. How did that chemical miracle happen?
It's a complex chemical dance. It involves what we call reducing conditions. So those circulating hydrothermal fluids carrying dissolved copper from the basalt eventually encountered reducing agents like iron oxides or organic material within those permeable layers.
Okay.
This interaction caused the copper ions in the solution to chemically reduce back into pure metallic copper, which then precipitated out of the water and filled the vesicles, the fractures, the pore spaces. It's a natural process of electrochemistry operating on a massive scale for millions of years.
And the result is you find copper in massive sheets, filling veins, or these huge dendritic masses inside the amygdaloidal flow tops. This isn't microscopic dust.
This is solid metal.
So this leads us to the first practical field test for you, the listener.
Oh.
How do you, standing on the shore, know that shiny red metal is indeed native copper?
Well, we can connect the knowledge right here. Because it is a pure metal, it displays the properties of a metal. Its hardness is low, about a 2.5 to 3 on the Mohs scale. It has a bright metallic luster, a copper red streak.
But the two most crucial diagnostics are physical.
They are. First, it is malleable. If you take a hammer to it, it will flatten, it won't shatter like quartz or glass would. That's the definition of a metal.
And in the second one.
It has a Hackley fracture, When you break it or cut it, the edges are jagged and rough, typical of tough, non-brittle materials. So if you find a rock fragment that you can actually dent with a knife, that is almost certainly native copper.
That makes it instantly identifiable.
And copper wasn't the only element to pull this trick.
No. Alongside the copper, we also find native silver, Ag, in significant quantities. Often it's physically intergrown with the copper in what the old miners called half-breed specimens.
And silver is also malleable.
Highly malleable, yes. Low hardness, just like copper. And another famous mineral found here is datelite, a beautiful borosilicate mineral that often forms these colorful nodules in the flow tops, sometimes even cementing together chunks of copper. We mentioned earlier that the agates are essentially the contents of those filled bubbles, linking them directly to that amygdaloidal process. Lake Superior agates are one of the most sought-after collector items in the entire Great Lakes region.
They are, and that's because their formation perfectly illustrates that long-term precipitation process. These agates are a type of chalcedony, which is a cryptocrystalline, or it's extremely fine-grained form of quartz, silica.
Okay.
They form when the silica-rich hydrothermal fluids we talked about are deposited very slowly and rhythmically within that empty vesicle cavity.
Rhythmic deposition, that's key, isn't it?
Yeah.
Because that's what creates the iconic banding.
Exactly. Imagine a tiny natural cistern filling up over geological epochs. Slight changes in the chemistry of the circulating fluids, maybe a temporary spike in iron content or a change in temperature, cause the silica to precipitate at slightly different rates or with different impurities.
And the iron gives it the color.
The iron oxides give them their signature warm colors, the red, orange, and brown bands. These successive layers of deposition, often starting from the outside and working their way in, result in the concentric rings or bands that make the Lake Superior agate so prized.
So every time a collector finds a beautiful banded agate, they aren't just holding a pretty rock.
Not at all. They are holding a tiny, perfect record of the temperature, pressure, and chemical conditions inside a cooling lava flow chamber a billion years ago. It's nature's own timeline, solidified and then polished by the lake.
Michigan is unique in having two official stones, and their difference really encapsulates the diverse geology of the state and, the exclusivity of the Keweenaw.
It really does.
So let's focus first on the state gemstone, which is truly exclusive. Greenstone.
Greenstone or chlorastrolite is not just any green rock. It is a highly specific, very rare variety of the mineral pompelliite. Its chemistry is complex. The formula is this daunting thing. Take a cis AROPLA, Al2, SiO7, OH2 pot H2O.
Okay, but the important takeaway.
The important takeaway is that this specific chemical fingerprint requires a very precise set of low-grade metamorphic conditions, the exact temperature and pressure during that secondary mineralization phase.
And the critical geological fact here is location.
It is found exclusively in the amygdaloidal flowtocs of the Keweenaw Peninsula and Isle Royale National Park. Nowhere else. It is the signature gem of the mid-continent rift volcanism.
And it have that turtleback pattern.
It has a radiating fine fibrous structure and often displays a distinct turtleback pattern when you polish it. It's a regional marker that speaks to a very specific, unique moment in geological time.
Now contrast that specific localized gemstone with the state stone, the famous Petoskey stone. It's a classic example of how different the state's geology is from one part to another.
A world away, geologically. The Petoskey stone is fascinating, but it's made of fossilized colonial coral polyps, specifically Hexagonaria precarnata.
So it's a fossil.
It's a fossil. Its formation involves sedimentary and biological processes dating back to the Devonian period about 400 million years ago. That's a completely different geological era than the billion-year-old Precambrian volcanism up north.
And crucially, you find it in Lower Michigan.
Right, primarily in Lower Michigan, not the Keweenaw. And this geographical contrast is powerful. While the Keweenaw is defined by massive volcanic fire and crystalline precipitation, Lower Michigan's geology is defined by warm, ancient seas and biological activity. It just reminds you that Michigan's geological story spans eons and includes everything from ancient lava flows to tropical coral reefs.
Okay, but this is where it gets really interesting. We move from stones defined by deep ancient history to stones that you need a special light just to find, and they shouldn't even be native to the area.
We're talking about euperlites.
We are. Discovered relatively recently.
Euperlites are scientifically identified as syenite rocks that contain small veins or disseminations of the mineral sodalite. In normalite, they are dull gray, completely unremarkable.
But the magic happens under UV light.
Because sodalite has a very specific crystalline structure that allows it to fluoresce intensely. typically a vibrant orange or yellow when you expose it to long-wave ultraviolet light. And this has turned nighttime rock hunting into this phenomenal glowing activity along Lake Superior.
But the scientific puzzle is their location. The source material is very clear that euperlites, although you find them on the shoreline, are not native to the surrounding basaltic bedrock of the Keweenaw.
That's the key. The surrounding rock is basalt. Euperlites are syenite, different rock types entirely.
So if those rocks originated hundreds of miles away, why aren't they just ground down to sand after traveling that far? How do we still find these intact glowing beacons just sitting on the beach?
And that's the challenge. It indicates a process of massive geological transport, specifically glacial action.
The Ice Age.
Right. You have to visualize the Laurentide ice sheet, the immense glacier that covered North America. That glacier acted like a massive, slow-moving geological bulldozer. It scraped the surface bedrock from vast areas far to the north, primarily in the Canadian Shield, and it carried those scraped fragments, we call them glacial erratics, southward.
So it's a Canadian rock.
It's Canadian rock. Syenite bedrock containing sodalite exists hundreds of miles north of Lake Superior. The glacier scooped up chunks of that bedrock, transported them, and eventually just dropped them along the Superior shoreline as the ice retreated.
And the fact that they're still intact.
Is a testament to the fact that they were often carried deep within or even under the ice, protected from surface weathering, and then they were deposited relatively recently, geologically speaking, as the ice melted. It adds this fascinating layer to the Keweenaw story. A rock that traveled for centuries to reach a shoreline created by a billion-year-old volcano.
It perfectly illustrates how two completely different geological forces, volcanism and glaciation, contribute to the unique collection of materials you find side by side on one small beach.
An amazing confluence of events.
Okay, so we've established that the ancient past yielded this immense wealth in native copper, leading to the great copper rushes of the 19th and early 20th centuries. But the Keweenaw's deep-time geology is still paying dividends in a very different way today.
It is. We need to turn our attention south a bit to Marquette County and the modern economic powerhouse that is the Eagle Mine.
And the Eagle Mine represents a singular point of interest on the national resource map. Its existence highlights the ongoing strategic importance of Michigan's resources.
It absolutely does. It is currently the only operational nickel mine in the entire United States.
Wait, the only one?
The only one. That fact alone underscores the mine's critical status for U.S. technology, defense, and manufacturing supply chains.
And nickel isn't some historical relic. It's essential for modern life. We're talking stainless steel, aerospace alloys, and most critically, high-performance lithium-ion batteries.
The EV batteries.
Exactly. Electric vehicles, large-scale energy storage. Relying on foreign sources for these key battery metals is a significant national vulnerability.
It is. And that makes Eagle Mine a strategic asset. Now, let's contrast the geology here with the native copper we just spent so much time on.
Right. Different process.
Completely different. The native copper was created by hot water circulating through old lava flows through basalt. The Eagle Mine nickel deposit, however, is a massive sulfide deposit.
Okay, so what's the host rock?
The host rock for the deposit is peridotite. It's a dense, coarse-grained, igneous rock that is ultramafic, which just means it's incredibly rich in iron and magnesium.
I see.
This peridotite was part of a relatively young, still Keweenawan era, but a later intrusion magma body that solidified deep underground. And as this molten, metal-rich magma intruded, the heavy nickel and copper sulfide liquids separated from the silicate magma and pooled. It's like oil and water separating.
And that concentrated the valuable stuff.
It concentrated it into these extremely valuable ore bodies.
So we're not looking for pure metal in a crack here. We're looking for metal that's chemically bonded with sulfur inside a dense, dark, igneous rock. What kind of grades are they getting from this deposit?
The grades are world-class, which is why the mine is economically viable. The material they extract contains nickel at an impressive 3.57%, copper at 2.91%, and trace amounts of precious metals, specifically gold and platinum.
And that 3.57% nickel, that's high.
That is very high. To put it into perspective, the global average for sulfide nickel deposits often hovers closer to 1.5% or maybe 2%. This high concentration drastically reduces the cost and the energy required to process the ore. It just highlights the exceptional quality of this ancient geological concentration.
So let's talk numbers. The sheer volume projected for this mine really underlines its importance to domestic supply.
The expected yield is truly substantial. Projections include 440 million pounds of nickel and 429 million pounds of copper over the life of the mine.
And that volume is critical for reducing our reliance on global, often volatile commodity markets.
It is. To extract those millions of pounds of metal, you need to target the specific minerals that contain them. And this is where the mineral dossier becomes practical again. We need to know what those primary ore minerals look like.
Okay, so what are they?
The two primary ore minerals are pentlandite and chalcopyrite. Pentlandite, with the formula Ni6Fa3S8-, is the dominant source of that high-grade nickel. It typically has a bronze-yellow color, and diagnostically it's magnetic after you heat it, though less commonly in its natural state.
And it's not malleable like the native copper.
Not at all. It's a brittle, fractured sulfide, not a metal.
And what about the copper here? Where's that locked up?
The copper is locked up in chalcopyrite, que faz $2. Now, chalcopyrite is often called fool's gold because it has a yellowish color and a metallic luster.
But it's softer than real pyrite.
Much softer, yes. Hardness of 3.5 to 4 versus 6 to 6.5 for pyrite, and it's usually distinguished by its greenish-black streak.
And being a sulfide means you have to smelt it.
Critically, yes. It's a sulfide, so the processing requires complex smelting to burn off the sulfur and extract the copper metal, a far cry from simply chipping native copper out of a rock fracture.
This difference in mineralization sulfides in the Eagle Mine versus native metal up in the Keweenaw Belt is a perfect modern demonstration of the diversity of the mid-continent rift system.
It shows its wealth goes far beyond that 19th century copper rush. It's a perfect modern example of how ancient geology dictates current industry.
Okay, we've covered the history, the major formations, the economics. Now let's tie it all together with a practical application. When you are looking at these rocks, how do you make a confident identification?
This is the fun part. We've already introduced several diagnostic traits, malleability, streak color, but now we're going to cover the remaining key field features for the most common minerals from your sources.
So this isn't just a list. This is the crash course in mineral ID that lets you stop seeing rocks and start seeing crystalline structures, cleavage planes, chemical reactions. We're turning the theory into a practical toolkit.
Exactly. Let's start with the most abundant group on Earth, the silicates, focusing on features that are immediately obvious in the field.
And we'll start with the softest, talc.
Talc. Formula Mg33Si40H22. This mineral has the lowest hardness of the entire group of 1 on the Mohs scale. You can scratch it easily with your fingernail.
And the telltale sign.
It's easily identified by its unique soapy feel. It feels almost greasy to the touch, which is highly diagnostic.
Okay, and the dark sheet-forming mineral, chlorite.
Chlorite. It's often confused with dark micas, but its defining traits are its pervasive green color and its mica-like perfect cleavage. It splits into thin sheets. If it flakes off easily and is distinctly green, that's chlorite, a common low-grade metamorphic mineral you find in altered basalts.
Now we have to address the most common rock-forming minerals. The feldspars. Orthoclase versus plagioclase. Both have two cleavages near 90 degrees, which makes them tricky.
It can be tricky, but color is a huge initial clue for orthoclase. It's commonly a pink or salmon color.
Okay.
Plagioclase is generally white or gray, and it requires a closer look. If you look very closely at its two cleavage faces, you'll see these fine parallel lines. We call them striations.
Like tiny little grooves.
Exactly. They're extremely thin lines resulting from its internal twinning structure, and they are the definitive characteristic that differentiates it from orthoclase in the field.
Okay, we also need to differentiate the two common dark, blocky minerals in igneous rock. Amphibole, which is usually a hornblende, and pyroxene, which is usually augite. They look very similar, dark and dense.
This is where geology demands precision. The primary difference is the angle at which their internal cleavages meet.
The angles.
The angles. Amphibole has two cleavages that meet at wide angles, specifically 56 and 124 degrees. So if you break it, you see a diamond shape in the cross-section.
And pyroxene.
Pyroxene, like augite, has two cleavages that meet at approximately 90 degrees. This results in a more square or rectangular cross-section. It's a subtle difference, but it's critical for identifying the overall type of host rock in the field.
And finally, the two colorful silicates, olivine and garnet.
Olivine is often instantly recognizable because of its highly diagnostic olive green color and its tendency to form in a granular fashion within the rock matrix.
And garnet is all about the shape.
Exactly. Garnet is known for its high hardness, 6.5 to 7.5, and it's most frequently identified not by color, which can vary wildly, but by its crystal shape. It often forms highly distinctive 12-sided dodecahedral crystals. They look like small, perfect spheres or faceted balls embedded in the rock.
Okay, let's move on to the diagnostic oxides and sulfides. We've covered some key ones, but let's review those simple field tricks. Streak and weight.
We talked about hematite, the iron oxide, diagnosed by its red to red-brown streak, no matter if the specimen is metallic gray or earthy red. Its relative, goethite, has a distinctly yellow-brown streak. You always have to rely on the streak test for these iron minerals.
And for the sulfides, galena and sphalerite provide the most memorable sensory diagnostics.
Galena, the lead ore, it has a low hardness, 2.5, and a lead-gray streak, but you'll pick it up and notice instantly. It is very heavy.
Right, because of the lead. You pick it up and you just know.
You just know. And it also displays perfect cubic cleavage. It breaks into perfect little squares or cubes.
And sphalerite.
Sphalerite is the source of zinc, and while its cleavage is complex, the simplest diagnostic is its smell. When you rub the streak plate, the streak actually smells like sulfur, a clear sign you're dealing with a sulfide mineral.
And let's not forget bornite.
Peacock ore. Bornite is a copper iron sulfide. If it's fresh, it looks dull bronze, but it almost always displays that highly diagnostic iridescent tarnish. It shifts to these vibrant purple and blue colors on the surface. That peacock flash is unmistakable.
Okay, now we get into the realm of simple chemistry. Tests that require nothing more than a few basic tools or even just your tongue. So what does this all mean? It means we have the keys to identify these treasures just by applying simple physical and chemical principles. Let's start with the famous fizz test.
That belongs to calcite. Casso, $1335. It's the most common carbonate mineral, and its distinguishing trait is its cleavage. It is rhombohedral. It breaks in 3 directions, but not at 90 degrees. It forms a skewed parallelogram shape.
And the critical test.
The critical chemical test is that it reacts with HCl, it fizzes because it's a carbonate. A drop of even weak acid will cause immediate effervescence.
Bubbles.
Contrast that with halio. Halite, or nalar talai, is just simple table salt. It shares the same cubic cleavage 3 directions at 90 degrees as galena, but the diagnostic test is unique. It has a distinct salty taste.
And fluorite.
Fluorite, KF22, has a moderate hardness of 4. While it often forms distinct cubic crystals and has variable color purple and green are common, its most useful cleavage characteristic is octahedral cleavage.
So it breaks into pyramids.
It breaks along 4 directions, which you can see as small 8-sided pyramidal faces on fractured samples. That 8-sided breakage pattern is a dead giveaway for fluorite.
What a wealth of information. We've moved from the scale of the mid-continent rift all the way down to the scale of crystal cleavage angles. That's the true definition of a deep dive.
It really is.
So we have completed a comprehensive deep dive into the Keweenaw Peninsula. We started with the immense scale of the ancient basaltic flows of the mid-continent rift. The evidence is still there in the deep layering and the microscopic vesicles from 1 billion years ago.
And that history created the unique abundance of native copper, silver, and the formation of those stunning Lake Superior agates.
And we transitioned through the fascinating mystery of the fluorescent, glacially transported euperlites. We brought the story right into the present day by detailing the critical importance of the Eagle Mine, the only source of domestic nickel, extracting valuable sulfides like pentlandite and chalcopyrite from that ultramafic peridotite host rock.
And finally, we gave you the specific diagnostic tools to differentiate these minerals, from the malleable properties of pure metals to the precise cleavage angles of silicates and the critical streak colors of iron oxides. It's a region just defined by its geological exclusivity.
Which leads directly back to where we started, in Deep Town.
Oh, it does. We learned that greenstone, the Michigan State gemstone, that highly specific variety of pumpleite, is found exclusively in the Keweenaw and Isle Royale National Park. We know these minerals formed only when those hot fluids circulated through the ancient basalt. So, if we use the active, ongoing basalt flows in Iceland as our modern guide for these volcanic processes, it raises a key, final, provocative question for you to consider.
What's that?
Does the unique chemical composition and structure of the pumpelleite that formed the greenstone reflect a specific, unrepeatable moment in geological time, a precise, perfect combination of temperature, pressure, and mineral cocktail that the continuing flows in Iceland or anywhere else on Earth haven't yet replicated?
So, is that small greenstone truly a singular geological fingerprint, unique in the history of the entire planet?
That's the question.
Something profound to mull over the next time you look at a seemingly simple green rock. Thank you for joining us on this deep dive. Welcome back to the Deep Dive, the place where we take stacks of technical sources, geological reports, economic analyses, mining surveys, and really distill them into the essential knowledge you need to be truly well-informed.
Today, we are undertaking a deep dive into the very bedrock of our civilization. We're talking about metallic ores.
Right.
These are the concentrated mineral deposits that form the foundation, well, literally everything we use, from the gigahertz speeds in your processor to the stability of the skyscraper outside your window.
That's right. Our sources cover the incredible science and, the staggering economics of these materials. And our mission today is to move well beyond just listing the metals we use. We want to understand the geological magic. I mean, the four incredible processes that concentrate elements from just trace amounts scattered in the crust into these rich deposits that are worth billions.
And that idea worth billions, that is the absolute starting point. Because what we'll be exploring are not just, random concentrations of rock. We're talking about geological material that is economically viable to extract. The planet is full of iron, but we only target a tiny fraction of it.
Exactly. We need to understand the fundamental accounting problem that geology poses. What transforms a common mineral into an ore? What are the three critical criteria that have to align for us to, justify pulling mountains apart?
It's a foundational goal in a resource management, and it's constantly shifting. So, okay, let's unpack this.
Okay.
Let's start with the precise, non-negotiable definition. An ore is a concentration of an element found within a mineral that can be, and this is the key phrase, economically extracted.
Economic.
Yes. If the cost to mine it, transport it, and refine the material exceeds the market price of the final metal, it just ceases to be an ore. It doesn't matter how much metal is actually present.
Yeah. So the idea of an ore is inherently dynamic then. Theoretically, a mountain of extremely low-grade copper could become a billion-dollar ore body overnight if the price of copper just spikes on the global market. Or if we invent cheaper processing tech.
Precisely.
Yeah.
That's the tension that makes this whole industry so fascinating. The viability of a deposit is dictated by geology, but its status as an ore, well, that's dictated by economics.
Okay.
And to quantify that relationship, we rely on three critical criteria, and all three have to be met at the same time for a deposit to justify the massive capital investment required for a modern mining operation.
Okay, lay them out for us. Let's start with the physical measure.
First, you have to have sufficient quantity. This is the tonnage, the sheer mass of the mineral present in the deposit. Volume matters immensely because mining is an economy of scale.
Right.
You need massive reserves to justify building roads, processing mills, tailings ponds, power connections, and buying all of that gargantuan specialized equipment.
So a small, incredibly rich vein of gold might be attractive to, say, a small-time prospector, but it wouldn't be classified as a major ore body for a global corporation.
Exactly.
Just because it lacks the volume to support a 30-year operational life.
Correct. You need that volume to amortize that initial setup cost. You're going to spend $1 billion building the infrastructure. You need to know you have the quantity to recover that investment plus profit over decades.
That makes perfect sense. Volume first. What's the second critical piece that balances this?
That would be sufficient quality.
Right.
This is defined as the concentration, the percentage of the desired element within the geological material. Miners often just call this the grade.
The grade.
The grade. So if you're dealing with a high-tier deposit, say 5% copper, that means for every 100 tons of rock you blast and haul, 5 tons are copper.
Sure.
But if you're dealing with a low-grade deposit, maybe 0.5%, you have to move 10 times the amount of rock for the same yield.
Right, and the quality is then directly linked to the processing cost. The lower the grade, the more crushing, grinding, flotation, smelting, refining you have to do, all of which consumes just staggering amounts of energy.
Exactly. And that trade-off between quantity and quality is constant, which brings us to the third and I'd say most critical criterion, sufficient value.
The bottom line.
This is the ultimate economic viability measure. It's often assessed in terms of dollars per unit of the recovered metal, minus all of the extraction and processing costs.
So this is where the first two really come together.
It is. You might have immense quantity, our criteria 1, but extremely low quality, criteria 2. We'll talk about some massive low-grade deposits later. But if the overall sheer volume of recoverable metal, even at a high processing expense, ensures a substantial profit margin based on current market prices, then criteria 3 is met.
And it's an ore.
And it is deemed an ore.
So if the price of gold doubles tomorrow, a deposit that was previously considered uneconomic because of its low grade, it instantly becomes a profitable ore body. The geology didn't change at all, but the accounting did.
The cutoff grade dropped. That's exactly it. That's why resource companies constantly monitor market fluctuations and technological advances. The definition of an ore is a moving target, eternally pinned between geological reality and market desire.
Wow.
And understanding the dynamic balance is just crucial because these metallic ores are the absolutely essential backbone of our modern economy. They provide the materials for steel, electronics, global infrastructure, everything.
Okay, with that foundation set, quantity, quality, and value, let's look at the specific players on the periodic table that dominate this market. I think we should start with the heaviest hitter of all.
Sounds good.
We're moving from the abstract principles of economics to the tangible materials that form our world. For you, the listener, think about the tools you rely on, the structures you inhabit, the complex machinery of global commerce. Here's where it gets really interesting. Let's start with the undisputed structural champion, iron.
Iron, Fe, it is absolutely foundational. Its consumption just dwarfs every other metal combined. It's the primary ingredient in steel. That's an alloy created by adding carbon and other elements, which gives us the strength and stiffness needed for massive infrastructure projects, cargo ships, automobiles, and, the rebar in every modern building.
Our sources note that iron is the most used metal globally by weight, accounting for 95% of all metal used. That statistic is just staggering.
It really is.
What are the key ores we rely on for this immense demand?
We primarily extract iron from iron oxides. The key players are hematite, which is Fe2O3, and magnetite, F3O4. Hematite is generally preferred because it contains a higher percentage of iron by weight and requires a little less intensive processing.
But magnetite has that magnetic property, which must help.
It does. Magnetite is great because it's naturally magnetic, which really aids in processing. You can use giant magnets to separate it.
And then there's taconite, which plays a massive role, particularly in North America, but it's a lower grade material. How does that still meet the sufficient quality criterion?
Taconite is a perfect example of sheer quantity overcoming low quality. It's a very hard, fine-grained rock made of chert, iron oxides, and silicates. It often contains only, say, 20 to 30% iron.
So much lower than hematite.
Much lower. To make it economically viable, it requires an additional, very energy-intensive process before it even goes to the smelter.
Okay, so what does that pre-processing entail? What do you have to do to it?
First, the taconite rock has to be ground into an extremely fine powder. I mean, we're talking almost the consistency of flour.
Wow.
And that's to separate the tiny iron particles from the silicate waste material. Once you've separated it, the iron concentrate is then mixed with a binder and rolled into these small marble-sized spheres. We call them taconite pellets.
I've seen pictures of those. They look like little gray marbles.
That's them. Those pellets are then fired at a high heat to harden them, which makes them suitable for shipment and use in blast furnaces. This extra step is costly, but the immense quantity of taconite deposits available, particularly around the Great Lakes region, ensures that the overall value calculation still makes it an ore.
Okay, so we've established iron is the structural backbone of the world.
Yeah.
But if iron is the weight, then aluminum is the metal that lets us defy it. Let's move to aluminum, Al.
Yes. Aluminum is defined by its lightness. It's roughly 1/3 the weight of steel, and its remarkable corrosion resistance. That's due to a thin, tough layer of aluminum oxide that naturally forms on its surface.
Which makes it vital for packaging, like cans and transportation.
Absolutely. If you're looking at aerospace or modern electric vehicles, lightweight aluminum construction is critical for efficiency and range.
But the processing of aluminum from its raw ore, bauxite, is infamous for its environmental and energetic cost. How much the final cost of a sheet of aluminum is literally just the electricity bill?
A substantial portion, I mean, this is perhaps the best illustration of a high-value metal being bottlenecked by an extremely energy-intensive process. Bauxite is plentiful, but it's an oxide, Al2O3. To strip that oxygen and create elemental aluminum, we have to use the Hall-Héroult process, which is purely electrochemical.
Can you walk us through why this process is such an energy hog?
Absolutely. So aluminum oxide, or alumina, has a melting point of over 2,000 degrees Celsius. That's just far too high to work with efficiently.
Right.
The brilliant breakthrough of the Hall-Héroult process was dissolving the alumina in a molten salt bath, specifically cryolite, which lowers the operating temperature to about 950 degrees Celsius.
Okay, so the energy first goes into just keeping the cryolite molten.
Exactly. And then the truly massive energy consumption begins. Large carbon blocks, we call them anodes, are immersed in this molten bath. A massive electrical current is passed through the system.
And that's what does the work.
That current tears the aluminum from the oxygen. The elemental aluminum, being denser, sinks to the bottom, and the oxygen reacts with the carbon anodes, releasing carbon dioxide. This process consumes an enormous amount of continuous electrical power.
How much are we talking?
We're talking about 15 megawatt hours of electricity per ton of aluminum produced.
That is why aluminum smelters are nearly always located right next to huge sources of cheap, consistent electricity, like massive hydroelectric dams. The location of the power source essentially dictates where the ore becomes metal.
That's absolutely correct. The logistical challenge is often easier to solve than the energy challenge.
Okay, let's pivot to the essential metal for modern power distribution, copper.
Copper is the quintessential conductor. It's second only to silver in electrical conductivity, but it's far cheaper and more abundant. It's also ductile, meaning we can draw it into incredibly thin, durable wires, and highly resistant to corrosion in water.
Which makes it perfect for plumbing.
Perfect for plumbing. It's indispensable for electrical wiring, motors, generators, the entirety of the electrical grid, and all modern electronics.
And the sources detail 4 key ways we find copper. What's the geological spread here?
Well, most of the copper mined today comes from sulfide ores, specifically chalcopyrite, QFES2, bornite, Q5FS4, and chalcocite Cu2S. These are complex compounds that require flotation and smelting to separate the copper from the iron and the sulfur.
And that high sulfur content in those ores is often why copper mining is associated with significant environmental issues, like acid mine drainage, if it's not carefully managed.
Precisely. The sulfur content of sulfide ores is a massive challenge in processing and waste management. But historically, we also found incredible deposits of native copper, elemental copper, in its pure metallic state.
And the sources highlight the Keweenaw Peninsula in Michigan as the classic case study for that.
The classic case. In the 19th and early 20th centuries, the Keweenaw region became the world's most prolific copper source because the copper was found pure. It wasn't locked in sulfides.
Which simplified the process immensely.
Immensely. Miners just had to crush the rock and separate the metal rather than dealing with complex smelting. This fueled massive booms and literally established the American copper industry. It's a great example of geology offering a temporary shortcut around complex chemistry.
Okay, now to silver, ag. We know it's conductive, but how critical is it today beyond just its role in investment?
Silver actually holds the title for the highest electrical and thermal conductivity of any known metal.
The highest of any metal.
The highest. So while we use it for jewelry, its technical applications are vast. Due to its superior conductivity, it's used in critical electrical contacts in switches and circuit breakers. And crucially, silver paste is essential in manufacturing photovoltaic cells' solar panels.
So it's a key element in the renewable energy transition.
The T element.
And its occurrence is often tied to other elements, which makes it a valuable bonus in mining.
Correct. It can be found natively or in argentite Ag2S, but the key economic nugget here is that silver is often recovered as a byproduct of much larger lead, zinc, and copper mining operations. A company might be mining a low-grade copper deposit that's only marginally profitable, but the trace amounts of silver and gold recovered alongside it can transform the entire project into a lucrative venture. It can push that value criterion right into the green.
That's wild. The economics of one metal often ride on the coattails of another. And speaking of value, let's turn to gold.
Gold possesses a remarkable suite of properties. It's non-corrosive, highly malleable. You can beat an ounce of it into a sheet covering 100 square feet, and highly ductile. While its monetary and jewelry roles are well known, its technical value is in high reliability applications where corrosion absolutely cannot be tolerated.
So we're talking about high-end electronics, connections and satellites, sophisticated medical devices.
Exactly. Anything where you need absolute long-term reliability and conductivity. Geologically, it is almost always found as native gold, either in quartz veins, which requires hard rock mining and massive crushing, or in placer deposits, which we'll discuss in the next section. It's a great illustration of how gravity can concentrate it.
Okay, let's wrap up this segment with lead and zinc. Two metals that are, maybe less glamorous, but absolutely critical to modern infrastructure and energy storage.
Lead, P, is a classic heavy shield metal. It is very dense, soft, and has a low melting point. And the sources highlight that despite efforts to replace it, a staggering 80% of its current usage remains devoted to car batteries.
80%.
80. The lead-acid battery is incredibly reliable, cheap, and recyclable, which keeps demand extremely high.
It seems like the transition to lithium-ion batteries for electric vehicles hasn't negated the need for lead, since most EVs still carry a 12-volt lead-acid battery for auxiliary functions.
That's the persistent reliability of the technology. It just works. Lead is also crucial for radiation shielding, protecting us from X-rays and nuclear sources, and of course, in ammunition. Its primary ore is galena, PBS, a sulfide mineral.
Okay, and finally, zinc. Zin-A, the protector.
Zinc's primary function is to protect other metals. Its number one use globally is in galvanizing steel. When steel is coated with a thin layer of zinc, the zinc acts as a sacrificial anode. It corrodes before the iron does, dramatically extending the lifespan of bridges, guardrails, and buildings.
It's the unsung hero that keeps the iron backbone from rusting away.
It truly is. Without widespread galvanizing, our infrastructure maintenance costs would just skyrocket. Zinc is also a component of brass, an alloy with copper, and is used extensively in die casting small, intricate metal parts. Its primary ore is sphalerite, ZNS, another sulfide, which means it often co-occurs and is mined right alongside lead.
That detailed breakdown gives us a real appreciation for the chemical and economic drivers behind each of these materials. But now we have to address the real magic. How did the Earth, over billions of years, manage to take these elements, which are often sparsely distributed in the crust, and concentrate them into these highly valuable, targeted ore bodies?
Right. That requires us to shift gears entirely. We're going to look at 4 immense geological sorting mechanisms that leveraged gravity, heat, chemistry, and even early biology to create the rich deposits we rely on today.
Okay.
We're moving from the inventory list to the manufacturing process. Think of the Earth as a massive, relentless recycling machine. It finds ways to take elements and, through various forces, accumulate them in places where they are easiest for us to find and extract.
And the first one is the most intuitive. It's perhaps the oldest mining method in human history.
Mm.
Placer deposits.
Yes, placer deposits are the result of purely mechanical concentration. They're driven by weathering and gravity. This happens when a primary rock source, let's say a quartz vein containing tiny flakes of gold, is broken down by erosion, wind, and rain.
So the quartz is ground into sand, but the gold resists that chemical and physical breakdown.
Exactly. Because gold is chemically inert, it doesn't rust or dissolve, and it is incredibly dense, it survives the process. The loose mixture of rock fragments, silt, and metallic flakes is then transported by water, usually in streams or rivers.
And this is where the sorting happens. The water carries everything, but it can only carry the heavy stuff if it's moving fast enough.
That's the key mechanism. As the stream current slows down, maybe in a wide bend or where the river gradient flattens, the material drops out of suspension. The lighter materials, like clay and fine sand, are carried further downstream.
Right.
But the dense, heavy metallic minerals like gold, platinum, and tin oxides, they settle rapidly. They accumulate in low spots, behind boulders, or in the cracks in the bedrock, forming a concentrated placer deposit.
The process of gold panning is the perfect small-scale demonstration of this. You're just manually replicating millions of years of river dynamics in a simple pan.
That's the principle in action.
Huh?
It's also important to note that placer deposits aren't just limited to riverbeds. We call those alluvial placers. They can also form along coastlines, creating beach placers where wave action is the sorting mechanism. And that concentrates heavy mineral sands like ilmenite or rutile, which are sources of titanium. The concentration is purely based on density, making a low-grade parent rock suddenly very viable.
That's weathering and gravity. The next process relies on a massive global chemical change driven by early life precipitation in seawater.
This formation type is responsible for the massive, ancient deposits that supply the bulk of our current iron needs. We call them the banded iron formations, or BIFs.
BFs?
BIFs. And these are arguably the most important type of ore deposit in human history.
The name itself suggests a layering effect. What are we looking at when we see a BIF?
BIFs are visually striking. They're these alternating layers of iron oxides, often red hematite or black magnetite, and then layers of chert or jasper, which is silica. They are truly enormous in scale, often extending for hundreds of kilometers and dating back to the Precambrian, maybe 2.4 to 3.5 billion years ago.
We mentioned earlier that iron constitutes only 5–6% of the Earth's crust, yet these BIFs can reach concentrations of 30 to 60%. How did the Earth manage such a colossal, uniform concentration across the whole globe?
This is where geology, chemistry, and biology intersect in just a spectacular fashion. For the first 2 billion years of Earth's history, the oceans were fundamentally different. They were anoxic.
Meaning they lacked free oxygen.
Exactly, no free oxygen. And they contained vast quantities of dissolved, soluble iron, which was continuously introduced by volcanic activity and seafloor hydrothermal vents.
Iron was just everywhere in the oceans waiting for a change in chemistry.
Precisely. Then, around 2.4 billion years ago, early photosynthetic organisms, specifically cyanobacteria, evolved and began releasing oxygen as a waste product. And this triggered the Great Oxygenation Event.
The moment the atmosphere changed forever.
As the newly generated oxygen dissolved into the surface waters, it instantly reacted with all that soluble iron. Iron oxides are highly insoluble. We know this simply as rust. This reaction caused the iron to precipitate or, rust out of the water column. And
It just settled on the seafloor.
it just settled onto the seafloor, forming the iron-rich layer.
So why the banding? Why didn't it all just precipitate at once?
The banding represents a cyclic balance. The cyanobacteria would produce enough oxygen to sweep the upper ocean layer clean of iron, causing a depositional event. That's the iron band.
Okay.
But then the free oxygen would be consumed either by the iron or by other reactions, and that would cause a period of silica deposition, the chert band, until the oxygen levels built back up again, which would trigger the next iron precipitation event.
And this cycle just continued.
For hundreds of millions of years, until the oceans were mostly depleted of dissolved iron and oxygen began accumulating freely in the atmosphere.
That is an immense geological timescale leading to the creation of the Negaunee Iron Formation in Michigan, which is a key example of this process, rich in hematite and magnetite. It's astounding that the oxygen we breathe today is the same substance that helped create the ore for the steel in our cars.
It connects our planet's ancient past directly to our industrial present.
Incredible. Okay, moving on. We leave the surface and dive deep into the heat of magma, where we find magmatic processes at work.
Magmatic processes are responsible for forming highly concentrated sulfide ores. These typically involve nickel, copper, platinum group elements, and chromite, and these deposits are found within igneous rocks that crystallized from magma deep within the Earth.
So we're dealing with the initial chemistry of the molten rock here, right?
Yes. When a magma body cools, it's not a uniform soup. It's an extremely hot, chemically unstable liquid. The key driver for concentration here is a phenomenon called immiscibility, which happens when a magma is saturated with sulfur.
Immiscibility. So it's kind of like oil and vinegar separating in a dressing, but inside a molten rock chamber.
That's a great way to put it. That's a good analogy. When the sulfur content is high, it bonds strongly with elements like nickel, copper, and iron, and it forms a distinct, dense sulfide liquid. This sulfide liquid does not mix with the main silicate magma melt.
And because it's denser.
Because it is denser, these droplets of sulfide liquid sink under gravity to the base of the magma chamber before the whole body solidifies.
So the valuable elements, the nickel and the copper, are effectively centrifuged out by gravity as the magma cools.
Precisely. This gravitational segregation leads to incredibly rich deposits at the bottom of the intrusion. These deposits are often found within or associated with ultramafic host rocks like peridotite. The primary ore minerals involved are pentlandite for nickel and chalcopyrite for copper.
And the scale of these magmatic deposits is immense. We're talking about global resource sources, aren't we?
Absolutely. Think of major global sulfide ore bodies like the Bushveld complex in South Africa or the Sudbury structure in Canada. These magmatic deposits can yield billions of tons and millions of pounds of recoverable metals. The cooling magma chamber provides the ideal closed, high-pressure, high-heat environment for really efficient chemical sorting. It creates highly reliable, long-term resource sources.
Our final major process utilizes the planet's internal heating system and water, hydrothermal fluid circulation.
Hydrothermal processes, which just means hot water, are responsible for perhaps the greatest diversity of metallic ores, including most of the world's gold, silver, and high-grade copper deposits. This mechanism relies on the circulation of water that has been superheated deep within the crust, often by nearby magma bodies.
And water becomes an incredibly aggressive solvent when it's superheated and under pressure, doesn't it?
It turns into a highly chemically active fluid. As this hot fluid, sometimes exceeding 400 degrees Celsius, circulates through faults, fractures, and porous rock, it acts like a giant scavenger. It leaches out trace amounts of metals, copper, molybdenum, gold, silver from all the surrounding country rock.
So it's essentially creating a metallic cocktail that's circulating deep underground. What makes that cocktail drop its metallic payload?
The moment of deposition occurs when that hot fluid encounters a change that disrupts its stability. This could be a drop in pressure as it rises toward the surface, a drop in temperature as it moves away from the heat source, or a change in chemistry like mixing with groundwater.
And that's when the metals fall out.
When the fluid can no longer hold the metals in solution, they precipitate out instantly, creating concentrated veins or replacing existing rock.
And the sources clearly contrast two major outcomes of this process, which have wildly different economic profiles.
Yes. The outcome depends entirely on the plumbing system. First, you have disseminated ores, often associated with massive igneous intrusions called porphyries. Here, the metals are spread or disseminated throughout a massive volume of rock. The Pebble Mine in Alaska is a world-class example. It has immense quantity, but an inherently low grade of copper and gold.
Right.
You process a colossal amount of rock to get a moderate metal yield.
This is the high-volume, high-waste approach, where the sufficient quantity criterion is pushed to its absolute limit to meet the sufficient value criterion.
Exactly. Contrast that with the second outcome, massive sulfide deposits. These form where hydrothermal fluids are funneled through discrete fractures, or most dramatically expelled onto the seafloor via black smoker vents.
Oh.
When that superheated, metal-rich fluid hits the cold seawater, the metals flash precipitate, forming thick, dense piles of metallic sulfides.
So the black smokers are, in a way, creating immediate high-grade ore bodies.
That's right. These massive sulfide deposits are smaller in total size than disseminated deposits, but they boast extremely high concentrations of zinc, copper, lead, silver, and gold. The Flambeau mine in Wisconsin is a classic continental example of this type of highly concentrated deposit formed billions of years ago by ancient black smoker activity.
That is a phenomenal geological toolkit. We've gone from gravity separation to ancient biology, from liquid rock dynamics to hot water highways. Now let's move from the theory of formation to the concrete, real-world projects that define modern mining and, more importantly, put those three criteria, quantity, quality, and value, to the ultimate test.
So what does this all mean in practice? Let's look at how the geology dictates the operational challenges and the economic decisions.
We established that the ultimate tension is between quantity, the sheer size of the resource, and quality, the concentration of the metal. Let's start with a high-quality finished example, the Flambeau mine, which perfectly illustrates that massive sulfide deposit type.
The Flambeau mine in Wisconsin is a textbook example of high-grade, targeted extraction. Geologically, it was a massive sulfide ore body formed about 2 billion years ago, a relic of ancient seafloor venting. Its value lay entirely in its high quality.
And the yield data on this mine is truly exceptional. I mean, almost unheard of today.
It was a geologist's dream. The ore averaged an astonishing 9.5% copper.
9.5%.
9.5. To give you perspective, modern large-scale copper mines often operate efficiently at grades well below 1%. So this deposit was essentially 10 times richer than many operations today.
Wow.
Additionally, it contained high concentrations of gold and silver, averaging 0.175 ounces of gold per ton.
That quality must have made the operation immensely profitable, even though it was a relatively short-lived mine.
It was incredibly productive. In just 4 years of operation between 1993 and 1997, it yielded 181,000 tons of copper and over 3 million ounces of silver. And that trace silver recovery, in particular, would have substantially inflated the overall sufficient value calculation for the project. It turned an already excellent operation into a world-class venture.
But the crucial lesson from the Flambeau mine is also about stewardship. The sources highlight that the site underwent comprehensive, successful reclamation post-mining.
That is the modern imperative. Flambeau serves as a crucial case study demonstrating that high-grade extraction, even of sulfide ores, which inherently carry acid mine drainage risks, can be completed with a full commitment to environmental remediation.
Right.
The entire life cycle, including the closure costs, has to be factored into that initial economic viability calculation. The land was restored to a biologically productive state, showing that responsible mining is technically achievable.
Okay, now let's look at the continuous tension that dominates current resource decisions by examining two proposed projects that illustrate the opposite end of the spectrum, the challenge of volume over concentration.
Let's first look at the Back 40 project in Michigan, which aims to tap another black smoker massive sulfide deposit. It's targeting high-grade gold and zinc. This again illustrates the lure of the high-quality ore. The potential for high value is what's driving the proposal.
But these high-grade sulfide operations, especially those near water systems, they automatically draw high levels of environmental scrutiny. The debate here centers on whether the potential short-term value justifies the potential long-term risk.
Precisely. It brings the three criteria right back into focus. Is the sufficient value high enough to cover the immense cost and technical challenge of risk mitigation and guaranteed long-term remediation that's required for a sulfide operation near fragile ecosystems?
hmm
The geological reality of a high-grade sulfide deposit forces an expensive and difficult risk calculation.
And that contrasts so sharply with the pebble mine, which we revisited earlier. This is the ultimate example of the sufficient quantity criterion just overwhelming the sufficient quality one.
Absolutely. The Pebble Mine in Alaska is a classic porphyry or disseminated deposit. It is cited as one of the largest undeveloped copper deposits in the world. Its sheer volume of recoverable copper and gold is globally significant. It represents a massive future resource.
But if pebble mine is so low grade, we're talking grades potentially below 0.5% copper, why is it even on the table? Doesn't that fundamentally contradict the idea that the cost of extraction has to be justified? Isn't that just bad economics driven by a desperation for volume?
That is the core conflict. Economically, the low grade means that you have to process exponentially more material. We're talking billions of tons of rock over the life of mine to recover the copper.
Right.
And that process creates gargantuan volumes of tailings or waste rock and requires astronomical energy consumption.
It's the sheer scale, the sheer quantity is the only thing that makes the sufficient value criterion work because there's so much copper there, despite the low concentration.
It's a pure volume play, yes. The potential resource security benefits, having access to that much copper for generations, is what drives the interest. But this project showcases the continuous tension between resource extraction and ecological concerns perfectly, maybe more than any other.
How so?
Because the operation must be so massive to be economically viable, the inherent ecological risk, particularly concerning regional water resources, is magnified enormously.
The choice between high-quality, targeted extraction like Flambeau and the monumental low-grade bulk extraction required at a site like Pebble really defines the future of resource procurement. We're moving toward a future where we have to mine the lowest grades available simply because the high-grade sources are running out.
And that means the cost in energy, waste volume, and ecological management is only going up. Our economic criteria are bending to accommodate geological scarcity.
This has been a truly fascinating deep dive, moving from the definition of a mere rock to a multi-billion-dollar ore body shaped by planetary forces.
To quickly recap, we started with the three criteria for economic viability: sufficient quantity, quality, and value, which must be constantly reevaluated. And we explored the four extraordinary formation processes that allow the Earth to concentrate these elements.
Placer deposits driven by gravity.
Right. Precipitation in seawater, which gave us the essential banded iron formations. Magmatic processes creating deep, dense sulfide ores like nickel and copper. And hydrothermal fluid circulation, which gives us both high-grade veins and massive, low-grade disseminated ore bodies.
Right.
You know, if we connect this to the bigger picture, the source material shows that we are entering an era of diminishing returns in quality. We are increasingly relying on the vast, low-grade, high-volume deposits like Pebble, which demands tremendous energy and creates immense waste, rather than the high-quality, targeted extraction of the past like Flambeau. This tension raises an important question for you, the listener. Considering the energy-intensive processing required for metals like aluminum and the known ecological impacts demonstrated by projects focused on sheer quantity, are we currently prioritizing immediate value extraction, or are we making long-term decisions regarding geological stewardship and processing efficiency? Which of the three criteria, quantity, quality, or value, do you think will dominate future mining decisions, and what will that look like on the landscape?
That's a powerful thought to end on. If you are intrigued by the sheer scale of early life's impact, look into the chemistry of the Great Oxygenation Event. Or, if you want to understand industrial energy consumption, dive deeper into the economics of the Hall-Héroult process. Thank you for joining us for this deep dive into the bedrock of the modern world. Welcome to the Deep Dive.
It's great to be here.
Today we are undertaking a truly monumental journey. It's one that takes us right beneath the very ground we're standing on.
And maybe more importantly, beneath the oceans that cover most of our planet?
Absolutely. We are diving deep into one of the greatest scientific revelations of the 20th century. It's this tectonic shift in geology, this realization that the continents aren't fixed, stable things.
They're not. They're dynamic rafts just sort of gliding across the face of the planet.
Exactly. This is the story of plate tectonic theory.
And it truly is a paradigm shift. Before this theory really became established, our understanding of the Earth was so fragmented.
Right.
We could explain mountains or, earthquakes, but only as individual events. We lacked a unifying theory that could tie them all together.
A grand narrative.
Yes, plate tectonics is that master key. It explains everything, from the distribution of, say, economic mineral deposits all the way to the patterns of ancient life.
Absolutely. So our mission for you today is to give you the definitive understanding of how we moved from what was a radical, almost a fringe idea, to a completely established scientific fact.
Yeah, and we've been immersed in the sources, really digging into the architecture of the theory.
We're going to focus first on the initial evidence collected by Alfred Wegener. It was highly intuitive, but as we'll see, incomplete.
And then we'll contrast that with the indisputable technological proof that came from oceanographers using things like paleomagnetism and advanced age dating.
We want to extract the structure, all the memorable details, and really trace that critical path.
From the historical puzzle that Wegener first identified, through the decades of skepticism that followed, and then to the ultimate discovery of the Earth's hidden engine right there beneath the sea.
And we begin where this narrative so often does in science. Not with agreement, but with a highly contentious idea put forward by one very, very persistent man, Alfred Wegener. His bold hypothesis from 1912, he called it continental drift, suggested that all land masses were once a single massive supercontinent,
Pangaea.
and that they had since broken apart and just migrated to their present positions.
It's so important to frame just how radical this was at the time. Wegener wasn't just suggesting a new idea. He was directly challenging the most respected geological consensus of his era. It was a huge deal.
Okay, let's unpack that. The intellectual environment of 1912. What was the accepted view that Wegener was trying to overthrow?
Well, the prevailing theory was something called the contracting Earth hypothesis.
Contracting Earth.
Yeah. The idea was that the Earth started out as, hot and molten, and as it slowly cooled over geological time, it contracted.
Like a piece of fruit drying out.
Exactly, like a raisin shriveling up. And this contraction, according to the geologists of the day, caused the surface crust to buckle and wrinkle.
And those wrinkles became the mountains, the trenches, all the major land features.
That was the idea. So mountain ranges were literally seen as the Earth wrinkles.
That sounds pretty plausible on the surface. I can see why people would buy into that.
It was highly respected because it offered a mechanism, right? Even if it was a limited one, it explained deformation. And within that framework, continents were fixed monuments.
Unmoving.
Permanent features in specific places. They might move up or down a bit locally due to erosion or rebound, but never, ever laterally across the globe.
So Wegener's 1912 proposal, the idea that continents drifted, it wasn't just a small change.
It was a total revolution, a complete rewrite of the rules.
So Wegener stands up and presents his idea. Pangaea, the universal land, existed roughly 200 million years ago. It broke up, and the fragments, our continents, slowly moved to where we find them today. What was the initial reaction from the scientific community?
Intense skepticism. It bordered on outright hostility, especially from the North American geologists.
Why them in particular?
It just ran so counter to their entire framework. So while his evidence for the fit was compelling, and we'll get into that in detail, his ideas were met with widespread rejection, often ridicule even.
And it didn't help that he wasn't a geologist in the traditional sense.
That was a huge part of it. He was a meteorologist by training, a climatologist, and his background often led to his ideas being dismissed as, amateurish, the work of an outsider.
It's fascinating how even the most persuasive evidence can just be thrown out if it contradicts the established physics of the day.
And that brings us to the absolute core of the issue. The scientific community, they could see he had compiled some strong circumstantial evidence, but they concluded he lacked a credible, accepted mechanism to explain the movement.
The how.
The how.
And this is the crux of why continental drift was basically shelved for decades.
Yeah.
The evidence was so compelling. The incredible fossil matches, the way the continents just locked together. Why didn't scientists just assume some force must exist, even if they couldn't name it yet? Why was the lack of a mechanism an absolute deal breaker?
Because the physics of the time and their understanding of material properties seemed to just definitively rule it out. You have to understand the composition of the different crusts.
Okay, let's break that down. What's the difference?
The continents, the land masses Wegener was saying, were drifting. They're primarily composed of granitic rock.
Granite.
Yeah, and this crust is relatively light. It's less dense.
Okay.
But the ocean floor, That's a completely different story. It's
Yeah.
primarily basaltic rock, which is significantly denser and, crucially, much more rigid.
So Wegener was essentially suggesting that these massive blocks of lighter granitic continental crust were somehow plowing through the solid, heavy basaltic ocean crust.
Exactly, like an icebreaker through a frozen sea, but a sea made of solid rock.
I can see the problem.
The geophysicists of the day, they could calculate the force required to drag or push a continent through that solid basalt, and the number was astronomical.
The force just didn't exist in any known physical process.
Right? They viewed the oceanic crust as this immovable, high-friction foundation, a solid base.
So the theory completely failed the physics test. The scientific community just determined the ocean floor was static, unmoving, and far too rigid for continents to slide across.
And because of that, all of Wegener's other evidence could be dismissed. The observation that continents look like they fit together,
A coincidence.
or maybe they were connected by temporary land bridges that have since sunk. They came up with all sorts of explanations to avoid the movement part.
And that context is so crucial for you, the listener, to understand. The ultimate breakthrough didn't involve finding a new way to plow continents through the ocean floor.
No, it involved finding out that the ocean floor itself was moving. The breakthrough had to come from discovering that the engine wasn't pushing continents, but was actually carrying them.
A completely different picture.
A whole new world.
So while the world was dismissing his how, let's take a moment to really appreciate the sheer depth of Wegener's what. He compiled this stack of evidence that, even today, is just incredibly persuasive. Let's look at the three main pillars, starting with the most visual one, the most intuitive.
This is the foundation of the whole idea. I mean, anyone who looks at a world map is immediately struck by the relationship between the east coast of South America and the west coast of Africa.
It's the first thing you notice.
They look like they were designed to fit together. It's an almost perfect match, like puzzle pieces.
But didn't the critics at the time point out that the current shorelines don't fit perfectly? That there are gaps or overlaps if you try to match them together?
They did, and that was a fair critique if you're only looking at the coastlines we see today. But this is where the precision of Wegener's data really came in.
Okay.
We have to remember that our current shorelines are very temporary features. Geologically speaking, they're fleeting. They're constantly being shaped by short-term processes.
Like tides, erosion.
Tides, erosion, and especially sea level changes associated with ice ages. The water level goes up and down, changing the shape of the coast all the time.
So the coast is just the water line of the moment. Where should we be looking for the true edge of the continent?
You have to look at the continental shelf boundaries. The continental shelf is the actual submerged edge of the continental block right before it steeply drops off into the deep oceanic abyssal plain.
The real edge is underwater.
Right. And when researchers later in the mid-20th century compared the 1,000-meter isobath, that's a line of constant depth along the shelf boundary, the fit between South America and Africa became remarkably clean.
So it solved the overlap problem.
It eliminated most of the gaps and overlaps, and this suggested a former connection that was far stronger than just mere coincidence. It was a structural fit.
Okay, that's the visual evidence, the puzzle piece. But where Wegener really started to make the scientific case was by using climate and geology to prove motion.
Yes, and this is where we find the highly surprising data. Ancient glacial deposits found in areas that are currently tropical.
This is a wild one. Explain that.
Okay, so imagine standing today in the middle of India. The climate is hot, often monsoon-driven, yet deep within the bedrock there, geologists found clear, undeniable evidence of past glaciation.
Like what kind of evidence?
Things like rock striations, deep scratches in the bedrock left by glaciers dragging rocks along, polished bedrock, and layered sedimentary deposits known as tillites. These are basically the fossilized debris left behind by a melting ice sheet.
All pointing to massive ice sheets having existed right there in India.
Yes. And this evidence wasn't just in India. Wegener found it in southern Africa, in southern South America, and in southern Australia, all locations that are currently very far away from the poles.
So this created what you called a powerful climate paradox.
It really did. If the continents had remained fixed in their current positions, the Earth would have required a climate so bizarre, so strange, that colossal glaciers existed near the equator at the same time they existed near the poles.
Which violates all principles of heat distribution on a spherical planet.
It's wildly implausible. It just doesn't work.
So the implication then becomes a geometric necessity. These land masses must have once been located much closer to the poles during that specific geological period.
Exactly. That was the late Paleozoic era. They had to be somewhere cold to accumulate those massive ice sheets.
And when you put the puzzle pieces back together,
When you mathematically reconstruct the continents, clustering South America, Africa, India, and Australia together into Pangaea, suddenly all those ancient glacial deposits form a single, cohesive, high-latitude ice sheet,
centered perfectly over the south.
neatly centered over the South Pole. This evidence solved the climate puzzle through movement. The continents moved, the climate zones themselves did not.
That is incredibly elegant.
It's a beautiful solution.
Okay, so we have the fit, we have the climate paradox solved, and the third, and maybe the strongest, support for a connected landmass comes from the distribution of life.
The fossil record. This is where the evidence becomes, I think, almost undeniable. It proves that ancient life forms didn't just evolve separately in parallel ways.
Right. If continents were always separated by these massive oceans, then the evolution of terrestrial life, and especially freshwater life, should have followed distinctly different paths on each continent.
Of course. But Wegener found instance after instance where identical plant and animal fossils were found across continents that are now separated by thousands of miles of salt water.
Posing an impossible migration
That's
problem.
a completely impossible migration problem. These were not marine species that could just swim across.
These were landlocked or strictly freshwater organisms. Let's make this really stick for you, the listener, by giving the specific examples Wegener used. These are the classics.
Okay, the first and most classic example is the Mesosaurus.
Mesosaurus.
This was a small, ancient reptile, maybe about 3 feet long, and it lived exclusively in freshwater environments, swamps, rivers.
So strictly freshwater.
Its fossils are found only in very specific corresponding regions of South America and Southern Africa and nowhere else in the world.
A freshwater reptile cannot cross the deep, wide, salty Atlantic Ocean.
Absolutely not. Its presence on both sides of that ocean demands a physical land connection. There's really no other way to explain it.
Okay, what's next? We had the reptile with maybe the widest distribution, the Lystrosaurus.
Lystrosaurus. This was a sturdy, sort of pig-like land reptile. It's famous for being incredibly hardy. It was a survivor of the biggest mass extinction event in Earth's history.
And where do we find its fossils?
Across 3 widely disparate continents today: Africa, Antarctica, and India.
Okay, look at a map. Those 3 land masses are scattered globally.
They're all over the place. Yet they share this common inhabitant from about 250 million years ago. Again, this organism could not have island hopped across thousands of miles of open ocean.
It's just not possible. And rounding out the terrestrial fauna, we have Cynognithus.
Cynognithus. This was a land-dwelling therapsid, which is a kind of mammal-like reptile, and its remains are also found on both Africa and South America.
Just like Mesosaurus.
Just like Mesosaurus. All these terrestrial animals, they share a single story. They originated on a single, contiguous landmass, and they were separated when that landmass broke apart and drifted away.
And the evidence isn't just from animals, right? There's plant life, too. The Glossopteris flora.
Right, the Glossopteris. This was a type of seed fern, and it's known for its very distinct tongue-shaped leaves. Fossils of this plant are found across all of the southern continents:
All of them?
Africa, Antarctica, India, Australia, and South America. All of them. This is crucial because it indicates a shared, unified environment and a common flora during that time. It's the biological fingerprint of Pangaea.
And the seeds themselves couldn't just blow across the ocean.
The seed structure suggests they were too heavy. They weren't easily spread by wind or by sea either.
So to recap, Wegener had the historical fit of the continents, he had the displaced climate evidence from the glaciers, and he had these identical fossils spread across oceans. The evidence stack was truly compelling.
It was.
Yet, because he couldn't explain the engine, his theory was largely rejected by mainstream science, and it languished for decades.
Yeah. The geological community needed indisputable proof of motion, and that proof was hiding in a place no one had really been able to look before.
Under miles and miles of seawater.
That's right. The problem of the mechanism, it remained unsolved until well after Wegener's death. And the crucial shift, it didn't come from geologists studying land. It came from oceanographers using new technology that was developed during World War II.
Right, so let's transition to that post-war environment. Advances in sonar, and especially magnetometry, allowed scientists to begin mapping the ocean floor in Just unprecedented detail.
And what they found completely changed the game
They stopped focusing on how continents move through the ocean crust.
and started focusing on how the ocean crust itself was moving.
And this is where the concept of seafloor spreading was first proposed. This was the mechanism everyone was looking for.
It was the key. Instead of continents plowing through the basalt, the idea was that the continents were simply passive riders. They were being carried by a moving conveyor belt of oceanic crust.
So what was the first key finding from these sonar surveys that even hinted at a dynamic ocean floor?
It was the discovery of the mid-oceanic ridge system,
A giant mountain range underwater.
a giant global mountain range. Scientists realized the ocean floor was not the flat, passive, boring plane they had always assumed. Instead, it was bisected by this massive, continuous underwater mountain range stretching over 65,000 kilometers across the entire globe.
That's longer than all the continental mountain ranges combined.
By far. And this system is characterized by a central rift valley running right down the middle of it.
So the ocean floor had this huge seam running through it, and that seam was where all the action was happening.
Exactly. The ridge system became the critical finding. It proved the ocean floor is dynamic, not static. It's a site of colossal volcanic and tectonic activity.
And this ridge is where seafloor spreading occurs. So how exactly does that process work?
It's the site where new oceanic crust is continuously formed. Hot magma from the mantle deep beneath the ridge rises up.
Yeah.
As it reaches the surface at the bottom of the ocean, it cools, it solidifies into basaltic rock, and it forms new crust.
And as more material comes up.
It effectively pushes the older crust outward, away from the ridge axis, symmetrically in both directions.
Like a conveyor belt moving away from the center line.
A perfect analogy.
So the continents are simply the baggage riding on this slowly expanding crustal system. But this still doesn't fully explain the force driving the entire global system. This is where we need to introduce the actual accepted physical engine that powers all of plate tectonics.
Right. When Wegener was rejected, the missing piece was the force. Today, we know the movement is driven by a combination of forces that originate deep within the Earth, and they're primarily associated with the behavior of the mantle.
Okay, let's start at the source of the heat. Mantle convection.
The mantle is not molten liquid, which is a common misconception. It's solid rock, but it behaves plastically, like very, very thick taffy, over immense timescales.
And it's moving.
It is. Because of heat differentials, the core is much hotter than the surface. This material circulates in slow, continuous convection cells.
Like boiling water in a pot.
Exactly like that. Hot, less dense material rises towards the surface. It spreads out horizontally beneath the lithospheric plates, and as it cools, it becomes denser and sinks back down. This flow generates a viscous drag that moves the plates above it.
So that explains the motive power underneath. But what about the forces that are acting on the edges of the plates themselves? The total movement isn't just passive floating, is it?
No, you're right. We have two other major forces. First, there's ridge push.
Ridge push.
At the mid-ocean ridges, the newly formed lithosphere is hot, it's buoyant, and therefore it's elevated. It sits higher than the older crust. Gravity then acts upon this elevated mass, causing it to effectively slide down and away from the ridge axis.
So it's exerting a pushing force on the rest of the plate.
Yes, gravity is helping push the material away from the center line.
Okay, so there's a push. What's the other force?
The second, and what many scientists now believe is the most dominant force, is slab pull.
Slab pull.
This happens at subduction zones. That's where one plate sinks beneath another, usually where oceanic crust meets continental crust, in the Pacific Ring of Fire.
I see.
As that dense, cold oceanic slab sinks back into the mantle, its own weight literally pulls the rest of the plate behind it. It's like a heavy anchor dragging the whole chain down with it.
So here's where it gets really interesting. Slab pull is estimated to be the single greatest force driving plate movement.
That's right.
So the old cold crust sinking back into the Earth is actually more important in driving this than the hot magma rising up at the ridge.
Absolutely. The engine isn't just one simple pump. It's a dynamic system. It involves deep convection, it involves gravitational sliding at the ridges, and it involves the massive gravitational pull exerted by these sinking slabs.
And this complete picture finally satisfied the mechanical requirement that caused Wegener's hypothesis to be rejected 60 years earlier.
Yes, but the critical next step was proving the spreading was actually happening and then beating it.
Okay, so we have the engine. Now we need the proof that the conveyor belt is actually moving, and moving symmetrically. You can't just stand there and watch it spread.
Right, it's too slow.
So this is where scientists used a really surprising tool, the Earth's own ancient magnetic field. which is stored in the rock.
And this brings us to paleomagnetism. It's the study of the magnetic signature that's locked permanently into rocks.
How does that happen?
When that molten basaltic rock comes up at the mid-ocean ridge and it starts to cool and solidify, there are tiny magnetic minerals within it, specifically a mineral called magnetite.
Okay.
And they align themselves like microscopic compass needles with the direction of the Earth's magnetic field at that precise moment in time.
So it's like a geological recording system. Every piece of new crust is essentially taking a magnetic snapshot of the planet as it cools.
Yes, and that signature is permanent.
Okay.
Once the rock drops below what's called the Curie temperature, that's the point at which materials lose their magnetic properties, the magnetic alignment is locked in. It creates a permanent record.
And that record lets us reconstruct the historical position of continents. And, crucially for this story, monitor the planet's magnetic field changes over time.
Exactly.
And the device they use to map this invisible history across the ocean floor is the magnetometer. How does that device actually work to find these stripes?
A magnetometer is a sensor that's towed behind a research vessel. It just measures the intensity of the local magnetic field.
Okay.
When the rock beneath the ship has magnetism that aligns with the current Earth's field, what we call normal polarity, the local field intensity is slightly stronger.
It adds to it.
It adds to it. But when the rock's magnetism is opposite to the current field reverse polarity, the overall field intensity is slightly weaker. It subtracts from it.
Creating a measurable magnetic anomaly.
Yeah.
A deviation.
Precisely.
Right.
And by towing the sensor across vast stretches of the ocean floor, scientists could generate a precise map of these alternating magnetic fields that are locked in the basalt.
And the magnetometer data revealed something truly revolutionary. But before we unveil that pattern, let's quickly talk about the phenomenon that's actually being recorded here. The Earth's magnetic reversals.
Right. The Earth's magnetic field is generated by the movement of liquid iron in the outer core, and it is inherently unstable over geological time.
Meaning it flips.
It flips
A
completely.
full 180-degree flip. So when scientists examine the rock's preserved magnetic signature, they can classify it into one of two states.
Precisely. We have normal polarity, which means the ancient magnetism stored in the rock aligns with Earth's magnetic field as it exists today. So magnetic north is roughly near geographic north,
And the other is reversed polarity.
which means the ancient magnetism is in the opposite direction. North is where magnetic south is now.
It's important to emphasize this reversal process isn't instant, right? It's not like a light switch.
No, it happens over thousands of years. But once the rock solidifies, it preserves that orientation perfectly for hundreds of millions of years.
Okay, so when oceanographers analyzed the data gathered by the magnetometers near these mid-ocean ridges, they found a pattern. And this pattern was so predictable and so profound, it basically settled the debate over continental drift entirely.
They found symmetric magnetic anomalies.
Let's visualize this for you, the listener. Imagine taking a continuous measurement, just sailing a ship right across the ridge axis. What did the graph look like?
It showed these alternating bands of stronger normal polarity and weaker reversed polarity magnetism on the seafloor. And these bands stretched parallel to the ridge for hundreds of miles.
But the stunning insight was the symmetry.
The symmetry, it was a perfect mirror image on either side of the ridge center.
Yes. For every, say, 20-kilometer wide band of normal polarity rock, you find 100 kilometers to the east of the ridge.
There was an identical corresponding 20-kilometer wide band of normal polarity rock found 100 kilometers to the west. This symmetric pattern could only be explained in one way.
New crust is continuously being created at the ridge axis.
Spreading outward simultaneously in both directions.
And it's recording the switches in the planet's magnetic field as it goes. If the spreading rate wasn't uniform, or if the process wasn't bilateral, the symmetry would be completely broken.
It would be a mess. The symmetry is the direct, physical, quantitative proof of continuous seafloor spreading. It acts like a unique geological barcode that gives us both the rate and the history of the movement.
And this discovery provided the indisputable confirmation that the ocean floor itself was dynamic, carrying the continents along with it.
It was the missing piece of the puzzle.
So they not only proved the movement, but now they could use the Earth's own magnetic history as a kind of ruler to measure the rate of that movement.
Yes, and these alternating periods of polarity, they've been categorized into specific intervals.
What do you call those?
These periods of time when the magnetic field holds a consistent direction, either normal or reversed, are known as crons, or magnetic reversal chronologies.
So we can build a timeline.
Exactly. By dating volcanic rock samples on land that exhibit these same reversals, scientists could create a global timeline. This allowed them to precisely calibrate the magnetic stripes they found in the ocean core.
And this timeline is surprisingly detailed, and it's variable. We often think of geological processes as happening over these unimaginably long timescales, but the magnetic field seems pretty sprightly.
It is. It really is. Our sources show that the duration of these crons has varied significantly. While some periods of stable polarity have lasted for many millions of years, the typical duration of a cron in the geologically recent past has ranged from as short as 0.1 million years.
100,000 years.
100,000 years, all the way up to a maximum of about 1 million years.
So what's the average duration we see in the magnetic timeline?
For dating purposes, the average duration of a cron is pretty tightly clustered around 300,000 to 400,000 years.
That's a really rapid pace. It shows just how dynamic the Earth's outer core fluid motion actually is.
It's constantly churning. And looking at the frequency of these reversals, especially in the last few million years, it gives us a very clear picture of just how unstable it is.
Now unstable.
If we focus on just the last 10 million years of Earth's history, the magnetic field has been highly active. The geological record indicates that the field has reversed frequently, occurring 4 to 5 times per million years. And that frequency is fantastic for scientists because it allows them to create incredibly high-resolution maps of spreading rates. There's a new barcode stripe forming every few 100,000 years.
And finally, the ultimate historical benchmark. When was the last time the Earth's field flipped completely?
The most recent major magnetic reversal event, this is the boundary between the Brunhes Cron, which is our current normal polarity, and the Matuyama Cron, the preceding reverse polarity, that occurred approximately 780,000 years ago.
780,000 years.
And that date is one of the most crucial geological reference points used globally. It serves as a timestamp in the oceanic crust that helps us calculate precise spreading velocities all over the world.
So the paleomagnetic evidence provided the smoking gun for spreading. It was the barcode. But for a theory as monumental as plate tectonics, multiple lines of evidence have to converge.
Right.
You can't just rely on one thing.
No, you need confirmation from independent methods. And the final, absolute confirmation came from applying absolute dating techniques directly to the moving ocean floor.
This is where we integrate the magnetic data with radiometric age dating.
Right. The magnetic striping tells us the pattern and the relative timing of the reversals, but radiometric dating provides the actual calendar age. It confirms the correlation between the magnetic barcode and the geological clock.
So how did scientists use this method to confirm the spreading? What was the critical finding they needed to observe?
Well, they took rock core samples. The deep-sea drilling project was essential for this. They took cores from various points on the ocean floor, traveling systematically away from the mid-ocean ridges in both directions.
A transect.
It's exactly a transect. And then they analyzed these samples using radiometric dating. Typically, they look at the decay rates of specific isotopes within the basalt, things like potassium argon or uranium lead, to determine their absolute crystallization age.
The moment they cooled from magma into solid rock. And what did the clock tell them?
The results were conclusive. They were perfectly consistent with the seafloor spreading hypothesis that was already established by the magnetic data.
And the critical finding was?
The critical finding was that the age of the ocean floor increases linearly and predictably with distance from the mid-ocean ridge axis.
So the youngest crust, the baby rock, is always found right at the ridge center, with an age of essentially 0 years.
Precisely. And as you travel outwards, say you go 1,000 kilometers away, the rocks are suddenly millions of years old.
And this observation proved two things simultaneously.
It did. First, that new crust is formed continuously at the center, and second, that the ocean floor is indeed a conveyor belt moving away from the ridge crust.
And the rate of that age increase matched the spreading rates they had calculated independently from the magnetic anomalies.
Perfectly. It created a complete, non-negotiable verification of the entire theory.
So this convergence of data, the historical fit from Wegener, the biological evidence from the fossils, the paleomagnetic barcode, and now the absolute age dating, this allowed geologists to finally transition from static maps to a truly dynamic model of Earth history.
And that's the real power of the synthesis. For the first time, scientists had a reliable way to map the movement of plates backward and forward in time.
They could run the clock back.
They could. Using all this gathered data, the rock ages, the specific magnetic chronology, the boundaries between different rock types, we can now accurately illustrate continental movement over hundreds of millions of years.
This is why we have those spectacular visual representations and animations you see in documentaries. The one showing Pangaea assembling, breaking apart, and the continents zipping around the globe to their current positions.
Those animations are the direct result of correlating all the data we've just discussed. They help us conceptualize the sheer scale and the dynamic nature of the Earth's surface. They transform this abstract concept of plate movement into a tangible reality.
It demonstrates that the lithosphere is broken into roughly a dozen major plates.
All moving relative to one another, driven by that engine we talked about. The forces of convection, ridge push, and slab pull. The Earth is a continuously evolving planetary machine.
So we've moved from Wegener's elegant but flawed initial observation to a comprehensive physics-based understanding of the planet.
We found the historical evidence, we identified the engine seafloor spreading, and then we proved the motion with absolute physical data.
That is the robust, complete architecture of plate tectonic theory.
It is arguably the most fundamental theory in all of modern Earth science.
It's hard to argue with that.
And the journey from Alfred Wegener's brilliant but unsubstantiated idea of continental drift met with those decades of skepticism because of the lack of a mechanism.
To the ultimate confirmation provided by deep-sea research and that magnetic barcode.
It's a powerful lesson in scientific tenacity and technological progress.
We started with that fundamental question. How could the ground beneath our feet possibly move? And we learned that the how was seafloor spreading.
Driven by those powerful forces originating in the mantle, the convection currents, the ridge push, and that dominant slab pull.
And the evidence stack just became undeniable. The way South America and Africa fit together along the continental shelf.
The presence of ancient glacial scars in equatorial regions.
The identical fossils of terrestrial creatures like Mesosaurus and Lystrosaurus spanning these vast oceans.
The discovery of the symmetrical magnetic anomalies, that perfect mirror image.
And finally, the absolute age progression of the oceanic crust, getting older as you move away from the ridge. All of it converge, leaving no room for doubt.
None at all.
And for you, the listener, understanding this transition really provides a fundamental understanding of Earth's history. And this isn't just academic knowledge, is it?
No, it dictates why volcanoes exist where they do, why earthquakes happen where they happen, why resources like oil and specific mineral deposits are distributed across the globe in patterns related to past continental collisions and movements.
The Earth is truly a living, breathing machine, constantly recycling its own surface. It's a process that takes millions of years, but it's one we can now measure in incredible detail.
Yes.
Okay, let's leave you with one final provocative thought. And this builds directly on the specific numerical data we discussed regarding the Earth's magnetic field history.
Okay. We established that the magnetic field has been reversing frequently in recent geological time, on average 4 to 5 times per million years.
Right.
And we also know that the last great switch in polarity, the one that marked the end of the Mattia-Macron, occurred approximately 780,000 years ago.
So, given that frequency, and the fact that we are approaching the 800,000-year mark since the last major event, it sort of implies that we're living in a period that is statistically past the average time for a magnetic reversal.
It does. Now, scientists cannot predict the exact timing of the next flip. And an average is just that. It's an average, not a guaranteed timeline. But it does raise an important question about scale and impact.
Because during a reversal, the Earth's protective magnetic field significantly weakens.
It does. It allows much higher levels of solar and cosmic radiation to reach the surface.
So what are the potential global implications? For our technology, for our satellites, for power grids, and perhaps even for life on the surface of living in a time when the Earth's polarity is, statistically speaking, due for a flip.
It's a reminder that even the deepest, slowest geological processes ultimately affect every aspect of our lives right here on the surface.
The dynamism of the deep Earth is our ultimate environment.
Absolutely.
And that's our deep dive for today. Thank you for joining us on this tectonic time machine.
Until next time.
Welcome back to the Deep Dive, where we take your stack of research and notes and really cut to the core of what you need to know, providing the context and the insights that turn all that raw data into durable knowledge.
Today, we're undertaking a truly massive task. We are charting the geological transformation of rock itself. We're diving deep into the process of metamorphism, which, literally translates from the Greek as change form.
And we are looking at rocks that have been buried, squeezed, and, well, baked under conditions that just seem impossible.
Yeah.
I mean, one of the interesting descriptions I found in your sources actually refers to these rocks as often appearing, and I'm quoting here, screwed up.
Screwed up or highly altered. Yeah.
Exactly. And it's precisely because they've endured such intense structural remodeling. But these transformations, they're actually incredible windows into the massive forces that govern our planet's history.
Our goal for this deep dive is really to give you a thorough understanding of the mechanisms behind this change, what the Earth uses to remake these rocks, and critically, how geologists read the resulting textures and mineral compositions to decipher their history. We're essentially learning to read the Earth's most dramatic diary.
Okay, so before we get into the agents of change, we have to start with the fundamental definition. Metamorphism is the transition of one rock into another by temperatures and Hedone pressures. Unlike those in which it originally formed. It's a complete overhaul, right? Mineralogical and textural, all happening deep underground.
And that transformation always begins with the original rock. We call this the protolith.
The protolith.
Yeah, the parent rock. Understanding the protolith is not just crucial, it's absolutely foundational for identifying the final metamorphic rock and predicting its characteristics.
The sources really emphasize this, that every single metamorphic rock, no exceptions, has a protolith. It doesn't matter if that starting material was igneous, sedimentary, or even an older metamorphic rock that got recycled back into the pressure cooker for a second round.
Exactly. The composition of that starting material dictates the chemical ingredients available for the final product.
It's like cooking, right?
That's a perfect analogy. If you start with chicken, a specific chemical cocktail, the final meal will always contain those base elements, whether you end up with a stir fry or a curry. So if your protolith is a chemically simple rock, like pure quartz sandstone, you can pretty much only make one thing.
Which is quartzite.
Quartzite. But if it's a chemically complex shale, then the possibilities, the resulting minerals you can form are much, much more varied.
That makes perfect sense. So it's a closed chemical system that's just undergoing immense physical stress. But speaking of that stress, there's one rule, one major constraint that makes this entire field distinct from, say, the study of igneous rocks.
And this is the big one. It's the non-negotiable constraint. The rock must remain solid during metamorphism.
All time.
The whole time. If that rock melts even a little bit, we cross a critical threshold. Once melting happens, we're not talking about metamorphic processes anymore. We've entered the realm of igneous rock formation. The entire transformation has to occur in the solid state.
That feels like the hardest part of the definition to really visualize.
Right.
And we're not talking about melting a crayon. We're talking about changing one crystal structure into a completely different, denser, more stable structure, like changing graphite into a diamondol while the material stays rigidly solid. It's atomic level restructuring under extreme duress.
It is intensely challenging to visualize, but it's essential. Think about the difference between casting a metal object and forging one. Casting involves melting the metal completely and pouring it into a mold. That's analogous to igneous processes. Forging, on the other hand, involves hammering and heating the solid metal to reorganize its crystal structure, changing its shape and strength without ever making it liquid. Metamorphism is the Earth's version of geological forging.
And this solid state boundary, it must get pretty complicated when we look at certain rocks, like you mentioned vigmatite earlier.
Yes. Migmatite is where this whole constraint gets tested. It's often described as a composite rock because it contains both igneous and metamorphic components. It really illustrates the absolute limit of solid state transformation.
So what happened there?
What happened is that the rock got so intensely heated that some of its lower melting point components, usually the silica and feldspar, they actually began to melt. But the higher melting point stuff, like the dark ferromagnesian minerals, they didn't. So what you get are these swirled bands of crystallized melt mixed in with solid metamorphic rock.
Wow. So it's literally a rock caught in the act of starting to melt. It has a foot on both sides of that geological line. That's a fantastic illustration of the extreme conditions we're talking about.
And that level of intensity is exactly what geologists track. The varied results, from something relatively mild like slate all the way to the extreme of migmatite, they showcase a huge range of conditions.
Hmm.
We're essentially charting the intensity, which geologists call metamorphic grades.
Great. Okay.
Yeah, ranging from low, where the alteration is pretty subtle, to high, where the rock has been nearly homogenized.
Speaking of the low end of that spectrum,
Yeah.
where does this process technically begin? We should probably talk about diagenesis.
Right, diagenesis is the crucial precursor. It's not quite metamorphism yet, but it's that early stage where unconsolidated sediment turns into a true sedimentary rock and then undergoes minor changes as it gets buried. Diagenesis happens at the very, very start of the pressure and temperature continuum.
So on a PT diagram, pressure temperature, diagenesis is down the lower left corner, low temp, low pressure.
Correct. We're talking below 200 degrees Celsius in the shallow crust. It involves processes like compaction, cementation, minor mineral changes, but the rock is still fundamentally sedimentary. Once you get above, say, 200 degrees C and the pressures climb, that's when the significant chemical restructuring begins. That's when we cross the boundary into true low-grade metamorphism, where a shale becomes a slate.
So diagenesis is just the first gentle step on the road to deep burial and a full transformation.
Exactly. It's the start of the journey. Metamorphism is the serious overhaul.
Okay, let's unpack the toolkit then. If we're using immense pressure and heat to fundamentally rebuild a rock, what are the primary levers the Earth actually pulls? It seems to come down to a trio of agents: heat, pressure, and fluids.
That's the entire geological toolkit right there. And understanding how those three heat, pressure, and chemically active fluids interact and combine dictates everything about the final rock.
Let's start with the big one. The source material calls it the most important agent: heat. Why is heat so dominant?
Heat is the energy source. It provides the thermal energy you need to break the existing bonds holding the original mineral structure together. Once those bonds are broken, the ions within the rock are free to migrate short distances and reorganize themselves into new, more stable mineral structures that are better suited for the new conditions.
So without enough heat, the process just stalls out.
Pretty much. And the sources of that heat can tell us a lot about the scale of the event. The first source is very localized.
Contact metamorphism.
Right, contact metamorphism.
Mhm.
This is heat supplied simply by being close to a magma body, an igneous intrusion. When a big blob of magma pushes up into cooler rock, the heat just radiates out, causing alteration. It's a very localized thermal event.
The analogy that comes to mind is like putting a thick steak next to a searing hot plate. Only the surface closest to the heat gets really cooked.
Precisely. And this type of heating event is typically pretty short-lived on a geological timescale. It affects a relatively small volume of rock, maybe just a few meters or at most a few kilometers around the magma.
And the second source of heat is much broader, tied simply to the geometry of the Earth itself.
That's the geothermal gradient. This is the natural, inescapable increase in temperature with depth. On average, the temperature rises about 25 to 30 degrees Celsius for every kilometer you go down.
So you just bury a rock deep enough and it gets hotter. No magma required.
No magma required. It's simply descending into the hotter inner zones of the crust because of overlying sediments or tectonic forces stacking rock on top of it.
Okay, so we have the energy from either a local oven, the magma, or deep burial. But heat alone only changes the composition. It doesn't necessarily change the structure in a specific direction. And that's where the second agent, pressure, comes in. And as the sources point out, pressure is rarely uniform.
This distinction is maybe the most important concept for reading metamorphic textures. It dictates whether the final rock will be layered and flat or just massive. And we have two fundamental types of pressure or stress.
The first one is confining pressure.
Confining pressure is the simplest one. It's just the weight of all the material above it. It applies force equally in all directions, like being squeezed from all sides if you're deep under the ocean or under thick layers of rock. The rock just sort of collapses inward a bit and becomes denser.
And if a rock is only subjected to that kind of equal pressure, what happens to the minerals inside? Do they line up?
No, they don't. Since the pressure is equal from all directions, the new crystals tend to grow in an equidimensional way, forming that massive, non-foliated texture. Think of a ball of clay being uniformly compressed into a smaller, denser ball. All the points on it are equally affected.
But this is where it gets really compelling. When tectonic forces are at play, when continents collide or plates grind past each other, the pressure is immense, but it's also directional. And that's differential stress.
Differential stress is unequal stress in different directions. Imagine the rock is being put in a massive tectonic vise, squeezing it way harder from the sides, that's the compressive stress, than from the top and bottom. This directional squeeze is the signature of mountain building.
So how does that directional force actually translate into a visible texture? What's the mechanism that creates what you call foliation?
Well, there are two main mechanics at work under differential stress, and they both help create that layering. First, there's rotation.
Rotation.
Yeah, any platy minerals that are already in the protolith, like tiny clay flakes or mica, they will physically rotate so their flat surfaces are perpendicular to the maximum stress. They line up like books on a shelf that you're pushing from the side.
Ah, they're seeking the path of least resistance.
Exactly. But the second and more powerful mechanism is recrystallization and neocrystallization. As the old mineral bonds break because of the heat, the new minerals that form, especially the platy ones like mica, they actually grow preferentially in the direction that's perpendicular to the maximum stress. The pressure literally forces the mineral growth into parallel alignment. And that organized structure, that's what we call foliation.
That clarifies it perfectly. So heat dictates if the ions can move, and differential stress dictates where they end up settling. Now, let's bring in the third agent, which apparently accelerates the whole process: chemically active fluids.
What's fascinating here is how simple substances, mainly water, but also things like carbon dioxide, they go from being just ingredients to being profound facilitators or catalysts. These fluids are often trapped in the rock's pores or they're released from hydrous minerals as they heat up.
So how do these fluids enhance the change? Are they acting like some kind of lubricant?
They're much more active than just a lubricant. They are the medium through which ions get transported.
Yeah.
Water, especially hot water under a lot of pressure, is an incredible solvent. It dissolves ions from one mineral surface, carries them through the fluid-filled pores, and then allows them to precipitate and integrate into a new mineral structure somewhere else in the rock.
So the fluids make the necessary chemical transformation, the migration of ions and the recrystallization, much faster and more complete than if the rock were just bone dry.
Oh, absolutely. The presence of these fluids promotes recrystallization and allows for large-scale ion exchange. This can even introduce or remove chemicals entirely, a process called metasomatism. But usually the fluids just enhance the local ionic movement to rebuild the existing rock. Without them, the whole process would be agonizingly slow, if not impossible at some of the temperatures we see.
Okay, so to summarize, we have heat providing the energy, pressure providing the directional force, and fluids acting as the solvent and facilitator for the chemical transfer. The interplay of these three agents determines everything.
And that's why we see such varied results. I mean, consider the difference between a simple hornfels, which is from high heat and just confining pressure, it's baked and dense, versus a schist, which is the product of immense differential stress and heat, causing all the micas to align perfectly. Same toolkit, but a different mix changes the result entirely.
We have the ingredients, the three agents. Now let's look at the two major geological kitchens where these transformations happen, the two primary paths to metamorphism. I gather we differentiate these mainly by how the heat and pressure are applied across the landscape.
That's right. Path A is contact metamorphism. We touched on this already. It's alteration caused primarily by heat from a nearby igneous body, and importantly, without significant regional differential stress. It's localized and thermal.
Right. And because the pressure in contact metamorphism is generally just that confining pressure from the overlying rock squeezing equally from all sides, not the tectonic vise, the resulting textures are almost always non-foliated, correct?
That is the defining textural signature, yes. The primary result here is intense recrystallization. The existing mineral grains grow larger, they fuse together, but they don't align directionally. This leads to textures that are often granoblastic,
Granoblasts?
meaning the crystals are visible, equidimensional, and randomly oriented. Or sometimes hornfelsic, where the rock is very fine-grained, compact, and extremely tough.
And the key geographical feature of this localized heating event is something called the metamorphic aureole. This sounds like a crucial term.
The aureole is essentially the halo of altered rock that surrounds the igneous body. It's an incredibly important zone for geologists because it gives us a direct, measurable gradient of metamorphic intensity. The degree of metamorphism systematically decreases as you move farther away from that hot igneous intrusion.
So if you're mapping an area, you might find the rock right next to the magma is intensely fused. Maybe it has high temperature minerals. But then a kilometer away, the rock is just lightly baked shale.
Exactly. The Oriole tells a very clean story of heat diffusion. Since the heat source is localized, the max temperature is right at the contact and it drops off quickly. This means contact metamorphism affects area, not really volume. It's a narrow zone of transformation.
And when we look at the results, the examples are often those incredibly sturdy, non-foliated rocks. We mentioned quartzite.
Quartzite is the prime example. It forms from the metamorphism of quartz-rich sandstone. And it's non-foliated simply because its protolith, quartz sand, is made of mineral grains that are already roughly equidimensional. Quartz doesn't have a platy shape, so even if you squeeze it, it doesn't really align. The process is just one of fusion, where the original quartz grains are entirely fused together.
And that fusion is what makes it so durable.
It is. It resists weathering extremely well. And another non-foliated powerhouse is marble.
Marble, which comes from limestone or dolostone.
Right, so its primary minerals are calcite or dolomite, and like quartz, calcite tends to form equidimensional crystals. So the resulting rock is non-foliated, characterized by a coarse crystalline structure. Its purity makes it famous for decorative uses, of course, but its chemical composition means it reacts very poorly with acid rain.
Now let's switch to the big kitchen, path B, regional metamorphism. This is where the Earth operates on a vast, continental, and frankly terrifying scale.
Regional metamorphism, which is also known as dinothermal metamorphism.
Dinothermal.
Yeah, a term that perfectly captures the dynamic force, the movement, and the thermal energy, the heat. It's the application of both intense heat and immense directed pressure over incredibly large areas. This whole process is driven by the grand forces of plate tectonics.
And when we say plate tectonics, we're mostly talking about subduction zones and continental collision zones, where mountain ranges like the Himalayas or the Appalachians are built.
Yes. When continental masses collide, the crust is shortened, thickened, and buried to incredible depths. Rocks that might have been at the surface are plunged miles down, and they're simultaneously subjected to the high temperatures of the geothermal gradient and the massive directional differential stress of the colliding plates. This can affect rock volumes covering thousands of square kilometers.
And the signature result of regional metamorphism, unlike contact, is almost always foliated rocks.
That is the critical differentiator. Because regional metamorphism involves massive directed pressure, that differential stress we defined, it physically forces platy minerals to align. And that alignment creates the pervasive layering or banding that defines foliation. It's the undeniable physical evidence that the rock was squeezed by a tectonic collision.
So that structural alignment is the immediate visual evidence that the rock wasn't just baked, it was intensely and directionally sculpted.
And if you connect this to the bigger picture, the degree and the type of foliation tell us the entire story of the stress the rock endured. The two major categories of metamorphic rocks are really defined by this structural difference: foliated versus non-foliated.
Let's just nail down those definitions one more time. So foliated is that planar arrangement of mineral grains, the layering that results directly from that directed pressure.
While non-foliated rocks lack any of that pervasive layering or banding, they develop either in thermal-only environments, like contact metamorphism, or when the protolith was made of minerals like quartz or calcite that simply can't be forced into a platy alignment.
If we look at the foliated rocks, they don't just appear layered. They actually show a specific, measurable progression of textures that correlates directly to the intensity of the metamorphism they endured. So a geologist can look at a handful of these rocks and essentially tell a story over time.
That structural progression is the beautiful roadmap of regional metamorphism. It allows us to chart a rock's journey from a humble protolith like shale all the way up through the maximum stress and temperature it experienced deep in a mountain belt.
Okay, so let's detail that physical texture progression. We start with the alignment of really fine grains, which gives us phylitic texture.
Phylitic texture indicates a moderate metamorphic grade. This is where we see the growth and alignment of very fine-grained white mica. These tiny mica flakes start to align, and while the individual crystals are often too small to see with the naked eye, the sheer density of their alignment gives the rock a very distinct, almost satin-like or glossy sheen.
It's that first hint of transformation where the rock stops looking like a dull sedimentary rock and starts looking like something chemically rearranged.
Exactly. Now, as the heat and pressure continue to rise, those mica grains grow larger, they become more prominent, and that leads to the next texture, cystosity.
Cystosity. It sounds like a more advanced version of phylitic texture.
It is. Cystosity is the definitive alignment of larger platy minerals, specifically the easily visible micas like biotite or muscovite. This texture is indicative of significantly higher grade metamorphism, generally above 400 degrees Celsius. The platy minerals are now coarse enough to be visible, and they dominate the rock's structure, giving it that characteristic shimmering, often wavy appearance.
And if we just pause for a second and go back to the non-foliated rocks, the granoblastic texture represents the complete lack of this directional story.
Granoblastic texture, again, is simply characterized by visible, equidimensional crystals with random orientations. It's the physical proof that directional stress was either absent, like in contact metamorphism, or the minerals just resisted alignment. But remember, a granoblastic rock and a highly foliated rock can represent the same grade of intensity, just under different stress conditions.
Which brings us to the core concept of metamorphic grades. We've used the term low, moderate, high. How do geologists precisely measure and define this intensity?
The grade is the intensity of metamorphism, a formal measurement ranging from low to high, based purely on the temperature and pressure conditions the rock experienced. Defining the grade is the primary way we interpret the rock's entire burial and tectonic history.
And the most powerful tool geologists have for quantifying this in the field is the observation of index minerals.
Index minerals are the specific chemical fingerprints that reveal the grade of metamorphism. They're incredibly powerful because they only form and are stable within very specific, well-known temperature and pressure windows. Their presence tells a geologist exactly what the conditions were, often miles below the surface, even though that rock is now sitting right in front of you.
Can you give us a few examples from the sources, these geological thermometers and barometers?
The trio of aluminum silicates, kyanite, sillimanite, and a mineral often associated with them, garnet, are some of the most important. Now, kyanite and sillimanite have the exact same chemical composition, but they possess entirely different crystal structures. They're polymorphs.
So the difference between kyanite and sillimanite isn't chemistry, it's the PT environment that allowed them to physically form their unique crystal structure. Same recipe, different cake.
Precisely. For instance, kyanite is a low-temperature, high-pressure mineral. Finding it tells a geologist that the rock was probably buried very deep, very rapidly, but didn't get excessively hot, which is common in some subduction zones. Conversely, sillimanite forms only under conditions of extremely high temperature and relatively moderate pressure, often deep within the core of a massive mountain belt.
And the presence of garnet is often a pretty dramatic indicator of intense conditions.
Oh, absolutely. Garnet, especially those large red crystals you see in a rock like schist, instantly tells you the rock was subjected to significantly higher temperatures and pressures than a simple piece of slate. Garnet requires very specific conditions of heat and pressure to force its dense, equant crystal structure to form. A geologist can actually map out the transition from a low-grade zone, where garnet is absent, to a high-grade zone where it appears.
So if you pick up a piece of schist and you see that large ruby-red garnet crystal embedded in it, you're literally holding a preserved snapshot of extreme geological history, a measurement of conditions that occurred 10 miles beneath the crust.
That rock is essentially reporting its maximum stress exposure, and that ability to read index minerals and map the transition between grades is the entire foundation of structural geology. We are using chemical evidence to reconstruct tectonic plate movement.
That brings us to the visual gallery. What did this progression actually look like in the field? Let's run through the common sequence in the foliated family, moving from low to high grade. This gives us the clearest timeline of progressive change.
This sequence, from slate to gneiss, is the textbook example of increasing metamorphic intensity under differential stress.
Okay, we start at the bottom of the ladder, right after diagenesis, with slate.
Slate is the result of low-grade metamorphism, generally below 300 degrees C. It's very fine-grained, and it's typically generated from the transformation of shale, mudstone, or siltstone. Its most important characteristic is its excellent rock cleavage.
And that cleavage is a really unique property. It's what makes it so useful.
It is. The fine mica flakes are aligned so perfectly that the rock splits cleanly into these thin, flat, durable slabs, and it splits independent of the original sedimentary bedding planes. That property made it invaluable for roofing, floor tiles, blackboards. It's an economically significant product of a low-grade event.
Next up, as the pressure and heat increase a bit, the mica grains grow. And that leads us to phyllite, the transition rock.
Phyllite represents the gradation between slate and schist. The mica grains are visibly larger than in slate, but still too small to easily identify individually. And this grain growth is what gives the rock its defining feature. A highly characteristic glossy sheen, almost like polished silk, and sometimes wavy surfaces. It still has strong cleavage, but the texture is visibly more complex and reflective than slate.
So if slate is matte, phyllite is shiny. A clear physical step up in intensity. And moving higher in grade, we arrive at schist.
Schist is where the platy minerals really come into their own. It's medium to coarse-grained, and the rock is defined by that schistosity texture. This represents significant metamorphic change, usually requiring temperatures above 400 degrees C. The platy minerals predominate and are visible to the naked eye.
And this is where the naming conventions get specific, tied directly to those index minerals we talked about.
Precisely. Geologists will include the predominant minerals in the rock's name. So if it's rich in mica, it's a mica schist. If those intense conditions forced the growth of specific high-grade indicators, it becomes a garnet mica schist or a staurolite schist. The structure is just highly defined by the alignment of these large, shiny mineral flakes.
And finally, the highest grade of foliation before the rock gets close to that melting point, that threshold of bigmatite, is gneiss.
Nice, and it's pronounced nice, which is helpful.
Oh, right.
It's the result of the highest grade metamorphism. It is medium to coarse-grained, but its distinguishing feature, what makes it look so dramatic, is its characteristic banded appearance. We call it gneissic banding.
And this banding is more than just alignment, it's actual chemical segregation. The rock has been so thoroughly cooked and squeezed that the minerals have physically separated themselves into distinct layers.
The segregation is astonishing. You'll see this vivid alternation. White or light-colored feldspar-rich layers, which are the felsic minerals, alternating with the dark bands made of ferromagnesian minerals, the mafic components. This separation happens because of ion mobility at high temperatures. It's the ultimate structural and chemical overhaul.
So those four rocks, slate, phyllite, schist, and gneiss, they give us a perfect tactile visual timeline of increasing temperature and differential stress.
But we can't forget the equally important non-foliated side. The results of uniform pressure or chemically simple protoliths. We already touched on the two most common, marble and quartzite.
Let's talk a bit more about marble. From limestone or dolostone, we see it everywhere in architecture.
Marble is a beautiful example of pure recrystallization. The original calcite crystals completely reform into a coarse interlocking crystalline structure. But because its main component is calcium carbonate, it's relatively soft and is chemically reactive. This is why marble statues and monuments get dissolved by acid rain, a chemical property it inherits directly from its protolith.
And our other non-foliated heavy hitter, quartzite, from quartz-rich sandstone.
Quartzite demonstrates the highest degree of chemical stability. The original quartz grains are entirely fused together, often making the resulting rock harder and more durable than the original sandstone. And it's defined by its fracture pattern. Unlike sandstone, which breaks around the cement between the grains, quartzite breaks across the original quartz grains. That shows the complete physical integration of the structure. It is extremely resistant to weathering.
Which is why you often find quartzite forming the peaks of highly eroded mountains.
Exactly.
That brings our rock gallery tour to a close. So we've covered the fundamental definition of change form and that critical solid-state constraint, the three agents of change: heat, pressure, fluids, and the two major paths, contact and regional. And we've mapped the progression from low-grade slate up to high-grade gneiss.
And we identified the critical, subtle tools geologists use: the index minerals, kyanite, sillimanite, garnet, which act as these precise barometers and thermometers, allowing us to accurately assess the intensity, the metamorphic grade of that transformation.
The complexity required to decipher a metamorphic rock is just astounding, and this really raises an important question.
It does. I mean, the entire field of metamorphic geology relies on reading incredibly subtle clues: a specific index mineral, that faint glossy sheen on a piece of phyllite, or how the light and dark bands have separated in a sample of gneiss. These rocks are proof that the Earth, which we assume is static in our short lifetimes, is constantly being recycled, rebuilt, and recorded under forces that are just beyond our easy comprehension.
And specifically, the forces required for regional or dinothermal metamorphism are just breathtaking. We're not talking about small localized changes. We're talking about conditions covering vast areas, driven by the massive collision of tectonic plates. Mountain building events that bury rocks miles deep.
That scale is the profound takeaway here. Regional metamorphism is the direct, physical, and chemical record of continental drift and collision. Every mountain range we see today has a core of these intensely altered rocks.
And that leads to our final provocative thought for you, the listener, to consider as you wrap up this deep dive.
Consider the sheer volume and the immense timescale required for this to happen. If you stumble upon a sliver of garnet mica schist exposed on the surface of the Earth, what is the story it's telling you? It's telling you about a history of burial that had to occur maybe 10, 15, even 20 miles beneath our feet, where temperatures exceeded 600 degrees Celsius and pressures were enormous high enough to chemically force the formation of those dense garnet crystals.
That little sliver of schist is not just a rock. It's a solid, enduring witness of continental collision and a measure of the deepest, most extreme stresses our planet has ever endured.
That's the depth of story contained in every metamorphic rock you find. Thank you for joining us for this deep dive into Earth's pressure cooker.
We'll see you next time. Okay, so let's unpack this.
Yeah, let's dive in.
We are about to start a deep dive into, the history of our entire planet.
And it's a history so vast,
Hmm.
it really does reshape how you see everything.
Your whole perception of reality.
Yeah.
Right? This history, it wasn't written down by people.
No, not at all. It was written in rock, layer by painful layer over just staggering amounts of time.
So if you want to understand how mountains get built, or how oceans come and go, or how life itself evolved,
You have to learn the language of deep time first.
and that language, it's complex.
It is. I think the challenge for any geologist is that this history book, it's got pages missing.
Mm.
The chapters are all out of order because of erosion and tilting and, well, magma getting in the way. And it definitely didn't come with dates stamped on it.
So that's genuine detective work.
Intense detective work.
Absolutely.
Yeah.
So our mission today,
Foundational principles.
the principles that geologists use to read this incredible, messy timeline. We're figuring out how they turn these jumbled stacks of rock into a story that makes sense.
A coherent narrative of billions of years.
We're decoding geologic time. And today we're really focusing on the principles of relative geologic time.
It's the ultimate sequencing problem. And before we even get into the rules, we have to grapple with the scale.
Yeah, the scale is mind-bending.
Our human perspective, based on a few decades or maybe a century if we're lucky, it's just
Useless.
fundamentally useless for Earth history. Yeah.
So we need new words, a new vocabulary to even talk about this. What are the units geologists use?
Right. You can't talk about it in just years.
Yeah.
So geologists rely on some very specific units to communicate this overwhelming scale.
Okay.
You'll hear us use kill years, or Ka. That's pretty straightforward. It's thousands of years.
Right.
But we move past that very quickly. The most common unit you'll see is the megayear, or Ma.
Which is millions of years.
Millions of years, and that's the unit we use to describe the time between, say, major rock formations or big shifts in life on Earth.
And then there's the big one.
The big one. For the really deep history, the formation of the planet, the first crust, the earliest signs of life, we use biggie years, or Ge.
Billions of years.
Billions. And when you start talking in billions, it changes everything. I mean, think about this. The oldest known rock minerals on Earth are about 4.4.
0.4 billion years old.
And we, as humans, we perceive maybe a few decades as a long time. A geologist has to operate on a scale where entire continents moving across the globe is just a slow background hum.
Not some sudden dramatic event.
Exactly. And that transition from our fleeting human time to this immense deep time, well, that was the first great philosophical hurdle that modern geology had to get over.
Right. So to even start doing the science, you first had to win a philosophical argument.
You really did. To understand modern geology, you have to go back to this battleground of ideas. For
Right.
centuries, people would look at a mountain range or a canyon a mile deep,
And they had to wonder, how did this get here?
and they were constrained by a very specific worldview, a very short timeline.
And that initial dominant theory, the one that sort of fit a timeline of a few thousand years, was catastrophism.
Catastrophism was the belief, and it was widely accepted in the 17th, 18th centuries, that Earth's landscapes were shaped by sudden, short-lived, violent, often worldwide events.
So if you needed to explain the Grand Canyon,
You'd say a single catastrophic flood did it if you needed to explain the Alps.
a huge instantaneous earthquake that pushed them up all at once.
Exactly. It's the geological version of, if I can't see it happen slowly, it must have happened instantly.
And this idea was completely tied to trying to make Earth's history fit a a scriptural timeline, right?
Yeah.
One that only allowed for a few thousand years.
That's the key historical detail. It's often anchored to Archbishop James Ussher back in the mid-1600s.
Right, he's the one who did the calculation.
He did. Based on a genealogical study of the Bible, he famously calculated that the Earth was formed on a very specific day. Sunday, October 23rd, 4004 BC.
And if your whole timeline is only 6,000 years.
Then catastrophism is the only explanation that works. There's just not enough time for slow processes to do anything. You need those planet-altering, violent events.
But there was another idea bubbling up.
There was. Waiting in the wings, kind of gaining ground as observational science got better, was the counterpoint. Gradualism.
Yeah, what was that?
It was the idea, championed by thinkers like Comte de Buffon, that maybe these changes were happening slowly, incrementally, over vast, maybe even unimaginable amounts of time.
So slow you wouldn't notice them in a single lifetime.
Exactly. And that idea, gradualism, it eventually grew up and matured into the revolutionary concept that is the cornerstone of all modern geology.
Uniformitarianism.
That's it. Uniformitarianism is the prevailing concept today. It's defined by the statement that the physical, chemical, and biological laws that operate on Earth right now are the same laws that operated in the deep past. And crucially, the rates of change, they might vary, but they're constrained by these unchanging natural laws.
And that shift in thinking provided the real philosophical shockwave, didn't it? It wasn't just what happened, but the realization that it needed an almost infinite amount of time.
That's the profound implication. Uniformitarianism basically gives geologists an infinite time budget.
Right. Yeah.
If a mountain range erodes 1 centimeter every 1,000 years and it's 10 kilometers high, well, you do the math. You need 1 billion years. Uniformitarianism says, you've got it. It suggests this fundamental continuity in the laws of nature.
Which gives us that incredibly powerful motto that you hear all the time in geology.
The present is the key to the past.
Let's clarify that, though. Because it doesn't mean that everything always happened at the same speed, does it?
No, absolutely not. That's a huge misunderstanding. Uniformitarianism does not deny catastrophes.
It just frames them differently.
Exactly. It integrates them into natural processes. A huge volcanic eruption, a massive flood, an asteroid impact. Those are natural processes that happen today, even if they're rare. The principle just means that the physical laws governing those events, the melting point of rock, the law of gravity, the physics of how water erodes things, were the same 1 billion years ago as they are right now.
So if we watch how a river deposits silt today, we can use that knowledge to understand an ancient mudstone.
Perfect example. If we see how magma bakes the rock around it today, we know what to look for in an ancient igneous intrusion.
And this big idea, it didn't just appear overnight.
No, it took decades. It was most famously proposed by James Hutton in his theory of the Earth in the late 1700s, and then Charles Lyell really popularized it later. Hutton essentially gave geologists permission to stop looking for, divine intervention.
And start looking at observable, repeatable, natural law.
And extending those laws backward in time. Billions of years.
And the implications are they're staggering. Because those laws are consistent, we can actually trust our interpretation of ancient rocks. It turns geology from speculation into a real science.
So if uniformitarianism is the philosophy, the why it all works.
Then the 7 principles of relative dating are the core rulebook. This is the how, the instruction manual for the detective work itself.
Right. And let's be clear about the goal here. With relative age dating, we are not trying to get a number like 250 million years.
Well, not yet anyway.
Not yet. We are just determining the sequence of events. The goal is simple, but often really hard to do. Which rock came first? What cut through it later? What was the order of everything?
It's like a cold case file.
Yeah.
You're just trying to reconstruct the timeline of events using only the physical evidence that's left behind.
Exactly. So let's get into these 7 rules.
Let's do it, starting with the most fundamental one.
Principle 1, superposition. This rule is the absolute bedrock, pardon the pun. It goes back to Nicholas Steno in 1669.
And it's deceptively simple.
It is. In any undeformed sequence of sedimentary layers, the oldest layers are at the bottom and the youngest ones are at the top.
It's just the principle of stacking things. If I put a book on a table and then another book on top of it, the first book was there first.
Yeah. That's all it is. Gravity at work. But, and this is where the detective work starts, we said, in any undeformed sequence.
Right. What if huge tectonic forces have flipped the entire stack of rocks upside down?
Which happens Near major fault zones, it absolutely happens.
So how does a geologist know?
You need other clues. You look for things like graded bedding, where the sediment particles get finer toward the top of a layer, or you look for fossilized ripple marks. Their shape can tell you which way was up when they formed.
So the principle is always true, but you have to prove the rock hasn't been messed with.
Precisely. Which leads us to principle 2, original horizontality.
This one also feels pretty intuitive. It's about the physics of how sediments settle.
Right. Layers of sediment, sand, mud, silt, they're originally deposited in a horizontal, or at least nearly horizontal position. Gravity pulls the particles down and they spread out flat.
So if you're hiking in the mountains
Mm-hmm.
and you see a cliff face where the rock layers are tilted at a 45-degree angle or even folded up like an accordion,
What does that tell you? It tells you that tilting and folding event happened after the layers were deposited and turned into rock.
they didn't form that way.
They didn't form looking like a giant wavy blanket. They were laid down flat, and then they were squeezed or broken by some tectonic force long after they solidified.
And flat layers mean they haven't been disturbed.
For the most part, yeah. That simple observation lets you sequence 2 huge events. Deposition happened first, deformation happened second.
Okay, that builds nicely into the next one. Principle 3, original lateral continuity.
This is a really powerful one for mapping large areas. The rule is that layers of sediment initially extend sideways, laterally, in all directions,
Until they run into something.
until they either thin out naturally, like at the edge of a basin, or they hit a physical barrier, like an ancient shoreline.
So they don't just stop abruptly in the middle of nowhere.
No, and the implication is critical. Think about the Grand Canyon. You stand on one rim, and you can see the exact same layers of rock on the other side, miles away. This principle tells you those layers were once continuous all the way across before the Colorado River started carving its way down through them.
That's the license a geologist uses to connect the dots between distant outcrops.
It is. So those first 3 are about how rocks are laid down. The next few are about what happens to them after they form.
The disruption rules.
The disruption rules. And this is where it gets really specific. Let's talk about principle 4, cross-cutting relationships.
This might be one of the most useful tools in the whole kit.
I'd agree. The rule is simple. If a geological feature cuts through another one, the feature that has been cut is older.
You have to have something
Wow.
there before you can break it.
Exactly. So let's run a scenario. You have 3 flat layers of sedimentary rock. We'll call them A, B, and C, with A on the bottom.
Okay.
Then a fault. A big crack slices through all 3 of them and shifts them. Which is younger, the rocks, or the fault?
The fault has to be younger. It had to cut through something that was already there.
It had to cut through A, B, and C after they were all deposited and solid. What if a vein of magma, a dike, pushes its way up through them?
Same logic. The dike is younger. It's the cross-cutting feature.
This applies to everything. An igneous intrusion is younger than what it intrudes into. An erosion surface is younger than the rock it's eroding. It's an undeniable sequence of events.
And this leads to a related idea, which is principle 5, inclusions.
Inclusions. It's a similar logic to cross-cutting, but instead of breaking something, you're incorporating pieces of it.
So the rule is what?
The rule is fragments of one rock unit, the inclusions that are enclosed inside another rock unit, must be older than the host rock that contains them.
Let's break that down. The little piece of rock, the inclusion, had to exist first as a solid chunk.
Right.
Before the stuff around it, whether it's lava or mud, could surround it and harden.
Exactly. Imagine a big body of granite forms deep underground. Millions of years go by, it gets pushed up to the surface and it starts to erode. Little bits of that granite break off. Those bits get washed into a river and deposited in a new layer of sand, which eventually turns into sandstone. Those granite pebbles in the sandstone
Are older than the sandstone itself.
They had to be. This is huge for dating massive rock bodies.
And it works hand in hand with the next principle, right?
It does. Principle 6, baked contacts. This one uses heat as the clue.
So we're talking about igneous intrusions again. Magma.
We are. When a body of hot magma pushes its way into older surrounding rock, that intense heat literally bakes the rock it touches. It causes contact metamorphism.
So the rule is that the igneous intrusion, the thing that did the baking, has to be younger than the rock that got baked.
The heat source had to come later. If you see that baked zone, that metamorphic halo, you have proof that the intrusion is younger.
But the absence of a baked zone is also a clue.
A huge clue. Let's say you find a layer of sandstone sitting on top of a body of granite. If the bottom of that sandstone shows no signs of being heated or baked,
That means the granite was already there, and it was cold and solid at the surface before the sand was ever deposited on top of it.
Which points to a massive time gap between the two. It's a key piece of evidence for a major unconformity, which we'll get to.
That's amazing. Using all these principles together is how you build the full story.
It is. And that brings us to the final seventh principle, which is a bridge to everything else. It's the principle of faunal succession.
This is where biology enters the picture and becomes the ultimate clock.
It really is. The rule is that fossil organisms succeed one another through time in a definite, recognizable, and non-repeating order.
And that concept is so important. It's really its own whole field of study.
It is, but it's still one of the 7 fundamental rules for sequencing rocks. Unlike rock types, you can have sandstone, then shale, then sandstone again. Life evolves and goes extinct.
Doesn't repeat.
It's irreversible. And that gives geology the arrow of time it desperately needs.
Okay, so we've laid out the rules for reading a perfect rock record, a complete story.
Right, the ideal scenario.
Superposition, horizontality, cross-cutting, all of that lets you build a local timeline. But you mentioned earlier that the Earth's history is rarely complete.
It's almost never complete. The record is full of interruptions, periods of uplift, long stretches of erosion, times when nothing was being deposited at all.
And that brings us to the missing pages, the unconformities.
Unconformities. This is one of the most challenging but also most important parts of geology. An unconformity is a major break in the rock record.
It's a gap in time.
A huge gap in time. It represents a period that isn't represented by any rock in that location, either because layers were eroded away or because deposition just stopped for millions, even hundreds of millions of years.
They are literally the missing chapters of this story.
And if you don't spot one, you're in big trouble. You might think a rock layer from 500 million years ago is directly followed by one from 50 million years ago.
And you'd be completely missing 450 million years of history.
Exactly. So geologists classify them into 3 main types, and each one tells a very different story about what was happening with the Earth's crust.
Okay, let's start with the most dramatic one, the one that requires a whole sequence of crazy events. Type A, angular unconformity.
An angular unconformity is a massive structural break. It's visually stunning. You have these older layers that were deposited flat, following original horizontality.
Right.
Then some massive tectonic event squeezed them, tilted them, folded them up. A mountain building event.
So it's deposition, then deformation, 2 big steps.
2 big steps. Then a huge amount of time passes. Those tilted, folded layers get pushed up above sea level and eroded down, planed off almost flat.
Wow, okay.
Then the whole region has to sink back down below sea level, and finally new, younger layers of sediment are deposited horizontally right on top of that eroded, tilted surface.
So you literally see a stack of angled rocks with a stack of flat rocks sitting on top of them. And that angle between them is undeniable proof of that whole sequence. Deposition, uplift, tilting, massive erosion, and then more deposition.
Is there a famous example of this? The classic example is Sycamore Point in Scotland. It's where James Hutton had his big epiphany. He saw that angular break and realized how much time it must have taken.
And that's where he came up with the idea of deep time. No vestige of a beginning, no prospect of an end.
That's the one. That angular unconformity was the physical proof of uniformitarianism.
Okay, so that's the dramatic one. What's the sneakiest one?
The sneakiest one, the master of disguise, is type B disconformity.
Why is it so hard to spot?
Because it occurs between layers of sedimentary rock that are parallel to each other. The whole stack looks perfectly normal, like deposition never stopped.
So everything looks like it's following the rule of superposition perfectly, but there could be a 100 million year gap in there somewhere.
Exactly. So how do you find it?
That's my question. How does a geologist spot that?
You have to look for really subtle clues. You look for evidence of an ancient erosion surface. Things like fossilized soil layers, we call them paleosols. Or you might see little ancient stream channels cut into the top of the lower layer that got filled in by the upper layer.
So you're looking for signs that that lower layer was exposed to the air and weather for a long time.
You are. Ancient rust. Burrows from worms that get chopped off at the boundary. Anything that says this was dry land for a while before the sea came back. The physical evidence tells you the gap is there, even if you don't know for how long.
And that leads to the final type.
Type C, nonconformity.
And this one is a boundary between 2 totally different kinds of rock.
Right. It's a boundary between sedimentary rocks on top and much older igneous or metamorphic rocks below.
So we're talking about rocks that form deep inside the Earth's crust.
Exactly. Granite, gneiss, schist, rocks formed by intense heat and pressure miles underground.
So for them to be at the surface, with sedimentary rock on top,
Yeah.
what has to happen?
A colossal sequence of events. First, the igneous or metamorphic rock has to form deep in the crust. Then, massive tectonic forces have to uplift that rock all the way to the surface.
Okay.
Then, unimaginable amounts of time have to pass while erosion strips away all the miles of rock that were originally on top of it.
And only then, after it's been exposed and weathered, can the sea come in and lay down new sediments on top of it.
Right. A perfect example is near Pikes Peak in the Rockies. You can see younger sedimentary layers resting directly on the ancient Pikes Peak granite. That granite had to cool, be uplifted, be eroded for millions of years, and then get buried again.
That one boundary represents hundreds of millions of years of history.
It's proof of immense vertical movement in the crust, a profound change from deep crustal processes to surface processes.
Okay, so we've covered the geometry of the rocks, the rules of the sequence, but to go from one canyon wall to connecting continents, you need something more.
You need consistent markers, external identifiable markers that you can find all over the world.
And this is where the biological clock comes in. This is where fossils take center stage.
Fossils are the foundation of this global clock. They are, simply put, the traces or remains of prehistoric life preserved in rock. But the fossil record is incredibly biased.
Biased and incomplete. Why is that? What does it take for something to actually become a fossil?
Two key things, and they're both rare. First, you need rapid burial.
You've got to cover it up fast.
Instantly, if possible. If an organism dies and it's just left on the surface, it gets eaten by scavengers, it decays, it falls apart, burial protects it from all that.
And what's the second condition?
You generally need to have hard parts.
Bones, shells, teeth.
Exactly. Or even tough wood. Soft tissues like skin or muscle, they just decay too quickly. They are sometimes preserved, but it's exceptionally rare.
So because of those conditions, we're only seeing a tiny fraction of all the life that's ever existed.
Minuscule fraction.
Okay.
But the fossils we do find, they serve three absolutely critical roles for geologists.
Okay, role number one.
They help us interpret the geologic past. This is about reconstructing ancient environments.
So if you find a fossilized coral,
You instantly know that rock formed in a warm, clear, shallow tropical sea. It doesn't matter if you found it in Antarctica today. That rock was once near the equator. It tells you about past climate, sea level, where the continents were.
okay, role number two.
They are critical time indicators, and this is because evolution is a one-way street.
And role number three.
They allow for the correlation of rocks from different places, and this is where we really get into the power of the principle of faunal succession.
Let's go deeper on that principle. The idea that fossil organisms succeed one another in a definite, determinable order. Why is evolution so important to geology?
It's because of extinction. Life forms evolve, they exist for a while, and then they disappear. Forever.
They never come back.
They never come back. Dinosaurs, for example. Once they went extinct, that was it. So you will never find a T-Rex fossil in the same undisturbed rock layer as a human skeleton.
And that biological fact gives geology a directional arrow of time.
An undeniable, non-repeating arrow that no physical rock property can give you.
So this means that any period of time can be recognized by the specific fossils you find in its rocks.
Precisely. If you find a certain type of trilobite, you know you're looking at a Cambrian rock. You find a specific ammonite, you know it's Mesozoic. We're dating the rock by the life that's in it.
Which makes certain fossils incredibly valuable. And that leads to the idea of index fossils.
The gold standard for relative dating. They're like geological timestamps.
And for a fossil to be a really good index fossil, it has to meet two pretty tough criteria.
They are tough, and they're often contradictory. First, it has to be widespread geographically.
So you can find it everywhere.
You need to be able to find it in North America and in Europe and in Asia. That's what lets you link those continents together and prove those rocks formed at the same time. The best ones are often little marine organisms that floated all over the ancient oceans.
And the second criterion.
It has to be limited to a short span of geologic time.
So it didn't live for very long.
Exactly. If a species was only around for, say, 1,000,000 years, finding it nails the age of that rock down to a very narrow window. That's way better than finding something like a clam that's barely changed in 200 million years.
The shorter its existence, the more precise a timestamp it is.
That's it. And these index fossils are what allow geologists to do correlation of rock layers.
matching up rocks of similar ages from places that are really far apart.
Miles apart, thousands of miles apart. Without fossils, you'd just be trying to match one sandstone to another sandstone, which is impossible because they all look kind of the same.
And we have to give credit to the person who first figured this out systemically.
We do, William Smith.
Yeah.
And what's amazing is that in the late 1700s, he wasn't some famous professor. He was a self-taught surveyor and a canal engineer in England.
That's what I love about this story. He was just a guy doing a job.
He was. He was digging canals, surveying for coal mines, and he needed to predict where certain rock layers would be.
Mm-hmm.
And as he worked his way across the country, he had this breakthrough. He realized he could identify and predict a rock layer not by its color or its texture,
But by the unique set of fossils inside it.
yes, he saw that strata in totally different areas could be identified and correlated by their distinctive fossil content.
So he wasn't just matching a limestone to another limestone. He was matching a limestone with a specific fossil snail in it to a shale layer hundreds of miles away that had the exact same fossil snail.
That's the key. The rock type can change as the local environment changes, but the life forms were evolving globally, marking that single moment in time.
And he used that to create the first real geological map.
He did. He proved that the order of life was the master key to unlocking the global timeline. This is what transforms relative dating from a local puzzle on a cliff face into a globally recognized geologic timescale.
So correlation, then, is what stitches all these little local rock records together.
Using biology as the needle and thread.
And lets you fill in the gaps left by the unconformities.
It does. It gives us that crucial, non-repeating timeline that the physical principles alone couldn't quite guarantee. It allows us to say with confidence, this rock is Devonian no matter where in the world we find it.
This has been an incredibly detailed journey. We've gone through the history, the philosophy, and the practical rules for reading Earth's timeline. You now have the core principles of geological detective work.
We really covered the foundations. We started with the philosophy, with uniformitarianism.
The present is the key to the past.
The idea that gave us the immense time budget we need for any of this to make sense, that was the why.
Then we got into the how, the 7 stratigraphic rules, from the simple stacking of superposition to the tricky logic of cross-cutting relationships and inclusions.
The tools for sequencing local events.
And we tackled the problem of the missing pages, the unconformities.
We did. We learned how to spot those dramatic angular breaks, the profound nonconformities, and those subtle, sneaky disconformities that hide huge gaps in time.
And finally, we saw how the biological record through fossils and faunal succession provides that reliable directional clock.
The clock that allows for global correlation. It's the convergence of physics, chemistry, and biology that makes relative dating so powerful. You now know how to look at a cliff and start putting the story in order.
And this knowledge, it lets you look at the world today with a geologist's eye. Because if we accept that core premise of uniformitarianism,
That the slow, grinding processes that shape the Earth are still operating today.
then it means massive, profound geological changes are happening right now, even if we can't see them on a human timescale.
Continents are colliding as we speak, sea floors are spreading, mountains are being pushed up, and erosion is relentlessly tearing them back down.
All in super slow motion, centimeters per year.
So here's a final provocative thought for you to take away. If these processes, deposition, tilting, uplift, erosion, if they're all ceaseless, what large-scale geologic event might be unfolding right now completely unnoticed by us?
That future geologists, millions of years from now, will only be able to identify as an ancient rock layer or a major unconformity.
Will the slow collision of Africa and Europe eventually build a new mountain range? Will future geologists see the folded rocks at the bottom of the Mediterranean and call it an angular unconformity, marking the end of our current era?
The present is the key to the past, but the present is also the future's past.
It is. Something massive is happening right now, setting the stage for the next billion years of Earth's history. And we are living right on top of it. Welcome back to the Deep Dive. Our mission for you, the learner, is simple: to give you the ultimate shortcut to being well-informed, stripping away the jargon, and jumping straight to the insight. Today, we are undertaking a geological investigation into, well, the most common, yet maybe the most misunderstood, rocks on Earth.
We're diving deep into sedimentary rocks. And it's funny, when people think geology, they picture these huge volcanic explosions or dramatic mountain building.
The flashy stuff.
Exactly, the flashy stuff, the igneous and metamorphic rock. But sedimentary rocks, they're sort of the quiet historians. They are the true hidden archives of our planet. They contain every clue about past life, climate, and geography.
Absolutely. I like to think of them as the compiled index records of Earth's 4.5 billion-year history. We are going to unpack the whole saga, right? The sequential story of how a mountain can turn into a layer of mud, what incredible secrets that mud holds about ancient ecosystems, and why these really unassuming layers are, foundational to our global industry and modern economies.
To start, you really have to appreciate the fundamental paradox of how they form. They are products of destruction that ultimately lead to rebirth. They're formed through the relentless weathering of any pre-existing rock type. It could be igneous, metamorphic, or even older sedimentary rocks that get recycled.
So it's a constant cycle.
A constant cycle. And this broken down material, which we call sediment, is then collected and deposited on or near the Earth's surface.
And it's not an immediate change, right? This isn't something that happens overnight. It's a monumental process that takes millions of years.
Exactly. It's a sequential cycle, and it has 4 key steps. Step 1 is weathering, which is the physical and chemical breakdown of the source rock.
Okay.
Step 2 is transport, so moving the resulting pieces and dissolved ions, usually by, water, wind, or glacial ice. Step 3 is deposition, and that's where the energy of the system drops and the material just settles out. And then step 4, the transformation.
Lithification.
Lithification, that's the magic word. That's the magic process, yeah. It converts that loose pile of sand or mud into a solid, durable rock.
That whole journey from solid bedrock to microscopic dust, and then all the way back to solid rock, that's what makes them the ultimate geological record. So let's start with their global significance.
When we talk about sedimentary rocks, we are really talking about Earth's memory. They serve as the definitive environmental record because they form right at the surface. They preserve evidence of the surface conditions at the time they were deposited. They can tell us about past climates. Was the region a scorching desert?
Right, leaving behind salt flats.
Or was it a humid tropical swamp which would eventually create coal? The rocks tell that story.
And they also track these massive scale geological events like mountain formation.
Oh, absolutely. If you find, say, coarse angular gravel suddenly appearing in a sequence of otherwise fine-grained mudstone, you know something big happened.
A sudden change.
A huge change. It tells you a significant tectonic event. A mountain uplift must have happened nearby. It suddenly changed the supply and the energy of the sediment flow.
It's so crucial for reading geological history. These formations are where we find ancient river channels, fossilized seabeds, the signatures of ice ages.
All the evidence. It's everything you need to reconstruct the planet's dynamic past.
It's kind of hard to grasp their dominance just by thinking about volume because when we look at the crust, we are mostly looking at this family of rock.
And what's really fascinating here is the distribution. Sedimentary rocks cover approximately 75% of Earth's visible rock outcrops.
75%.
They are the dominant surface feature globally.
So, okay, if they cover 3/4 of the visible surface, wouldn't that imply they form the bulk of the crust? You'd think so, right?
And that's the paradox. This is where the context becomes so key. Despite covering so much surface area, they only account for about 5% by volume of Earth's outer 10 miles.
Only 5%. Wow.
So you have to think of them not as the main structure of the Earth, but as this incredibly thin, extensive, and vital veneer. Or like a geological blanket, just draped over the vast, dense, underlying igneous and metamorphic basement rock.
That is a critical distinction. It really underscores that they are fundamentally surface products. They need low pressure and low temperature to form.
Completely unlike rocks that form deep in a magma chamber or under immense tectonic squeezing.
So it also raises an interesting question. If they're only a 5% sliver, does that make them less important geologically?
Not at all. In fact, their thinness tells us something incredibly important about the rate of surface change.
How so?
Well, the fact that the process of weathering, transport, and deposition is constantly accumulating this veneer over billions of years suggests the surface environment is incredibly dynamic. It's constantly recycling material.
While the deep crust remains, relatively static in comparison.
Exactly. So that thin veneer, it holds all the history.
And that history translates directly into practical wealth. Which brings us to what the massive economic implications of this thin layer?
Sedimentary rocks provide a direct, massive link to human economies. They are fundamentally important because they are the ideal environment for capturing and storing essential resources. The most obvious examples are energy sources.
We are talking about the entire global fossil fuel market. This is not a small thing.
Precisely. Fossil fuels such as oil, coal, and natural gas are primarily found in these formations.
Yeah.
They function as both source rocks.
So where the organic material is buried and cooked.
Right. And as reservoir rocks, porous layers like certain sandstones or limestones, they can actually trap and hold the fluid or gas.
So without that unique porosity and permeability, which you find almost exclusively in sedimentary formations?
Accessing that energy would be impossible. It just wouldn't be concentrated in one place.
And it goes far beyond energy. I mean, we use the raw materials for construction and industry every single day.
Oh, absolutely. They are also sources of crucial metals: iron, aluminum, manganese. These are all essential for steel, modern electronics, construction, and they are often concentrated in specific sedimentary formations. These formations develop through processes like, say, deep-sea precipitation or the extensive chemical weathering of entire continents over vast periods of time. This allows these elements to concentrate into economically viable ores.
So they truly are the economic backbone of the modern industrialized world.
Without a doubt.
Okay, so we know these rocks are made from the pieces of older rocks. We have to start with the destruction phase, weathering. You identified two distinct yet often collaborative processes, physical versus chemical.
Yeah, they are the fundamental forces shaping our landscape, and understanding their difference is key. Physical sources, they just break rock into smaller fragments. They increase the surface area.
Right.
Chemical forces, on the other hand, fundamentally change the mineral composition of the rock, which prepares it for the next stage of transport. Mechanical or physical weathering involves forces breaking the source rock into smaller and smaller pieces. The mineralogy remains exactly the same. A quartz grain is still a quartz grain, but the size is dramatically reduced.
Okay, and why is that size reduction so important?
The importance of this is that the reduction in size significantly increases the total surface area available for the second type of weathering to act upon,
The chemical attack.
the chemical attack. You're exposing more and more fresh surface.
So in a way, physical weathering is almost a necessary precondition for the most effective chemical weathering.
It's a huge accelerant.
Yeah. So what are the main physical mechanisms at play here?
Well, aside from the obvious forces like abrasion from wind and running water, we see three really powerful, often kind of hidden mechanisms. One is pressure release, or exfoliation. As massive overlying rock loads are removed by erosion, the deeply buried rock below, which was under extreme pressure, it expands upward and outward.
It's like it's taking a deep breath.
That's a great way to put it. This expansion creates these large, onion, skin-like sheets of rock that fracture off. You see it all the time in granite batholiths.
And then we also have the biological impact, like the power of tree roots.
That's root expansion.
Yeah.
A biological force leveraging a physical mechanism. It's amazing.
Yeah.
Roots grow into these tiny, tiny fractures, and as they expand over time, they exert incredible pressure.
They act like persistent levers.
Exactly. Wedging the rock apart year after year.
And then there's the power of salt, which is surprisingly effective.
Salt crystallization is highly effective, especially in arid coastal or desert environments. Water that contains dissolved salts seeps into the cracks. When the water evaporates, the salt crystals grow.
Okay.
And as those crystals expand within the rock's pore spaces and fractures, they push the mineral grains apart with considerable force, causing the whole thing to just disintegrate.
But the classic, relentless mechanism everyone learns about in school is the freeze-thaw cycle, frost wedging.
And for good reason. Frost wedging is perhaps the most significant physical agent in temperate and high-altitude zones.
Yeah.
Water seeps into cracks, even microscopic ones, and when the temperature drops below freezing,
It expands.
it expands by about 9% in volume. And this expansion generates immense localized pressure. We're talking often exceeding 2,000 pounds per square inch.
That is a staggering amount of pressure delivered over and over again. I can see why this is so effective in carving alpine valleys and, breaking up roadways in northern climates.
It is relentless. It requires frequent temperature fluctuations around the freezing point. That's what maximizes the number of expansion cycles.
So a climate that's permanently frozen or permanently tropical would see less of this.
Much less. It's that daily oscillation across 0 degrees Celsius that does the most damage. This brute force, delivered microscopically and repeatedly, is what slowly transforms solid mountains into piles of jagged talus and gravel.
So that's the physical destruction, just breaking things into smaller bits. Chemical weathering takes a completely different, and you could argue, a more transformative path. This is a fundamental change in the rock's actual identity.
That's right. Chemical weathering is the process where minerals are chemically transformed into one or more new compounds. The mineral composition is fundamentally altered. This means the resulting material behaves differently. It often becomes much softer and more soluble.
So what are the main reaction types that are driving this geological alchemy?
We group them into three major categories. First, you have dissolution, where certain minerals dissolve readily in water, especially if the water is slightly acidic.
Okay.
Second is hydrolysis, which is the reaction between water and silicate minerals, and that's the one that forms clay. And third, oxidation, which involves the loss of electrons. Most people know it as rusting.
Let's focus on hydrolysis for a moment because it's so critical for understanding soil and clay formation. Why is quartz so stable, but something like feldspar is so vulnerable?
That's a great question. Quartz is composed almost entirely of silicon and oxygen, and it has an extremely stable crystalline structure that just resists chemical attack. Feldspars, however, contain aluminum, calcium, sodium, or potassium in addition to the silicon and oxygen.
So more things to react with.
Exactly. So when feldspar reacts with slightly acidic water, and you have to remember, rainwater absorbs carbon dioxide from the atmosphere, making it a mild carbonic acid.
Right.
Hydrogen ions in that water displace these metal ions in the feldspar. This entire chemical transformation leads directly to the formation of clay minerals.
And clay minerals are highly stable.
They're the highly stable end products in the weathering environment, and that's why clay is so abundant everywhere. It's the stable residue of countless ancient feldspar grains being chemically destroyed.
That transition from hard feldspar to soft, pliable clay is the basis of most of our fertile soils. It's incredible. Let's switch to dissolution. You mentioned limestone, which creates some of the most dramatic landscapes on Earth.
The dissolution of limestone, which is made of calcite, or KCO3, is incredibly efficient. It's because calcite reacts so readily with that carbonic acid in rainwater. The reaction removes the calcium carbonate and transports it away, but not as solid particles. It's carried away as dissolved calcium ions and bicarbonate ions.
This raises a profound thought. The rock itself is literally being carried away molecule by molecule in solution.
Exactly. And this leads directly to what we call karst topography. This is that specialized landscape characterized by extensive underground drainage systems, massive caves, and surface features like sinkholes and disappearing streams.
And the rate of this dissolution is higher in certain climates.
Yes, it's often maximized in warm, humid climates where biological activity in the soil adds more carbon dioxide, which in turn creates a stronger acid.
But the implications of karst topography go beyond just scenic caves. I mean, doesn't this geological structure cause major infrastructure problems?
It raises important societal questions, yes. Karst regions are beautiful, but they pose serious engineering challenges. Sinkholes can open up rapidly, right under a road or a building.
And groundwater is an issue too, right?
A huge issue. Groundwater flow in karst areas is very poorly filtered because water moves rapidly through these large conduits, the cave systems, rather than slowly seeping through porous soil. This makes these regions highly vulnerable to groundwater contamination from surface pollutants.
So whether it's a physical fracture from frost or a dissolved ion from hydrolysis, this raises the ultimate question. What happens to all the resulting fragments and dissolved ions?
They become sediment. They are the raw material, now mobilized, ready to be transported by gravity, water, or wind. This marks the end of the breakdown stage and the beginning of the reconstruction stage.
Right.
So we have established the raw material. Sediment is the result of weathering, and it takes two forms. You have the solid particles, like fragments of quartz or newly formed clay.
And then the dissolved stuff.
And the dissolved ions, exactly, such as calcium, sodium, or silica, being carried in solution by water.
And the final step, the process that truly converts that loose, mobile pile of sediment into a stable sedimentary rock, is called lithification. This is where the Earth kind of presses the save button on its history book.
Lithification is the general term for the processes that convert sediments into solid sedimentary rocks. It always involves some combination of the two primary mechanisms, compaction and cementation.
Okay, let's start with compaction.
Compaction is the physical force. It is driven purely by the weight of overlying material, the accumulating layers of mud, water, and eventually more rock on top. This weight compresses the deeper sediments.
How effective is this weight? And is it, universally effective on all sediment types?
It's incredibly effective, especially for fine-grained sediments like mud and clay. Mud, when it's first deposited, may be 60% or even 70% water. It has very high porosity, a lot of empty space. As burial depth increases, the sheer gravitational force squeezes out this interstitial water. The sediment volume can be reduced by 50% or more.
Wow.
and it forces the flat, tiny clay particles to align themselves horizontally and stick closer together.
So compaction alone can turn mud into mudstone or shale.
It can, yeah. However, for coarser sediments like sand and gravel, compaction is much less effective.
Why is that?
Because the grains are rigid, they don't deform easily. You can compress sand a little bit, but the volume reduction is limited. You still have significant pore space left between the grains.
And that's where the second step comes in.
That's why the second step, cementation, is usually necessary, especially for those coarser rocks.
And while compaction is physical squeezing, cementation is the critical chemical step that provides the permanent bond. It's the glue.
It's the glue. Cementation is where the remaining pore spaces between the particles are filled with a chemical precipitate. Water circulating through the buried sediment carries dissolved mineral matter, often silica, calcite, or iron oxide. As conditions change, maybe the temperature increases or the pressure shifts or the water chemistry is altered, these dissolved minerals precipitate out of the solution.
They are essentially acting like a geological mortar or, like you said, a superglue, locking the grains together permanently.
Precisely. For instance, quartz grains in a sandstone are very often cemented by calcite, which chemically locks those grains together, and this dramatically reduces the porosity and increases the rock's overall rigidity and strength.
So the presence, type, and even amount of cement are major factors.
A huge factor in determining a sedimentary rock's durability and its economic utility, for instance, how well it might hold oil or gas.
Once that process is complete, we classify the resulting rock based on its texture and origin. How do we differentiate these large families?
The defining characteristic is texture. And we use two major textures, and they are clues about the entire formation history of the rock. The first is the clastic texture, which is defined by discrete fragments or particles clasts that are cemented together. If you see fragments, physical weathering and transport were the dominant processes.
Okay, so clastic means fragments, and the second texture.
That's the non-clastic or crystalline texture. Here, the rock consists of a pattern of interlocking crystals. It looks a lot like an igneous rock, but it formed at the surface.
Okay.
This texture is the hallmark of rocks formed by chemical precipitation, like rock salt or some limestones. That distinction, fragments requiring transport versus crystals requiring chemical saturation, is the fundamental pivot point for the entire classification system.
So moving from the microscopic to the macroscopic, let's explore the family tree. This is where it gets really interesting, because we use the ingredients and the formation process to sort them into three major groups: detrital, chemical, and organic.
Right. The detrital, or clastic rocks, are formed from sediment transported as solid particles. They're the fragmented rocks, the piles of gravel, sand, and mud that were physically broken down. They have that clastic texture we just defined.
What are the primary mineral constituents that typically survive this long, destructive journey? What's left at the end?
The chief constituents are those minerals with really high durability. Quartz is number one. It's both physically tough and chemically stable.
Okay.
We also find abundant clay minerals, which, as we discussed, are the chemically stable end products of feldspar weathering.
What about less common stuff?
You might find remaining grains of feldspar and micas, but their presence usually indicates that the source rock was relatively close, or that the weathering process was incomplete. They didn't have time to fully break down.
And the beauty of this family is that the classification isn't based on complex chemistry at all, but simply on particle size.
That's the primary way we distinguish them. They're defined by the size of the clasts, leading us through this gradient from gravels down to sand, to silt, and finally to clay. This simple size difference tells us everything about the energy and the distance of transport.
Okay, let's get into it. Let's start with shale, the most common sedimentary rock globally.
Shale is defined by mud-sized particles, so silt and clay. These particles are the smallest, and they require the least amount of energy to transport.
So they only settle out in really calm water.
Extremely quiet, low-energy environments. You have to think of deep ocean basins, lagoons, or the bottom of ancient lakes where the water is almost perfectly still.
Given that it's just compressed mud, why is it so structurally significant?
Well, it's important because of its sheer abundance and its key structural characteristic, which is called fissility.
Facility.
Fissility is the ability of the rock to split into thin, parallel layers, much like the pages in a book.
And why does that happen?
It develops because those tiny, flat clay particles are forced to align horizontally under the immense pressure of compaction. And this creates natural planes of weakness throughout the rock.
This facility is why shale can be an economic challenge, isn't it? From an engineering standpoint.
It is. Shale is relatively impermeable, which actually makes it an excellent cap rock for sealing oil and gas reservoirs. But it is structurally weak and very prone to landslides when it's exposed to water because it just easily breaks along those fissile plains.
Okay, moving up in size, we arrive at sandstone.
Sandstone is defined by sand-sized particles. It's incredibly common, and it forms in the widest variety of environments. Deserts creating dunes, beaches, river floodplains, shallow marine areas.
So it's more energetic environments?
Substantially more energy. The grains are larger, so they require faster wind or stronger currents to be moved and deposited.
And the quality of a sandstone, how uniform it is, that tells a profound story about its history, right?
It gives us two vital depositional insights. First, sorting, which is the degree of similarity in particle size. A well-sorted sandstone implies long, sustained transport by a constant mechanism, like wind or stable waves on a beach. If a river slows down just slightly, all the grains of a certain size draw out at roughly the same time, leading to a very uniform size. This indicates a very mature sediment history.
And what about poorly sorted sandstone? What does that tell us?
Poor sorting means you have a wide mix of sizes, from large pebbles all the way down to fine mud, all jumbled together and deposited at once. This suggests a very limited transport distance and extremely rapid chaotic deposition.
Like a flash flood.
A flash flood or a debris flow, exactly.
Yeah. And the second insight is particle shape, rounding versus angularity.
Right. Highly rounded grains have been subjected to prolonged abrasion. They've been tumbling and colliding for long distances or long durations, maybe across an entire continent in a river system or along thousands of miles of shoreline.
And highly angular grains.
They haven't traveled far from their source. They basically broke off the source rock and were buried very quickly.
Let's use the local example, the Jacobsville sandstone, to illustrate the sorting insight. What do we see there?
The Jacobsville sandstone, which you find in the upper Midwest, often features highly well-sorted, rounded grains, and it frequently preserves these spectacular ripple marks.
So what does that combination tell you?
The combination of well-sorted, rounded grains points to a very stable, long-distance transport environment. Probably a large, consistent stream system, or a vast, ancient sandy coastline where currents were steady and persistent over a long, long time. The energy was sustained, but it wasn't chaotic.
Okay. And finally, we hit the coarsest end of the spectrum, conglomerate and breccia, defined by gravel-sized particles.
These require the absolute highest energy to transport. We were talking about particles larger than 2 millimeters, so pebbles, cobbles, and even boulders.
And the difference between them comes down entirely to that particle shape insight we just discussed, round versus angular.
Exactly. Conglomerate consists largely of rounded gravels. This means the high energy, a violent river, a powerful wave zone on a coast, was sustained long enough for the pieces to smash into each other and become worn smooth before they were finally deposited.
And breccia retains those sharp edges.
Breccia consists mainly of large, angular particles. The angularity means minimal transport. This material was deposited almost immediately after the source rock fractured.
Where would you find that?
Often in landslide deposits, at the base of cliffs, in fault zones, or in very high-energy debris flow systems where gravity was the primary short-distance mover.
The Copper Harbor conglomerate provides a striking example of that high-energy, chaotic deposition.
It truly does. The Copper Harbor conglomerate is characterized by large, poorly sorted gravels and cobbles that are often quite angular. This formation strongly indicates that a high-energy debris flow, or maybe a rapid alluvial fan, existed.
So a sudden, chaotic dump of material.
A sudden, chaotic dump of material from an uplifting mountain range that was being actively and rapidly eroded right nearby.
Yeah.
The rock record immediately signals proximity to active tectonics.
Okay, so we're going to shift gears entirely now. We're moving away from fragments, from clads, to rocks formed from invisible, dissolved material that precipitates out of water.
The core identity here is precipitation. These rocks form when the dissolved ions, the end products of chemical weathering, exceed the saturation capacity of the water they're in.
And this can happen through purely inorganic means or through, well, organic life.
Right. And you should define those two precipitation paths in more detail.
Okay, so inorganic processes are strictly chemical, driven by environmental changes. The most common trigger is evaporation, which concentrates the solutes until they crystallize out.
Like forming salt in a brine pool.
Exactly. Another trigger is a shift in chemical activity. For example, a change in pH or temperature causes precipitation. We see this with mineral crusts forming around hot springs.
And the organic or biochemical processes, which involve biological intervention.
Yes. And these are massive drivers of rock formation. Water-dwelling organisms, from microscopic plankton
Like coccolithophores or diatoms.
to large shell-forming creatures like mussels or coral polyps, they extract dissolved ions, primarily calcium carbonate or silica, to build their shells and skeletons and hard parts.
And when the organisms die, these hard parts accumulate on the seafloor to form entire rock layers.
So let's talk about the king of this category, limestone, the most abundant chemical sedimentary rock made primarily of calcite.
Limestone, calcium 3 is highly variable because it forms in so many different ways.
Yeah.
But what it always tells us is that the depositional environment was warm, shallow, and probably marine, allowing either biological processes or chemical saturation to dominate.
So what are the main biochemical varieties that illustrate the sheer power of life to build rock?
Well, the most impressive are massive structures like coral reefs, which are just vast, biologically constructed frameworks of calcium carbonate. Then you have coquina, a fascinating variety you find on beaches and shorelines, which is just poorly cemented shell fragments. It sometimes looks like breakfast cereal piled up.
And then the really small stuff.
Most subtle, but geologically massive, is chalk, a very fine-grained, soft, porous limestone, formed almost entirely from the accumulation of microscopic skeletal remains of plankton, the White Cliffs of Dover.
And inorganic varieties.
Travertine is a beautiful example. This forms in caves as stalactites and stalagmites, or around hot springs where calcium carbonate-rich water degasses carbon dioxide upon reaching the open air. This shift in equilibrium causes rapid precipitation.
And oolitic limestone.
Right, oolitic limestone, which is characterized by oids, these small spherical grains that precipitate chemically as they roll around in highly agitated, shallow marine water.
Mammoth Hot Springs in Yellowstone provides a perfect, colorful illustration of travertine formation in real time, doesn't it?
It does. It showcases a modern example of rapid inorganic precipitation. The hot water dissolves massive amounts of subsurface calcium carbonate. When the water emerges and cools, the CO2 rapidly escapes, causing the calcium carbonate to just crash out of solution immediately, building those intricate, colorful terraces layer by layer.
Moving on, we have dolostone, which often gets confused with limestone.
Dolostone is chemically distinct. It contains calcium magnesium carbonate. It's typically a secondary rock, which means it doesn't usually form directly from precipitation.
So how does it form?
It forms when magnesium-rich groundwater circulates through existing limestone after deposition, causing a secondary alteration where magnesium atoms replace some of the original calcium atoms in the calcite structure.
Okay. Next is chert, which is fundamentally different because it's silica-based, SiO2, not calcium-based.
Right. Chert is microcrystalline quartz, which makes it exceptionally hard and dense. While some chert can precipitate chemically, the largest deposits often originate from the accumulation of microscopic silica shells of organisms like diatoms and radiolarians in deep marine environments. These tiny biogenic sources gradually dissolve and then reprecipitate as nodules or layers of chert within other rocks.
And this is the rock type that was crucial for human history, used for tools.
Absolutely. Its hardness and its conchoidal fracture pattern made varieties like flint, the dark variety, indispensable for tool making and for starting fires throughout prehistory. We also see colorful varieties like jasper, which is red due to iron oxide, and agate, which is banded.
And finally, we cover the evaporites. The name tells you exactly how they form.
Evaporites form when a body of water becomes isolated, a restricted sea or a drying lake, and the rate of evaporation significantly exceeds the inflow of new water. As the water volume drops, the concentration of dissolved salts increases rapidly, forcing precipitation.
Is there a sequence to the precipitation? Do all the salts precipitate at the same time?
No, and this is key to reading the environmental record. Minerals precipitate in a precise order based on their solubility. So calcium carbonate, calcite, precipitates first,
Okay.
followed by gypsum, calcium sulfate, and finally the most soluble and familiar salt, rock salt, halite. These vast deposits tell us the environment was intensely arid and contained a systematically isolated basin.
The Bonneville Salt Flats instantly comes to mind as an active, immense example of this formation process.
The Bonneville Salt Flats in Utah, or ancient Mediterranean deposits, perfectly illustrate this. In the Bonneville Basin, during periods of arid conditions, water evaporates, leaving behind these massive layers of mineral residue, predominantly rock salt. These deposits are geological records of persistent aridity and basin isolation.
Okay, so our third and final family member bends the rules because it's not mineral-based. Coal is unique, being composed entirely of carbonized organic material.
It is the ultimate testament to the preservation power of sedimentary processes. Coal is formed exclusively from vast amounts of buried, altered plant material. Typically, this accumulates in oxygen-poor swamp environments that prevent complete decay.
And this entire formation process is a chronological story of increasing heat, pressure, and crucially, increasing carbon density.
That's right. It's a gradient of quality and maturity. It starts in the swamp with peat. This is just partially altered plant material, still fibrous, with high moisture content and the lowest heating value. It's the starting line.
And then burial and compression start turning that organic sludge into rock.
Next is lignite, or brown coal. Lignite has been buried deeper, compacted, and chemically altered enough to reduce moisture, increasing the carbon content. It's soft and still relatively low quality, but it's a fuel source.
The critical stage for industrial use is the next one up.
That is bituminous coal, or soft black coal. Here, the compaction and temperature have been significant. Most of the remaining moisture and volatile organic compounds have been driven off, creating a high carbon content and a high heat value. This is the stage most often used globally for electrical power generation.
And the final, highest grade of coal.
That's anthracite. This is hard black coal with the highest fixed carbon content and the highest energy density. However, at this final stage, the heat and pressure have been so intense.
It's often involved in tectonic squeezing, right?
It has, so intense that it has actually transitioned beyond the realm of pure sedimentary rock. It is technically classified as a low-grade metamorphic rock. It's undergone change beyond mere compaction, achieving the highest level of maturity and heat output.
The implication here is profound. The jump from lignite to anthracite isn't just a matter of deeper burial. It reflects major regional tectonic stress and elevated temperatures, linking the history of coal directly to the history of mountain building.
Right. And if we connect this all back to the bigger picture, the resulting sedimentary rock is a geological compass. It doesn't just contain fragments of the past. It contains the imprint of the energy, the direction, and the rhythm of the ancient environment. So how do we read this archive? Through its structures.
The most visible and defining characteristic has to be the layering itself.
That layering is called strata, or beds. They are the parallel layers of sedimentary rock, and their presence is the single most characteristic feature of this entire rock family. Each stratum represents a distinct phase of deposition, perhaps a year, a season, or a single flood event.
And the division between those layers is just as important as the layers themselves.
Exactly. Bedding planes are the flat surfaces that separate one stratum from the next. These planes represent a significant break in deposition or an abrupt change in the sediment source or energy level. A sharp bedding plane might mean a flood suddenly ended or the climate shifted dramatically, changing the type of material being delivered.
Beyond just simple layering, we find structures that can point to the direction of ancient currents.
This is one of the most powerful tools in geology. Think about structures like cross-bedding. When wind or a water current deposits sand on the slope of a ripple or a dune, those inclined layers are preserved.
And you can measure them.
You can. By measuring the angle and direction of those inclined layers, we can determine the precise direction of the prevailing wind or water current from millions of years ago.
That's incredible, a literal geological compass. We also find structures that tell us about water depth and gravity.
That would be graded bedding. This is a structure where the particle size within a single layer systematically decreases from bottom to top, from coarse gravels at the base to fine mud at the top.
What causes that?
This structure is universally indicative of a waning current. The fast, heavy particles drop out first. It's often associated with a turbidity current in deep water that's slowing down. It is a definitive sign that gravity was the sorting agent.
And of course, these layers are the only place we find direct evidence of life. Fossils.
Fossils, the traces or remains of prehistoric life, are indispensable, and they are preserved almost exclusively in sedimentary rocks because of the heat and pressure required to form igneous or metamorphic rocks, which just completely destroy the organic material.
What makes them so important for reading the record beyond just saying, oh, look, an ancient shell? What's the real utility?
They serve three critical roles that go beyond novelty. First, they are vital for determining past environments. Finding a specific species of clam or coral tells you precise details about ancient salinity, temperature, and water depth.
Okay.
Second, they function as index fossils, organisms that lived for a very short, well-defined geological period. If you find that specific index fossil, you can accurately date the rock layer to a narrow time window, no matter where in the world you find it.
And third, they are the key to connecting continents.
They are used for matching rocks from different widespread places. If we find identical fossil assemblages in strata across separated continents, it helps confirm continental drift theories and allows us to correlate the geological timelines of continents that are now oceans apart.
So putting all this together, the difference in texture and structure is the immediate insight into the rock's history.
Absolutely. The difference between clastic texture, fragments, and non-clastic crystalline texture, interlocking crystals, gives immediate insight into whether transport and abrasion dominated or whether pure chemical precipitation was the defining event. By studying the size, the sorting, the shape, the structures, and the fossil content, we piece together the environmental puzzle. If we find a sandstone that is highly rounded, extremely well sorted, and exhibits pervasive cross-bedding,
You know where you are.
you know you are looking at an ancient desert dune system, even if that rock is now buried under a mile of farmland.
So we started this deep dive seeing sedimentary rocks as merely the product of destruction, but we've ended by recognizing them as these crucial indexed historical documents. We've covered the full circle, from the initial physical and chemical breakdown through the chaos of transport to the final permanent process of lithification.
And we've seen how our system of classification, detrital based on size, chemical based on precipitation, and organic based on carbon content, reveals the rock's entire birth story. It provides immense detail about the energy, the environment, the climate at the time, and the duration of the process.
The immense value of these rocks, not just economically for energy and resources, but scientifically as environmental and climate records, it just cannot be overstated. They are the pages that record the rise and fall of ancient oceans, the march of ice ages, and the evolution of life, all captured in these compressed layers of mud and sand. My final thought goes back to the sheer scope of time recorded in the Humble Shale. You said shale is the most common sedimentary rock, easily split by its facility. Think about what a tiny, thin layer of shale represents. A period of geological quiet, a vast, low-energy sea, accumulating only the finest dust and microscopic life. Every single split layer you hold in your hand might represent hundreds, thousands, or even tens of thousands of years of silent, continuous history. It's staggering that such a fragile, thin page can hold such an immense temporal record.
That leads to a provocative thought for you, the listener. We discussed how the ground beneath us is constantly cycling. It's being destroyed, transported, and rebuilt. Despite the apparent permanence of rock, we know that sedimentary formations are really just compressed, ancient water and air, containing the fossilized remains of microscopic plankton and long-dead plants. So consider the significance of the smallest grain size, like the mud that formed shale. What microscopic secret in an unknown fossil, a unique chemical signature from a past climate, might be contained in the mud beneath your feet right now, waiting for the weight of time to turn it into rock and reveal its history? Find out, and we'll see you on the next deep dive. Welcome back to the Deep Dive. This is where we strip down vast, complex topics, handing you the essential, fascinating, must-know nuggets of insight. Today we are putting on our geological hard hats. We are moving beyond surface erosion and into the deep architecture of the planet's structural geology. This field isn't just about rocks. It's about the sheer physics of how the Earth's crust gets twisted, folded, and spectacularly broken over geologic time. It's the study of the planetary stress fractures.
It really is.
So our mission today is custom tailored for you, the learner. We need to gain a crystal clear understanding of the forces at work, which we call stress, the resultant permanent changes, the strain, and how those fundamental concepts build colossal structures like the Himalayas, a process known as orogenesis. This is your shortcut to being genuinely well-informed about why the mountains are there and what they're made of.
And we have an incredible stack of academic sources guiding us today. We're moving through the hierarchy of geological understanding, starting with the fundamental physics of why a rock moves.
The cause.
Exactly, the cause. Then classifying the resulting structures, and finally connecting those structures to the planetary scale forces of plate tectonics. We will meticulously connect the stress tensor, that microscopic force acting on a grain, to the huge visible features you can track across an entire continent on a geologic map.
It's truly a journey from the atomic level all the way up to mountain belts. It's the moment you stop seeing a hill as just a hill and start seeing it as the exposed core of an ancient, permanently squeezed structure.
Okay, let's unpack this. Before we look at the results of deformation, we have to establish the cause.
We must begin with the basic language of change. The general term for any change in the original form, shape, or size of a rock body is deformation. It's an umbrella term, really. It covers everything from minor chemical alteration to the creation of a major fault system.
And crucially, the sources note that this isn't evenly distributed around the globe. The vast majority of crustal deformation happens exclusively along plate margins. That's the engine room of geology. When we talk about the power driving this deformation, we must define stress. Stress is not the same as simple force. Stress is defined as force applied over a given area.
Okay, so if I push my hand against a rock, that's a force. But if I push the rock with a tiny pin, concentrating that same force into a minuscule area, the resulting stress is enormous, and the rock will likely fail.
Exactly. Stress is all about concentration. But before we get to the active, the exciting types of stress, we must acknowledge the constant pervasive background pressure that every rock in the crust experiences. Lithostatic stress.
That's the one that increases with depth.
Precisely. Lithostatic stress is the pressure exerted by the sheer, overwhelming weight of the overlying column of rock. Imagine being buried thousands of feet down. The pressure is equal in all directions, kind of like being deep underwater, but the medium is rock.
So it's squeezing from every direction at once.
Right, and this confining pressure is a massive factor, often measured in thousands of atmospheres, and it dictates how the rock will respond when we introduce a directional stress.
So the lithostatic stress is the baseline. It holds everything together. Now, what happens when a tectonic plate starts pushing or pulling? That introduces the three primary types of directional stress that actively shape the world.
Let's start with the first one.
First, we have compressional stress. This is the familiar squeeze. It shortens the rock body. This is the stress that builds continents, pushing material together, squeezing sedimentary layers into intricate folds, and forcing one plate over another.
And if compression is the squeeze, its opposite is tensional stress. This is the pull it works to elongate or stretch the rock body apart.
The stretching force.
Yep. This is the dominant stress regime at divergent boundaries, where crust is being ripped apart, leading to rifting and thinning and creating structures like the East African Rift Valley.
And the final primary type is shear stress. This one is often harder to visualize. It produces slippage or translation.
It is. Imagine a deck of cards or a book resting on a table. If you push the top couple sideways while holding the bottom still, the movement between the layers is shear stress.
An immense sideways grinding action.
Exactly. And if stress is the cause, the directed energy, then strain is the effect. Strain is the measurable change in shape or size caused by that stress. It's the permanent damage or the temporary flex.
This raises an important question. We know that mountains are being pushed together constantly. Why aren't we seeing enormous earthquakes and breaks everywhere all the time? How do rocks manage this constant pressure?
Well, they manage it by starting with temporary adjustments. First, rocks often experience elastic deformation.
The rubber band analogy.
The rubber band analogy, right. The rock stores the energy, and if the stress is removed, it returns almost exactly to its original shape and size. Earthquakes are essentially the rapid release of that stored elastic energy.
But rocks aren't infinitely elastic. Here's where it gets really interesting. Every rock has an elastic limit. Once the stress surpasses this boundary, the rock is forced to undergo permanent, irreversible changes. The stored energy is just too great, and it must adjust its shape.
And that permanent adjustment, that permanent strain, manifests in one of two fundamentally different ways which define the architecture of the crust. First, we had ductile deformation, often called plastic flow. This is permanent deformation where the rock changes shape without fracturing. It bends, warps, or flows like warm taffy or clay. It flows. We find this behavior deep within the earth where conditions are, conducive to softness.
And the second type is the failure most people visualize. Brittle deformation or fracture. This is the sudden, catastrophic failure where the rock cracks and breaks.
This is the domain of faults and joints, and it happens when the rock snaps like cold glass.
It bends or breaks.
It's that simple. And the shift between ductile flow and brittle fracture is the key to structural geology. The style of deformation, whether the rock bends or breaks, is controlled by four primary factors, as detailed in our sources: temperature, confining pressure, rock type, and time.
Let's start with temperature. This is perhaps the most intuitive factor.
Indeed. If you heat something up, its internal crystalline structure loosens, making it easier to deform. Therefore, the cooler upper crust, say the top 10 to 15 kilometers, strongly favors brittle deformation.
It's rigid, so it breaks cleanly.
Exactly. But as you go deeper, the rock becomes warmer and promotes ductile behavior. Think of the crust as a massive layered cake. The top layer is cold and brittle. The bottom is hot and pliable.
And confining pressure. That background lithostatic stress must play a massive role too.
Absolutely. High confining pressure essentially pushes the rock's constituent particles closer together, making it stronger and harder to pull apart or shear. This pressure, when combined with high temperatures at depth, tends to push the rock toward ductile flow.
It sort of holds it together while it bends.
It prevents the expansion and separation needed for brittle fracture. A rock that would shatter on the surface might flow like toothpaste 30 kilometers down, provided it's also hot.
But wait, if pressure makes the rock stronger, making it harder to break, how does the rock eventually fail, even in that deep, hot environment?
That's where time comes in. If the stress is applied instantaneously, like hitting a rock with a hammer, it fractures immediately, brittle failure. But if a relatively low stress is applied very slowly over millions of years, the timescale of plate tectonics, the rock has time to adjust internally.
That's fascinating. You're saying a rock under a constant, gentle squeeze for 5 million years might slowly creep and flow ductily, whereas if that same amount of stress was applied in 5 minutes, it would shatter instantly.
Precisely. This slow adjustment is often referred to as creep. Ductile deformation requires time. And finally, the fourth factor is the rock type itself.
Of course, different materials.
Right. Certain rocks, especially highly crystalline ones like granite, are naturally strong and tend toward brittle failure, while layered sedimentary rocks like shale or limestone, especially if they contain water, are often weaker and more prone to ductile folding.
So if we synthesize this, shallow, cool crust, quick stress, and strong rock equals brittle failure. We get faults. Deep, hot crust, slow stress, and weak rock equals ductile flow. We get folds. This contrast fundamentally dictates where earthquakes happen and why mountains look the way they do.
That's the core relationship that defines Earth's architecture.
Now that we know the cause, stress, and the effect, strain, we need to discuss how geologists actually record these features. To analyze these structures, whether they flowed or broke, we need a universal language, a set of tools to map these 3D changes onto a flat geologic map. We're talking about the two key measurements that define the orientation of any inclined surface: strike and dip. These are non-negotiable for understanding subsurface structure.
Let's elaborate on strike first. Strike, or the trend, is defined as the compass direction of the line produced, where an inclined rock layer intersects a horizontal plane.
The analogy you offer here is the book in the bathtub. Imagine a huge, flat, calm lake. That's your horizontal plane. Now, take a layer of tilted rock, like a massive slab. Where the waterline meets the rock surface, that intersection is a horizontal line. The direction that line points, north, south, east, west, is the strike. It tells you the line of orientation.
And that only gives you one dimension. To get the third dimension, we need the dip. The dip is the angle of inclination, measured downward from that horizontal plane. It tells you exactly how steep the rock layer is and the direction in which it slopes.
So if a rock layer is perfectly flat, its dip is 0 degrees. If it's vertical, its dip is 90 degrees. You can't have one without the other, right? If your strike is north, you need to know if the rock is dipping east or west, and by how much.
Precisely, and this is why they are profoundly important, especially for applied geology. Together, strike and dip allow geologists to extrapolate the 3D orientation of layers and faults beneath the surface.
So for mining or oil?
Absolutely. If you are a mining engineer, understanding the strike and dip of a mineral vein allows you to predict where that vein will be 500 feet deeper. If you are an oil exploration geologist, you use these measurements to determine the precise volume and depth of a hydrocarbon trap.
They truly are the coordinates that turn a flat map into a complete structural cross-section. It's the essential language we use to read the Earth's history.
It is.
Now that we can map them, let's look at the structures created by ductile deformation, the result of slow, intense compression in a warm, deep environment. We're focusing on folds, the wave-like undulations resulting from compression that shorten and thicken the crust without widespread breaking.
When you look at mountains, the folds often look like simple waves, but their internal anatomy is quite specific. A fold has two sides, known as the limbs. It has an axis, which is the imaginary line tracing the points of maximum curvature of each layer. Think of the crest or trough of the wave as it travels through the rock.
And finally, the axial plane is the imaginary surface that connects all those axes, dividing the fold as symmetrically as possible.
Now for the fun part, classifying the folds. These classifications are the key to reading the tectonic history of a region instantly.
Okay.
The first type is the anticline. This is the classic upfolded or arched layer. Visually, it looks like an arch or the letter A if you slice through it. It's the crustal arching upward against gravity.
But the real insight for the learner is the age relationship. If you walk across an eroded anticline, what do you find?
The crucial identifier for the anticline is that the oldest rocks are found right in the center, in the core.
Why is that?
Erosion is the key here. As the top of the arch is scraped away, it reveals progressively deeper and therefore older layers toward the middle. This pattern is often exploited economically. Anticlines are classic geological traps for hydrocarbons because petroleum fluids are less dense than water and migrate upward, getting trapped by an impermeable cap rock at the crest of the arch.
That's the so what moment right there, a structural feature that defines our energy resources. Now for the opposite, the syncline.
The syncline is the downfold or trough of rock layers, looking like a U or a bowl shape. If the anticline is the crest of the wave, the syncline is the trough.
And following the logic of layering, the crucial identifier here is that the youngest rocks are in the center.
That's it. The more recent deposits settle and are preserved right in the middle of that downwarp structure.
So you could be standing on much younger rock in the middle of a syncline than on the edges.
You can see this beautifully in places like Sidling Hill in Maryland, where road cuts expose miles of the Appalachian Valley and Ridge Province, clearly showing alternating anticlines and synclines evidence of the immense compression that folded that part of the crust. Synclines are also vital for hydrology, as they can act as traps for groundwater, preserving water resources in arid regions.
And there's a third major type that doesn't look like a wave, the monocline.
A monocline is a large, step-like fold in otherwise horizontal strata. Picture a carpet lying flat, and then you push up sharply on one side to create a single, dramatic bend.
A single bend.
Yes, and it's often the result of movement on a deep fault below the surface. The fault moves, and the overlying, more pliable sedimentary layers bend dramatically to accommodate the displacement without actually breaking all the way through.
That provides a great link between ductile and brittle structures. It's ductile deformation occurring because of brittle failure deep below.
Absolutely. And when we look at folds in the real world, their axis is rarely perfectly horizontal. That's where we differentiate between non-plunging and plunging folds.
A non-plunging fold has a horizontal axis, which, when eroded, tends to leave long, parallel bands of rock on the map, sort of like stripes.
Right, very linear. But a plunging fold has an axis that is inclined, it dips into the ground. When these plunging folds are eroded, they create a very distinctive, often beautiful zigzag pattern on the geologic map. The layers appear to curve and then point sharply in the direction the axis is plunging.
It's the boat nose analogy. If the fold axis is plunging downward to the north, the layers, when viewed on a map, appear to wrap around the end of the structure pointing north.
The example often cited is Sheep Mountain, Wyoming, part of the Bighorn Basin. There, you can see these gigantic plunging anticlines exposed, making a spectacular, recognizable feature on a map. It's the 3D reality of the fold meeting the 2D surface of the map.
Moving beyond linear folds, the compressional stress can also result in large, circular structures, large-scale warping.
Exactly.
We have the dome. This is a circular or elongated structure that results from upwarp displacement of rocks, often caused by the buoyant rising of less dense material, like salt or magma, in the subsurface.
Since it's an upwarp, following the anticline logic, the oldest rocks are always found in the core of a dome. The layers dip uniformly outward from that central point.
And the basin is the opposite. This is a circular or elongated structure resulting from massive downwarp displacement.
And here, the youngest rocks are found in the core. The layers dip uniformly inward toward the center, accumulating new sediment over time. This concept sounds simple, but the scale is enormous.
Let's connect this to a real-world example. The Michigan Basin, that's not a lake. It's a giant geological bowl that covers most of Michigan and parts of the surrounding states.
It is a phenomenal example. It formed over hundreds of millions of years, slowly sagging under its own weight and the weight of the accumulated sediment, acting like a giant geologic sinkhole.
So it's been sinking for ages.
For ages. And if you look at a geologic map of Michigan, you see these almost perfect concentric rings of rock layers. The youngest layers are exposed right in the center of the state, while the oldest layers are only found out near the margins, like the Upper Peninsula.
That tells you that state has been steadily sinking and accumulating deposits for an enormous period of time. These massive, subtle warps are ductile deformation on a truly continental scale, invisible to us on a daily basis, but essential to understanding the continental history.
Absolutely.
That was the architecture of bending. But what happens when the stress is too quick, the pressure is too low, or the rock is simply too cold and brittle? We move now from ductile flow to brittle deformation, cracks, and slips.
The breaking point.
The breaking point. We start with the simplest type of brittle failure, joints. These are fractures in the rock where there has been no appreciable visible displacement. They're just cracks, and they are typically formed under tensional stress, either from stretching or from unloading.
Joints might seem minor, but their significance is immense. They form perpendicular to the direction of the greatest tensional stress. They can form when overlying rock is eroded away, causing the remaining rock to expand slightly, or when magma cools and shrinks.
And what's their impact?
Well, their impact is widespread. First, they act as major conduits for water. Groundwater flow often follows joint networks deep underground. Second, and crucially, they are the primary weakness that dictates how a landscape weathers. Water seeps into the joints, freezes, expands, and pries the rock apart. If a massive granite slab has systematic jointing, it will inevitably break along those predetermined planes, defining the shape of the boulders and cliffs we see today.
The sources mention some truly spectacular examples of jointing, especially in lava flows. Columnar jointing. Think of Devil's Postpile National Monument in California, or even the iconic Devil's Tower in Wyoming. These formations are composed of thousands of uniform, often hexagonal fracture columns. How does that happen?
It happens when hot lava cools very slowly and uniformly. As the lava shrinks, the tensional stress creates a hexagonal fracture pattern, the most efficient way to relieve that tension, producing these mesmerizing, near-perfect geometric columns.
It's a geological marvel born entirely from simple, brittle failure under slow, uniform tension.
Now we transition to the brittle structures that involve significant movement. Faults. Faults are defined as brittle fractures in rocks along which appreciable displacement has taken place. They represent permanent, violent failure, often accompanied by earthquakes.
The big ones.
To talk about movement on a fault, we need two absolutely essential historic terms. We have the hanging wall, which is the rock surface above the fault plane, and we have the footwall, which is the rock surface below the fault plane.
The history behind those terms is fantastic, and it helps the terms stick. They were coined by early miners working along tilted ore bodies. The miners would literally hang their lamps on the block of rock above their heads, the hanging wall, and they would stand on the block of rock below their feet, the footwall.
That's the key context. Knowing which side is which allows us to classify the movement. Let's look first at dip-slip faults, where the movement is primarily vertical, parallel to the inclination or the dip of the fault surface.
The first, the most common in stretching environments, are normal faults. In a normal fault, the crust is pulled apart and the hanging wall moves down relative to the footwall.
This movement always accommodates lengthening or extension of the crust. Therefore, they are the result of tensional stress.
So when you see a lot of them,
When you see a massive region dominated by normal faults, you know that area is being pulled apart. Classic example, the Basin and Range province in the western United States. That landscape is defined by parallel mountain ranges, horsts, separated by down-dropped valleys, grabens, all caused by tens of millions of years of crustal stretching along normal faults.
so normal faults are found in places where the crust is thin and stretching. Now for the opposite forces, the squeeze.
When compression dominates, we get reverse faults and thrust faults. Here, the hanging wall moves UP relative to the footwall. Pushed up. This accommodates the shortening of the crust and is caused by compressional stress. The crust is being shoved together. We distinguish between reverse and thrust based on the angle of the dip.
Okay.
Reverse faults have dips greater than 45 degrees, meaning they are relatively steep. They still create shortening, but usually on a more localized scale.
And then we get to the giants, the thrust faults. These are low-angle reverse faults defined by a dip of less than 45 degrees, often much less, sometimes only a few degrees. Why does that shallow angle matter so much?
It matters because of leverage. Because the fault plane is almost horizontal, a relatively small amount of compressional force can push massive sheets of crustal rock horizontally over great distances.
How far are we talking?
We're talking about transporting rock units sometimes 50 to 100 kilometers or more. Thrust faults are the fundamental building blocks of colossal mountain ranges, often placing incredibly old rocks on top of much younger rocks.
That creates immense geological confusion for anyone who doesn't understand the structure, but once you identify a thrust fault, you know exactly how much shortening and thickening occurred.
Finally, we turn to the third class of movement, the purely sideways motion, strike-slip faults. These faults are defined by a dominant displacement that is purely horizontal, running parallel to the trend or strike of the fault surface. They are the result of pure shear stress.
We classify large strike-slip faults that cut through the entire lithosphere as transform faults. These are often plate boundaries themselves.
And the key distinction here is the right versus left lateral designation, which is often confusing for those new to geology.
Let's clarify this for the listener. The determination is based on the apparent motion when you stand on one side and look across the fault.
That's the key, your perspective.
If the block on the other side appears to have moved to your right, it's a right lateral strike-slip fault. If the block on the other side appears to have moved to your left, it's a left lateral strike-slip fault. It doesn't matter which side you stand on. The apparent motion will be the same relative direction.
And the most concrete, globally relevant example is the San Andreas Fault in California. It is the classic illustration of a large, crust-cutting right lateral strike-slip fault. It marks the boundary where the Pacific Plate is grinding horizontally past the North American Plate, constantly releasing enormous amounts of stored shear strain. This single structure dictates the geology and seismic hazard of the entire region.
That's why the difference between a dip-slip vertical movement, shortening or lengthening, and a strike-slip fault horizontal movement, shear, is so important. It tells you instantaneously what kind of stress regime the region is under.
It's the first thing you look for on a map.
So what does this all mean when we put the pieces together? We see the forces, the failure modes, and the resulting structures. Now we put it all together to understand orogenesis, the collection of processes that produces an entire mountain belt.
Orogenesis is the planetary scale of structural geology. It involves simultaneous folding, faulting, metamorphism, and igneous activity, often spanning hundreds of millions of years. It's where plate tectonics leaves its ultimate signature.
So this is the grand finale of all those forces.
It is, and the sources confirm that the majority of mountain building occurs at convergent plate boundaries, driven primarily by intense tectonic compression. However, as the crust thickens and stretches under gravity, secondary extension and normal faulting can occur, leading to a complex interplay of different structures within the same mountain range.
We can categorize mountain building into three distinct types, based on the environment where the collision or subduction is happening. First, the island arc type.
This involves the steady subduction of oceanic lithosphere beneath another oceanic plate. Since continental crust isn't involved yet, the mountains are smaller, forming volcanic island arcs. Think of the Aleutian Islands or the Marianas.
Not a huge mountain range then.
Not yet. The crust is thickened by the constant production of magma and the accretion of deep-sea sediments scraped off the subducting plate.
Second, we have the Andean-type mountain building.
This is the classic continental volcanic arc where oceanic lithosphere subducts beneath a continental plate. This is far more complex structurally. You get immense compressional stress, not only driving the volcanism, but also crumpling and thickening the continental margin.
So the continent itself gets deformed.
Massively. This thickening leads to large-scale folding and the creation of great reverse and thrust faults right along the continental edge. The Andes in South America are the textbook example. A high, steep mountain range defined by years of simultaneous compression, uplift, and volcanism along the subduction zone.
And finally, the most spectacular and largest mountain ranges are created by the alpine type or continental collisions, the ultimate geological traffic jam.
That's a perfect way to put it. Two continental masses meet, and since neither is dense enough to easily subduct, the crust buckles, shortens, and thickens dramatically. When two continents collide, the result is extreme, unimaginable crustal shortening. This is where you find the most dramatic ductile structures, huge overturned folds, and the most massive brittle structures, specifically stacks of low-angle thrust faults.
Like the Himalayas.
Exactly. Look at the Himalayas, where the Indian continent is still colliding with Asia. The crust there has more than doubled in thickness, creating the highest mountains on Earth. Or the Appalachian Mountains, which are the eroded remnants of this same type of alpine collision that occurred hundreds of millions of years ago.
Speaking of history, these mountain-building events, or orogenies, are key markers in Earth's deep timeline. Our sources mention historical examples like the Laramide orogeny,
which was responsible for lifting many of the modern Rocky Mountains far inland during the late Cretaceous and early Cenozoic.
and the much older Pinocchian orogeny in the Precambrian, which shaped the basement rock of the North American Shield. These names give structure to the past.
They do. But the mountain belts themselves are fundamentally different from surface structures. They aren't just piles of rock, they are supported by deep features, which brings up the concept of crustal roots.
If mountains are just rocks stacked on top of the crust, shouldn't they sink under their own weight?
They absolutely should, and they do, but the crust itself behaves differently under mountains. This is where the concept of isostasy comes in, the idea that the crust is floating on the denser mantle, much like an iceberg floats in water.
So there's more beneath the surface.
Much more. During collision, the extreme shortening forces not only push the crust upward to form the visible mountains, but also push a tremendous amount of crustal material downward into the mantle. This mass forms a deep, less dense crustal root that stabilizes and supports the towering structure above, ensuring the mountains are in isostatic equilibrium. As the mountains erode, the root slowly buoys them back up, keeping the cycle going.
And for a historical deep dive, we have to look at the Appalachian Mountains. The sources note that the Appalachians provide a billion-year historical example of mountain building. This isn't just one event, it's a series of massive orogenic cycles.
That's right. The Appalachians are the remnants of at least three major collision events, the Taconic, Akkadian, and Alleghenian orogenies, which occurred as the ancient supercontinent Pangaea was forming and breaking apart.
Three different mountain ranges, essentially layered on top of each other.
In a way, yes. Each collision event piled new material onto the continent's margin, creating massive thrust faults and tightly folding the sedimentary layers. If you drive through Pennsylvania or West Virginia today, the zigzag patterns of ridges and valleys are the result of intense compression that led to massive ductile folding. Those folds were so intense they sometimes overturned, meaning the layers were literally flipped upside down.
Wow.
And interspersed throughout are ancient, gigantic thrust faults that transported continental fragments hundreds of miles inland. It's the ultimate synthesis. A perfect showcase of every structural feature we've discussed, now eroded down to the roots.
It truly connects the small to the large, showing that a simple anticline in a road cut might be evidence of a continental collision that occurred 300 million years ago.
That's geology.
That brings us to the end of this deep dive. We move from the foundational microforces stress, to the consequences strain, to the structures themselves, and finally to the planetary scale of construction orogenesis.
And if there's one final, single takeaway, it is this. When you see a geological structure, you are not just seeing a shape. You are reading a complete history of temperature, depth, time, and force. Knowing the difference between brittle failure, faults and joints, and ductile behavior, folds, is absolutely essential. A geologist looks at a map and instantly knows if that region was cold and shallow.
So it was faulted.
Right. Or hot and deep, so it was folded during its moment of major deformation.
We hope this deep dive provided the aha moments you were looking for, connecting the underlying physics of stress and strain to the stunning, complex landscapes you encounter every day. The mountains aren't just mountains, they are enduring permanent monuments to unimaginable tectonic force.
And let me leave you with a final provocative thought for the listener. Considering the factors that influence rock strength, temperature, confining pressure, and time, if the deep crust were suddenly and dramatically cooled while maintaining the same extreme pressure, how fundamentally would that change the way Manning ranges form? If the core of a collision zone became cold and rigid, would we see fewer of those massive, shallow-dipping thrust faults that accommodate shortening and instead observe catastrophic, steep-angle reverse faults penetrating far into the mantle? Something to mull over until our next deep dive.
An excellent, chilling question to consider. Until next time, keep digging into the details. You know, if you've ever watched footage of a volcanic eruption,
It's mesmerizing.
it is. It's this terrifying, but just completely mesmerizing spectacle of creation and destruction. You know, you're looking at one of Earth's most powerful forces.
It really is.
But for us, the question isn't just about the show, it's about the science.
Yeah.
What's the mechanism that actually drives that force?
And why the huge difference in behavior?
Exactly. Why do some volcanoes just, quietly ooze lava for decades, while others just explode into these ash clouds that can literally circle the globe and block out the sun?
That really is the ultimate puzzle. And you can't understand any of it, not really, unless you understand what generates the magma in the first place.
Right.
And that means we have to do a deep dive into geology, into chemistry, and, most fundamentally, plate tectonics. When you look at a map of the planet, the first thing that probably jumps out is the Pacific Ring of Fire.
Okay, let's unpack this, because the scale of the Ring of Fire is just immense. It's not just a few mountains.
Yeah.
It's this vast, active tectonic seam that just snakes all the way around the Pacific Basin. And our sources say something like 75% of the world's active and dormant volcanoes are located right there.
75%. It's an incredible number.
And that can't be a coincidence. It's like the most compelling evidence there is for some huge, unified system at work underneath it all.
Exactly. So our mission today is to go from that huge macro scale, the churning of tectonic plates, and drill right down to the microchemistry of the magma itself.
Okay.
We need to understand why the volcanoes are clustered there and why they all have such wildly different personalities. We're going from the world map down to the behavior of gases trapped inside molten rock.
And based on the sources, it seems like you just can't get away from it. Tectonic activity isn't just a factor, it is the primary driver.
It is.
The way the plates interact seems to dictate everything, from how the magma gets made deep down to, its composition and how explosive it's going to be when it finally hits the surface. Is that the most foundational takeaway you had?
Absolutely. When we talk about global volcanism, we are, for all intents and purposes, talking about the mechanics of plate boundaries.
Right.
The movement of the lithosphere doesn't just shuffle continents around. It creates the very specific conditions of pressure and heat you need for solid rock to melt, rise up, and build these fiery mountains. If you miss the tectonic setting, you miss the entire story.
So, okay, let's start with that geography then. The basic rule seems to be that volcanoes are usually found at plate boundaries where all the action is the friction, the pulling apart.
That's where the interactions lead to magma formation. But the type of boundary is immensely important.
Why is that?
Because it completely changes the source material and the melting process itself. It creates three really distinct categories of volcanism. Each one has its own characteristics and, more importantly, its own specific way of melting rock.
So that we have to detail those mechanisms to really get it.
We do, to appreciate why the eruptions are so different.
Okay, so let's start with the really dramatic one. The one that's responsible for the Ring of Fire and, the most destructive volcanoes we always think of. Subduction zone volcanism.
The convergence, the collision zone.
Right.
So this is the environment where one tectonic plate, usually the denser oceanic plate, is forced downward.
It's subducted.
It's subducted, exactly, beneath a less dense plate. And that could be another oceanic plate or could be a continental plate. The key thing is that this descending slab takes water with it, trapped in the minerals and sediments from the seafloor deep into the mantle.
Now, how does that water, which is what, only 1 or 2% of the total mass, how does that manage to melt solid rock? It feels kind of counterintuitive. You'd think you'd need to just crank up the temperature.
And that's the real aha moment of subduction. The mechanism isn't just simple heat. It's something called partial melting induced by a flux.
A flux.
Think about putting salt on an icy road. The salt doesn't make the ice hotter, right?
No, it just makes it melt.
It lowers the melting point. Water does the exact same thing in the mantle. It acts as a fluxing agent. As that descending plate heats up, it releases the trapped water vapor into the hot mantle wedge above it.
Okay.
And that added water drastically lowers the temperature at which the surrounding rock begins to melt, so it starts to partially melt and rise. It's not about more heat. The water is the catalyst.
That is a crucial distinction.
Yeah.
So we're talking about rock that is already hot, but it's not hot enough to melt under normal pressure. But then the water gets in there and just unlocks the whole process.
Precisely. And the structures that result from this are these massive volcanic arcs that define coastlines all over the world.
And we can break those down even further.
We can. Based on what kind of plate is on top, if you have an ocean convergence where one oceanic plate dives under another, you get island arcs.
Like long chains of volcanic islands.
Exactly. Long, majestic chains.
Yeah.
Specific examples would be the Aleutian Islands in Alaska with very active volcanoes like Mount Shishaldin, or the Kuril Islands with the towering Klishevskaya Sopka. These are purely oceanic.
But then, when an oceanic plate dives under a continental plate, that's when you get the continental volcanic arcs.
Yes.
And these often seem to be the most spectacular and dangerous, I'm guessing, because that rising magma has to deal with the continent's crust.
You've got it. I mean, think of the Andes Mountains in South America running for thousands of miles. They host giants like Cotopaxi in Ecuador, or Closer to home for many of us, the Cascade Range in the US and Canada.
With Mount St. Helens and Mount Rainier.
Right. In those cases, that water-catalyzed magma has to travel through really thick continental crust, and that journey profoundly affects its chemistry. It often makes it much stickier and way more explosive.
So we're moving from convergence to divergence now.
Yeah.
Let's talk about spreading center volcanism. This one is less dramatic on the surface, but it actually produces the greatest volume of volcanic rock on the planet.
That's absolutely right.
Yeah.
The subduction zones give us the huge explosions, but the oceanic ridge system, this vast continuous mountain chain hidden under the oceans, that's the real powerhouse. This is where tectonic plates are pulling apart, creating a rift, and allowing magma to just well up and fill the gap to form new crust.
So if water is the key ingredient in subduction zones, how does the magma get made here? What's the mechanism at a spreading center?
This is a textbook case of decompression melting.
Decompression melting.
Yeah. Deep in the mantle, rock is solid because it's under such immense pressure. But when the plates pull apart, the hot mantle material underneath rises up really quickly to fill that void.
And as it rises, the pressure drops.
The pressure drops rapidly. And even though the temperature of the rock hasn't really gone up, that reduction in confining pressure is enough to lower its melting point. The rock literally changes state from solid to liquid.
So it's like opening a bottle of soda.
Perfect analogy.
The liquid is totally stable under high pressure. You don't heat it up, but the second you pop the cap, the pressure drops and all that dissolved gas just rushes out as bubbles.
That is the perfect way to think about it. The mantle rock rises, pressure drops, and it starts melting.
And this happens continuously.
Continuously. This massive constant pressure relief along these ridges lets the mantle partially melt, forming huge quantities of low-viscosity basaltic magma. It's constantly creating new seafloor.
And that's where we get those pillow basalts, right?
Yes, that's the characteristic product.
Oh.
That really fluid, hot lava hits the freezing cold ocean water, and it instantly forms these bulbous, rounded shapes. It's a massive process, but it's happening almost entirely out of sight.
Which brings us to the third type, intraplate or hotspot volcanism. This one is the anomaly. It seems to break the rule about boundaries.
It absolutely breaks the boundary rule, which is why it's so fascinating. Hotspot volcanism happens within a tectonic plate. It can be hundreds or even thousands of miles away from any major boundary.
And the cause is different again. We're talking about these deep-seated mantle plumes.
Exactly. These plumes are narrow columns of unusually hot rock. It's significantly hotter than the mantle around it, and it rises slowly from deep within the Earth.
Like a blowtorch from below.
Kind of. When this column of hot material reaches the base of the lithosphere, it causes this intense, localized melting. And since the tectonic plate is slowly moving over this relatively stationary hotspot, the plume just keeps punching through the plate.
Creating a chain of volcanoes.
A long, sequential chain over millions and millions of years.
And the classic example here has to be Hawaii.
The Hawaiian Islanders are the textbook case, yeah. It's a perfect volcanic chain formed as the Pacific plate just slides slowly over that hotspot.
But it's not just in the ocean. There's also Yellowstone.
And Yellowstone is a great example that this can happen right under a continent. The dynamic is a little different there, though. When a plume rises under a thick, silica-rich continental crust, it causes massive amounts of melting and mixing.
Oh.
And that often leads to huge volumes of really explosive, sticky, rhyolitic magma. So it tells us the melting source is important, but the crust it has to travel through is just as critical.
So just to recap the blueprint then, subduction zones use water as a flux.
To lower the melting point?
Spreading centers use decompression.
To release the melting potential.
And hotspots use a deep, localized heat source of plume.
Right. And in each case, the tectonic environment defines the melting process, and that process defines the starting chemistry of the magma.
Okay, so now that we know how and where the magma is generated, we have to look at what it's actually made of.
Yes.
And this is the connection for you, the listener. The tectonic setting dictates the chemistry, and that chemistry dictates the volcano's entire personality, from a quiet flow to a violent explosion. And this is where it gets really interesting. We're going from miles-wide plates down to the molecular level.
It truly is. Because once that rock melts, its composition is determined by the source material and the path it takes to the surface. And the single most important ingredient, the chemical control knob, is silica.
Silica content, SiO2. That's the key measure. So let's lay out the three common compositions our sources talk about.
Okay, so on the low silica end, you have basaltic magma. This is the most fluid type, with a low silica content, around 50% IO2.
And this is what we find at spreading centers and hotspots like Hawaii.
Exactly, it dominates the oceanic crust. Then, in the middle, you have andesitic magma, which is intermediate. It's somewhere between 50 and 60% IO2. You see this a lot in subduction zone environments.
And then at the high end?
At the high end, you have rhyolitic magma, or granitic. This is the stickiest stuff. It contains the highest amount of silica, pushing 70% or even more. This is typical of melting continental crust.
So why is silica so powerful? I mean, it seems like a relatively small difference in percentage, but it introduces this core concept of viscosity.
It's all about the molecular structure. Viscosity is just a material's resistance to flow.
Syrup versus water.
Perfect example. When you have high silica content, the little silica tetrahedra, that's a silicon atom bonded to 4 oxygen atoms, they start linking up. They form these long, complex polymer chains inside the magma.
So it gets tangled.
Imagine trying to pour a bucket of tangled string versus a bucket of water. Those tangled strings, the silica chains, make the magma incredibly sticky and resistant to flow. That's high viscosity. Low silica magma has a simpler structure, so it flows easily. Low viscosity.
But hang on. If subduction zones often produce this explosive rhyolitic magma, but the source material is oceanic crust, which is basaltic, how does the silica content jump so high?
That's a fantastic question. And it brings us to this concept of magma differentiation. As that primary basaltic melt rises from the mantle up into the continent above it, a couple of things happen.
Okay.
First, it goes through what we call fractional crystallization. As it cools slowly in a magma chamber, the first minerals to crystallize out are the iron and magnesium-rich ones. They're denser, so they sink.
Which leaves the leftover melt with more silica.
Exactly. The remaining liquid becomes progressively richer in silica. And second, it assimilates the surrounding rock. It melts and mixes with the continental crust it's passing through, which is naturally high in silica.
So the rising basalt gets contaminated and refined, basically.
Yes, it gets refined into a highly viscous silica-rich rhyolite by the time it reaches the surface. And that's why a volcano in the Cascades is often so much more explosive than one in Hawaii.
That makes perfect sense. So let's talk about the physics. Our sources point to 2 main physical factors that control how fluid or sticky magma is. The first one is simple: temperature.
Right, a very straightforward principle. Hotter magmas are less viscous, they're more fluid.
More energy to break the bonds.
You've got it. Increasing the temperature gives the molecules the kinetic energy they need to break those silica bonds and flow more easily. Basaltic magmas, for example, erupt at incredibly high temperatures, 900 to 1,000 degrees Celsius, so they're inherently fluid.
But the second factor, composition, that silica content, often seems to override temperature when it comes to explosive potential.
It does, because the structural resistance from high silica is just so immense. Even though rhyolitic magmas erupt at much lower temperatures, maybe 600 to 700 Celsius, the stickiness from all those silica chains makes them incredibly viscous, regardless of the heat.
So if you had to pick one factor.
It's high silica content. That's what determines the violent eruption style.
But we still haven't talked about the actual trigger for the explosion itself. That comes down to the volatile factor, the dissolved gases.
This is the engine, the driving force of the destruction. Volatiles, mostly water vapor and carbon dioxide, they only make up about 1% to 5% of the magma by weight. But as that magma rises to the surface, the confining pressure drops.
And when that pressure drops,
The dissolved gases start to come out of solution. They exsolve, they form bubbles.
back to the soda bottle analogy.
Exactly. The gases are dissolved under high pressure. You release the pressure, and they immediately try to expand into bubbles. In magma, those bubbles are expanding with incredible force, and that provides the push to extrude the lava.
And the violence of the eruption is directly linked to one critical question. Can those expanding gases get out easily?
That is the entire story right there. If you have low viscosity magma, like basalt, the gases escape easily. The bubbles can rise and pop, and you get these spectacular but largely non-violent effusive eruptions, like fire fountains. But if you have high viscosity magma, that sticky, tangled silica structure traps those expanding gases like a cork in a champagne bottle. The pressure just builds and builds and builds inside the vent until the rock above it can't contain it anymore, and you get a catastrophic release.
Let's use the data to really nail down the extremes. We can connect the plate environment right back to the chemistry.
Yeah, let's look at the 2 ends of the spectrum. First, you have basaltic magma. This is the easygoing type. It's born from decompression melting. It has low SiO2, about 50%, low water content, maybe 1–2%, and a very high eruption temperature, 900–1,000 degrees Celsius.
So the result is low viscosity. Gases get out. You get fluid, quiet eruptions.
Exactly. Now contrast that with the granitic or rhyolitic magma. This is the highly modified stuff from subduction zones where water is forced into the system.
Okay.
This is the highly explosive material. It has high SiO2, around 70%, and critically, a much higher initial water content, maybe up to 10% because of that subducting slab. And even though it erupts at a lower temperature, that high silica content is so resistant to flow that it traps that huge volume of dissolved water vapor.
So high gas content trapped by high viscosity.
That is the perfect, deadly recipe for violence. The water tries to expand 1,000 times its volume, and the silica holds it hostage until everything fails.
So the chemistry dictates the style of the eruption, and the eruption style dictates the physical shape of the volcano. We're moving now from the molecular level up to the visible landforms it creates.
Yeah, you can draw a straight line. Low viscosity basalt builds one type of volcano, high viscosity rhyolite builds a completely different one, and that gives us the three main structural types that we see across the globe.
Okay, let's start with the one made by the most fluid magma, the shield volcano.
These are built almost entirely from that highly fluid, low-viscosity basaltic lava. Because the lava flows so easily, it can cover huge distances before it cools.
So it spreads out.
It spreads out. And that process, repeated over thousands of years, creates this very broad, gently sloping, slightly domed structure. It really does look like a warrior's shield lying on the ground.
And they're generally the biggest volcanoes in terms of volume?
By far. But their explosivity is extremely low. The perfect examples are Mauna Loa and Kilauea in Hawaii. The activity there is, relatively gentle. These magnificent fountains and rivers of molten rock you can stand nearby and watch.
Okay, next up we have cinder cones.
Cinder cones are born from magma with a more moderate viscosity, often basaltic to andesitic, but with enough trapped gas to fragment the lava as it comes out.
And they look totally different. They're much steeper than shield volcanoes, but also much, much smaller.
That steepness is the key. They're built almost entirely from ejected lava fragments or cinders.
Little bits of rock.
Yeah, typically pea to walnut-sized particles. They get hurled into the air and they fall back down around the vent in a loose pile. Because the material is loose, it has a high angle of repose, and that creates that classic steep slope. They're pretty small, often just a few hundred meters high, and you frequently find them in groups or along fissures.
And that brings us to the majestic but terrifying structures, the composite cones, or stratovolcanoes.
These are the signature volcanoes of the subduction zones. They're the result of that high-viscosity, gas-rich magma we've been talking about.
Big, steep slopes.
And their defining characteristic is how they're built. They're constructed over many eruptions with alternating layers of sticky lava flows that don't travel very far, and then layers of pyroclastics, the ash and rock from the explosive events.
So they're stratified.
Exactly. Interbedded, stratified. That's why they're called stratovolcanoes. And it's that alternating process that gives them both their height and their danger.
Right.
Because their magma is so viscous and traps so much gas, their activity is the most violent type. And their location is almost always right there along the Pacific, along those continental and island arcs. Think of the iconic shapes of Mount St. Helens, Mount Rainier, Mount Fuji.
They all fit the profile.
They do. They represent that cycle of violence and rest that defines subduction volcanism.
So let's detail the actual materials that get extruded, because magma takes on a lot of different forms at the surface. With the fluid basaltic lava flows, our sources contrast two main types.
Yes, we distinguish between pahoho and lava. And they can often come from the same eruption. It just reflects the lava's state as it cools and moves.
Okay, so pahoho.
Pahoa lava is the smooth, kind of a glassy or ropey-looking stuff. It's sometimes described as looking like braids and ropes. It's highly fluid, moves pretty quickly, and forms when the lava is still very hot.
And a lava, on the other hand, sounds like exactly what you'd yell if you stepped on it.
You're not wrong. It's unforgiving. A lava has this really rough, blocky surface made of jagged, sharp rubble. It forms when the lava loses some heat and gas, so it gets a little more viscous as it moves.
So the crust breaks up.
The solidifying crust on top gets continuously broken up by the moving liquid core underneath, and it creates this chaotic, clinkery pile of rubble.
Now, beyond the flows, those explosive eruptions from composite cones produce huge amounts of what we call pyroclastic material.
Fire fragments.
Right. And these are the bits that cause widespread damage.
They really are. They are the solid materials ejected violently during an explosion, and they range massively in size. At the finest end, you have ash and dust. These are microscopic, glassy fragments that can be carried for enormous distances in the atmosphere.
Creating those hazardous clouds and coating everything like snow.
Exactly. Then you move up in size, you get pumice, which is that frothy, air-filled lava. It cools so fast in midair that it stays porous, light enough to float on water.
Okay.
Then there's lapilli, which are about walnut-sized, and cinders, which are pea-sized. Those are the building blocks of cinder cones.
And the force needed to launch the really big stuff must be just incredible.
It's staggering. The largest fragments are blocks, which are just pieces of hardened lava ripped from the conduit walls. And then you have bombs. They're ejected as hot, molten lava, and they cool and streamline into this aerodynamic, often football-like shape as they fly through the air. I mean, you're talking about launching car-sized rocks for miles. The sheer volume of these pyroclastics defines the intensity of a violent eruption.
And that brings us to the so what section. We've gone through the complex science, but now we have to talk about why it matters to communities, how these eruptions impact human life.
Right.
Because when we talk about volcanic hazards, we're not just talking about slow-moving lava. We're talking about terrifying, instantaneous annihilation.
That's right. Slow lava flows, they destroy property, but they do it methodically. The truly deadly hazards are driven by the explosive power of those high-viscosity composite cones. And the most dangerous phenomenon, the one that kills fastest, is probably the pyroclastic flow.
The nuée ardente,
To nuée ardente, the burning cloud.
the speed and temperature of these things are just, they're almost incomprehensible.
A pyroclastic flow is essentially a fluidized avalanche. It's a dense, fast-moving current of superheated gas just infused with ash and pumice and other volcanic matter.
So it flows like a liquid.
It flows like a liquid mass, but it's hotter than 800 degrees Celsius, and it's moving down the volcano's slopes at up to 200 kilometers or 125 miles per hour.
That's faster than any highway speed limit, carrying material hotter than a pizza oven.
And because they're so dense and fast, they just fill up entire valleys instantly. They are far too fast to outrun, and their temperature incinerates or suffocates everything in their path.
And there's that classic historical tragedy.
The destruction of Saint-Pierre on Martinique from the eruption of Mount Pelée in 1902. The pyroclastic flow just wiped out the city in minutes. It killed nearly all 30,000 residents.
A truly horrifying event. Now, the second major threat, especially in places with a lot of rain or snow, is lahars.
Lahars, volcanic mud flows, and they pose these immense, often long-distance risks. They happen when huge quantities of volcanic ash and rock mix with water.
Water from where?
It could be from rapid snowmelt during an eruption, intense rainfall on loose ash, or even the failure of a crater lake wall. And this creates a slurry, like wet concrete that moves incredibly fast and can travel for dozens, even hundreds of kilometers.
And because of that density, they just flatten everything.
Everything. They pose a chronic long-term risk. I mean, look at Mount Rainier in the Cascades. It hasn't had a major eruption recently, but it has this massive glacial cap.
Right.
If it erupts, the lahars that result could travel all the way through the Seattle-Tacoma metro area. They could impact millions of people who live in what are basically ancient lahar floodplains. It's a continuous hazard that requires constant monitoring.
And we also have to mention volcanic gases. These are often silent, invisible killers.
Yes, the gases include things like SO2, sulfur dioxide, which causes volcanic smog or VOG and acid rain. But then there's CO2, carbon dioxide.
Which is particularly insidious.
It is, because it's heavier than air and it's odorless. It can pool silently in low-lying areas, displacing all the breathable oxygen without any warning at all.
And the sources point to a really specific, tragic example of this. The Lake Nyos disaster in 1986.
Lake Nyos in Cameroon demonstrated something called a limnic eruption. It's chilling. Dissolved CO2 had been seeping into this crater lake from the magma below, just accumulating at the bottom under immense pressure.
For years.
For years. Then, when the lake suddenly overturned, maybe from a landslide, it released this immense, suffocating cloud of carbon dioxide gas that just flowed down the surrounding valleys.
And because it was heavier than air.
It literally displaced the atmosphere. It hugged the ground and killed thousands of people and all their livestock in the surrounding communities. No fire, no ash, just silent suffocation. It's a chilling reminder of the chemical dangers.
Moving on from the immediate dangers, let's explore some of the unique volcanic landforms that are left behind. starting with calderas.
A caldera is a massive, collapsed volcanic basin. It's a steep-walled depression at the summit, and to be a true caldera, it has to be more than a kilometer in diameter.
So how do they form?
They form when a huge eruption, usually of rhyolitic magma, empties the magma chamber so fast that the overlying summit of the volcano just collapses inward. It just falls into the void. Crater Lake in Oregon is the perfect example. That's the collapsed remains of Mount Mazama.
Then you have fissure eruptions and lava plateaus. This takes us back to the really fluid stuff.
It does. Back to our fluid basaltic magmas. Instead of erupting from a single pipe-like vent, the lava is extruded from these long, linear cracks in the crust called fissures.
Right.
And these eruptions can produce enormous volumes of lava that spread out across vast landscapes, building up layer after layer to create these huge, flat plains. The Columbia River Plateau, covering parts of Washington, Oregon, and Idaho, is a spectacular example of this.
Just miles and miles of solidified lava.
Kilometers-thick layers of basalt that covered 250,000 square kilometers. It's incredible.
And finally, we have volcanic pipes and necks, which really tell the story of a volcano's inner plumbing long after the rest of it is gone.
They do. Volcanic pipes are the short conduits, like a chimney, that connect a magma chamber to the surface. Over millions of years, the softer parts of the cone, the ash and cinders, they erode away.
But the pipe is left behind.
The pipe, which is filled with hard crystallized magma that cooled really slowly, remains. And that resistant standalone structure is what we call a volcanic neck. A spectacular example is Shiprock in New Mexico. It just stands there like this massive, isolated monolith. It's the skeleton of an ancient volcano.
We have covered a tremendous amount of ground today, from global plate tectonics all the way down to individual rock fragments, and it all seems to hinge on a few core connections. Let's just quickly synthesize that central logic for everyone.
I think the foundational connection is this. Tectonics determine chemistry.
Right.
Whether it's decompression melting at a spreading center making fluid basalt, or partial melting with water in a subduction zone making sticky rhyolite, the plate interaction defines the raw material.
And that chemistry determines viscosity. Low silica means fluid magma, which means quiet, effusive eruptions.
While high silica means viscous magma, which leads to catastrophic, explosive eruptions because those gases get trapped.
Like pressure in a sealed chamber.
Exactly. And finally, that viscosity determines the volcano type. The broad shield, the steep cinder, or the layered composite cone, and all the resulting hazards. Pyroclastic flows, lahars, CO2 emissions, it's all one integrated, logical system.
What really stands out to me is how the most spectacular and dangerous volcanoes, the composite cones, are created by what is really a minority of the total volcanic output. We're always focused on those big, dramatic events.
And that leads to an important final thought, I think, rooted in the scale of the data. We said earlier that the greatest volume of volcanic rock on the entire planet is produced silently, continuously, along the oceanic ridges.
Not the spreading centers.
Driven by decompression melting. This is the least visible, the least publicized of all the volcanic environments.
So the majority of Earth's molten rock is just extruded beneath the ocean, totally out of sight, flowing gently, building new crust mile after mile.
So it makes you ask the question, if the most significant engine of global volcanism, the one creating all this new crust, regulating the Earth's thermal balance, is the one we rarely, if ever, see, well, does that redefine what we should consider the most powerful geological force on the planet?
Is the most important volcanic activity the quiet, continuous creation happening deep underwater?
Rather than the spectacular, destructive events that just happen to grab our attention at the surface, it's a bit of a perspective shift, something for you to mull over and maybe explore on your own.
A perfect, thought-provoking place to end this deep dive.
Bye.
Thank you for joining us.